Network fundamentals, basic network theory, and terminology. Network fundamentals is our first lesson, since before we can get into discussing networking and its complexity, we first need to define some of the terms, some of the theory, and get a nice framework for where we're going to be going. One note about the Network Plus exam is that they assume you have around 18 months experience in the industry. If you don't, that's okay, but I am assuming that you do have some basic knowledge of computers and perhaps some working knowledge of networks. So in some cases, this might be redundant for you, and in other cases, you might be learning some new stuff. Either way, I'm going to focus on exactly what the Network Plus exam wants to see and what you need to know to pass. So in this module, we're going to be introduced to networks and what makes up a network. The terminology that's used to describe those objects, it becomes flexible after a little bit of time and experience spent on the field. But to understand what each object does and what its functions are in a network, I want to break down some of the jargon or the technical speak and talk about what exactly is networking. So some of the module objectives that we're going to cover are first to define and describe a network and a computer network. You've heard the term network before, and so I want to define what that is and how that relates to a computer network. Next, I want to describe the components of a network, what makes a computer network. I want to define the terms node and server, which will be helpful going forward when we use those terms. Define and describe the network backbone and the various variations of a network backbone. And finally, I want to define the difference between a terminal, a client, and a peer. All right, so let's get started. Now, because networking is ubiquitous, we need to define a few specific things in order to keep things in order. So first, network. This is an interconnected or interrelated chain, group, or system, generally based on a purpose. So for instance, if we say that you're going to Facebook or LinkedIn are social networks, because the purpose is to be social and to connect with other people who have similar interests, likes, etc. In the same way, you are interrelated and you form a group. Now, based on that, a computer network is the interconnecting of two or more computers that have a basic core purpose of communicating electronically. So, the network of social network is to communicate with individuals about a specific topic. On a computer network, we need to communicate data electronically. And that's the thing that joins us together. The internet is one really large computer network. And we will see how that comes to play later on in this course. Now, whether your network is comprised of 2 computers or 2,000 computers or, like the internet, 2 million computers, there are some commonalities in networks and requirements for what makes them. The first thing that are needed, obviously, are devices. These are the actual computers, the printers, the switches, the routers, all of the devices that are going to be connected together by media. Now, media can either be a physical connection, such as copper, or newer forms such as fiber optics, or it can be something wireless, like Wi-Fi, or radio frequency, or even cellular Wi-Fi. Each device, however, has its own language when networking, and not every device knows how to communicate with the language of these other devices, right? Because obviously a computer communicates slightly differently than a printer, slightly differently than a router, etc. So in order to allow all these devices to communicate with the rest of the network, we have something called a network adapter, sometimes referred to as a network interface controller or a NIC, specifically in the term of computers. And it serves this network adapter as a translator between the components, the devices, over the media by which the data is sent. So finally, to manage and govern how everything talks with everything else, the network needs an operating system, which is similar to like the ringleader in a circus, if we can use a metaphor there. It tells the network how to work together in order to perform as efficiently as possible over the adapter, over the media, and with each of the devices. Without the operating system, there wouldn't be any order or direction in the network, and no one would really know what they were doing. So the network operating system is responsible really for allocating resources, monitoring the activities of devices on the network over the media, and managing files and data, etc. Now, we have two devices that I want to define. One is a node, and a node is any device that is connected to a communications network. And this can be just about anything. So we have clients and servers are nodes, and so are printers and network-attached storage devices. And these are all what we call endpoint nodes. I'm going to write that up here, because that's where the data ends. Whereas something like a router or a switch, or previously we used to see a lot of hubs, do what's called redistribute. So those are what we call redistribution nodes. Okay? So it's important to understand that these are both nodes. Anything on the network, really, any sort of device that's communicating is a node, or being communicated with. The endpoint nodes where the information sort of ends up or is going to. A redistribution node, its responsibility is to pass the data on to another either redistribution node or onto the endpoint node. Now, a server is a network device that's responsible for sharing resources and managing certain services, like addressing. And we'll talk about this, which is called an IP address, a little later. It also manages devices on the network and controls the network-wide functions like permissions. So not only is it going to give all our clients, all the other nodes, addresses that allow it to communicate, it's also going to manage how those devices communicate and what they're allowed to do, which is what we call permissions. All right. Now, this is, so you can see that the server is a type of node, but I just want to describe server. We're going to talk about some of the other devices in just a moment. Before we do that, let's talk about the network backbone. Okay. The network backbone is responsible for carrying the majority of network traffic, and it works very quickly at a very, very, very high speed. Now, it might use different technology throughout this on the backbone that's different from the rest of the network, because it basically connects all the smaller networks together. That's why it's called the backbone. And it needs to be large, fast, and capable of communicating at very high speeds, because all of these computers, all these smaller networks, are communicating. We'll talk about how that all works in a bit. Now, there are 4 different types of network backbones, and I'm just going to give you a brief definition of these now, and we will come back and talk about these more in depth a little later. Okay? The first one is called serial. That's where one backbone cable connects to another, one after the other, like so. All right? So there's one backbone cable, and multiple switches are connected to that cable, which allow devices to connect to it. There's also something called a hierarchical or distributed backbone, which, like a family tree, it has more of a family tree layout, if you can imagine, right? Okay, and this backbone is, in this case, it's much easier to manage, typical for what we'll call local area networks or LANs. It's much more easily scalable, as you can see, because I can update one part a lot faster. And in this case, the backbone is responsible for the traffic of the nodes on each branch. So we have different branches, and on each branch, the backbone is responsible for that, and that's how it gets a little easier. Now, a collapsed backbone uses a router as the connecting point. All right, and we'll talk more about how that works a little bit later and what exactly a router does and how that's different from a switch. And that's a pretty major point. Finally, we see something called parallel, which is just like a collapsed backbone, except it has multiple cable connections, and that's because that allows for more redundancy. Remember, if you took the A+ class, we talked about redundancy and how we want to make sure that we don't have what are called single points of failures. So there's more than one cable connection, which not only is great for redundancy, it also allows for what we call load balancing, and also a faster throughput because the computer can decide which of the cable connections to use. All right. So these are, again, we have serial, hierarchical or distributed, collapsed, and parallel. As we talk more about networks, these differences will become clearer. But I just wanted to cover them now, and you won't probably see these specifically on the exam in this format. You'll see them in other formats, and but I want to lay the framework for what we're going to be talking about. All right. Now, a terminal. A terminal is a network hardware device that's used for entering data into it and displaying data from another computer or computing system. It's commonly called a dummy computer because it doesn't have any processing capabilities of its own. It also doesn't have much memory or anything else, okay? So it is literally, this is a dummy. It's basically a screen with a keyboard, a mouse, some sort of input tool, right? And what it's doing is simply displaying information on a bigger, better server computer someplace else. All right? We also need something called a terminal emulator placed onto this computer so that it can emulate what's going on the server and communicate with it, since it doesn't have processing capabilities or memory of its own. Now, this is different from what's called a client. A client has its own processor and memory of its own, but it accesses network resources on other nodes, other servers, and other clients. All right, so it is, rather than a server which serves up information, the client takes the information and uses it. Now, a peer is a network computer that provides its own resources and services and computes on its own. The best thing about a peer is that it can act, it is self-managed, self-contained, and it is both a server and a client. Okay? So you can see how this works. This peer computer serves information to this peer computer as a client. This computer can serve information to this one as a client. So this is what we call peer-to-peer networking. It manages its own set of local policies. It has its own set of users. It is completely self-contained and does not need a server to operate, unlike a client, which does. All right. So, just to recap what we've talked about, we defined what a network is and how that's different slightly from a computer network, which is really what the Network Plus exam covers. We described the components of the network, the adapter, the network operating system, the devices, the media. Let's go ahead and write those. We had media, right, which allowed the devices to communicate using a network adapter. Communicated and managed by an operating system. We also defined a node and server, right? The node is really any sort of device that's on, we have the endpoint. And we also have a redistribution. We defined and described the network backbone, remember, which is really fast. And the different variations of it, which, if you recall, included serial, which is one after the other, hierarchical, also called distributed, Then we looked at collapsed and a more redundant form called parallel. Finally, we defined terminal, client, and a peer. Remember, the terminal is a dummy. Client accesses resources on other computers. And a peer both serves and accesses. All right. So now that we've covered some of this basic terminology, let's continue on talking about the fundamentals of a network and discussing more of what we need to know in order to get into the majority of this information on the Network Plus exam. Network fundamentals, network categories, and models. Having discussed some of the basic components of a network and having established sort of a baseline of some terminology that we all need to be familiar with, I now want to talk about the different categories of networks. And as we begin to understand the differences between these categories, we're also going to look at some of the basic models that networks are placed into, depending on different configurations and layouts. So our objectives in this module are, first, to describe the characteristics of a LAN, or what's called a local area network. Now, this is different from a WAN, or a wide area network. You're going to need to be familiar with both of these terms, and actually we're going to see a few different types of WANs, including MANs, PANs, CANs, and none of these are what you think. These are all acronyms. So MAN is a metropolitan or municipal area network. PAN is a personal area network. CAN, campus area network, etc., etc. And as you can see from the name, these terms are really amorphous. So it really depends on some subjective opinions as to what these types of networks really describe. But anyway, we're going to cover all of those so you'll be prepared for them if and when you see them out in the field or on the test. We're also going to define the difference between the internet, something that I'm sure you all have heard of, and then two other terms, the intranet and the extranet, which are more specific towards organizations and sort of using internet technologies for a specific organization. We're then going to look at the way networks basically are organized. We're going to look at something called a centralized network, which, if you recall from the previous video, is going to involve a terminal and a mainframe. And then we're going to look at a client-server network, which sort of takes the pressure off of that central mainframe and puts it onto a server with a client. And then finally, we're going to look at what a peer-to-peer network is. And again, that is like where we have all clients, no servers. So we're really looking at a descending order of centralization, but at the same time, we're putting more power and resources into the individual computer. Finally, because nothing is as simple as it seems, we're going to look at what's called a mixed mode network, which is a combination of sort of all of these. And that'll help us, as we go forward, understand how an administrator of a network, something we'll also talk about, deals with these different types of needs on their entire network. So let's first start talking about a local area network. A LAN, or a local area network, is a network that spans a small area, typically either a building like your home or office, or a floor of a much larger building. You might find this in like a skyscraper. So take the Empire State Building, for instance, which is one of the largest or tallest buildings in New York, or used to be. Every floor of the building might have a different company using it. So each one of those has their own LAN, or local area network, to keep them separated from one another, even though they might even be using some of the same infrastructure running into that building. Now, in a LAN, the most commonly implemented technology, and something you've probably heard of, is something called Ethernet. And this means that the communication path taken utilizes cabling or short-range wireless technologies. We're going to talk about Ethernet and really what it means, because it's also not just the hardware. It really has to do with how the data is being communicated in greater detail in an upcoming module. Now, in a local area network, a connection is leased by a service provider, but it isn't necessarily for the LAN to function properly. So this means I don't need an outside sort of connection in order for my LAN to work. The reason I might need a connection to the outside from an internet service provider is going to be thanks to a WAN, or a wide area network. But let's talk really quickly about LAN administrators, the people who are running these LANs. That might help us understand them a little clearer. Now, LAN administrators are like jugglers. They have to keep their eyes on all of the components of their network at the same time, hence the little GIF over here. They have to have, therefore, a broad range of versatile skills that allow them to manage and maintain all the different parts of their network. Now, that's only within their domain. And the juggler also has to be mindful of each of the objects in the air at the same time, or else they might lose track of one or all of them. And like the juggler, if the LAN administrator loses track of one part of their job, it's likely the entire network of moving components could come, quote-unquote, crashing to a halt. The LAN administrator, therefore, has to have a strong working knowledge of all aspects of their network. Now, the LAN administrator should be able to handle tasks such as installation of software and hardware, troubleshooting all components of the network, including the servers, which we'll talk about, connectivity devices, and media, and so on and so forth. And not to mention security for the network. So if that isn't enough, one of their most difficult tasking duties of the LAN administrator is being responsible for users and attending to their requests and their requirements. So you can tell that the LAN administrator really has to be able to do a lot. And we're going to, as we go through this course, you'll see more and more specifically of what they have to do. But let's talk about a WAN. A WAN, or a wide area network, is a network that spans a larger geographical area than a LAN. In most cases, the WAN is going to connect, as this picture demonstrates, multiple LANs together. And it might even utilize long-range communication such as satellite or radio frequency, otherwise known as RF. And one main factor that differentiates a WAN or wide area network from a LAN is that it can enable users to connect to one another from different physical locations. So whereas these are each physically sort of isolated in some ways, you can tell the WAN connects all of these LANs together. Okay? Now, a WAN can be private, where an organization has complete control of access to it, resources, and it's solely responsible for everything that occurs on that network. Or a WAN can be public. And of course, the world's largest WAN is the internet. Now, we're going to talk more about the internet in detail shortly, but I just want to point out that the biggest wide area network we have is the WAN. And unlike the LAN, which is geographically isolated and can be controlled by a relatively few number of people, the WAN has very different needs. Now, there are also different types of WANs that are out there. Now, some of these classifications, we might get argument from certain individuals just because this is sort of open to some subjectivity. But these are covered on the exam, and which is the reason I want to make sure we cover them. The first one that we've seen a few times when we talked, if you were here for A+, is called a PAN, or a personal area network. A PAN is 2 to 3 computers connected together by cables. And a wireless PAN, or WPAN, is going to be using Bluetooth or infrared technologies. Generally speaking, when we are talking about PANs, for purposes of the exam, we're really talking about Bluetooth. Now, I might consider PAN a sort of local area network, but for our sake, we're just going to group this into WANs right now, but this could be considered something a little different, okay? So I'm just going to sort of put brackets around that. And a WPAN, or a wireless PAN, if we put that W in front of it, occurs when the computers are connected together wirelessly, but not through an access point, right? So they're connected literally to one another thanks to the wireless technology, but there is no sort of central access point that they all connect to. Now, the next type is a CAN, or a campus area network, and I'm assuming from the name you can guess that this is a WAN that spans the geographical area comparable to like a school or a campus or a business park such as Yahoo. Now again, some people might consider this a LAN, some might consider this a WAN, but for our sake, we're just going to assume that this is dealing with some sort of campus, some sort of school, some sort of area that is contained all by one organization. So for instance, if I had 4 buildings all connected, and each of them has, let's say, 4 floors, right? There might be a LAN on each floor or in each building, and then connecting each LAN together is going to be this CAN, which is a sort of wide area network. But because the wide area network could denote the internet, and the cloud is sort of the best descriptor of that, we want to call it something slightly different. Now, a MAN is a metropolitan, or it could also be a municipal area network. And as the name implies, it's relatively the size of a city or a town or a metropolitan area. So if I have a business that, like the CAN, has several buildings, but the buildings are now separated over the course of the city as opposed to simply in my own campus, then I'm probably going to use this terminology. A GAN, or a global area network, I think it's sort of redundant, but these are networks that go from country to country or around these are networks that go all the way from country to country all the way around the world. They span the globe, and they're going to utilize technologies like satellite probably. And the reason we're going to call this a GAN is because, generally speaking, the global area network, or GAN, is all controlled by one sort of company. As opposed to a WAN, which, as we just discussed, could include either all being controlled by one company or all being controlled by disparate companies such as the internet. Finally, an EN, which is the only one that breaks from this convention, is called an enterprise network. It's a network that includes usually aspects of both a WAN and a LAN, and it's typically owned and operated by a single entity or organization, just like a GAN might be. Now again, these terms are very fluid and flexible, and depending on who you talk to, they'll call it different things. So you might, I worked for an organization, we never used the word MAN, we always used the word WAN when talking about the network that was deployed over the entire city. However, certain individuals, certain organizations will call these different things, and the names might change as well. But it's important to have a firm understanding of this just from a basic definition standpoint, but also so that if you go out in the field and you hear people talking these different terms, you can talk the talk as well. Now, unlike LAN administrators, whose duties are quite varied, WAN administrators are typically specialists in their respective fields. So they're responsible for more complex infrastructures, and as a result, they need to be more fluent in, say, routing structures and troubleshooting difficult or different network issues. They're also responsible for, say, data versus voice systems. And WAN administrators concentrate generally on network-oriented problems and not user-related issues like a LAN administrator. So with a LAN, we're really going to get these user-oriented tasks, right? Because they're dealing with the user on a day-to-day basis. A WAN administrator is really not dealing with the user. They're dealing with sometimes what we would refer to as the back end. And in some cases as well, they're also going to be a little more specialized in what they do, since what they're dealing with is a lot more complex. A LAN administrator can sort of be a jack of all trades. A WAN administrator, we want to be a master of exactly what it is he or she is dealing with. One of the other main duties of a WAN administrator is the development and implementation of certain scripts that are going to automate certain network processes, and they're also going to plan for and test and push out upgrades and updates to the infrastructure of the network-wide. Whereas a LAN administrator is going to do this on a sort of local basis, perhaps to the computers in their network. So we can see sort of how these are getting differentiated here. A WAN administrator is a lot more specialized, and they're not focused on user-oriented tasks. They're looking at network stuff. So you can see a WAN administrator, again, dealing with the back end, much more specifically, generally more technical, and generally also a little bit more training than a LAN administrator. Now, let's talk about the internet, or the World Wide Web, which is a public wide area network, right? It is the largest WAN that we have, and it essentially connects every country on the planet, in some ways every computer on the planet. It's used for many different things, including, but certainly not limited to, sending and receiving email, initiating and completing commercial and private transactions, communicating and allowing people to connect to one another that are sitting in the same room or perhaps even on the other side of the world. The internet is really the method by which everyone in the world can communicate in one way or the other. And in some ways, we can actually use it to create our own virtual WANs that are private, and we'll talk more about that. The other thing that's important to know is every bit of data is stored somewhere on a server, typically in the form of a web page. And in order to access the data on the internet, you're going to have several different considerations that are going to be made. First of all, you need to have a web browser of some sort, or you're going to need to utilize a certain generic protocol and have something like, so if we're talking a web browser, we're going to need to use a Safari, Internet Explorer, Google Chrome, Firefox, etc. But they're all using HTTP, which is a specific protocol, and it has a certain port, which by the way is 80, and we'll talk more about those later, in order to allow communication to occur. And this might be different from, say, another form of communication, such as FTP or remoting in and so on. And secondly, all devices that want to connect to the internet must be assigned what we call an IP address. All things on the internet, due to the way it works, are governed by this IP, or the Internet Protocol. We're going to revisit this in a future module, but IP allows all of this to happen. If it wasn't for IP, we wouldn't have an internet, at least in the way we know it. So again, the internet is this largest global wide area network that we have in the world, and it's for use, it's public, and everyone can use it if they, have a provider that gives them access. Now, this is different from an intranet. An intranet is a company's private version of the internet. It's commonly connected to the internet so that people can connect even if they're not locally at the same place physically. But the purpose of an intranet is to keep your network or portions of your network segregated from the unsecure and possibly even dangerous internet. So a company might use an intranet for security purposes, or for confidentiality if they have certain files and folders they want to post up. And the intranet uses the same services and protocols as the internet. So the reason it shares this name is it's inner to the organization, but it shares the same name because it's using all of the same services. In other words, IP, HTTP, you still use a browser, so on and so forth. So it's still accessed the same way you would the internet, through a browser and a web page on the World Wide Web. Now, all of this is different from an extranet. As the name implies, with an intranet, your network is completely secure from the internet, right? You control who has access to your network in every facet. But what if your company or organization needs to allow certain individuals to have access to your network, but you don't want them to have access to all of your network? In this case, we're going to use something called an extranet. It gives you the ability to grant access to specific portions of your network in your extranet. So you can give access to specific people, typically vendors, suppliers, individuals that might need minimal or temporary access. At the same time, your extranet is restricting them from having full access to the rest of your network or your intranet. So it's really an extension of your intranet, but it's the part that is exterior, look at that, extra, to your organization. So again, the internet is using a certain degree of protocols and technologies that allows anyone in the world to access information. The intranet is sort of a private internet for your organization, and the extranet is the part of that intranet that you're going to let other people from outside of your organization have access to. Now, I just want to define what a segment is, since we might see this term come up a bit in the future. A segment is a portion of a network that has linked devices and that are separated by a connectivity device such as a switch or a router. All right, so we haven't talked about switches and routers yet, but we're going to. And so what I mean is I might have a LAN, okay, and let's say that for simplicity's sake, my LAN is consisting of 4 computers, all connected through a central device, which we're going to call a switch. Now remember, if they weren't connecting through that central device, this would be called a PAN, a personal area network. But this is a LAN that has that central device. And let's say this central device, and I'm really simplifying it, but let's say it connects to another switch, and that other switch has 4 computers connected to it. Now I have different segments of my network that I can join together in certain information, but I can also exclude them from certain information in order to allow for performance. By segmenting, we allow communication between the nodes on each segment to be uninhibited by the traffic on other segments. So I'm not worried about if computer A wants to talk to computer C. I don't need to involve all of these guys. I can just allow them to talk directly. And so what it's doing is it's basically keeping a lot of traffic from going over this line. And therefore, we're increasing speed, we're increasing throughput, and we're decreasing the amount of sort of errors that can occur. And we're segmenting everything out to make it easier to fix in the future as well. Now let's talk about a network model. We just talked about some network categories, so now let's talk about the different models that these are going to fit into. A network model is a design specification, if you will, that identifies the transmission path that nodes on the network are going to use in order to communicate. It basically determines whether the communication and the processing is centralized or distributed. So in a centralized network, this is where we have our mainframe and our terminals. The host computer, this guy, the mainframe, provides all of the processing and all of the network communication. And the users that interface with the host computer do so through these terminals and by using a terminal emulator that's on the screen. Centralized networks are highly effective, but the problem is they can be a little costly to maintain because this sucker right here needs to be so powerful that what if I have, instead of just 3 computers, what if I had 1,000 computers? And what if this goes out? Well, now I'm in major issue. I have a major problem. So this is why a lot of times we use what's called a client-server model. The client-server model, in the client-server model, the server is responsible. The server right here is responsible for providing services like file sharing and printer sharing and authentication services and data storage and management to these clients. The main difference between the centralized and the client-server model is that in this client-server network, the processing and the resources can be allocated wherever they are needed, including on the client. And they can also be distributed whenever necessary. And the end nodes, these clients, can still perform their own processing and end-user tasks without having to constantly talk over to the server. So if I need a file, for instance, I can get that file, do the work on my computer, and then I can save it back to the server. Whereas here on the centralized mainframe terminal setup, all the work is actually done on this major, huge computer. And here in the terminal, we're just sort of having a portal to see what's going on. Now, both of these are different from what we call a peer-to-peer network. We talked about a peer in the previous module, but a peer-to-peer network, which you might also see as P2P or PTP, is a network in which each node on the network is responsible for its own computing, its own management, its own security, its own storage, its own resource sharing like printers. It's completely decentralized, and it's commonly referred to as a work group. Now, this is sort of like if we were going to make a reference to a political metaphor, this would be like communism. Everyone works together equally, and everyone is responsible for their own thing, and then they can share that with everyone else. Whereas in a client-server sort of model, we're dealing with, say, a democracy in which you have a president or prime minister, someone who's going to make a lot of the decisions, but you are still at liberty to exercise a lot of your own stuff. And that's very different from, say, a terminal mainframe, which would be equivalent to like a monarchy, a really strict, tyrannical monarchy in which everything is decided for you and you make no decisions on your own. So one of the problems with work groups is that user accounts need to be replicated onto each node so that if I want to get access to this computer, and I usually work on computer Y, all of my username, password, everything is going to be on there. And if it's not done, if I don't sort of copy everything over, there's no way I can gain access. So this is the problem with this model, is each person's their own, but if X has wheat and I have corn, there's sort of no sharing that's automatically set up. We have to create our own sort of share, and then if someone else has something, I have to share with them, and so on and so forth. Now, we might sometimes mix these together into what's called a mixed mode network. And that's just like it sounds. It mixes aspects of two or more of the different network models. An example might be a work group of computers connected together via some sort of short-range wireless, while allowing those computers to connect to a mainframe computer and using terminal emulation. So alternatively, we might have a work group and then a centralized server, etc. So we can see mixed mode networks. They're usually not as popular in huge enterprises because of the lack of control, except in certain specific instances. But we do see them, and it's important to know that just like in anything, we can mix and match to however we want the network to work. All right, so now just to recap what we've talked about, we can now describe and define the characteristics of a LAN, or a local area network, as well as a WAN, or a wide area network. And we also talked about several of the different types of WANs, or in some cases LANs, including a CAN, or campus area network, a MAN, or municipal or metropolitan area network, a PAN, or personal area network, which is where the computers connect directly to one another. And then we looked at a GAN, or a global area network. And then we also talked about an EN, or an enterprise network. Okay, so these are all different acronyms that you need to learn for the exam. We also talked about an internet, intranet, and extranet. Remember, the internet is that World Wide Web, right, the cloud. The intranet is sort of using this cloud, but in your company and keeping it private. That's my little building. And the extranet is allowing access of your company private intranet to perhaps certain individuals from outside. So it's just a little bit of that. We also talked about a centralized network, which is mostly what we talk about when we deal with terminals and mainframes. And we'll sort of deal with this a little bit too when we get into virtualization. When we talked about thin and thick clients, this is the idea of a thin client on a network with a server of some sort, or a mainframe, I should say, that is going to do all the processing for it. We also looked at a client-server network, which is the majority of the types of networks we see in enterprise settings, and a peer-to-peer network, which we also call a work group network, in which every peer is both a client and a server, responsible for its own resources and so on. I think we used a metaphor that this might be like communism. This might be like a client server, might be like sort of a democracy of some sort, or a republic of some sort, and a centralized network would be more like, I guess I should say, a democracy that is also a republic, since we do have officials and there's someone above us, right? But a prime minister or a president sort of system. And then a centralized network would be like a tyranny, or a tyrannical monarch, I should say. And then we have a mixed mode network, which is sort of a combination of the above. Great. So we've talked now about some of the basic terminology. We've talked about the models. We've also talked about the different categories. So let's finish up this basic network fundamentals area by talking about what are called topologies, how the networks are physically set up, and how they logically communicate with one another. Network fundamentals, network topologies. So now we're going to explain network topologies, or the network layout, both physical and logical, physical being how it's physically connected, and logical being how the information is communicated over that physical network. And we're going to define the different standard topologies that are in use for today. So we're first going to define topology in general. Then we're going to talk about physical topology, followed by logical topology. We're then going to explain a few of the different types of topologies you need to be familiar with for the exam, including a bus topology, a star topology, a ring topology, a tree topology, and a mesh topology. We're also going to talk about a mixture of all of these topologies that is called a hybrid topology. These are the things you really want to pay attention to, these different names, and the names correspond directly to how everything is set up, so I don't think it'll be too hard for you to remember or to memorize. So as administrators, regardless of the specific role we're in, we have to have a complete understanding of the layout or the arrangement of the network. This allows us to effectively design, manage, and troubleshoot the networks for performance and scalability. Scalability, by the way, and I'm just going to write that out here because it is a term we'll see come up over and over again, is how you can either make the network larger or smaller depending on needs. Certain topologies have characteristics that allow us to have more efficient communication, while other topologies focus more on immediate or faster communication between certain devices. So understanding the topology of the network allows us administrators to troubleshoot the problems we're having and then implement solutions easier and more efficiently. So there are two types of topologies in general, and then there are specific names for each of those topologies. But the two types are physical and logical. So let's take a look at the characteristics that define a physical topology and a logical topology. A physical topology is the actual physical layout of the devices. So this is like looking at the blueprint of our network. This tells us how the devices are actually physically connected to one another. It's also the shape of the network, and it gives us a sort of picture to represent the layout or the blueprint. The physical topology ensures that we administrators know and understand how the physical media, like cables, connect the devices to one another. So, a logical topology, on the other hand, describes the how. In other words, it's the pathway that data takes regardless of how the network is physically laid out. This is how the data is actually communicated over the physical. So the logical topology allows administrators to troubleshoot and fix the problems we're having with communication between devices by understanding the path that the data is actually taking. And we'll see some pictures of this in just a second, so that will make this all a lot more clear. In a lot of cases, the logical topology could be very different from the physical topology. So only because one logical topology is, for instance, a star, doesn't mean the physical topology is also going to be a star. You can have a physical star and a logical bus. So that's why it's important we understand the difference between logical and physical. So now that we've defined the difference between a physical and a logical topology, I want to look at some of the different connection methods that we use in these topologies and the specific layouts, both for physical and logical. But first, let's talk about how these things connect, because that's going to keep coming back up. So the first type we have is called a point-to-point connection. This is a direct connection between two nodes on the network. And remember, when we're talking nodes, that could be to computers, printers, etc. And remember, we had endpoint nodes, and then we had redistribution nodes. So these can either, by the way, be wired or wireless. So an example of a wireless point-to-point connection would be, for instance, two nodes using an infrared connection to communicate with one another, like your TV and your remote control. A wired point-to-point connection, on the other hand, would be two computers with network interface cards, or NICs, remember that term, okay, connected directly together with what's called a crossover cable, so there's nothing in between them, right? They're connected directly to one another using cables. This might also be the same thing we do if we connected two computers together somehow using USB cables, although that's not really going to happen very often in a network setting. The next type we have is called a multi-point connection. Now, as the name implies, we had point-to-point, that's like one-to-one. And then we have multi-point connections, which means that there are connections between multiple nodes. So there are two or more endpoints connected together by each multi-point connection. In other words, all transmissions are not private because every node on the network can detect the signal being transmitted. Now, there's also something called a radiated connection, and as the name implies, radiated, this is specifically a wireless connection. So data is transmitted wirelessly between devices. It's also, by the way, called a broadcast connection, although broadcast also means something different, as we will see in just a minute. So some radiated connections would be like Wi-Fi or wireless LAN, and in some cases even an infrared like your a remote control. But the reason that that's a point-to-point is infrared requires direct line of sight, whereas radiated connections, that can be either point-to-point or multi-point. So it sort of is, it sort of involves all of these different ones. All right, now let's talk about some of the specific topologies. The first one I want to talk about is a physical bus topology, not a logical bus topology, okay? So again, this is the physical, how things are physically connected. And what this means is each node is arranged, as you can tell, in a line. So this is like seats on a school bus. Everyone on the bus can hear the transmission, but the message is only received by one specific recipient. So a bus topology is an example of a multi-point connection, right? Because we have, it goes to all these different points. There are many points connected to it. If the message is for everyone on the bus, so I'm meaning I want to send this message out to everyone, that would be called a broadcast connection. Broadcast meaning it is intended and sent to every single person on the bus or every node on the network. If the message, on the other hand, is meant to just go to one person or one node, we're going to call that unicast. Finally, if it's intended to go to more than one recipient, but not all of them, then we're looking at a multicast. Okay, so unicast, as the name implies, means one recipient. Multicast is two or more recipients. And then I'm just going to write this up here. Broadcast, as the name implies, like a television broadcast, goes to all recipients on the network. It's important to understand the difference in these types of messages. We have broadcast messages go out to everyone, unicast messages go out to one recipient, multicast to two or more, but different from broadcast because it's not going to everyone or all of them. The way multicast works is that only the stations or the nodes that have subscribed to a message will receive it. So we could, if we're using a TV sort of example, unicast would be like if you have a direct line to your sort of television provider. Multicast would be like HBO, only those subscribing to the specific cable network get access to it. Broadcast is sort of it's in the air, anyone can get it, right? So on a bus topology, like we're looking at right now, when the data is transmitted, the signal will bounce or reflect off of the ends. And so it's important that when the signal bounces, it's going to interrupt the transmission if there's nothing there to stop that bounce from occurring. So to keep this from happening, we generally have something called a terminator, and it's generally around 50 ohms. I would remember that for the exam because I do see that pop up. And what this does is it really grounds the bus transmission or the bus connections to reduce, and it reduces static electricity to keep this bounce from occurring. If that bounce occurs, then we're having all sorts of problems start to occur in our network. Now, if the way that these nodes are connected, as you can see, are by these T connectors, and the reason they're called T connectors is because they look like an upside down T. Now, the downside to using a bus connection are obviously these terminators, and it's a little frustrating to sort of connect these up. But the upside to using a bus technology, or topology rather, is that it's inexpensive and it's relatively easy to implement. Now, this is different from a physical star topology. As you can see now, instead of a line, everything is connected to every other device using a central connection device, such as a switch or a hub. In a physical star topology where a switch is used, what happens is the node that's transmitting the data to another node, the switch actually will determine where that information needs to go and send it only to the node that is the intended recipient, like a unicast, right? On the other hand, a hub is going to send the data out to everyone in what's more like a broadcast connection. Now, and we'll talk more about hubs and switches a little bit later when we get to devices. The physical star topology, it's very common today, and it's easy to implement and maintain, and it's much more reliable than bus topologies because if one node fails, or one connection to a node fails, for instance this one, then the rest of the network isn't affected. In a sort of client-server arrangement, each node is inherently not aware of all the other nodes on the network because the node only has a connection to this central sort of host. Now, the negative aspect of this physical star topology is we have what's called a single point of failure here in this connectivity device. And if that fails, all of the other devices won't be able to communicate. So the benefit is now not everyone has to get the message, and it's easier to, it's sort of really cheap and easy to implement. It's also the most popular because if any of these connections go down, I don't lose connection to the whole thing, unlike the bus where if one of those connections goes down, obviously the connection can't continue. But the downside is that I now have a single point of failure in this central device. Now in a physical ring topology, each node is connected directly to its upstream and its downstream neighbors. So if we're looking at this device, we'll call it A. Those are the upstream and downstream neighbors. It's much like water in an actual like river or stream. The flow of data in the physical ring topology is unidirectional, meaning it only goes in one direction. So the terms upstream and downstream are only used in the ring topology. Now here's the positive in using the ring topology. Because data is received and then retransmitted from node to node, the transmission is guaranteed to be strong and clear because each node is acting as a sort of like booster for the signal. Also, because the data can only be transmitted unidirectionally in one direction, there's no collisions that are going to happen on the network. In other words, if this guy can't send data that way and then this guy's sending this data that way and then they sort of cancel each other out. So we're going to eliminate where problems can occur, and that's going to help administrators determine where an issue is occurring if they're having an issue with the network. Now negatively, if one of these nodes goes down on the network, the entire network potentially goes down as well. And also because data can only transmit in one direction, there's a high potential for data to take a longer time to reach its destination. Because obviously if I want to send data to this guy, but I'm unidirectional, I actually have to go here, then here, then here. Whereas if I was using a star topology, I could reduce that by 1. A variation, by the way, of this physical ring topology that attempts to correct some of the limitations is what's called a dual ring topology. I'm just drawing that out. And a dual ring topology gives a sort of redundancy to the network by having a second ring either on the inside or the outside of the first ring, and it allows data to flow in the opposite direction. So this can double the speed of the network by sending data through the path that's going to be the shortest between nodes. So if A wants to talk to C, or actually we'll call that B just because of where it is, and we'll call this one C. If A wants to talk to B, it knows to take the blue line as opposed to the red line because the blue line is going to get it there faster. So dual rings also allow the network to continue to operate if one of these goes down, which I think you could probably see from this. So if the outside ring fails, then the inside ring can actually pick up the slack for the outside ring. A physical tree topology, it's much like its namesake. As you can see, it's a tree. Each branch of the tree can only receive its signal from its parent node or its linked branch. Right? So all of these can only receive a signal from this guy. The root node is what we call the top portion of the network, and it does not have a parent. So it is the root. Just like a tree, it's the roots. It's directly connected to each of the child nodes, that's what these would be called, by a point-to-point connection. Now, depending on how many levels you have here, and we can see we have 3 levels here, your tree topology is gonna dictate what we call the branching factor is, and this might be a little beyond the scope of the exam, but I'm going to cover it here anyway. The higher the branching factor, the longer it's going to take from data to go from one node through the network to the other, because obviously if this needs to talk to this, then right we're going to have quite a bit of data that it has to go through. A positive aspect of this entire topology, by the way, is that because each level is connected only to its parent and its child nodes, it's very easy to troubleshoot where the problems in the network occur, because obviously if you're having a problem with, this connection over here, you know that none of these have anything to do with it. It's also, the other benefit is it's really scalable. Remember that word? Because obviously if I want to add another network, I can just add it either here or I can add another child here and then just sort of branch off there. Now negatively, if the connection should be interrupted or if a node at sort of a higher level in the chain should go down, then all of these subordinate nodes would suffer. So if the connection between the root and their children goes down, we're going to be in major issue because now none of these can talk. Obviously, if this computer goes down, then none of these will be able to talk to the rest of the network either. So this is a problem with it. It is a variation, by the way, of the bus topology. So again, if the backbone fails, then nothing else is going to work. Now with a physical mesh topology, each node in the network is directly connected to every other node on the network. So if we call this computer A, you can see it's connected to B, it's connected directly to C, and it's also connected directly to D. So for every computer on the network, for every node on the network rather, it's connected to every other node. As a result, because each connection is similar to like a point-to-point network, communication between multiple nodes can happen at the same time, and so it's very efficient, highly reliable, and has minimal data congestion because B and D can talk at the same time as A and C. Now, for the same reason, these types of topologies, the mesh topologies, are very difficult to manage and to maintain because each additional node that's added requires you to connect every single other node to it. So if I wanted to add an E, for instance, look at all of the connections I now have to add to this already existing network. So to alleviate some of the negatives of this type of network, we sometimes have what's called a partial mesh. The partial mesh basically means only specific nodes on the network have to have direct links. This is sort of where we're going to go when we get into hybrid topologies. It's going to limit the number of connections that are necessary throughout the network. So a partial mesh topology would be useful if your network is comprised of, say, like N nodes that don't need a connection to all the other nodes on the network, but it still allows high-end devices to maintain the maximum transfer rates and the maximum amount of efficiency and reliability. The Internet's major divisions are connected to one another by a mesh topology. So we're really going to see this in sort of large-scale implementations that need high redundancy and efficiency, I should add. Now, a hybrid topology, as we've discussed, utilizes aspects of more than one type of individual topology. So hybrid topologies are usually not created on purpose. They're usually actually created out of necessity. So topologies like this are difficult rather to maintain and to manage because each segment in the hybrid topology might have its own set of rules it needs to follow. The technologies on the different segments might not be the same either. So I might have a different type of technology on this segment than I do on this segment, and then I have a different type of technology on this segment right here. So there are a few common types of topologies that are in the hybrid sort of breed that we come across. This one's called a star bus, obviously, because we have stars here, and then the stars are connected by a bus connection. Notice again the terminators on either side. We also have what's called a star of stars hybrid. You can see that each star is connected by another star, so it's not only different topologies, but when we connect the topologies together sort of in different ways, that can be a different hybrid topology as well. And then another popular one is the star ring topology. Similar to bus, except there's no terminators on the end because everything connects together. You might also have a star dual ring topology, which I have seen, although very infrequently. By the way, this one is also called, although I doubt you'll see this, a snowflake topology. Now, network protocols are the controlling factor in how all of these topologies are going to transmit data And depending on the protocol, data might need to be transmitted to all the nodes on the network, regardless of the physical connection. So this is why having a logical topology is different from a physical topology. In other words, the way the data is transferred over the network might be different than the way the physical network is actually connected. So let me give you an example. With this logical bus topology, okay, data is received by all nodes simultaneously, even when the physical setup is different. So for example, we're using a logical bus topology with this physical star. So the central device is receiving the transmission from, let's say, the sending node, which is this one. So let's say A is sending it out. And then it's passing it to each node in succession in a continuous stream. In other words, it's doing this. It's going down there, and then it's sending it here, and then it's sending it there, and then it's sending it there, and then it's sending it there. So you can see what it's doing is, although it's connected in a star physically, the nodes are talking to one another as though they are logical. Now with a logical ring topology, just like with a physical ring, the data is only transmitted between its upstream and its downstream neighbors. So even though the star layout is physically laid out in a certain way, the data from the transmitting device is sent in specific order, one to the next. Now actually most ring networks are physical stars, right? So every time the data is sent, it has to be sent to its downstream neighbor in succession like so. So it just goes in a circular route. We also have, of course, the logical star topology, which can utilize a central device, and it's going to poll each node to see if it has the data to be transmitted. So basically it says, hey, do you have any data you want to transmit? Okay. Do you have any data you want to transmit? All right. Do you have any data? Oh, you do? Great. Then it'll transmit that data and then come back around. So the device ensures that each node has an opportunity to transmit, but it also governs how long that's going to happen for, and it's going to make sure that there's not any sort of problems or collisions with the data. So just to recap what we just talked about, albeit a 5,000-foot overview of it, we talked about topology, which again is like how the network is arranged. That arrangement can either be physical, meaning how it is physically connected, or logical. We then talked about a bus topology. The bus topology meaning that it is connected to each device, one in sequence. We also need to terminate these with a 50 ohm terminator on either side. And remember, we have a T connector that's connecting them. We looked at a star topology, which means that these are all connected through a central device. A ring topology. A tree topology, which has branches. This might also be called, by the way, a hierarchical topology, and so on. And then a mesh topology, which would be every device connected to every other device. And then we also looked at a hybrid of these. Most commonly, we're going to see a physical star with a logical ring. So it's important that as administrators we have an understanding of how the network is designed both physically and logically, in other words, how the data transmits over that physical stuff. Network hardware and media, bounded network media. Having discussed some of the basic terminology and some of the basic network setups, I want to get into now the hardware, the media, how this stuff actually physically connects to one another. So we're going to discuss the different network hardware and media types in this module. So the objectives that we're going to cover are, first, defining network media and specifically bounded network media. Bounded network media meaning the stuff that you can hold, bounded, contained in cords and wires, unlike unbounded, which is wireless. We're then going to describe the different types of copper media and also explain the different types of STP, that's shielded twisted pair, and UTP, unshielded twisted pair. Then we'll describe the different types of coaxial cable types in connectors. And finally, describe fiber optic median connectors, fiber optics being that type of media that transmits data via light and photons rather than electricity over copper. After that, I want to explain the 568 A, B, and C standards, which is how standard UTP and STP is cabled on one end and on the other so that we can plug it in. And finally, explain something called premise wiring and structured cabling. So network media is simply the method or medium by which data will be transmitted. It's further classified based on the hardware and associated technology of the media itself. Now, there are both wired and wireless technologies associated with network media. So in this one, we're going to take a look at the first one, wired network media, which is also characterized as bounded because it is bounded by a cord. So bounded media is media that can be physically held. There are a few types of bounded media that we need to be familiar with. We're going to look at either copper or fiber. Now, bounded network media is the basic and original form of media, and as administrators, you're very likely, if not guaranteed at some point, to have to work with it in one form or another. So having a solid understanding of the different types of bounded media will help you succeed in managing any type of network, whether it's at your home, a small office, or even a very large corporate WAN or wide area network. So the first type of bounded network media I want to go over is copper media. Copper media is the term used to describe any media that uses copper conductors as the method to transmit data in the form of electromagnetic energy. So copper media can come in many different forms. There are also many considerations that need to be taken into account when choosing between these different types of forms, such as distance, the speed requirements of the network, and of course the cost. A lot of the time, copper media is going to be fitted with some sort of shielding, which also looks like braided metal wires, or sometimes it looks like a metallic foil, like you'd buy at the grocery store, but it is a little different. The shielding on the outside helps the cable prevent the cable from being subjected to what's called electromagnetic interference, or EMI. And of course, if I allow EMI or electromagnetic interference to get into the copper within the cable, then that's going to disrupt the sort of data that's going on inside of it. Now, there are two different types of very common copper media that I want to go off, specifically of coaxial or coax, as shown here, and twisted pair. Now, twisted pair cable is one of the most common cable types that you need to be familiar with. Depending on the specification of the cable and the type of twisted pair cable being used, there's going to be anywhere from 2 to 100 pairs or more. Now, the pairs are color-coded so that technicians know how to recable the cables on either end, and it ensures that certain wiring standards and schemes are maintained in case another technician was to come in and start or end the work that you've already begun. Now, all twisted pair cables are basically the same. However, it's how they are terminated that makes the biggest difference, meaning how the endpoints, so what happens at the endpoints. Now, there are two typical types of standards that we need to be aware of. These are T568A and T568B. So we're going to take a look at these right now. Now, 568A It's less common than 568B today in today's networks, but it's still necessary for you to know, and you need to understand the difference between the two of these. And it'll also help you in case you ever wanted to make a cable at home. 568A is wired in this way: green-white, green, orange-white, blue, blue-white, orange, brown-white, brown. Now, the only difference between the 568A cabling standard and 568B is that the first two pins, 1 and 2, are swapped with pins 3 and 6. That means that the orange-colored wires are swapped with the green-colored wires. So then in 568B, we see a wiring of orange-white, orange, green-white, blue, blue-white, green, brown-white, and brown. Now, the reason you need to know both of those is because of something called crossover cables, which we'll talk about. By switching those pins around, it switches the data and how it's sent, and we'll talk about the purpose of that a little bit later on. But for now, let's talk about something called STP, or Shielded Twisted Pair Cabling, which is a cable type that contains pairs of copper strands, like we just looked at, orange, white, and orange, for instance, being a pair, that are twisted together and wrapped with a metal sheath, or a kind of foil that decreases the cable's susceptibility, as we've already mentioned, to EMI. Now, because it's wrapped in its metal, it makes the cable much more expensive than its counterpart, UTP, or unshielded twisted pair, and it can make it more difficult, therefore, to manage or work with. Now, although it has this shielding to prevent it from EMI, it doesn't mean the cable is prevented completely from any sort of susceptibility. It just reduces it. I also want to mention the reason that we have that twisted pair, each pair of cables, for instance, orange and white-orange, are twisted together, is to reduce what we call crosstalk, meaning that so that the data doesn't sort of jump between the two cables. This was something that was actually discovered way back when Edison was dealing with electricity. Now, UTP, or unshielded twisted pair cabling, does not have that metal shielding around the twisted pairs. This is the only difference. Now, this makes the cable much more susceptible to EMI than STP. However, it's so inexpensive and so much easier to install and maneuver with. And in most instances, a lot of folks don't need the extra EMI protection, so it's why it's one of the most common. Now, there are several specific implementations of STP and UDP, and each one has different standards and characteristics and speeds and so on. So let's take a look at those in a little more depth right now. Now, you may have heard of the or seen the terms Cat5 or Category 5 or Cat6 or something similar to this before. Let's take a look at what these terms mean and what the specifications are regarding them, because you'll need to know that for the exam. Cat simply stands for category. There are both STP and UTP versions of these category cables that stand, if you recall, that's shielded and unshielded. And the first category of cable is, as you'd imagine, Category 1 cable. Now, we don't really see this in the field anymore. It's been superseded by the following categories cabling, but its original purpose was for voice. I wouldn't worry about memorizing that one. Cat 2, or Category 2, is rarely used today, only in something called token-based networks, which we'll talk more about in the future. But again, it's not very common. You're not really going to see it very much at all. Now, Category 3, or Ethernet, which is different from the current Ethernet, but this was the first category established by an organization called TIA-EIA. This is the Telecommunications Industry Association and Electronics Industries Alliance. Don't worry about memorizing that. But in today's networks, Category 3, or Cat3, is used almost completely for voice transmissions because it has a limited transfer speed of 10 megabits per second and a 16 megahertz bandwidth. So a lot of old telephone cabling is Cat3. Cat4, just like Cat2, it's not used anymore, not even worth really spending time in. Now, when we get to Cat5, this is sort of where we start really getting to modern day stuff. Cat5 cabling, which is also called Fast Ethernet, provides performance of signals up to around 100 megabits per second. It's important that you know this. The maximum distance for Cat5 cabling is 100 meters or 328 feet. Now, Cat5e is the specification that superseded Cat5, and it addressed some of the weaknesses, including crosstalk prevention and other specifications and the like. Like Cat5, the maximum cable length of Cat5e is also 100 meters. The bandwidth is also the same at 100 megahertz, but it's said that data rates can get up to about 350 megabits per second, although sometimes in application that's not exactly what we see. Cat6 is a standard that increased the transmission speeds quite a bit. It's what's called gigabit Ethernet because it's rated for data rates of about 1 gigabit per second. So we're going from, again, with Cat3 from 10, Cat5 100, Cat5e 350 theoretical, and now we're at 1,000 megabits per second or 1 gigabit per second. The signaling rate also of Cat6 rather is tested at 250 megahertz, but is guaranteed at 200. There was also another one after this called Cat6a, which was also known as Augmented Category 6, and it had a rating of a little bit more than 1 gigabit, but many people said that they could actually get to 10 gigabits, and its megahertz or frequency was also higher. By the way, I wouldn't worry about any of the frequencies. I'm just throwing those in there so that you know them. What you really want to worry about is the data transfer speed. Cat7, which is one of the newest implementations, it's not even fully recognized yet by TIA, EIA. It's also gigabit Ethernet, and it supposedly supports a signaling rate of 1 gigahertz and has a potential for over 10 gigabits per second. So you can see where we want to go there, but at the same time, wireless technology or unbounded technology has taken us to a point where we might not need to spend as much time on some of the bounded media. So now that we've seen all of these individually, let's take a look at an easier breakdown of the specifics of all of these. So as we can see here, each of these CAT standards has a maximum cable length of 100 meters for standard use, and the frequencies and maximum data ranges go up with each of the standards as well. In most cases, when you're looking at the physical cable, the exact specification is typically printed on the cable itself, helping technicians ensure that the same standard is going to be used throughout the organization. Now, while Cat5 through 7 cables are very similar, because they all use the RJ45 connector, which is the connector at the end that plugs into your network card or into a port, should a technician install a Cat5e cable in a Cat6 or higher network, the network's still probably going to function correctly, but the network's only going to operate at the maximum speed of the lowest standard. So if everyone else in the network has Cat6 and you install a Cat5e cable, then you're limited now to the Cat5e specifications. Now here's a picture of an RJ45 connector. I want you to note there are 8 pins, which means there are 4 twisted pairs. And next, here's a picture of an RJ11, which is used for phone lines. And notice that this one has 4 pins, so that's 2 twisted pairs, and it's also much smaller than RJ45. This is what's used in what's called POTS, plain old telephone system, or PSTN, the public switched telephone network. All right, now moving on past CATs and twisted pair, let's talk about coaxial cabling. It gets its name, by the way, from, this is sort of a fun fact, common geometric access, or common core, because the shielding and the conductor share the same center, or axis, as the name implies in common geometric access, or axis. Surrounding the single copper core is a non-conducive, meaning that it's not going to conduct electricity, insulated coating, which is typically some sort of dielectric insulator separating the core from the shielding. The next layer after that is braided metal shielding, And this could be either copper or steel. Sometimes it's a mesh of multiple metals, depends on the manufacturer. The purpose of this shielding, just as it was with the twisted pair, is to protect the cable from EMI or electromagnetic interference. It also allows the cable to be grounded and acts as sort of a drain when there is noise on the line. We'll talk about noise in just a few minutes and also ways to prevent it. The final layer on the coaxial cable, as you can see, is this outer sheathing or a plastic insulating jacket, which just sort of keeps everything protected from the elements. Now, there have been several types of coaxial cables used in networks over the past few years. Here's a breakdown of what you should be familiar with. The first is what's called an RG58U. It was used for Ethernet networking, actually. If you see old network cards, you'll actually see a coaxial cable on them. And it has a solid core and requires a 50 ohm resistor, and it's about 5 millimeters thick. This is different from the stuff that brings cable into your home. And if you remember 50 ohm resistor, that is what was used on a bus topology, and that's why where we actually used most of these was on a bus topology. Now, the RG58AU is slightly different in that instead of having a solid core, it has what's called a stranded core, which means there are multiple strands or cores at its center as opposed to one solid one. Next, and this one might be a little more, we're going to get a little more into some that you've probably seen, is what's called the RG8 standard. It was also used for Ethernet networking, but it's not seen very frequently today because it's typically was used for backbone wiring. Which has largely been sort of superseded by fiber optics. Finally, we have RG9 coaxial cables, which are used with cable TV, cable modem installations, and so on. It's about 10 millimeters thick, which is twice the thickness of the original RG58. Now, we're getting into some others here that I wouldn't worry too much about for the test, but I just want to go over them since we're covering these anyway. We have something called RG62 cabling, which is utilized for something called an ArcNet protocol networking. It was a LAN protocol commonly used in what was called microprocessing. And then we have an RG59 cable, which is used with low power video and receivers, and it had also resistors, and it was about 6 millimeters thick. The RG6 cabling, which is greatly preferred, by the way, over RG59, because it's more common, is utilized for cable television signal routing and also requires 75 ohm resistors. The term, by the way, thin net, is in reference to Ethernet networking that uses the RG58U or AU cabling. These thin net cables, coaxial, and the reason they're called thin is because that thin 5 millimeter coaxial cable can be up to 185 meters in length, which is quite different from the 100 meters we got with Ethernet twisted pair. Network segments that utilized coaxial cabling have to be terminated at the ends, like we've talked about, to provide that signal bounce from occurring. They're terminated by installing that resistor that matches impedance, that matches the impedance of the cable on the ends. So, as we've mentioned, some of these are 50 ohms, 60 ohms. On a typical bus topology network, we're looking at 50 ohms. Now, here's a visual of what the most common coaxial connectors are. First, we have a picture of a BNC connector with different types of resistors attached. If we look closely at the top connector, you can see the small needle at the center is just slightly bigger than the 50 ohm on the bottom. This is important in case you have a 75 ohm, which is plugged into a 50 ohm, because there's going to be a potential of damaging the connector that's being received. Now, this next picture is a shot of a T connector and a terminator. Remember, we talked about these when we were talking about bus topologies. And when purchasing these, you want to make sure you check that they're properly rated because, every manufacturer has different color schemes and different types of ways of categorizing their terminators. Now, moving away from copper cabling, which is what twisted pair and coaxial is, let's look at fiber optic cabling, which is cable that uses pulses of light sent down glass or plastic core. The components in fiber optic cables start out from the center working their way out. So the inner strengthening rod gives the cable its most of its rigidity. Otherwise, we would just sort of crack this stuff because it's very thin. So we have something that's going to strengthen the rod. And then the outside of the inner strengthening rod, there is filler compound in between the strands of cable. At the center of these individual strands is the fiber core, which is between 5 and 100 microns in diameter. And I don't know if you are familiar with that term micron, but that is very small. That's roughly slightly larger than, like, I think a human hair. So just to give you a context there. Surrounding the glass or the core, which might be made of plastic as well, is what we call core cladding, which is responsible for trapping the light in the core and reflecting it in a particular way depending on the cable mode. And on the outside of the core's cladding, there's a buffer that is color-coded so a technician knows which strand they're working on. Next, we have strengthening fibers that are typically made from very strong material. And finally, on the outside is an outer protective layer called the jacket. The transmission method, again, utilizes pulses of light. These lights can come from LEDs or light-emitting diodes in cases where there is a slower network, or in network with a much faster connection, we might even have a laser. Now, there are different types of fiber modes, and as a Network Plus administrator, you need to be familiar with the different methods of transmission for each. In single-mode fiber, only one single beam of light passes through the core. Now, a bandwidth of up to about 30 megahertz can be reached, and the signal is modulated by intensity to transmit data. So the intensity determines the data. With the next thing we look at is step index multimode fiber. The core of the fiber and the clouding surrounding it, have different indices. By the way, if you're not familiar with that word, that's the plural for index of refraction. If that's a little confusing, that means that they have different densities, which changes the speed and velocity of the light that travels through the medium. So when the velocity changes, it's called the step down. This is why we have step index. Finally, we have something called graded index multimode fiber. This has a glass core rather, that itself has differences in variations in the form, and that allows for a large amount of bandwidth that reaches up to about 2 gigahertz. Now, the thing I want you to remember most about single mode versus multi-mode, I wouldn't worry so much about the graded index and step index, but what you do want to remember is that single mode is good for longer distances, but not as high transfer speeds. Multi-mode is good for short distances and higher transfer speeds. Think about it this way. If I have a very large bus, I'm going to be able to carry more people in a shorter distance. If I have a sports car, I might be able to carry one person or two people, but we'll go a lot faster. So you can think about it that way. Now, ST connectors or straight tip connectors are one of the most common you're going to see today. They look very similar to the coaxial BNC connector. And one way you can remember it is you have to twist them on, and I think about that T for twist. The SC, or otherwise known as a subscriber connector, is also one of the most common connectors, so you want to recognize that one as well. We also have something called the LC connector, which looks almost like an RJ45 type connector, and it snaps in place. It's also about half the size of an ST and SC connector. I also want to show you some of the other connectors that are listed on the outline, although I don't see them much on the exam. An MTRJ, or mechanical transfer register jack, which is also called a fiber jack. It's, again, just like the same size as an RJ45, and it's usually used to connect two strands of fiber together. There's also a few other connectors. FC, which is face contact. It's used in industrial environments. It has a different center that sort of gives it more strength. There's also something in this you will see is called FDDI, or Fiber Distributed Data Interface, which can also be called MIC or SMA or Sub-Miniature Assembly, all these different names. It's an older connector, and it's one of the original connectors that was used. Now, because of the different technologies that are available for networks today, it may become necessary to go from one type of medium to the other. In some of these cases, we have to utilize what's called a media converter. Here are a couple common media converters you may have come across in certain networking environments. Now, there are media converters that convert signals on fiber to coaxial cable when you're converting multi-mode fiber into Ethernet in order to extend the Ethernet network over a fiber backbone. We also have, similar to multi-mode fiber, there are also converters that go from single-mode fiber to Ethernet as well, which is for the same purpose. Generally speaking, we're going to see more multi-mode in the backbone environment because it's a shorter distance, high throughput. Lastly, there's also a single mode, which converts to multi-mode fiber. These connectors are generally used to extend the range of multi-mode signals. Now, the TIA, EIA, which we've already mentioned, the organization, Telecommunications Industry Association, Electronic Industries Association, created standards for all this cabling that covers the proper implementation, design, and maintenance to ensure that there's a certain level of performance that's met, and that's also going to ensure that if someone else comes into your environment, they know what they're getting themselves into. Now, there's the standard is comprised into 6 different categories, and it's important that you actually know these for the exam. This, by the way, is called structured cabling. So first we have something called entrance facilities, and this covers the entrance of the communication service into the building, and this includes what's called the demarcation point. The demarcation point is that point at which the responsibility of the network changes from you to your ISP or from your ISP to you or your company. It also contains the backbone connections as well. Next, we have the backbone wiring, which is the wiring connection that goes from the communications closet to the equipment rooms. So the characteristic of this wiring is going to depend on the type of media chosen, such as copper or fiber, but nonetheless, we need to make sure it's very sturdy and also very fast. The equipment room now, so we've gone from demarc to backbone, or we've gone from entrance facility or demarc to backbone to equipment. The equipment room is the point of termination for the backbone wiring. It's also called the MCC, or the main cross contact, and this can also be considered, what I've seen it more considered on the Network Plus exam, the MDF, or the main distribution frame. We're going to talk more about this shortly. The next portion of structured cabling are the telecommunications closets. So these contain the connection equipment for any of the nearby workstations, as well as the connections between any communications that cross-connect. We also have something called horizontal wiring, which is the cabling that goes between workstations in the telecommunications closet, and this is typically in the wall and the ceiling. Finally, we have the work area, which is everything coming from the wall outlet to the workstation. So this is the faceplate, connectors, wiring, and so on. So you can see that we're going from the sort of main point in our building, that entrance where the demarc happens, where the ISP, the internet, comes into our building, all the way down to the workstation or the user. The TIA EIA has also set out a specification of standards that line out minimum performance levels for network media in commercial environments. Now, these standards are 568A, B, and C. We saw earlier the T 568A and B, which were the standards for cabling colored twisted pairs and how they should be arranged and terminated. But there are also some other specific attributes that you need to be aware of. The 568A specification is an older standard. It governed data, voice, video in commercial buildings, and it's basically been outdated and superseded nowadays by 568A, B and C standards. The B specification now is an earlier standard, still in use quite frequently, that defines minimum performance levels for cabling, including twisted pair performance minimums, shielded twisted pair minimums, fiber optic standards, and etc. Portions of this are now obsolete and have been replaced by 568C. The 568C standard, which is the current specification that's set out, designates minimums for optimizing network media performance in commercial buildings. Currently, it specifies Cat6a as the media type that is recommended. So again, the 568A and B, the T568A and B that we saw earlier, those are how everything is cabled. Those fall under the umbrella of the more general 568A, B, and C standards, which speak more to performance. Now, while the TIA and the EIA have established standards for structured cabling, premise wiring, the terms that we're going to use are industry-wide. So although there might be these standards, the terms you're going to see over and over again. Hierarchical cabling is recognized and used, which is what we're talking about when we talk about premise wiring, everywhere. It's a telecommunications design tradition that basically allows for main cross connects, or MCCs, to be connected to what are called ICCs, or intermediate cross connects, in a star topology with horizontal cross connects. In most cases, you're probably going to see the terms wiring closet, MDF, or main distribution frame, and IDF, or intermediate distribution frame, instead of MCC and ICC. However, they're both used interchangeably. So I just want to take a look at some of the components that make up this premise wiring right now. The patch panel is the connection point for drop cables and patch cables. They're connected to the patch panel via the RJ45 connectors that we saw with Twisted Pair. Now, you might find a patch cable with a single row of connections, or one with a dozen or more rows. Now, a drop cable, what I just mentioned, is the cable that goes from the workstation and the network devices to the wall. A patch cable is a cable that is connected to the patch panel and connects to drop cables. This cable might be either a normal straight-through cable or a crossover cable, which is something I mentioned earlier. That crossover cable has one end that has the 568A wiring and the other end that has 568B wiring. This is in order to connect two like devices, such as computers or switches, directly to each other. Remember, the pinout on these is different because the 1 and 2 pins are switched on one end with the 3 and 6 pins. So this allows data to go directly between two devices. A lot of devices nowadays, however, don't require the crossover cable because they have an auto sort of sensing feature within them. Now, a patch panel and patch cables are located in wiring closets. The IDF is the communications connection point, or cable rack, that connects all the workstations to the MDF, or the main distribution frame. The main distribution frame, MDF, is the main connection point or cable rack that distributes cables from itself to all the other IDFs. Now, there's only going to be one MDF, but there can be many IDFs. The wiring closet is a room where the patch panels are installed and the wiring runs through it too. So here we have a building where we have an MDF on the bottom floor and an IDF on each of the floors above. The connections going from the IDFs through the walls go to the workstations. Then there is a connection that's typically much faster than the rest of the network that goes between the IDFs and the MDF. When installing cable in a building, there are fire code requirements that have to be met. Specifically, when you're running cable in air handling spaces, which are like under floors and in walls, most of the fire codes require a specific cable. PVC cabling, which is the typically standard network cable that's fairly inexpensive and easy to work with, allows fire to travel through the cable if it burns, and then it releases these poisonous and noxious fumes. So, as a result, plenum-grade cabling, which is part of the plenum, or a plenum space, is part of a building that is used for air circulation and HVAC systems and so on, by providing pathways either that are heated, conditioned, or have return airflows. The space between the structural floor and the drop ceiling, or under a raised floor, is what's called plenum. So we have some special cabling called plenum cabling. This has jacketing that's wrapped around the wires very tightly, and it prevents fire from moving through it. Therefore, it's not going to put off those noxious and poisonous fumes. It also makes the cable a lot more expensive, and it can be a lot more difficult to work with at times. However, it is required by fire code that if you're running cabling in between these spaces where there is no sort of sprinkler system to put out the fire, that you use plenum grade cabling. That's important. All right, so now let's go over what we learned. First, we defined network media as well as what bounded media is. We're going to talk about unbounded media a little bit later. We also described the different types of copper media, including the different types of shielded twisted pair and unshielded twisted pair. And the difference between those, remember, shielded, it protects from EMI, unshielded does not. And we discussed a few of the standards that are set by the TIA EIA, including 568A, B, and C. And remember, we also have the 568A and B wiring requirements, which fall under these. We also looked at the different connector types, not only for the twisted pair, which is that RJ45, but for coaxial, like the BNC, and fiber, such as ST or SC. And we looked at structured cabling and premise wiring, where we also talked about the differences, and this is important, between PVC cabling and plenum grade cabling.
Welcome to Module 2, Lesson 1A, straight through crossover and rollover cables. We've actually covered some of this already in earlier lessons, but what I've done is added upgrades for the new exam syllabus. So consider some of it a refresher and some of the new material. So we're still under network hardware and media, bounded network media. A few of the objectives, looking at modular connectors, the T568A and B wiring schemes, MDI and MDIX, straight through cables, crossover cable, and then auto MDIX, which is a bit of a mouthful. And another cable you'll be using regularly as a network engineer, which is a rollover cable. They've got different names actually. They can be called console cables if you're working in the Cisco side of things. We tend to call them rollover cables or flat cables, but I'm sure you'll find out wherever you end up working what they're called. So modular connectors, a type of electrical connector that's commonly used in the following systems. We'll see these in telephone systems, data networks, which is what we're more interested in as network engineers. Low-speed serial connections can also use them. Known by the following names: RJ, which is short for registered jack, modular phone jack stroke plug, Western jack stroke plug. Just go back there, you can see the port, which is the interface that the modular connector goes into, and then the physical layer, which will specify a whole bunch of things like the voltage on the wire and how many wires and what each wire is used for. Some of them are unused, and as the connections get quicker, the engineers worked out how to use spare wires to increase speed, which we'll see in a bit. The male modular connector is known as a plug. Basically the cable is terminated inside here. Normally you do buy these, however if you become a cabling engineer, you can have your own tools to make your own network cables. I did it for a while. I can't say it was particularly a lot of fun, but it did pay pretty well. A female modular connector is known as a jack or socket, used on fixed locations such as on equipment. Example of the modular connector is the 8P8C connector. I think Josh may have referred to that elsewhere. But here we go. Here's an image of one used in Ethernet computer network that uses the twisted pair cables for connection, which is pretty much every network now, unless you went into some old basement or some old unit somewhere. Commonly referred to as RJ45. It resembles the connectors you'd have on many phones we have at home, which uses an RJ11 telephone cables, but as time goes on these will all be changing, and I think a lot of people don't really even use their home phones much anymore. Has nothing to do with the actual RJ45 standard. Looking at the T568A and B wiring schemes, these are the specifications in more detail. It's a 4-pair 100 ohm unshielded twisted pair cable, usually terminated into an 8-position modular jack. Now there's 2 wiring schemes, 568A, 568B. This defines the pinout and the order of the connections, and this is very important. We can't just connect any colour cable inside and attach them to any of the pins on the end. There has to be a specific order depending on what we're trying to achieve. You can obviously buy the cable. It comes off big rolls, could be a few hundred meters long, and it's twisted into 1, 2, 3, 4 pairs there, and they can be just untwisted slightly at the end, and then you can see the blue shielding there is normally inserted just enough so it catches inside the jack, and then you've got a crimping tool which squeezes it onto the plastic connector on the end. Now we, as I said, we need to know which wire of the cable connects to which pin, which wiring standards we use. The T568A and B standards govern the assignments of the wires, so it says which wires go where. Now here's a graphic. You can see the pairs are put together with similar colours, and then the specific colours allocated for each pin, going from 1 to 8. So white and green, green, white and orange, blue, white and blue, orange, white and brown, and then brown. You can see different pins on the right because we've got a different standard. Yes, and I've put on here which one's which. So there's an interchange of green and orange wire pairs between the 2 different standards. Now I'll come to horizontal cables in a minute, because you don't actually hear this term very often in internet working, and I hadn't heard of it for until I come to put all the information together for the presentation, but it's a recognised name even though it isn't used very often. So the 568B pinout became widely used because it matched the older AT&T pinouts, and you can see the standard there. Widely used in UTP cabling at the time the infrastructure regulations and numbers were published. Just for your information, you can research in your own time if you want, but you can see horizontal cabling in action here. Generally it's the cabling that runs between all the user devices, the patch panels and the network switches. Now however you've got your network designed, you'll normally group the switches together with what's known as backbone cabling. So that's it in image format. There's a definition which I got from Wikipedia. It can be the inside wiring or plenum cabling, connects your telecoms rooms to individual outlets or work areas on the floor, usually through the wireways. So this is the part of the cabling that you would normally be concerned with as a network engineer, and then the core cabling, the backbone cabling, may well be done by a cabling company. It's not something that you would normally get involved in. Again, it depends, every network's a bit different. Moving on to MDI and MDIX. Devices on Ethernet networks use 2 types of hardware interfaces, which I've already mentioned here. The MDI, it all stands for medium dependent interface. It's a hardware interface that establishes the direct physical and electrical connection with a UTP cable. This is the traditional port on the back of a computer's network interface card. An MDI device is a device with an MDI port, which kind of goes without saying, I guess. A computer or laptop. And this is a reference for specifications, really. I mean, in all the years of networking, I've never referred to a device as an MDI device. Tend to discuss it more when we were using hubs in the earlier days of networking. The MDIX stands for the MDI, but with a crossover. This is a crossover of the medium dependent interface. I'll show you an image actually in a moment. The ports of the devices that provide connectivity, such as a switch or hub, are set up as a MDI with the crossover. So examples of the devices are switches or routers, and I've put in an image here to give you more a frame of reference. You can see here it's the front of an old fashioned Netgear, maybe they don't even sell him anymore, hub, and you can see to the right there's a little black switch with a little line that connects to the number 4. Now however you press that button, it will act as an MDI or an MDI-X interface. Now if you wanted to connect that number 4 port to a PC, you would leave it running in normal mode. You might be able to see the actual word normal, it's a bit blurry this image. So this is MDI, and they've put normal because you probably wouldn't be a network engineer using it at home or a small office. The MDI-X they've designated as an uplink. That means you would connect it to another hub, and so it would change the way it communicates using the different pin outs, and it would act as if you were using a crossover cable, which we'll come to later. So this is basically what I've said. It's going to, using the button, you would designate whether it's going to act as an MDI or an MDI-X interface. This all basically changes how we use our transmit, which is designated as TX, and our receive, which is designated as RX on the different wires, and that's what that setting would do. The straight through cable, the easiest way to think about a straight through cable is using dissimilar devices. For example, a computer to a switch port, a router to a switch. Here's some examples, also known as a patch cable, in case anyone asks you to check a patch cable or get them a patch cable. I've mentioned UTP cables. They're used in the modern Ethernet networks. You can't directly connect, and this is stating the obvious I think, but you can't directly connect these wires to a computer's network interface card. If you want to be picky, I suppose you could if you had a soldering iron and individually soldered each wire, but that would just be a little bit of an act of desperation, not someone who desperately needs a plug. So both ends are terminated with the IP8C connectors, and you can see the two wiring types here using that IP8C connectors. Now the pins and the wire assignments are the same on both ends, so we know this is a straight through cable or a patch cable. The numbers match, and well, that's just a number of the pins. The colours of the different wires inside match, and that's how you could tell. You would hold the cable together if you didn't know, if you wanted to see if it was the right kind of cable. Hold it up, look at it, and check that all the wire colours match. The wiring standards for the RJ45 is the 568A and B. They specify how to wire the actual connector over an Ethernet network. Technically, you could choose any order of colours you like if you were making your own cables, and as long as it matched the other side, then it would all work, because the cables inside the 8 little wires are all exactly the same. But you wouldn't obviously be following the standard, so maybe you could do it for your home network if you wanted to make your own cables, but certainly not recommended for commercial networks. So only one of the following standards is used for terminating ends of the UTP. You could choose either, but I think I mentioned earlier the recommendations for the horizontal cables. So the example of a straight through cable is computer or a server connecting into a switch port. I've already mentioned that you wouldn't use both standards on your cable. Straight through cables are used when connecting to an MDI device or an MDI device to an MDI-X device. And again, we've seen this is just zoomed in and giving you a better detailed image of the cable type here. If a straight through UTP cable is terminated on both sides using the type A wiring, then the A colour scheme should be, so I'll say that again, then the colour scheme and the pin out, the order of the connections will be shown in the diagram. So this is the A standard, and you do it a few times for a few days, and then you probably have it in your memory of what order to put the wires in. Again, if it was you making the cables, which would only really happen if you were a cabling engineer for a very large network. And there's the pinouts and the colours in more detail. You can see the transmit and the receive indications on either end there. So when a computer uses pins 1 and 2 of a pair of wires to transmit, the switch will receive those data on the same pins. When a switch transmits the data using pins 3 and 6 on a different pair of wires, the computer will receive those. So you can see a TX is going to an RX and vice versa. In an Ethernet network, such as a 10 base T or 100 base TX, pins 4 and 5 of the blue pair and pins 7 and 8 of the brown pair are not used. So technically you could have a cable that doesn't have connections on those pins there. Now you're more likely to be using a faster connection type if possible. So on the 1000 base T Ethernet cable, such as Cat5e, all 4 pairs of wires will be used, and that's how they get the faster speed but using the same cable types. Now the crossover cable you can see here is used to connect like to like. So if you had 2 switches, then you could connect them using a crossover cable. 2 router Ethernet ports, you could use a crossover cable, or if you had 2 PCs at home and you didn't want to pay for a switch, you could also use a crossover cable. Used to connect the following MDI device to an MDI device. You could also connect 2 switches together, as we have here in the diagram, the MDI-X device. Okay, wiring for a UTP crossover cable. Easiest way to remember is 1 goes to 3 and 2 goes to 6. Everything else stays the same. You can see that rule applies for both sides, so left to right and right to left. A crossover UTP cable has an 8-pin modular connectors, each ends terminated in the below manner. Okay, so these devices will be transmitting on the same pins 1 and 2. These devices will also be receiving on the same pins 3 and 6. Might be worth remembering that in case that pops up in the exam, which ones are receiving and which ones are transmitting. Okay, pin 1 on one side is connected to pin 3, that's what I said, and 2 to 6. Terminating the crossover, you would terminate by using the 568A wiring on one side and the B wiring on the other. So using 2 different standards for either end. If one end of the cabling uses the A standard, the other has to use the B. That's if you're making the crossover cable. Auto MDI-X. It's auto sensing. So do you remember earlier we had this picture of a hub and you had to press this, the little switch on there? Well, modern devices can actually auto sense what type of cable is attached and then change the designation for how it uses which wires on the 8 pins on the inside. And most modern Ethernet devices, for example switches, use the Auto MDI-X feature, so it's pretty handy. This is why sometimes you can plug the wrong cable into a switch and it all still works because it's got this automatic feature. Rollover cable is something you will have with you normally at all times as a network engineer in your briefcase, and normally used to connect your PC or laptop to the console port on a router or switch, and it lets you configure the device when you first buy it and it's blank, or do emergency recovery, for example if you've forgotten a password, to configure the router or switch. So it has an 8P AC connector, RS232 based connector such as a DB9. This has actually changed now, so you can see the DB9 connector. Your laptops don't actually come with DB9 connectors anymore, it's pretty old fashioned. So what you'll do is you'll have a DB9 to a USB connector, and you'll use one of your free COM connections using Device Manager to see which port to connect on. So I mentioned Cisco console cables and recovering your Cisco router. In order to, you can make your own rollover cable, rollover flat console, same thing, cable. and the wires are basically reversed, so every wire goes to the opposite number. 1 goes to 8, 2 goes to 7, 3 goes to 6, and carry on with that numbering. So basically the whole thing's twisted somewhere in the middle. Alright, so we've covered modular connectors, the A and B wiring schemes, MDI and MDIX, straight through, and crossover cable, auto MDIX and rollover cables. So that's all we need to look at for now. Thanks for watching. Welcome to Module 2, Lesson 1B. Some more cables, connectors and transceivers. This is all new stuff that's landed into the Network Plus syllabus. Some of it's a little bit strange in as much as it's almost redundant, but I'm guessing they want you to know this stuff in case you come across it in an environment for whatever reason. Alright, so network, hardware, media, bounded network media. A few things we'll be looking at. Copper connectors, the stuff we haven't already looked at earlier, by the way, transceivers, some termination points, copper cable standards, network storage connection types. So this is it used to be called D sub actually, but it seems to have been hijacked into DB connectors. But you can see the shape of the connector here is like the letter D really, but on its side. Kind of like that. So the theory is you can't plug it in the wrong way. I say in theory because when I've ran computer courses, it might just be a Cisco thing because this looks a little bit thicker, but the Cisco housing here was so thin that the students would come and somehow manage to plug in the D connector for the serial cables upside down. Now this did a couple of things. Things don't work when they're upside down obviously, but these tiny little pins, they're much smaller than the ones you see here. They actually got forced in the wrong way and all got bent like that, so that actually cost me a lot of money. It was quite distressing when I started up my business. So this is the theory behind the shape anyway. I don't know why I put in two male connectors here. I wanted to have one female, but I put in two male. You used to see these on the back of old style PCs and their laptops as well. You don't really see them anymore because USBs replaced all of it, so you'd have to be looking at a fairly old machine. They were created a long time ago, before I was born, when my dad was a young man, as they used to say. 1952, exclusively by Canon, and it looks like they've probably released a license so that people could use them. They were used in token ring networks. I do remember those. I actually supported those for a while at Cisco, although there was hardly any left. It was pretty scary when somebody called in with a token ring issue. External floppy drives, if you remember those, you'd buy an real old, probably wasn't even a PC then, it was an Amiga or Commodore 64 or something, and you could invest extra money to put these floppy drives in. And if you wanted to load a game, you'd probably have to individually insert, I think it was around 10 floppy drives to upload each part of the program. And I think I had to do that for early versions of Microsoft Word or the equivalent. Used in mouse connectors also. As I said, eventually replaced by USB, thank goodness. The D shape, so I've covered this already. The theory is, in fact I'm sure it works for most people. I'll just give you a heads up that when I ran Cisco it didn't work that way. But I wanted the students to plug their own cables in to have their confidence, but it kind of backfired a bit. Designed to work with the EIA TIA 232 serial interface standard. I guess you should make a note of that for the exam. Sort of silly question would be asked. The number DB whatever, so what would DB9 or DB25? This is supposed to refer to the amount of pins that are in the male and female parts. So it'd be pretty hard to mix them up actually, looking at them. You're more likely to see the 25 on like a printer cable, something like that. Again, if you see it at all. Now the F connector or F type has been added to the syllabus, not to be confused with fibre cables such as ST, LC, SC, which are covered elsewhere in the course here. So it's a coaxial RF connector type, used more commonly for cable, satellite TV. If you've got the back of a box, you can see here there's a thread on the inside of the cable here, and you'd have to turn it round and it'd lock in with the nut here, so you'd have to, hopefully with enough finger pressure, be able to secure it into place and then unscrew it as and when you need to. TV antennas for those users that aren't using your broadband or Ethernet or whatever. Bandwidth could go up to several gigahertz. Punch down blocks. This is a pretty tricky skill really, and one that takes a bit of time, but you can see here the cable has just been placed in between the runners, and then the punch down tool has kind of got this shape, as you can see here, and this would force the cable in, and the theory is it would strip back some of this coating for the wire and create a contact inside the punch down block. Takes a bit of skill, and it's quite frustrating if you don't do it right, or if someone hasn't used the correct tool. It leads to this nightmare of intermittent connectivity that you'll have to go and troubleshoot. You'll typically see this inside telephone switch mechanisms. Copper wires punched down, as I said. The numbers are for these models are given are 66 block. It's a model number, so it doesn't mean there's 66 connectors. That particular one has 55 rows. It was subject to crosstalk, which is known quite well in the industry. Had a reputation for that. Not suitable for high-speed connections of 100 meg or higher. Now the 100 block replaced the 66 block. So just remember the numbers here, the 66 block. Hopefully they won't try and catch you out with the question saying it's got 66 connections in. It's a model number, just to confuse you. Often used, the 100 is to terminate cable runs. The fiber distribution panel, hard to get images of this, but I've got one that you can actually buy from the manufacturer. This one obviously hasn't been set up at all. It's a bare bones system that you would run all of the cables through here and then terminate. So this is also known as the fiber distribution hub if you're searching for one to buy. I think they give you different terms depending on which part of the country you're in or which country. And at the bottom here I've got a URL for a particular company that sells them. Obviously speak to the sales advisor and find out what you need. Saves you making expensive mistakes. This is the patch panel used to terminate fiber optic cables. Access to the cable's individual strands, so the strands inside the cable for cross connection. Now I do apologise for this, however it's in the syllabus now for some crazy reason. Previously we had other RG standards. I think it was RG9 and RG58. I'll have to check. You can see it in earlier presentations anyway. However, now they've asked for RG6 and RG59. So I've highlighted what you need to do. I suggest you make some notes as to impedance, which is all the same actually, so it shouldn't be too easy. Shielding here, and then just make a note of what they've said here. So RG6 /U, what it's used for, the UQ. Again, this is just such a pain, and it's silly because if you were having anything to do with this, you'd check the documentation before you went on site. It's very unlikely most engineers, if you asked most network engineers, what can you tell me about RG59 /U? There's probably not a lot they could say. However, I don't make the rules, it's in the syllabus, so just take note and just chalk that up to something you're going to have to learn. Transceivers, I've got some images here. These are for the SPF, SPF Plus and GBIC, which are connectors for Cisco equipment. These these would stand proud from the switch chassis, and then this would be inserted in and make contact to the back of the chassis. So here's the front of the chassis here, and you wouldn't actually see the back. And this has got a nice thin slot that you would insert to. Here, I'll do the 3D version. So transceiver is short for transmitter receiver, as we mentioned earlier. It converts the electrical signals from one type to another type, so serial to optical signals and vice versa. The Cisco Gigabit Interface Converter, we call them GBICs, is hot swappable. So you pull it out, push it back in again. Hot swappable here is very handy, and I think we'll come to this later actually. Trying to find my cursor. It means you don't have to power down your unit, which is just absolute gold if you're working in a production network, because it's just horrible, especially if you've got paying customers that are paying for 99.999 recurring uptime, and then you tell them you've got to power down the device they're connected to just to swap out something. So very handy. Plugs into the Gigabit Ethernet port or slot. SPF stands for Small Form Factor Pluggable. It's a Gigabit Interface Converter. That too is hot swappable. Bear in mind, what you've got to do is check for bugs. So if, say for example, you've got a Cisco device and you've read the documentation and it says hot swappable, you ask them to do, if you've got a contract, a bug sweep for the say for example this with the model, so say WC36, whatever the model is. You say I've got this switch, this model, it says it's hot swappable, just do a bug sweep. This is I only tell you this because, and this is the advantage of having someone like myself, not that I'm boasting, but I worked at Cisco and we had a customer who asked one of our engineers if something was hot swappable. The documentation said it was, however, not that it was his fault, there was a bug which he didn't know about, and the customer hot swapped it, brought down a core switch. It caused a massive amount of problems. There was, I think, some legal claims or whatever. It's just headaches you don't need. So if you've got the contract, just because it says hot swappable, don't necessarily take that on face value, and if you can, log a ticket or do a search. SPF Plus is the enhanced version. The hint is in the plus, that supports higher data rates, this time up to 16 gigabits per second. And then finally, I don't have a picture here, quad small form factor pluggable, and you've got different speeds. Just check the documentation on that. I just wanted to flag it up. I think it's actually in the syllabus also. So we've just got the GBIC module here, and you can see the chassis would actually be here, so you wouldn't see all this typically, and then you'd have obviously the slot here. And I mentioned that only the end bit would be proud, and you've got two fiber cables in here. I'm not sure what this model of the model is that it's actually plugging into. We're just having a sneaky look here at the circuit board. It's SPF Plus, and yeah, so just so you can see it working in an actual device, and however you would set this up, I'm not sure if this is these have been linked together or the one's operating as a backup to the other. So you can see what it would look like on a live environment. Network storage fiber channel over Ethernet. It basically encapsulates fiber channel frames over Ethernet. It's a protocol in its own right, and it was developed just specifically for this environment. And you can see the fiber channel over Ethernet is working in this part of the connection here. And then it looks like we've got Ether channel here, which I don't think Ether channel is specifically covered, but we do. There's a part of the syllabus that covers increasing your uptime. I can't remember what it's called now, but there's redundancy we do talk about later. So it's a non-routable network protocol, so it won't go, whatever your connection is, it wouldn't be carried out here to the internet. it wouldn't work. It'd be converted, something would be converted to BGP or whatever you're using out here. Differs from iSCSI, which runs over TCP/IP. Again, this is non-routable, so I doubt very much whether it would be working over TCP/IP. And then just to tick the box, InfiniBand, it's added in the syllabus. There's a diagram here I got from Mellanox, whoever they are, just so you could see a topology of it working. Used in high performance computing. Just think of exam questions basically. Why is it used? It's high performance, low latency, so if it meets your requirements, you'd consider using it. Direct or switched internet connection between servers or storage, so it can be server to server, server to storage. Alright, so we covered a lot of ground, but we're just topping up on what we already learned earlier. You learned about some copper connector types, transceivers, so it'll convert one type of connection to another. We talked about the DB, the DB9. I think the other one was 25, the D connector, and basically the shape is there, hopefully, so nobody plugs things in the wrong way. That's the only reason. Termination points, copper cable standards, which is the F standard I think we talked about, which isn't fiber. Could be FIBER or FIBRE, depending on where you are. And then the network storage connection type. Alright, so that's all for now. I'll look forward to seeing you on the next presentation.
Network hardware and media. Unbounded network media. As we just discussed, bounded media is that media or cabling that is bounded in the limits of a cable, something you can hold. Unbounded media, as the image here describes, and the image right here describes, is wireless in nature, meaning that there isn't any sort of cord that you have to rely on. And therefore, it allows for certain advantages and also certain disadvantages. So we're going to look at the hardware and unbounded media types involved in these sort of connections. So the objectives for this module are to define unbounded as opposed to bounded network media. We're also going to define the difference between radio networking and broadcast radio. Look at something called spread spectrum, which was created in order to help wireless technologies work more efficiently and effectively. We're also going to look at IR or infrared connections, Bluetooth connections, and microwave connections, all of these different types of unbounded media and devices. And then we're going to look at something that most of you are probably more familiar with, a wireless access point, also WAP. And then we're going to describe the characteristics of an SSID, which many of you might know as the name of a network, also called the service set identifier. And finally, we're going to look at the basic ways of properly installing an access point. And by properly installing an access point, of course, we're referring to the Network Plus methodology of installing an access point. All right. So unbounded network media is any network media that's not bound by a physical connection such as copper or wire, fiber that we've just seen. The unbounded simply means it's wireless, or it's using a sort of wireless technology. Now, using unbounded media has some specific advantages, such as it's easier to install and manage over its bounded counterparts because you don't have as much stuff to deal with. In the same regard, however, unbounded network media has the potential to be less secure than bounded. And actually, a lot of folks will say that there is no way to have a secure wireless or unbounded network because traffic across the network can be intercepted a lot easier when it's wireless and anyone can just sort of tap in. In radio networking, data is transmitted as RF or radio frequency. So one of the first forms of communications, these signals of RF waves were transmitted in the 10 kilohertz to 1 gigahertz range. And in the US, the FCC, or the Federal Communications Commission, regulates these radio transmissions. This kind of networking is unfortunately very susceptible to EMI, or electromagnetic interference, which we've seen previously, especially from stuff like power lines, metallic obstacles, even atmospheric conditions. Some people tell me that they lose connectivity when a plane flies overhead. Now, radio networking can also be very long range depending on the method of transmission, the amount of power behind the signal, the kind of antenna being used, the portion of the frequency spectrum, which is located in here, that's being used. Now, with broadcast radio, which is also considered a broadcast network, the signal is sent out in all directions and utilizes a single frequency for transmission. So there's low power transmission for shorter distances is more common and is easy to install, but there's also high power transmissions, which are used for further distances, as you would imagine, and it's typically a little more difficult to install because it requires really specially trained technicians, proper installation and maintenance techniques, and so on. With radio networking, line of sight is not necessary, which means that the device sending the signal and the device receiving the signal don't need to literally be able to see one another. Now, because radio networking is sent over the airwaves, the signal can be intercepted really easily. And so in order to utilize the technology for day-to-day transmission of information, we need to make sure that it's kept confidential. And so a new form of radio transmission was developed. This is called spread spectrum. A spread spectrum was introduced to address some of the concerns that I've just mentioned. It takes the radio signal to be transmitted, and it sends it over more than one frequency. So this makes it more difficult to intercept the data in transit. Now, there are two different types of spread spectrums. First is DSS, or direct sequence spread spectrum. The direct sequence spread spectrum, that's a mouthful, utilizes multiple channels to transmit the message simultaneously. So it's going to use multiple channels, and it's going to send that message all at the same time. With DSS, there's also a method of error checking, and it's called EDAC, which I don't think you'll see on the test, which is error detection and correction. And this allows for a certain degree of signal loss while still being able to put the original signal back together on the receiving end. On the other hand, we also have something called FHSS, or frequency hopping spread spectrum. In this method, it sends the signal across one channel at a time and hops to the channel. Each channel just sort of hops to another one at a predetermined interval. This method can hop from frequency to frequency anywhere from 50 to several hundred different frequencies. Per second. The sender and receiver, as you can imagine, need to be synchronized with one another, and they also have to have the same set of frequencies to hop to, which is called a hop set. This method of radio communication, by the way, it's commonly used in the military because it has a fairly strong sense of security about it. Infrared, or infrared, which you might have heard of, transmissions are also unbounded forms of communication, and the data is sent via pulses of infrared light, hence the name infrared. This light is between 300 gigahertz and 300,000 gigahertz range, and in the electromagnetic spectrum of ranges and frequencies. There are also a few types of IR that can be used. all of which need an absolutely unobstructed view between devices. This means that they are what we call line of sight, or LOS. Because of this, it nearly guarantees that there's a secure connection between the devices because they have to be so close to one another. Another example of infrared being used, by the way, is your remote control, which is the reason that we probably found them on a lot of laptops. Now, there are different types of infrared connections. There's serial infrared, which means that the data is sent in a serial fashion. In this case, you're looking at probably around 115 kilobits per second. Then we also have fast infrared, which goes up to 4 megabits per second. And finally, very fast infrared, which gives you up to about 16 megabits per second. So you can see that there is the technology has changed quite a bit. That being said, we don't see this a lot in sort of consumer markets just because it is because of the line of sight necessity of it. Now, there's also Bluetooth transmissions, which is another form of short-range wireless communication. It's increasingly popular. You've probably seen it with these sort of headsets. And it uses a 2.4 gigahertz frequency, which, by the way, is the same we're going to see with Wi-Fi. And so this can actually cause some interference with your at-home Wi-Fi network. Now, today, Bluetooth is used to connect devices like headsets, cell phones, laptops, mice, gaming consoles, so on and so forth. The accepted maximum range of Bluetooth communication is about 30 feet, which is equivalent to around 10 meters. But the newest implementation, Bluetooth 2.0, is said to reach up to 30 meters or 100 feet, but it's not guaranteed to run that distance, and in application, it might not actually get there. Now, when you're connecting devices by Bluetooth, we call it pairing devices, and if you've never done this before, generally there is a PIN code that's used to pair these devices together to make sure that they are secure and you're not connecting to a different device. The next type of wireless transmission I want to talk about is microwave transmission. It is the same term for that thing in your house. The microwave operates in 1 gigahertz to 300 gigahertz frequency range, and for the microwave transmission to be received successfully, there has to be an unobstructed view or point-to-point line of communication. So just imagine that the satellite, for your television, for instance, if our satellite dish at home doesn't have a clear line to the satellite in the sky, we see that its signal degrade or drop off altogether. So obstructions such as buildings, trees, even atmospheric conditions like rain, etc., can all play a major factor in microwave transmissions. One of the greatest benefits of microwave transmissions is it has a really long range of communication. As you can imagine, your satellite at home can reach all the way up to the sky and hit that satellite in the sky, or rather your receiver at home or your dish at home can reach that satellite in the sky. And so there's a real strong benefit to these satellite microwave transmissions. Now, the one you're probably most familiar with here is a wireless access point, which is a radio, a type of radio frequency device. It allows wireless devices to connect to a network. It has a network interface that allows it to connect to a wired network as well. So generally speaking, this would go off to, say, a switch or a router. Now, how do we know which wireless access point we want to connect to? This is something. This is where we get into something called an SSID, and there are also other settings that we need to take care of when we're setting one of these up. So first, let's talk about the SSID, or Service Set Identifier, which is up to a 32-bit alphanumeric string, and it identifies the name of your wireless access point. So in some ways, we might call this the name of your network. Right out of the box, when you just set it up, the access point is going to do what we call broadcast your SSID. This means that it's transmitting the name of the network into clear text so that anyone who's within range can see it. If you live in a building or if you're in an office space, you've probably seen this. So this creates a vulnerability on the network, especially if you want to limit the number of users that are trying to access your network. So with your wireless access point, there are a few steps to make to ensure that we're going to install this correctly, safely, and efficiently. So the first thing we want to do is to choose the proper device for your needs. Obviously, there are different types of access points. If you were around for A+, we talked about what are called SOHO routers or SOHO access points, which also have routers in them. But an access point simply is the device that's connecting you wirelessly to your network. Now, if you have a corporate environment or a home office network, you're going to need different things. So the next thing, once you've decided which device you want, we then have to talk about where we want to place it. And specifically, we need to ensure that our users can access the network from all the places they need to, which is just as important as considering which users we don't want to be able to connect. So we want to be able to place it in a place that is, of course, central, but also is limiting or limited in the amount of people who are going to connect to it. If you put it near a window, for instance, our next door neighbor might be able to connect. Now, almost immediately after bringing the WAP or the wireless access point out of the box, we want to change the administrative default password. So, and disable any guest accounts. This means that all these settings that we're talking about, you need a password to be able to get in and change them. So we want to change that or disable the guest account, change that, and we also want to make sure there are no other backdoor accounts. You can generally check in your administrative sort of manual to see if there's anything like that. So that way we don't have any unauthorized access to the account. Next thing we want to do is configure these wireless access point settings, including the SSID, what encryption we're using, power, and so on. We'll talk about encryption in further detail in later lessons, so don't worry about that so much right now. Now, after all of the configurations have been set, we also want to disable, as we've mentioned, the SSID. This doesn't mean that users aren't going to be able to connect to the network, by the way. It just means that if you're looking for available wireless networks, it's not going to be broadcast out there. So in other words, you need to know the name in order to find it. It's sort of like a door that's hidden in the wall. If you know where the door is, you can find it. If not, it just blends into the wall. Finally, after we've set everything up, the last thing we want to do is test for functionality, make sure that all the users can connect, make sure that they can get in from the locations they need to, and also make sure that people who shouldn't be able to connect can't. All right. So now we've talked about a couple different things. First, we talked about unbounded network media, which again is sort of wireless in scope. It means there's no cord. We looked at radio networking and broadcast radio. We also looked at the spread spectrum. And if you remember, we have two different types. One which is going to broadcast on several different channels on the spectrum at once, and one which hops around at certain intervals. We also looked at infrared, Bluetooth, and microwave connections. These two much more shorter distances, microwave a much longer distance. This requires a line of sight, so does IR. Bluetooth does not, but does have a very limited degree of distance that it'll work. We also looked at a wireless access point, or a WAP. By the way, a wireless access point is also going to be built into what's called a SOHO router. Those are those Linksys or Netgear routers that you buy at the store. And finally, we described the characteristics of an SSID, specifically the fact that we want to disable their broadcasting. So we've talked about the bounded and unbounded media. Let's talk about some of the devices this media is going to connect to. Network hardware and media, network connectivity devices. So having discussed the way that devices connect, either using unbounded or bounded media, let's now talk about the connectivity devices themselves. So the objectives of this module are first to define and describe a NIC, which also stands for a network interface card. This is the main way in which devices connect to a network. We're also going to talk about a transceiver, a chip that is on the NIC and basically allows it to communicate. We're also going to identify the characteristics that make a switch one of the main central devices in our star topology that allows for communication on a local area network. And then we're going to identify some of the qualities and some of the characteristics that we can put into a switch, including trunking, port mirroring, and channel bonding. All of these do come up on the exam, and so they are pretty important to cover. Then we're going to talk about a router and a gateway. These two devices allow us to communicate outside of our local networks onto a wide area network, or a WAN. Now, as with anything, we have noise that interrupts the signal. And so we're going to talk about what that noise is and the sources of that noise so we can better alleviate and avoid it. Finally, we're going to talk about that alleviation and avoidance by talking about noise control and reduction techniques, sometimes getting into the specifics of how this works. Now, some of this might be a little too complex for the Network Plus exam, but it's good to go over anyway so you have a firm basis in the theory behind it. So the NIC, or the Network Interface Card, is a physical connectivity device that can be either wired or wireless. For wired networks, the NIC's going to have an Ethernet port, which is right here, that allows you to connect to an RJ45 cable. If you recall, the RJ45 cable is the ones used with most twisted pair installations. You can either connect it directly to the motherboard, or it can be connected through another card or a riser card or an expansion bus, as this one would be. Now, there are typically connectivity lights on the outside of the NIC that allow administrators to get a quick status of the network connection. The connectivity lights can mean different things depending on the manufacturer of the NIC. However, most commonly, there are going to be at least 2 and possibly even 3, and each of those lights are going to be different colors. You can see on this one we have 3 different lights. Now, there should be one light that is on to dictate that there is a connection. That would be a solid green light most of the time, and it's going to stay lit when connection. And there's also going to be another light that's sort of going to flicker. The flicker is letting you know that there is activity or that traffic is being sent across the NIC. The faster the flicker, typically this means that the higher the network speed or the more data that's going over. Occasionally you might see one with different colored lights. The different colors might dictate, for instance, the speed of the connection. For instance, a green for gigabit speeds, which would be 1,000 megabits per second, and amber, for instance, for 100 megabit speed across the network. Again, this is going to really vary depending on the NIC. It's also important to know that the MAC address, which might be written out here, is actually hardwired or hard coded into the NIC. So it's something that comes with the NIC itself. Now, a transceiver is a connectivity device that has the ability to send, transmit, or receive traffic simultaneously. The ability that this has is due to a specialized chip that's right here, and this assists the NIC in transmitting traffic across the medium. Almost every modern NIC has a transceiver built directly onto the device. Now, a great example of a transceiver at work is something called the GBIC, or Gigabit Interface Converter. This is something that allows the conversion of electrical signals into optical signals, and then back again. The GBIT can also be used to convert different optical technologies from one to the other. And the benefit of this is it allows a network to be upgraded without actually having to upgrade all of the components. So if we're going to be using, for instance, fiber optics and copper on the same network, this is something that we're really going to want. I wouldn't worry too much about transceivers for the Network Plus exam, but I did want to cover them because they are listed on the outline. And as I mentioned, they're really built onto a NIC, so it's sort of a subset of a NIC, something that is on the NIC that allows it to transmit and receive that data, and also allows it to convert sometimes those signals from one into the other. So this is how a computer is going to connect. Let's talk about switches. A switch is a connectivity device that connects multiple nodes together, acting as the common connecting point. If you think back to our star topology, we have all the nodes connected in this way. Now the switch looks at something called the MAC address, or that physical address that's burned onto the NIC. It's a 48-bit hexadecimal address, and we will talk more about it later. And what it does is it looks at the MAC address of each packet of data to ensure the data goes to the proper destination, or to the node for which it is meant. Now, because of this, because the switch looks at the MAC address of each packet, it ensures that traffic is only going to the intended recipient. A managed switch, I'm just going to write that here, is a switch that allows an administrator access to its configuration and is able to be monitored. Now, the way that this works is that there's generally something called a console port on the back of the device, and you use something called a console cable in order to access this. Depending on the manufacturer of the switch, this might be light blue, for instance, in Cisco switches, which is generally the most common, and sometimes you might have light yellow or orange for others. Now, switches forward traffic to destination nodes via these ports on the switch. And there might be as little as a few ports, maybe 8, 4, or even up to 168 or more. Now, administrators have the ability to do a couple different things. The first thing they can do is do something called port mirroring. Port mirroring effectively, as the name implies, takes all the traffic on a specified port and replicates it or copies it to another port. Now, this is used for monitoring. For instance, if I want to see what's going on in a port, but I don't want to stop the traffic, I can monitor this traffic for analysis and diagnostic purposes. It's also going to allow administrators to diagnose whether traffic across the port is being interfered with by a nefarious individual or someone who has a malicious intent, such as a hacker. Now, if administrators want to combine 2 or more network connections, it's called link aggregation. Or port teaming, and there are other names as well. What this does is this serves to increase or effectively double the bandwidth, as well as allow for some redundancy, obviously, or a backup connection or something else. Another name you might see this as, by the way, is trunking. So that's the one I most see on the exam. So that's, again, taking 2 and sort of treating them as 1. Finally, we have something called channel bonding. Which is the process of adding multiple NICs to one MAC address. This is also called NIC bonding, and we'll discuss it in greater detail when we're talking about IP addresses and some of the other protocols. As opposed to a switch, a router is a connectivity device that typically connects multiple networks or network segments. And unlike the switch, it looks at the IP address of each packet of data to forward to the destination node. So instead of the MAC address, we're looking at the IP address. Now, a router is usually used to connect networks that use the same routable protocols. So a routable protocol is any protocol that identifies the node versus the network using addressing, i.e. the IP address. Now, a router can be installed as a hardware device, as a function of a multifunction device like a SOHO router. And it's also can be installed as software in another device in a virtual environment, for instance, on a server. In the case of a router being installed as software in a virtual environment, the device or node has to have two NICs, one NIC for the node itself, and then one NIC for the routing function, sort of like one to go in and one to go out. A gateway is a connectivity device that's very much like a router in the way it functions, and it routes traffic in much the same way. But the difference between a gateway and a router is that a gateway connects networks that have different protocols or dissimilar protocols to communicate. So the gateway performs the translation between incompatible networks. I'm just going to put translation here since I think that's pretty important. Or even different email systems or operating systems. Now, although it can be easy to confuse a gateway with the default gateway that we see when we do an IP config, it's not the same thing. A gateway is a device on the edge of the network that's used to convert traffic between different systems, while this default gateway simply forwards data packets in TCP/IP. So we're going to discuss that in more detail later, but I just want to point out this is not the default gateway. And just like a router, by the way, it can be a hardware device or software within a router or on another virtual device. And it uses routable protocols that are similar to a router, but again, it allows the translation between different types of protocols. Now let's look at virtualization a bit, since this is really the big thing in computing nowadays. A virtual switch, for instance, functions just like a physical switch. You cannot, however, directly communicate between two virtual switches. If you want to do that, you need a virtual router or a router. Now, a virtual router is the software that can be installed on a device with two NICs for routing traffic. A virtual server is a server that operates independently of its host machine, meaning that it's all software-based. CPU, RAM, etc. can be independent of its host machine, whatever that might be. Now, virtual machines are similar to a virtual server in that it has its own software, like software-based CPU, RAM, NIC, hard drive, etc. But it's a software implementation of a machine that performs specific tasks and executes specific commands, but it's not a server per se. All right, remember, a server is something that's serving up information to a client. And then finally, we have a virtual desktop, which in Windows systems is a single desktop. Which in Windows systems, a single desktop is the default that can be opened, but a virtual desktop allows you to open multiple different desktops at the same time. Linux also supports this, by the way, but Microsoft requires extra software that you install for this to be changed. For instance, Virtual PC. We've seen this, if you remember, with an A+ with XP mode. Now, continuing to talk about virtualization, if an organization or a company builds their network infrastructure and chooses not to use it, they can lease it out to others. So, for instance, Amazon would be a great example of this. They have a huge infrastructure, but they don't use all of it. So what do? They lease it out to others. This is a very common practice, and what it's labeled as is networking as a service. Now, An area of Network as a Service, or NaaS, depending on what is being leased, might be considered one of several different things. It might be considered IaaS, or Infrastructure as a Service, meaning like the hardware. I provide you the hardware, I provide you the infrastructure. It could be Software as a Service, much like Gmail, which simply provides you certain software, and just like infrastructure would be like Amazon's EC2 or Elastic Cloud. And then the last one is Platform as a Service, which would be like an application sort of engine, or allowing you to deploy certain development tools. Most of the time, you're going to see most of these in the field. This one is really more for developers. So the term legacy indicates that this is an older device, one that's not really in use in today's networks, or that have been replaced by newer or higher functioning devices. So some of the things we're going to talk about in this one might appear on the exam, and the reason for that is because they might appear in the field, just because they haven't been replaced yet, by perhaps due to expense or something. However, these have probably been replaced by switches, routers, and gateways, but it's still good to go over them anyway. So a repeater is a simple device that does not look at the traffic at all. All it does is it simply boosts the signal after it receives it and transmits it out. So it just repeats the signal as the name implies, just boosting that signal. We also have something called a hub, which you might have heard of, and this is similar to a repeater in that it doesn't look at the data. It just retransmits it. But the thing that a hub does is it receives traffic from one port and sends it out to all the ports without looking at the data traffic. Now, it's vastly been replaced by switches because, as you can imagine, if I wanted to send data to only one node, the hub doesn't allow me to do that. It makes me send it to all of the nodes. And so this is going to cause quite a bit of extra traffic on my network. Finally, there's something called a bridge, which the purpose was to divide logical bus networks into segments, and it did this by looking at the MAC address. So it is operating at sort of the same level as a switch, and it looked at the MAC address of the packet and transmitted the data accordingly. Now, if the MAC address was on another segment, it forwarded it out, and if the destination was on the same segment, then it didn't forward it. So in older networks, this implementation was logical, and it was handy because it reduced traffic congestion and improved performance, obviously, because it wasn't forwarding data that didn't need to be forwarded on. All right, now let's talk about noise. Noise, or electrical noise in networking, it's the term that interferes with, implies rather, interfering with data and normal data traffic. It can come from many sources, and as network administrators, it's really important that we know where all this noise is coming from and how to prevent it as well. So not only can noise affect our network performance, but it can also affect data transmission, electrical current as well. Now, if the electrical current is interrupted or interfered with, then that can affect our electrical devices. So, for instance, if there is a surge in the current, that means a lot of extraneous noise in the electrical line goes to our devices and then damages them. So sources of noise are found in many places. As you see here is a power line, electric motors used in HVAC systems, elevators, refrigerators, just about anything that draws power to run. Fluorescent lights, neon or high intensity discharge lights, or what are called HID lights, also cause significant amounts of noise that interfere with networking over both bounded and unbounded media. This is especially important to be mindful of when you're running or installing your cables or placing your wireless access points. You want to really avoid running data cable parallel to those lights, as well as any cables used for power. It can also come from devices that give off heat, like personal heating devices. And while that might sound a little strange, it's due to the amount of power that those devices consume when in use. The power or the electricity has the potential to give off a lot of noise, which makes sense. Now lastly, normal ambient noise, also called background noise, or the noise that's present due to atmospheric conditions like solar disturbances, radio broadcasting towers that are nearby, etc. The main thing to consider with ambient noise is the distance or the length of your media. The longer your media run is, the closer to its maximum rated length, then the more susceptible your signal is going to be. So to combat this, one thing we can do is called grounding, which is a method of taking the shielding or a conductor and connecting it to an electrical ground point that is directly in contact with literally the Earth's ground. Now, when we connect a network segment at one point to a ground, this basically shunts or drains the extraneous noise, only leaving the data signal. So at the same time, if more than one point is grounded, this can introduce even more noise, which is going to greatly reduce the quality of the signal, if not even completely get rid of it. So we only want to ground the point once, which is important. If we do it more than once, we're going to be in major trouble. Not only do we ground for network for performance, but we also do it for safety, because most electrical devices have to be grounded in one way or the other. Otherwise, we just like we saw with A+ and touching devices, if we don't ground something, we could possibly damage it. This is mostly to redirect high voltages into the ground where they're not going to harm your equipment. Now, electricians have special ground points or dedicated ground points that are designed specifically for sensitive electrical equipment. These isolated grounds, they're usually going to be colored orange, which helps differentiate them from normal plugs. So if you see an orange-looking plug, that is a special isolated ground. Now, the shielding around a cable, as you can see here on this coaxial cable, is a noise prevention measure that takes the noise and drains it through the shielding away from the conductor in the center that is carrying the data traffic. Now, the shielding is then connected to a single ground point, flushing the noise away. The connection between the shield and the ground point is also called the drain, which is why we say it's drain. And this same thing doesn't just go for coaxial, it also goes for STP or shielded twisted pair as well. Now, because the noise is often going to be constant, the method of differential signaling takes two received signals and subtracts the equal signals, which is typically going to be the noise or the noise floor, and that's going to give us an end result of simply the noise. So basically it takes this signal input, which is a digital input signal, and it takes that, subtracts this, and then we can get a signal without any noise in it, as you can see. Now, besides differential signaling, there are also a few other noise control considerations. We talked about earlier something called termination, which is really important in networking. Some cables require termination to be installed at the end of either connection, right? If you remember that from our bus, and it has to have the appropriate ohm rating. If you install the terminator and it doesn't have that proper ohm rating, then it's probably going to actually it won't work effectively. Now, luckily for us, in most cases, the terminators are installed in these network devices by default, but not too long ago, you had to install them manually, and you had to make sure the impedance or the amount of ohms was matched. It was a fairly simple task, but the specific impedance could have been marked on a cable jacket, or if a large amount of cable was installed, it just added another step to the process. Now, something else to keep in mind is how you run the cable or your cable run. You don't want to run data cable and electrical cable in the same tray, and you should try to avoid running your data cable parallel to any electrical cables or any other data cables in order to reduce what's called crosstalk, which basically means the signal sort of jumps from one to the other. Now, if you keep data cables away from motors, fluorescent lighting, high power devices like we saw, you always ground your electrical equipment and electrical circuits according to the manufacturer, and you allow for all the recommended installation requirements and grounding requirements that they provide, then you should be good to go when you're connecting your cables together and when you're running your cables as well. So just to recap what we've talked about here, first we looked at a NIC and a network interface card. We described a transceiver, something that goes on the card and how it functions. We also looked at identifying the characteristics of a switch, which, if you remember, use MAC addressing. We defined trunking, port mirroring, and channel bonding. Remember, trunking was using 2 or more ports as though they were one. Port mirroring, usually going to be used for diagnostic purposes. And then channel bonding, which is sort of bonding those NICs together. We also described a router and a gateway, which again operate with IP addresses instead of MACs, and they allow us, whereas switches allow us to work within a LAN, IP addresses, or rather routers, allow us, and gateways, to operate within a WAN or a wide area network. Finally, we looked at some legacy devices, and we defined noise and the sources of noise, including any of those high-power devices. And then we looked at some noise control and reduction techniques, including proper grounding and shielding.
So welcome to Module 2, Lesson 4, new topic added to the CompTIA syllabus, the, what is the syllabus number? 007. Advanced networking devices. So this is stuff that we need to be aware of because it's becomes of prominence, maybe in the industry a while, but now in regular use, or ubiquitous as they say. So advanced networking devices, network hardware and media. Going to look at multi-layer switches, wireless controllers, a load balancer, IDS and IPS. We're going to look at AAA and radius server. I think that's dotted throughout the syllabus, so we pick it up as a security subject and also an advanced networking device. UTM, next generation firewalls, VoIP gateway, in terms of PBX that is, content filter. So this is one of the, I think it's the first device actually that Cisco ever brought to market. It's known as the Cisco, pretty hard to see there, it was the AGS. A husband and wife first started Cisco, and I think they had a colleague that they used to work with, and they actually bought the first Cisco switch was actually created by a company called Kaplana or Kalpana, if you pronounce it. This was their very first ever switch, and switches used to run some old code. I think something like I think we used to call it CATOS, and then the routers. Well, there was no code that because they created it. They created their own code. And that's called the Internet Operating System. Cisco brought the whole thing together now, so there's this, you don't have to use the old command line that worked for CATOS, but they just weren't compatible at all. So you had to kind of learn how to program 2 different type of devices. So this was the early, I think this is from the Cisco Museum actually, and you can see the Kaplana switch up here. So real old-fashioned connectors. Maybe they're DB25s, but you can see there's no high-speed connections here. Massive switch, and then your power connector here. So I'm sure this was cutting edge when it first came out. Huge thing in the 1990s. But when you were supporting networks back then, really there wasn't an awful lot to it. A server, a router, a hub. There wasn't that much traffic because people couldn't afford the kit anyway. Early 90s, the web was invented. I'm sure most people weren't really using it. Ethernet was running at 10 meg half duplex. Cisco in the early 90s had 251 employees. Obviously there were just, I think, 3 people to start, then it grew to 251. And then scroll forward to the current era and you can see obviously things are a lot more complicated. We have multi-layer devices working at 7 different layers of the OSI model, incorporate wireless into our networks. We cover wireless later. There isn't anywhere you go now really where there isn't somebody offering some sort of wireless connection. Virtualization is a hot topic and it's obviously used by pretty much all of the cloud providers, Amazon, Google and Microsoft, to cut costs and improve performance. Cloud computing is a red hot topic that I encourage everyone to learn. Video, voice over IP and quality of service. You need to be aware of advanced security threats, and obviously the larger the network now, they'll have their own dedicated security team for hardware, software and protecting from employees and that kind of thing. Cisco currently has 72,000 employees. I know when I worked there, when was it, the early 90s, they were getting rid of swathes of different employees from the legal team and marketing teams and some engineers as well. So I'm not sure if it was ever higher than that. But as stated on the interweb, it's 72,000. It is quite a lot. So one of the devices that's mentioned now, brought into the syllabus, is the multi-layer switch. Switches, generally layer 2 switches, which is the cheaper models, will switch frames at layer 2. And they'll use hardware for this. Multi-layer switches operate at layers 2 to 7. You can buy a switch that operates at layers 2, 3, 4, or another switch. And you can see here, it might not be clear, but this is actually a connection bracket here. And what happens is this is a switching module that you can buy and slot into the chassis. So what you could have there instead is there's 2 modules here, and depending on what you buy, you could have one here for voice, one here for remote connections. You could have a mini switching module here, or one that's only dedicated for voice connections. You can see actually these are exactly the same, and it looks like there's USB there for you connecting management interfaces, a console connection, and there's 1, 2, 3, 4 switching modules here, and it looks like it's got quad power as well. So if anything goes wrong with the power supplies, you've got 3 possible power supplies. I'm not sure, they're probably going to be hot swappable, and I'm not sure if they're working as 1's a backup for 2 and 4's a backup for 3 and vice versa. You'd have to check the documentation. But this whole chassis would obviously be connected into the cabinet here, and you could probably have 1 major switch here and then a second one to take up the whole rack. So multi-layer switches operate multiple layers from 2 to 7. Bandwidth can be up to several gigahertz. And you can stack Cisco switches so they all become one. You could have 2 or 3 switches all becoming one logical switch. Ports can be switched, which is MAC address, MAC addressing, or you can configure them to be a layer 3 port and route IP addresses. I think that's outside the syllabus how to actually configure it. So this would be your typical layer 2 switch. Now if you wanted to route, so if these devices down here on VLAN 20, you can see they're on 192.168.20. Well, that's on a different subnet to 192.168.10. So this would be host 1 and 2, for example, on that subnet, and this would be host 1 and 2 on that subnet. Well, the only way, because this is working at layer 2, the only way to route, because we're dealing with layer 2, layer 3 here, so all layer 2 traffic this switch would take care of in its MAC table, which we've covered earlier. Now if you wanted a route, then traditionally you would have to send out the packet to the router. The router has a directory of all the networks, 10, 20, This network 30 will probably be for management traffic, or it could be whatever you want. And then it would route, and then it would decide that it needs to send that traffic out. It could be an interface or a sub-interface. This is what's known as a router on a stick, one-armed router or router on a stick. And unfortunately, the physical cable will carry all the traffic coming in and out. Not a great way to run your network. I mean, it's okay if you're running a small business and nobody would notice, but this is carrying all your bandwidth, and obviously this is a single point of failure here. If this cable breaks, or this interface, then you can't route traffic. The only traffic that would pass would be within the VLAN. Sorry, it couldn't pass this traffic. So this is a multi-layer switch. So call it say a layer 3 switch. And what happens is, as you've seen, you've got the modules that are slotted in here. The more you pay, the more options you have, obviously. And this module here is for switching, so you've got all your Ethernet connections, and this could be your routing module. And so all contained within the same chassis, and the technology isn't really covered in the syllabus, but it would switch the traffic depending if it's layer 2 or layer 3 within the same unit. So you basically, what you don't have to have is this device here and this device here. It's all within the same unit, and depending on what you spend, this could be doing access lists and also your connection out to the internet, depending on how much money you have and what your requirements are. Next device is a wireless controller. This is a Cisco 2500 Cisco wireless controller. The cheaper devices you've probably seen, you've probably got one at home here, is your wireless access point. And what happens is you've got a few wireless access points, probably. Say this is your office. And normally these would take care of all of the connections. What happens is these become lightweight access points, in as much as all they're doing is taking in all of the signals and then passing it over to this master device. Obviously it costs a bit more. And so these are lightweight access points, and this is your wireless LAN controller, which some people refer to as WLC. So it allows your wireless devices to communicate, and you can see you've got some wired connections there as well. Takes over from the access points, becoming lightweight forwarders, so you don't have to throw them away, which is handy. The wireless access controller has your service set ID. You can have logical interfaces, and as you can see down here, you've got physical ports for Ethernet. And when you first buy it, if you want to, you can connect to the console port here and then use your PC to set it up to whatever parameters you want. And also you can use this port here for disaster recovery. You obviously have to be physically present unless you connect a Cisco access server, which we'll cover later, which that would have an internet connection out here. So you could, I nearly said telnet, probably SSH in through here, and then you could from this Cisco access server here, you would have a connection going into your console port. But we'll cover that later. Ports can be switched. So they're just dealing with MAC addresses, or they can be configured to route, just depending on what you need. So your wireless controllers, your wireless LAN controllers permit mobile devices to roam. Roaming means keeping the same IP address. Now you can have intra-controller roaming, so you've just got one controller, or you can have inter-controller roaming, which is a little bit more difficult. But as you're walking through your say you're in a coffee shop and you've got ground floor here, and say there's a concrete, which normally there's a concrete floor, and you go up the stairs, look at my amazing stairs there, and you're in the first floor. I think you don't have a ground floor in America. Maybe the first floor is called the first floor, but on the ground in the UK we call it ground floor and then first and so on. What you don't want to have to do is reassociate with a new controller. So basically you'd have to connect to wireless network 1 and wireless network 2. You don't really want that. You want to go in, connect to their free wireless, and then keep your IP address, so 172.168.1.1. So keep it as you're roaming around the building. If you're just using lightweight access points, then you would have to just keep reassociating, which in this day and age is obviously a pain because we're so lazy. So I've mentioned intra-controller and inter-controller, you can see in the diagrams there. The load balancer. So this distributes incoming requests between 2 or more devices. So this will be transparent. So what your clients think is happening is basically it thinks this is happening. It doesn't realize that this device is here, which is fine by us. As network engineers, we'll take care of that. And what it will do is balance. So it will take say the first connection here, and then oh no, this is getting really bad now. It will log internally here, and then this could be a network or just a device. Third connection here, and it will balance. And you don't have a single point of failure. So your third connection goes here. This load hits say 90%, but this server, it could be a higher powered server, doesn't have to be the same. This is only sitting at 20%. Then it will route more of the traffic to here. If this goes down for whatever reason, transparent to all the end hosts, it will load balance between these two. And you can be routing between different devices. It doesn't have to be servers. So you can balance web traffic, streaming videos, databases, whatever you so wish. Now the IP address is actually sitting on here. So say 12.1.1.1, and then these will probably have non-routable addresses. So RFC 1918 addresses, which is whatever, you know, the private IP addresses. But we won't care about that as customers. Moving on, IDS and IPS. Cisco are market leaders in this type of equipment. I can't see what the model number is, 4240. Always great to surf the sales pages for all of these vendors, Cisco and Juniper and whoever, because it gives you lots of useful documentation. You can see what's available. Now both of these do the same job. They inspect traffic to detect unauthorized access and monitors the network for intrusions or malicious activities. Now what it can do is send an alert, which is oh no, I'm going to have to draw a... This is actually a telephone. I hope you're impressed. Old-fashioned telephone there. If you recognise that, then you're officially old. So it could send a message to your mobile phone. It can send SMS, log messages, whatever you so wish, or an SNMP trap, and that will it can shut down a port or whatever you instruct it to do. Now IPS works inline, so it's placed in the traffic flow. So you've got internet, and I'll stick it here actually. Your IPS, and then that will go off to your router, switch, and then your hosts here, however many hosts you've got. I know, don't give up your day job. So this is in line. Your traffic will come through here, be inspected, and then go to your end device. The IDS is not in line. So what will happen is router, switch, host, and it can be put here or here. I'll say there's an Ethernet connection here. Now your IDS receives a copy of the frame. So the frame, I'll call it frame Y, and then that is just a copy because frame Y is actually being passed through to your switch. Obviously you can see the problem here. It's receiving a copy, but this traffic is actually going through your network. So these are less common now, the IDSs. We're going to talk about this later in the security sections. AAA or radius, used for authentication to validate the identity. It does a few things actually, and Josh talked about the different aspects of AAA earlier. Authorization determines what you can do, and accounting is for the audit trail. So this the accounting will normally go off to a server where you can interrogate the server logs, and sometimes you need to do it for compliance, or if you're going to legally take a case against somebody. So it's a modular and scalable model for network and device access. You can run it on its own server, or certainly in the terms of Cisco, you can have the server software running on your router and switch. Probably not recommended because routers are designed specifically to route traffic. Uses Radius, TACACS Plus and Kerberos as authentication methods. I don't think Kerberos is actually in the syllabus, but I know Radius and TACACS is. Certainly worth looking at the CompTIA Security Plus, which we go into a lot more detail in this stuff. Already mentioned using the servers. UTM is an appliance. Integrates a range of security features, but it does it into a single appliance. A while ago, actually, I was when I was consulting in the early 2002-03, there was one company in particular that brought out everything in a box. Bearing in mind the needs weren't as complicated back then, so this box, I say box, a server would do your email, it would do your web, it would get you out to the internet as well, and then it would obviously connect off to your switch, and I think it also had your firewall. There's a few things it did, but basically this was everything in a box that a small business would need. So it does several things, and it's designed to do them all pretty well. Your firewall, your antivirus, your IDS or IPS, you can it has VPN software built in. Brands that you want to check out that are market leaders at the moment are SOHOs, which this is a copyright from their page, and YJungle. A lot easier for you to install and manage. Most of it will be running off the graphical user interface, so rather than have to configure a Cisco device, which is frankly quite a nightmare for most people unless you know what you're doing, it just makes it a lot easier. Probably I'm saying it's more suitable for the check the software, because they may say different, the small business, the small to medium sized enterprise where you don't have a lot of employees, and you may just have one support person or somebody that comes in just to do patches and maintenance. Obviously saves time and money, so a big pull for any small businesses. The only problem is if you're running everything off this, I guess it's running off a server of some sort, because it's software based, then you've got a single point of failure. So you've got to take this into account with your business continuity planning, what you're going to do if part of it breaks, all of it breaks, etc. NGFW, next generation firewalls. So the hackers, as you know, are getting smarter and smarter and smarter, and whereas we'd have to be checking the IP headers or the TCP headers to find any malicious code, it's actually now been buried inside the application data, and traditionally your firewalls may well have been just checking these particular fields, headers, footers, trailers, whatever. So I just got this image off this URL here. So these are known as third generation firewalls. This combines your firewall with your other filtering, looking at application, and this is where the crypto lockers are hiding, which we cover later. They can include antivirus, ID management, your transport layer security, which is the latest version, secure sockets layer, quality of service if you're running it on your network. So if you're trying to prioritize voice or video conferencing, whatever you want to run at your work. Combines firewall, antivirus, gateway, IDS, IPS, VPN software. Now 80% of the malware now targets your application. So this is the software stuff, and normally we wouldn't have been inspecting inside this part of the packet, but this is where they're hiding it. So things that have been downloaded off the websites or hidden inside emails. So this is why we need this third generation of firewall. So blocking ports and filtering is no longer enough, unfortunately. So it means just gathering more data, spending more cash, and having more stuff to support. What this is known as here is Deep Packet Inspection, DPI. So we're looking deep inside the IP packet to see if there's anything nefarious in there. The Deep Packet Inspection, you can see things that you wouldn't normally see looking at the headers and footers and trailers, worms, viruses, and it can also do so, most importantly, at wire speeds. So the thing that we all hate in networks is latency, i.e. slowing stuff down. It's really bad news for us, and it obviously frustrates the users, especially if you're doing voice and video conferencing. It would be a nightmare. They've added voice over IP, PBX, into the syllabus. And you can see we've got the voice gateway router here. I've got this from this website here, easytalks.com. So you've got your public switch telephone network, which Josh talked about, which is your voice stuff. And then we've got our traditional phones, we've got our IP phones being managed here, so we can all communicate within each other. And then your voice, PBX, if you need to make calls to traditional landlines, they can go out through the traditional public switch network. So IP Private Branch Exchange is a phone system, but it also offers IP connectivity. You get your traditional extensions connecting through your LAN, and obviously you can go through the internet if you've got your traditional IP phone and you want to call somebody in a remote office with another IP phone. You can do that okay. Otherwise, it would have to go through to the public switch telephone network. You can buy actually software, so it will run off a server if you so wish, or you can have a hardware which you have to wire it up yourself. Mention that it connects to the phone network, and obviously use it if voice is enabled on your network. Content filters. What you can and can't surf, and I've got something similar on my home router, although at a fairly rudimental level, where I can block stuff that the kids shouldn't be watching. Also referred to as information filtering, depending on where you are. Usually software based, and it's very simply blocks harmful websites or files such as .exes. It would probably block Facebook, Instagram, stuff you don't want people surfing while they're at work also. You can work your local network, so your office here, you could actually have it working your core network, or you could let your ISP take care of it. Sometimes they actually automatically block certain content and certain websites, especially in some countries where they control politically what you can and can't see. I think Egypt and some other countries where they don't want you to see certain things, which I won't go into that. So if voice is enabled, sorry, that's put there in error from another slide. So multi-layer switch we've talked about, your wireless controllers, turning your access points into lightweight access points, so they just forward traffic, and your wireless LAN controller takes care of all of the routing, security, associations, SSIDs, that kind of stuff. Load balancer, where it's sending your traffic transparently to 2 or more servers, and obviously it's got your the capability of, if there's one of your servers goes down, it can balance between what others are left. RDS and IPS, you've got to bear in mind what's in line and then what is out of line and just receives a copy, because that's your typical exam question. AAA server, which I'll talk more about later. UTM, again, probably small to medium-sized enterprise, but do check the marketing spiel. Next generation firewall, which is deep. Packet inspections. Voice, again, if you're going out to the public switch telephone network, you'll need the voice gateway. Content filter is blocking sites or content, definitely .exe files. And even my online file that I share with my providers, some of my freelancers that work for me, they can't reach this from their corporate network either. They're often blocked. Alright, so that's all for now. Thank you very much for listening.
Network communications data transmission. As you may know, computers talk in bits, ones and zeros, ons and offs, and this is how all of the data that we deal with in computers is transferred from one computer to the next, or one node to the next, over the media, as we've discussed. But we want to talk exactly about how these bits, these ones and zeros, get from point A to point B. And so in this module, we're going to talk about data transmission, or how data makes it from one point to the other. So we're going to start by talking about data transmission methods and defining exactly what data transmission is. We're also going to talk about instantaneous data transfer and what might require it. The word instantaneous meaning the data is sent instantaneously the minute that it is created. In some instances, data is first stored and then converted and then transferred. In this case, instantaneously, the data is transferred over the media. We're also going to discuss, which we've seen in A+, serial data transmission, meaning that one bit is sent at a time, one after the other. And remember, just as you can recall, 1 byte equals 8 bits. Byte being represented by that uppercase b, and bit being represented by the lowercase b. We're also going to talk about two different communication methods in serial data transmission, asynchronous and synchronous communications, which have to do with how the data is synced up to a clock cycle with the CPU, and therefore how it's sent. Then we're going to define parallel data transmission, meaning that the data, instead of being sent one after the other, you may have 8 bits of data all sent at once in parallel with the other. Finally, we're going to discuss baseband transmission, a digital transmission method, and broadband transmission, or analog transmission method. These are specifically called out in the Network Plus exam, and so it's important that we pay special attention to those. Now, when we talk about data transmission, it's important that we have to understand there are many ways that data can be sent and received. In essence, data transmission is the exchange of data between devices on a network by one method or another. The main thing that differentiates data transmission from, say, voice or telephony transmission is that we're transmitting many different things, including text, video, and graphics all over the medium, whereas telephony is only dealing with voice. This is different from our telephones, which are also transferring a sort of data, but that data doesn't include as many different things. Now, when you might hear the term computer network, I just want to be clear that computer network is the same as a data network. And so we might be using those terms interchangeably, but when we're talking about data transmission, sometimes the term computer network as opposed to data network comes up, but they are interchangeable. Now, in most cases, when we're dealing with networking, the data is stored somewhere at some point. This also goes for data that's ready to be transmitted, right? We store it, and then we send it. However, there are some instances when data needs to reach its destination as soon as it's been generated or created, and we don't want to wait for it to be written to memory or written to a hard drive. In these cases, instantaneous, as the name implies, being instant to the moment, data transfer occurs. Some programs and applications, such as online chat, video conferencing, and voice conferencing programs, all via the internet, require such a transfer. This method of data transfer doesn't store the data at any point before transmitting it to memory. Instead, it immediately converts that data into a network-compatible format and as it's being generated, and then it instantaneously transmits it. Now you can understand why we would want to use that in these specific instances. I don't want to store my chat stuff to memory and then send it. I want to chat and then have it sent. Same with video conferencing or voice conferencing. I don't want the lag that's going to occur due to having to save it to memory and then save it, and then send it, which is why we want this instantaneous data transfer. Serial data transmission is a transmission method that transmits bits once per clock cycle. Now, this clock cycle refers to the CPU or central processing unit of the computer and how that's processing information. And as you can see from this illustration, basically what happens is we're sending one of these bits at a time. And if you recall, 1 byte equals 8 serial bits, and that's what we're going to call 8 serial bits, 1 byte. Now, a couple examples of what uses serial data transmission includes Ethernet, as well as some peripheral devices that connect to our computer, like mice and keyboards. Now, with serial data transmissions, there are different methods that can be used to delineate between the start bit and the stop bit, basically how they know where the data begins and ends. And also error checking or correcting bits that allow the data to be fixed in case it arrives incorrectly, and the data itself. So let's take a look at the difference between synchronous and the asynchronous methods of serial data transmission. Synchronous data transmission utilizes standardized time intervals when transmitting each bit. Now, the assumption that is made is that 1 byte is sent every interval. So the two devices have to be in sync with each other in regards to their timing. A clock chip, therefore, not a great picture of it, but imagine that this is a chip, is needed to ensure that the devices are in sync with one another. Now, a special bit pattern is inserted during a specified time interval to maintain this synchronization. Asynchronous, on the other hand, uses special start and stop patterns to differentiate between the bytes in the data stream. So the receiver just has to look for these special patterns and then can easily keep track of whether the data has been successfully received. So for instance, the pattern might be 1010, and then, or 10101010, and then the device knows that that is the beginning or the end of a pattern of bytes of data. The benefit, of course, is we don't need this chip because the start and stop times are built automatically into the data itself. Now, stepping away from serial data transmission, parallel data transmission is a transmission method that uses multiple transmission lines, wires, or cables simultaneously. Unlike serial transmission that sends start and stop and synchronization bits along with the data, parallel does not and doesn't have to. Those bits are sent separately via one of these multiple other different transmission lines other than the data. Because of this, throughput is generally better than standard serial transmission. And these 8 of these parallel bits are referred to as a character as opposed to a byte. Now, some examples that use parallel transmission are SCSI, parallel ports, PC card, or PCMCIA. Remember parallel ports, those are those printer ports. And they all use parallel data transmission. It's not as used or widely used as serial data transmission is. Now that deals with how the data is sent. Let's deal with the type of signal that's sent. In baseband transmission, this utilizes digital signals sent via a direct current pulse. And remember, we're talking about direct current versus alternating current. With baseband, all the devices share the same medium or channel and can't transmit and receive simultaneously. However, multiple baseband channels can be combined over one medium to use a channel separated with specific time slots. And that's how we can determine when it's being sent and when it's being received. One thing to notice in a digital signal as well is that we're only dealing with ones or zeros, on and off. And so the signal is either on or off. There's no sort of wave that we're going to get with the analog signal, which we'll see right now. So where baseband used those digital signals to transmit data, broadband's going to use analog signals, and you can see that represented in this wave. Also, unlike baseband, broadband utilizes the entire bandwidth available, and it's only going to travel in one direction, or unidirectionally, because devices can't send and receive over the same channel. Now, if more throughput is needed, that's fine. We can combine and send across multiple frequencies, channels, or we can use over just one medium. Generally speaking, we're going to see a lot of broadband in the field because a lot of our current infrastructure was created for analog signals as opposed to digital or baseband signals. Now, broadband over power lines, or BPL, is an emerging technology that's still mostly in the testing phases in the US. The premise of it is that we can essentially bring high-speed internet to power outlets using the power lines and the infrastructure that's already been built. Once this technology is fully developed, you would be able to plug your computer into a power outlet in your home, and you can get decently fast internet between 500 kilobits per second and 3 megabits per second, which are about equivalent to DSL or cable speeds. Now, of course, the main concern with this type of transmission is the effect that since we're dealing with electrical infrastructure, the effect that the electricity is going to cause on the data being sent. Remember, we were talking about EMI and crosstalk and the noise issue previously, and also security, since if we're using something that everyone has access to, we're also going to be opening our data up to some issues. So for these reasons, we might not ever see BPL or broadband over power lines really come to full fruition, especially with the prevalence of Wi-Fi technologies that are now becoming installed all over the place and might make BPL extinct before it even has a chance to flourish. So just to cover what we've talked about, we talked about data transmission, meaning that we're transferring data over a computer or a data network. We looked at instantaneous data transfer, which means that the data is not stored to memory. We also talked about serial data transmission, in which one bit is sent at a time. And remember, we have 8 bits in a byte. We looked at asynchronous versus synchronous communication. Synchronous requires some sort of clock chip, whereas asynchronous embeds the start and stop into the transfer. We also looked at parallel data transmission, having bits sent all concurrently at the same time, not as widely used. And remember, although I don't think you'll see this on the exam, 8 parallel bits equal 1 what we call a character. We also looked at baseband transmission. The important thing to remember there is that it is digital, and broadband transmission, which is analog. Finally, we talked about BPL, or broadband over power lines, which is a technology that would bring broadband speeds over the power lines that are already in place. Network communications, media access methods. So we've discussed and explained the different media and the different devices that exist on different types of networks, and we even just talked about how that data is transferred from point A to point B. But we have a lot of different devices all vying for access to this media in order to send its data. And so we need to create certain rules that provide access to the media. And so what we're going to talk about in this module is first what media access is and why we need it and why we need to understand it for the Network Plus exam and as administrators. We're also going to describe 2 different broad areas of media access, including contention-based media access versus controlled media access. One in which we sort of fight for access to the media, contend for it, if you will, and the other in which it is controlled generally by some sort of central device. And then we're going to define multiplexing, which allows us to send multiple signals over a single medium. And we're going to talk about 2 different types of multiplexing: time division multiplexing and frequency division multiplexing. And we'll discuss how those work and why we need 2 different ones. Then we're going to discuss polling, which is how we check to see which devices need to send data. And we're going to differentiate between CSMA-CD and CA. Now, CSMA, you don't really need to worry about that, but it does stand for Carrier Sense Multiple Access. But the real important thing here is to know the difference between collision detection and collision avoidance. And these are the 2 main methods we're going to see for Ethernet and then for wireless. And we'll explain why that is later on. Finally, we need to differentiate between a contention domain and a broadcast domain. Basically, how large or how many other devices they need to contend against or that can get broadcast a certain message. And these are also divided by those 2 different devices that keep coming up: switches and routers. So if that seems confusing enough to you, let's delve in order to shed some light on what all of this is. Now, as administrators, it's really important that we understand the rules that are in place for different types of networks. For instance, if I were in a crowded room and I had a secret message that I needed to get across to someone in the corner of the room, and I were just to shout out that message, there's no rules in the world that say everyone else has to ignore what I'm saying, and they could just listen. Or there's nothing that says that everyone else couldn't talk at the same time, meaning that then my message wouldn't make it. Now that means there's no rules for communication in real life, but in networks and computer networks and data networks, there are many different types of rules. And here we're going to talk about some of the media access rules, or the rules that govern which node or which device has access and the ability to transmit on the media at any one time, and when they're allowed to send and receive, and for how long. Now, these rules are crucial. They ensure that data delivery and integrity, and by the way, when we say integrity, we mean that the data we intended to send is actually what was sent, it hasn't been tampered with, are maintained. Now, there are two general categories for types of media access. These are contention-based and controlled media access. So let's take a look at the differences between those now, and they'll come back when we talk later about CSMA, CD, and CA, not to mention contention and broadcast domains. With contention-based media access, nodes on the network are competing with one another for media access, time, and utilization. Another term for this kind of media is competitive or collision-based. And yes, that means that they're actually the data packets are colliding, and that's how we determine which can go, right? Which is allowed to be sent. Now, these are pretty easy to implement. However, data can be delayed for nodes that need immediate access to the network media because collisions are going to occur, as the name implies, and that's going to delay network traffic. Now, as opposed to contention-based media access, we also have controlled media access. So instead of me fighting for access to the media, I'm granted access to the media. And the way this works is we use a central device that's put in place to ensure that access to the media is guaranteed for devices that have certain time-sensitive data, and they can transmit it when necessary. Because of this and these devices that need to be added, these are much more difficult to implement and maintain, but they're highly reliable, as you can imagine, and also make sure that no device has more access than another when it comes to access time. So take, for instance, a device that has a safety function, that when an emergency event occurs, right, it has to have immediate access to the network and to the network resources so it can send instructions to, say, heavy machinery that it needs to shut down in case of an emergency. In that case, we don't want it to be contending for access. We want it to be granted immediate access. And so this is where controlled media access can really come in handy. So while we're talking about controlled media access, and we've just talked about controlled and contention-based media access, let's keep talking about controlled-based media access more specifically, discussing a few different controlled-based or controlled media access methods. The first I want to talk about is called multiplexing. And multiplexing is a controlled media access method. I'm just going to add controlled there so that we remember that this is related to controlled, not contention-based. It takes multiple signals and combines them over one single network medium. Now, data can actually be multiplexed using two different methods: time division multiplexing and frequency division multiplexing. So let's first look at time division multiplexing. This is where channels are divided into time slots, and each node on the network is assigned a specific time slot. During that time slot, the node has dedicated sole access to the network until that time has ended, and then the next node is allowed to transmit. Now, there's a device that we're going to talk about in just a minute called the MUX, and this MUX takes the signals from each of the nodes and sends it across the network. Now, with TDM, multiple baseband signals, and remember, baseband is digital, again represented here by that digital signal, because there is no curve in the wave, which would be analog, and we'll see that in just a second. It allows these digital signals, these baseband channels, to be combined and sent over one network medium. On the other hand, we also have something called frequency division multiplexing. This is where data from multiple nodes is sent over many different frequencies as opposed to given a specific time. Each node has complete access to its frequency and dedicated communication with the MUX, that device that is basically controlling all of this. the MUX combines the received signals from the nodes and then transmit it across the medium. The important thing you're here to know is that this we're dealing with broadband or analog signals. Now, we've been talking about the MUX, so let's just talk about that really briefly. The MUX is the central device that, which is also called a multiplexer, that combines the signals and transmits them to the receiving end, or a demux or a demultiplexer separates the signals out again. Now remember, this is all controlled access, and this MUX is that device we were talking about that is doing the controlling. Now, a different type of controlled media access method is called polling. And as the name implies, we have a central device as well that goes to each node in the network in turn and sees and queries them, do you have any data to transmit? With polling then, there is guaranteed access because the process is constantly repeating. Basically, it's just constantly, if we have this middle MUX sort of device, it's constantly going to each device and saying, hey, are you ready to send something? You now have access. Although this guaranteed access and this method is reliable, it might not be as effective in time-sensitive networks, and time can sometimes potentially be wasted in this querying, in this polling, because sometimes I'm having to ask devices that don't need to transmit anything to if they need to transmit, and so this basically wastes time. Another example of this, by the way, is if, for instance, node A at one point finds it has data to transmit, node A has to wait until basically the polling device comes all the way around to it before it's allowed to transmit the data. Now, this can take a lot longer than simply just asking if it can then just send the data along. Now, because of these negatives, there's a variation of this polling, which is called demand priority, where each node signals when it has to transmit or not transmit. This method contains within it measures to grant priority to nodes that have immediate data that it needs to transmit. It also contains measures and controls to ensure that nodes can't constantly signal they have priority data, because then you would have one device that's constantly sort of hogging your network. So those are our controlled-based media access. And really we see these employed in certain circumstances, but you're going to more encounter contention-based media access. And in contention-based media access, there are two different types I want to talk about. Collision detection is a contention-based media access method that attempts to provide collision-free data transfer in Ethernet local area networks. So the key here is this is what Ethernet uses. With CSMA CD or collision detection, nodes transmit when they have data to send, and then when a collision occurs, they're basically detected, managed, and then the data is resent or retransmitted appropriately. To get a better sense of this, and because it's one that we really need to understand, let's take a look at an image to give us an idea. So there are 5 steps in this collision detection, which again, I'm just going to throw this up there, is a contention-based media access method. In step 1, we just say that the node itself wants to transmit data. So what it then does in step 2 is it basically checks the network for availability. Now in step 3, the node transmits that data and waits for an acknowledgement from the receiver that it got there, which is called an ACK packet, an acknowledgement packet. In step 4, this is where stuff really happens. If there is a collision, the packet size will identify if one occurred, because what happens is, boom, I have this collision and now my packet size changes. So in step 5, if that collision occurred, both transmitting nodes, and by the way, the reason a collision is going to occur is because another device is also trying to transmit at the same time. So in step 5, if the collision occurred, I wait a set period of time and then I try to retransmit again. Now, this might seem like it's not a very effective way of transmitting data, but it happens at such a fast speed that actually it works quite well. as long as we don't have too many devices in the same network contending for access, which we'll talk about in just a bit. Now, you can understand why this works really well in Ethernet networks, wired networks, because I can continue to collide and then send something out again, and many times as I need until the data gets there. But in wireless settings, this isn't really going to work so well for us. In this case, we're going to use carrier sense multiple access collision avoidance, meaning we don't want a collision to occur. In this contention-based media access method, there are 6 steps that provide collision-free communication in wireless LANs specifically. Now, similar to CSMA CD, nodes transmit when they have data to send. However, the node takes preventative measures basically by sending out a jamming signal or a signal to all the other computers that tell all the other computers that there is something to be sent. And therefore, no one else is going to send anything for a set period of time. So let's take a look at this in a visual way. So the first step in here, like with the CD, or like with CD as opposed to CA, is that the transmitting node has data to send. Now, the node checks the network for any jam signals being transmitted by other nodes. Basically, has another node already sort of said, hey, I need to send something. If not, the transmitting node sends its own jam signal saying, hey, no one else send anything because I'm going to send something right now. Then it waits a set period of time to allow all the other devices to receive this jam signal, and then it transmits the data. Now in step 6, which is the last step, the node monitors the network for any other jam signals from other nodes, and if a signal is detected, it halts its transmission, waits a delay, and then tries to transmit again. This process, as you can tell, allows wireless devices to communicate efficiently in a contention-based network, one in which it's contending for the right to send and receive data. So this allows all nodes to have relatively equal access to the media. Now, we need to have an area in which all of these are going to contend for access. And in a contention domain, nodes on the network are allowed to compete with each other for media access. And then the collisions might occur as a result. But this is why a contention domain is also considered a collision domain, because this is where these collisions are going to occur. Now, in a contention domain, switches control the size of this domain. And in larger networks, we want to make sure to divide these into smaller networks, so that way we're not having to contend with as many devices at the same time. So, on the other hand, a broadcast domain is simply a logical area of the network where all the nodes can communicate with all the other nodes without having to go through a centralized device. Because of this, the device we're going to use is actually a router, which is going to control the size of the contention domain in a broadcast domain. Now, the broadcast domain refers to the set of devices that are going to receive broadcast data transmissions from any node on that portion of the network, which is also called a segment. Essentially, if a node were to transmit a broadcast message, the broadcast domain dictates where the message is going to go. Now, in a contention domain, if a broadcast message were to be transmitted, there's going to be a greater number of collisions as a result of the traffic. You can have multiple contention domains that make up a broadcast domain. So I can have, again, divided by switches, 2 different contention domains. And multiple ones of these can make up a larger broadcast domain. And because these switches are all connected by one central router. When one of the nodes branching off of one of the switches sends a broadcast message, the router dictates that only the connected switch and its devices are going to receive that broadcast transmission. So, we first talked about defining media access. Basically, the rules by which devices are allowed to communicate on the network. We then looked at the 2 broad categories of access or media access that we deal with. Contention-based media access, meaning we're basically fighting for the right to access the media, or controlled media access, in which we have a central device that decides for us. We looked at then a couple different types of controlled media access. These are all controlled media access types. Multiplexing, which allows us to send multiple signals over one media, and we looked at TDM, or time division, which divides it up by time, and remember this is for digital signals. And then we looked at frequency division, which allows us to use analog signals, or multiplex analog signals. Remember, both of these use a device, a controlling device called a mux, or a multiplexer, and a demux, or demultiplexer. We also described polling, in which we ask, are there any devices on this network that want to send data? But we talked about the fact that this can actually add more time to the process, since I have to ask every device before I get back to the device that's ready to send. We then looked at two contention-based media access methods: carrier sense multiple access collision detection and collision avoidance. And remember, the important thing to know here is collision detection simply has a collision occurs, and then I just wait and I try sending again. And this is what Ethernet really is going to use, as opposed to collision avoidance, which is going to be used mostly in wireless situations, because I send out a jamming signal first. We then looked at the difference between a contention-based domain, or where we're contending for access, and remember that's defined by a switch, because a switch, everything connected to the switch can contend for access and can have a collision, and a broadcast domain, which is created by the router, and is simply a logical division of all the devices that one device can contact. Network communications signaling methods. We've talked about digital and analog signaling quite a bit, but we haven't really gone into what that exactly means at a waveform level, at a basic level. And so in this module, I want to cover some of the background information about these and outline some of the attributes that go along with them. Now, this information might not specifically be on the exam, but I think it's still good background information to understand anyway. So, in this module, we're first going to define what a signal is and what analog is. We're then going to talk about the attributes of an analog signal. We'll then take this and talk about a digital signal, different from analog, and a digital data transmission, or how this digital signal is transmitted. We're also going to define modulation and outline the way digital signals are modulated. And modulation really has to do with length, or making sure that a signal can be broadcast or sent over a very long or large area or distance. Finally, we'll look at digital signal reference methods, how we know when the message begins and when it ends. And finally, wind up talking about digital data units, or the unit of measurements that we hear often when we're referring to digital data, such as kilobytes and megabytes. So at its most basic level, a signal is simply data or information that is translated into measurable, transmittable, and receivable formats, meaning that it is what allows us to transmit and receive data. Now, an analog signal is a signal that carries data in a continuous stream or a waveform via either electromagnetic or optical energy. Now, this energy can come from many different sources, such as electric current, and the analog waveform's characteristics determine the information that it contains, because the analog signal will oscillate between minimum and maximum values over time. Basically, the analog signal has many attributes to it, and it can be read in many different ways depending on the values and the information in the signals given. Now, this analog signal, as I just mentioned, has many different possible values, depending on the characteristics and how that signal is being read. Now, the characteristics of an analog waveform can be described using the following terms. These won't necessarily appear on the exam, but they're good background information for you anyway. First, we have the crest or the peak of the signal. This is the distance from the midpoint to the topmost part of the wave. And when we talk about the midpoint, we talk about this line that's sort of going through. Inversely, the trough is the distance from the midpoint to the bottommost portion of the wave. Now, the next term I want to talk about is amplitude. Amplitude is exactly 1/2 the distance between the crest and the trough of the wave. So it would either be, this could be the, what it's measured, it could be the amplitude. Alternatively, this could be the amplitude. Now, the cycle is one complete oscillation of the wave from start to finish, changing from one state to another and back again. Basically, from the midpoint going up until we get to the next midpoint after it goes down. Now, the wavelength is determined by the distance between two consecutive troughs or peaks. So here we're measuring the wavelength between two troughs. We could also measure it between two peaks, like so. Now, the frequency, also called the period of the wave, is the number of complete cycles per second in a wave. This is generally measured in hertz, such as gigahertz or megahertz. Now, the last term is the phase of the wave. The phase is the relationship of the cycles beginning to a fixed point in time, meaning if two waves with the same frequency are transmitted at the same time, they are said to be in phase, and two that are purposely offset from each other, or if they have different frequencies like these do, they will be out of phase. Now, the device that plots the amplitude of an analog signal, what would show you this wave, is called an oscilloscope. And you may have seen this perhaps at a store or even on TV. And we can measure waves of all sorts of things. For instance, sound might be a wave that you've seen when you're running a program on your computer. This gives you a real-time view of the analog waveforms and its shape, as we've just described. Now, unlike analog signals, which can have many different values assigned to them, digital data transmissions utilize voltage differences, represented either by ones and zeros. These ones and zeros are what make up all of the information. When there is a presence of a signal, or voltage, meaning that it is on, it translates to 1. And a lack of voltage, or an absence of this signal, translates to 0. Now, in computer networks, digital waveforms can switch between two voltage levels, depending on its relation to the ground, if you recall what that is. Now, because digital signals utilize voltage to represent its values of ones and zeros, this is also called the logical state of the data. Each bit or binary digit takes a predetermined period of time to transmit, and bit patterns are used to establish the start and the stop of the sequence and to sync clocks, which allows the receiver and the sender to be on basically the same page. The sender and the receiver have to then synchronize these clocks to ensure proper reception or receipt of the data. Now, there are a couple different ways that we encode in order to allow devices to tell which bit is what. In other words, to tell it when it starts and when it ends. The first method I want to look at is called on-off keying. This looks at the voltage change from one state to the other within a pre-specified interval. Which is represented by the binary digit 1, and the lack of voltage or no voltage is represented by 0, as we just saw. Now, the synchronization between the sender and the receiver occurs with the receiver waiting for a series of 1s. Because of this, there is a potential for problems to arise, especially when the sender has a long series of 1s to transmit within the data. This means that it could take a long while for the sender and the receiver to synchronize their clocks together. In the event that the clocks are not synced, then there's a high probability for data corruption, as the receiver can't determine how many 1s and 0s have to be transmitted. Now, there are two variations of on and off keying I have listed here. One is called the non-return to 0 variation, and the other is the non-return to 0 inverted. This type of data encoding scheme is typically used over serial ports and fairly slow connections. I'm mentioning these because they're good to know, but you won't have to worry about these for the exam. Now, the next encoding scheme, a little more popular perhaps, is called Manchester encoding. This scheme was developed in order to address some of the downfalls that we saw with on and off keying. Firstly, Manchester encoding uses voltage differences to represent both binary digits. So instead of just having 1, which is represented by a voltage, and then 0, which has no voltage, both 0 and 1 have voltages. The way it does this is it works by assigning the voltage change from positive to ground, or the binary digit 0, and a negative to positive change equals the binary digit 1. So, positive to ground 0, negative or ground to positive equals 1. This effectively eliminates the issue of too many 1 bits being transmitted and throwing off the synchronization, as we saw with on and off keying, which relies on those 1 bits in order to sync up the clocks. Okay, so modulation is the process of taking a weaker, lower frequency analog signal that can't travel large distances and superimposing the signal over a stronger, higher frequency called a carrier signal. The carrier signal, being constant, takes on the attributes of the analog signal, and it's shaped by either the phase, amplitude, or the frequency. The resulting signal then has characteristics of both the original signal and the carrier signal. That process, this, is called modulation, and when the receiving end decodes the signal by separating these two signals, the carrier and the data, the process is called demodulation. So again, we have demodulation, which would basically take these away from one another, and modulation, which puts them together. Devices that perform this operation, you've probably heard of before, they're called modems. And a modem is known for its ability to modulate and demodulate, hence the name. A modem is in effect a type of codec, which is a software or hardware that translates digital to analog formats and back. This is an important thing to know for the exam. A DAC is a digital to analog codec, and an ADC, as you guessed it, is an analog to digital codec. Both of these exist in a modem. Now this is it in analog terms, but digital modulation is also required, which allows the digital signal to travel along distances. And demodulation is the representation of digital data in an analog format for transmission over those longer distances. So the analog signal has a characteristic changed to signify the difference between logical states of the digital signal. This is fairly simple, as digital signals, again, only have two states, 1 and 0. And so the analog waveform needs only be changed or modulated in one way, such as the graphic here. The frequency is changed where the higher frequency represents 1 bits and the lower frequency represents 0 bits. In this way, I can convert this digital signal into an analog one in order to transmit it over a long distance. Now, there are various methods to modulate the digital signal depending on what part of the analog waveform is being changed. The first one is called ASK, or amplitude shift key modulation. Here, only the amplitude of the wave is modulated. And remember, the amplitude is the distance between a peak or a trough and the midpoint. And the result of this can only be 1 or 0. The next method is called frequency shift key. Here, the frequency is modulated to only represent 1 or 0, as opposed to the amplitude. And remember, the frequency is the amount of times we have this wave over a certain period of time. We also have something called binary phase shift key, in which case the phase of the wave is changed. And remember, the phase would be if I have two next to each other, the difference between those. And then I have quadrature phase shift keying. Here, the phase is changed as well, but we can actually have two logical states at a time. For instance, 0, 0, 0, 1, 1, 0, or 1, 1. This method actually allows for data to be more secure when it's transmitted. So this is a more secure method. Finally, there's something called quadrature amplitude modulation. And in this case, I can also have more than two states at a time. But what I'm shifting here instead of the phase only is I'm also shifting the amplitude. And so these are both combined into one different modulating wave. Now, in order to demodulate these, once I've modulated them, there must be a reference to differentiate the data from the rest of the signal. Now, there are two digital signal reference methods that can be used. The first reference method is called differential demodulation. This takes the modulated and the demodulated signals and compares them. The output then becomes one signal, which is the data. There's also something called a single-ended. This method, instead of using two different, the modulated and the demodulated signals, uses the ground as a reference point, and the resultant information then becomes the data. Now again, if this is a little confusing, don't worry about it. It's not going to come up on the exam. I just want to cover this to give you a broad basis outline of what we're talking about here. Now, while there is very good possibility that you've probably heard of some of these data units I'm about to mention at one time or another, it's really important that you really understand them in their actual quantities. Now, originally, before computers became household items, and now nearly ubiquitous, computer engineers came up with these measurements of data, and it was pretty straightforward. As we mentioned before, in computer systems and networking, data is stored in binary digits, or bits, and a single bit is either a 0 or a 1. This is the most basic form of measurement, 0 or 1 being no power or power. A lesser known term, but still cool nonetheless, is that 2 bits together form a crumb, 4 bits contain a nibble, and 8 bits together a byte. That's how we got there. Bits, crumbs, nibbles, bytes. Now, depending on the processor you have, a word would either be 16, 32 or 64 bits. We generally don't see 16-bit processors anymore, so generally speaking, a word is either going to be 32 bits or 64 bits. This doesn't mean a word that you've written on your word processor, but a unit of measurement, just like byte is. Now, in most places, a kilo is 1,000, such as kilometers, and in 1,000, such as kilometers means 1,000 meters. While this is true in networking, it becomes slightly more complicated because some sources define a kilobit as 1,024 bits, while others might define a kilobit as 1,024 bytes. One of the reasons for this confusion is, and you can see right here how we get that 1024, 2 to the 10th bytes. And one of the reason for this confusion of bits versus bytes is because of the little b versus the big B. So here is a fairly easy breakdown that nearly anywhere you go, and more importantly on the exam, is going to allow you to have a perfect understanding of how much data we're actually talking about. This chart specifies how the breakdown of binary data is mathematically calculated. And as binary is a base 2 system, and we'll talk more about that when we get into binary and creating binary numbers like IP addresses. And why is it base 2? Because we only have two options, a 1 and a 0, which is a bit. And remember, 8 bits go into a byte. So this chart mainly demonstrates how that numbering system works. The magic number I really want you to pay attention to is 1024. That's the number of bytes in a kilobyte, the number of kilobytes in a megabyte, the number of megabytes in a gigabyte, the number of gigabytes in a terabyte, so on and so forth. Now, you're not going to be asked to calculate this necessarily, but it's good to know nonetheless. All right. So we just talked about a signal and what analog means. The signal being how that data is sent, modified, and received, and then analog being that it can have many different values. We looked at the attributes of an analog signal, including amplitude, a peak, a trough, frequency, and so on. We also looked at a digital signal and digital data transmissions, remembering that a digital signal can only have generally two values, a 1 and a 0. And depending on whether we're comparing it to its own or to the ground, we have different digital data transmission methods. We also looked at modulating, which allows us to send a signal over a more powerful carrier signal in order to allow it to travel long distances. We looked at digital signal modulation techniques. Perhaps we got a little too involved in it. And we talked about how then we can convert these digital signal into an analog signal for sending over data, and then how we demodulate it back. And we talked about the device doing this is called a modem, which modulates and demodulates. We also described digital signal referencing methods, in other words, how it knows where the signal begins and where it ends. Finally, we described the digital data units. Specifically, I wanted you to pay attention to the fact that 1 bit equals the fact that 8 bits equal 1 byte, and the fact that 1024 bits are in 1 kilobit, or 1024 bytes are in 1 kilobyte. Network protocols and services. common network ports and protocols. Alright, now we start getting into what I think is the fun stuff in this Network Plus exam. And in some ways, it's also where a good bulk of the questions are going to come from. By the end of this module, you're going to be able to say what each of these numbers represents in terms of a protocol. Now, if you took the A+ exam, and I hope you did, you probably recall some of these from there. So this might be a bit of a recap for you. But that's okay. It never hurts to go over this stuff again, especially because it just always pops up on the exam. And as far as knowing stuff, this is one of those things that you just have to know. These protocols are what you really have to know. And we're going to talk about the protocols in more depth later, too, when we talk about what TCP/IP is. But I want to start talking about these now, since a port is really the end point, logically, of a connection. So we're going to start by talking about what a port is in a little more detail and outline the different port ranges. There are 3 of them: well-known ports, registered ports, and then the last range, which is experimental sort of ports and private ports. So we're going to outline the most common, well-known default ports and the protocols that go along with them. I'm actually going to give you a huge list of all the protocols you need to know, and we're going to talk about some of those in depth in this module, some in the next module, and then some later on in the course. But I'm going to get them all out onto a chart for you right now. Finally, I want to define and describe the common ports and protocols dealing with FTP, or the File Transfer Protocol, NTP, or the Network Time Protocol, SMTP, the Simple Mail Transfer Protocol, POP3, or the Post Office Protocol, used to receive email as opposed to SMTP, which is used to send email, IMAP, which is also used for receiving or accessing email, which stands for the Internet Message Access Protocol, NNTP, or the Network News Transfer Protocol, something you may have used if you've ever used RSS feeds, HTTP, or the Hypertext Transfer Protocol, and HTTPS, which is the secure version. These are what allow you to browse on the internet. And finally, we'll talk about RDP, or the Remote Desktop Protocol, which allows you to remote in to a Microsoft computer. All right, so let's talk about these in more depth. First off, we have to define a port. In computers and networking, a port is a process-specific or application-specific designation that serves as a communication endpoint in the computer's operating system, meaning where the communication logically ends once it reaches the user. The port identifies specific processes and applications and denotes the path that they take through the network. Now, the Internet Assigned Numbers Authority, or the IANA, is the governing entity that regulates all of these port assignments and also defines the numbers or the numbering convention that they're given. Now, these ports range from 1 to over 65,000. Port 0 is reserved and it's never used, so don't really worry about that. Now, within this range, we actually have 3 different subsets of ranges. And as administrators, knowing the common ports is crucial to managing a successful network. The common ports are some of the guaranteed few questions that I know you're going to have on the Network Plus examination, and nearly every other network examination as well. So covering these and committing these to memory is of the utmost importance. Now, within that range from 1 to over 65,000, there are 3 recognized blocks or subsets of ports. The first block is considered the well-known ports. These ports range from 1 to 1023. This is where we're mostly going to look at ports when we look at them in just a minute. These are used by common services and are pretty much known by just about everyone in the field. Now, the next range of ports is called the registered ports range. These span from 1024 to 49,151. These are reserved by applications and programs that register with the IANA. An example might be, for instance, Skype. which registers and utilizes port, I think, 23399 as its default protocol. Don't worry about that, but if you're curious for your firewall's sake, this is the port I believe Skype uses. Finally, we have the dynamic or the private port range. This is everything else, 49,152 to 65,535. These are used by unregistered services in test settings and also for temporary connections. You can't register these with the INA. They're just left open for anyone to use for whatever purposes you may need them. So now let's talk about the well-known default ports you need to know for the exam. This chart is really what you should commit to memory, since and when you get to the test, you want to be able to basically recreate this chart before you sit down and take the test. You'll be able to do this on what's called a brain dump sheet. So let's talk about the first portion of these ports we need to know. The first is port 7. This is for the ICMP echo request, or ping. If you've ever pinged something from the command line, this is what we're talking about. We'll talk more about this a little bit later. Next, we have port 20 and 21. These are for the FTP, or File Transfer Protocol, which allows you to transfer files over a network. We'll talk more about this in just a minute. Port 22 is for the Secure Shell, or SSH, and port 23 is for Telnet. Both of those we're going to discuss later on in a different module, but they're sort of allowing you to remote in and control a remote computer, albeit not from a graphical standpoint. Port 25 is the SMTP, or Simple Mail Transfer Protocol, which allows you to receive email, and DNS, or the Domain Name Service, which uses port 53, is what allows you to transmit or to translate, say, google.com into its IP address when you're browsing out on the internet. This is a really important protocol, and we'll talk more about it later, along with the DNS sort of server. Ports 67 and 68 are for what are called DHCP and BootP, or the Bootstrap service for servers and client respectively. One for servers and one for clients, as we can see right here. We're going to define and describe those in more detail in the next lesson. Now, port 69 is the Trivial File Transfer Protocol. This is related to the file transfer protocol we mentioned up here, but it is trivial, meaning that it is not connection-oriented and doesn't really guarantee that the file has been transferred. Port 123 is the Network Time Protocol, which keeps the clock on a network or on computers on the network up to sync. A great way to remember this is that time is always counting. 1, 2, 3. Port 110 is for the POP3, or the Post Office Protocol, which is how many of us download our email onto our local device. And then port 137 is the NetBIOS naming service. This is similar to DNS, but is specific to Windows operating systems or Microsoft operating systems. Related to POP3 is port 143, which is IMAP, the Internet Message Access Protocol. This is another way of accessing and managing your email. Let's continue taking a look at a few more protocols that are equally important. The first is the Simple Network Management Protocol, which allows you to manage devices on a network, say by getting error messages from your printer or from a router. This uses port 161. We'll discuss this a lot more in detail later as well. Port 389 is the Lightweight Directory Access Protocol. This is what allows a Windows server to have usernames and passwords. Port 443 is HTTPS, or the Hypertext Transfer Protocol over Secure Socket Layer. Notice the S here. This is what allows us to browse the internet, but securely. We also have port 500, which is IPSEC. This one also has another name, which stands for Internet Security Association and Key Management Protocol. Basically, IPSEC, or IP security, is what allows us to have secure connections over IP. Finally, we're going into RDP, or the Remote Desktop Protocol, which allows us to remotely access a computer, Windows-based specifically. Port 119, or the Network News Transfer Protocol, which is not only used with Usenet, a sort of message board that's been around for a very long time, but also RSS feeds, which you might be more familiar with. And finally, port 80 is HTTP, or Hypertext Transfer Protocol. The other thing to know about HTTP is it has an alternate port of 8080, so you might see either one of these on there. All right, now I know that was a lot of information I just threw out there, but we're going to cover these all in a little more depth as we go through here, and I just wanted to lay them out in a very simple chart-based way so that you could commit them to memory. Now let's talk about these in a little more depth, understand how they function, and why. First up is the File Transfer Protocol, or FTP. This protocol enables the transfer of files between a user's computer and a remote host. Using the File Transfer Protocol, or FTP, you can view, change, search for, upload, or download files. Now, while this sounds really great as a way to access files remotely, it has a few considerations that need to be kept in mind. The first is that FTP by itself is very unsecure, and an FTP daemon, which is a Unix term for a service, has to be running on the remote computer in order for this to work. You might also have to have an FTP utility or client on the client computer in order for you to have this protocol operate effectively and for you to be able to use it. Now, trivial FTP is the simple version of FTP and does not support error correction and doesn't guarantee that a file is actually getting where it needs to. It's typically not really used in many actual file transfer settings. Now, just as I just mentioned, you might need a client FTP software on your computer. Generally speaking, there is a command line prompt that you can use. It goes like this: FTP space the fully qualified domain name, for instance, google.com/FTP, which I don't think is the actual one, or the IP address of the remote host. You only need one or the other. If you provide the IP address, you're sort of using the direct route. If you're using what's called the fully qualified domain name, which we'll talk about a little bit later, then you allow something called DNS, or the Domain Name Service, to do the translation into a IP address for you. Remember again that FTP uses ports 20 and 21 by default. Next is the Simple Mail Transfer Protocol, or SMTP. This is used to manage the formatting and sending of email messages. Specifically, we're looking here at outgoing email. Using a method called store and forward, SMTP can hold on to a message until the recipient comes online. This is why it's used over unreliable wide area network links. Once the device comes online, it hands the message off to the server. The SMTP message has several things, including a header that contains source information as to where it's coming from, and it also has destination information as to where it's going. Of course, there's also content information, which is inside of the packet. The default port for SMTP is port 25, although sometimes you might see it use port 587, which is by relay. I wouldn't worry too much about that one for the exam, but just keep in mind port 25. Now, like SMTP, POP3 is a protocol that's used in handling email messages, and POP3 stands for the Post Office Protocol, version 3, which is the commonly used version now. Specifically, POP3 is used for the receipt of email or incoming email, and it does this by retrieving email messages from a mail server. It's designed to pull the messages down, and then, once it does that, the server deletes the message on the server source by default, although you can change that if an administrator wants to. This makes POP3 not as desirable and weaker than some other mail protocols, specifically IMAP, which we're going to see, because it puts all of the brunt of the responsibility onto the client for storing and managing emails and deletes all the emails at the source. So if something happens to your computer and you don't have a backup, you're in big trouble. The default port for POP3, as we mentioned, is port 110. So remember, port 110 is POP3 and port 25 is SMTP. Now, IMAP4, usually just called IMAP, is the Internet Message Access Protocol. And it's similar to POP3 in that it's also utilized for incoming mail or mail retrieval. But in nearly every way, IMAP surpasses POP3. It's a much more powerful protocol because it offers more benefits like easier mailbox management, more granular search capabilities, and so on. With IMAP, users can search through messages by keywords and choose which messages they want to download. They can also leave IMAP messages on the server and still work with them as though they're on the local computer. So it seems that the two are synced together perfectly, the server and the client. Also, an email message with, say, a multimedia file can be partially downloaded to save bandwidth. Now, the main benefit here is we're going to use this instead of for, say, a computer. Let's say I have a smartphone and a computer. Now, it's going to make sure, because the source is all stored at the server, that if I delete something, say, on my computer, that syncs up to the server, and then the server will have that sync with my smartphone. So all of these are in perfect synchronization. This is why it's much stronger than POP3, which simply downloads the email onto your client device. By default, IMAP uses port 143, which is different from IMAP, POP3 rather, which uses 110. Now, NTP, or the Network Time Protocol, is an internet protocol that synchronizes system clocks by exchanging time signals between a client and a master clock server. The computers are constantly running this in the background, and this protocol will send requests to the server to obtain accurate time updates up to the millisecond. This time is checked against the U.S. Naval Observatory master clock or atomic clock. So the timestamps on the received updates are verified with this master clock server, which is again that U.S. Naval server. And the computers then update their time accordingly. The port this uses is port 123, which is as easy to remember as time keeps moving up. 1, 2, 3. Now, if we add an additional N to the previous one, we get what's called the Network News Transfer Protocol. This is very different from the Network Time Protocol. It's used for the retrieval and posting of news group messages or bulletin messages to the Usenet, which is a worldwide bulletin board that's been around since the 1980s, really since the internet was in its nascent stages. The Network News Transfer Protocol is also the protocol that RSS feeds are based on. This stands for Really Simple Syndication. Basically, this is where a user can subscribe to an article, web page, blog, or something similar that uses this protocol. And when an update is made to that page or to that article, the subscriber is updated. So in this way, you can get updated articles from your favorite web page just like you would new emails. With NNTP, however, only postings and articles that are new or updated are submitted and retrieved from the server. Slightly different from RSS, but RSS is based on NNTP. The default port for this is port 119. So, we're covering a lot of different numbers here. It's really important, perhaps even more than memorizing specifically what each protocol does, that you definitely memorize which port it's a part of. If you can memorize, by the way, the number and what the acronym means, you should be fine. Now, a protocol you use every day, even if you don't realize it, is HTTP, or the Hypertext Transfer Protocol. This is used to view unsecure web pages and allows users to connect to and communicate with web servers. Although HTTP is going to define the transmission and the format of messages and the actions taken by web servers when users interact with it, HTTP is what we call a stateless protocol, meaning that it may be difficult to get a lot of intelligent, interactive responses to the information. If you remember ever making very basic web pages using HTML or the hypertext markup language, the language that HTTP is reading, then you probably know this. So if you want more interactive web pages or interaction with web pages, then you're going to use different add-ons, such as ActiveX that you might have heard of. HTTP default port is port 80, and a common alternate port for it is port 8080. Now, similar to HTTP is HTTPS, or Hypertext Transfer Protocol over SSL, which is the Secure Socket Layer. This is a secure version of HTTP. So if you ever see an S on the end of just about any protocol, you can bet that that has to do with this, being secure. And it creates secure connections between your browser and the web server. It does this using SSL, or the Secure Sockets Layer. We're going to discuss the Secure Sockets Layer when we discuss encryption in more detail in a future lesson. Now, most web pages support HTTPS, and it's recommended that you use it over HTTP almost every time you're able to. The way you do this is simply by using, instead of http://facebook.com, just put an S in front. Yes, Facebook supports this, as do other social media sites, and even email, and even Google supports HTTPS. Why would you want to do this? Well, say someone is browsing or listening in to your Google searches. That might be information you don't want someone else to know. Just as a recommendation, absolutely anytime you visit any website, but especially financial institutions such as your bank or your credit union, you want to ensure that in the bar it says HTTPS. If it's not, then opening anything in this, including typing in your bank password, could be really serious. The same goes for anything when we're dealing with credit cards, for instance, buying something. Make sure that HTTPS appears in the bar or in your URL bar at the top. As we've mentioned before, too, the default port is port 443. Now, the last port I want to discuss is RDP, or the Remote Desktop Protocol. RDP servers are built into the Microsoft operating system, such as Windows, by default. And it provides users with a graphical user interface, or a GUI, to another computer over a network connection. So this protocol allows users to remotely manage, administer, and access network resources from another physical location over the internet, which is represented by the cloud. There are a few security concerns that come with RDP, and there is potential for certain sort of computer attacks. So there are also non-Microsoft variations available, such as something called RDesktop for Unix, which if you are going to be doing a lot of remoting, you might want to look into. RDP, by the way, uses default port 3389, although you can change that. Usually as well, when we're using RDP, we're also going to use it over what's called a VPN, or virtual private network, which creates a tunnel through which your connection occurs. This improves the security we were just talking about. So let's review what we've just talked about. First, we talked about a port being the logical endpoint of a connection, and then we outlined the port ranges. Remember, we had the well-known ports, the registered ports, and then the dynamic or private or experimental ports. What we really want to learn for ourselves are the well-known ports. I then outlined the most common well-known default ports and their protocols. You want to memorize this table for the Network Plus exam. I guarantee you doing that will get you a bunch of questions on the exam. Finally, we defined and described some of the specific ports, and we looked not only at the protocol and their protocols, including FTP, or the File Transfer Protocol, NTP, or the Network Time Protocol, SMTP, or the Simple Mail Transfer Protocol, POP3, or the Post Office Protocol. We also looked at IMAP, the Internet Message Access Protocol, and again, all three of these have to do with email. We also looked at an NTP, which is not Network Time Protocol, but the Network News Transfer Protocol. We looked at two different versions of HTTP, one that is secure. These allow for browsing, and it stands for the Hypertext Transfer Protocol, which, if you know HTML or the Hypertext Markup Language, then that might be familiar to you. And finally, we looked at RDP, or the Remote Desktop Protocol. I know this seems like a lot, but I guarantee memorizing all of these and all of the numbers that they're associated with is going to help you so much on the exam. Network protocols and services, interoperability services. This word interoperability is a really long one, but it's also a good one. Basically, what this means is how different types of operating systems and computers can communicate with one another over a similar network. And that's what we're going to be discussing in this module. So we're going to first cover what interoperability services are in a little more depth. Then we're going to define some specific services that qualify as these, particularly NFS, or the Network File System. I'm sure you can imagine what that is from its name. We're also going to look at SSH, which is the Secure Shell, and SCP, Secure Copy Protocol. Remember, every time we see that S, we want to think security. That's a great tip that'll help you out on the test. By the way, Secure Copy Protocol is similar to SFTP, or the Secure File Transfer Protocol. We're then going to look at Telnet, or the Telecommunications Network, and SMB, or the Server Messenger Block, which is what allows us to share, for instance, files and printers. We're also going to look at LDAP, or Lightweight Directory Access Protocol, and that word directory is important as it allows us to manage users in our network. And then ZeroConf in networking, which also stands for Zero Configuration Networking, a set of protocols that allows us to sort of plug in and go without having to do a lot of advanced configuration and setup. This is what allows us to have very easy plug-and-play network devices such as our SOHO routers, which is a good way to think about it. However, it's also deployed in much larger operations in order to ease the burden on administrators and technicians. So in the previous module, we discussed several different protocols that were used in the TCP/IP protocol suite. And these allowed us to do a lot of different things. By the way, TCP/IP, which is what basically allows us to communicate over the network in general, is going to be discussed in more detail and depth later on in this course. Now, because not all computers are made the same, or by the same people or individuals, certain protocols and services need to be in place to allow dissimilar systems, such as PCs and Macs, to be able to interact with one another. So TCP/IP also contains these interoperability services that allow dissimilar services or systems to share resources and communicate efficiently and securely, which is important if I want to make sure that no one is reading all of the information I'm sending between computers. So these services is what we're going to spend the rest of this module discussing. Now, the first service is the Network File System. It's an application that allows users to remotely access resources and files, a resource being, for instance, a printer, and a file being like a Word document, as though they were located on a local machine, even though they're someplace else. This service is used for systems that are typically not the same, such as Unix, which is the larger version or the commercial version of Linux, and Microsoft systems. Now, NFS functions independently of the operating system, the computer system it's installed on, and the network architecture. This means that NFS is going to perform its functions regardless of where it's installed. And since it's what we call an open standard, it allows anyone to implement it. It also listens on port 2049 by default, but I wouldn't worry about memorizing that for the test. Next, SSH, or the Secure Shell, is one of the preferred session initiating programs that allows us to connect to a remote computer. It creates a secure connection by using strong authentication mechanisms, and it lets users log on to remote computers with different systems, independent of the type of system you're currently on. With SSH, the Secure Shell, the entire connection is encrypted, including the password and the login session. It's all compatible with a lot of different systems, including Linux, Macs, and PCs, and so on. Now, there are actually two different versions of Secure Shell, SSH1 and SSH2. These two versions are not compatible with one another, which is important to know, because they each encrypt different parts of the data packet, and they employ different types of encryption methods, which we'll talk about later. However, the most important thing to know is that SSH2 is more secure than SSH1, and so in most cases we want to use that. This is because it does not use server keys, SSH1 doesn't, which are keys that are temporary and protect other aspects of the encryption process. It's a bit complex and over the course of the objectives of this course. However, SSH2 does contain another protocol called SFTP. And SFTP, or the Secure File Transfer Protocol, is a secure replacement for the unsecure version of plain old FTP. And it still uses the same port as SSH, which, if you recall, is port 22. So it's important to know that if we're going to be using SFTP, remember FTP uses 20 and 21, if we're using SFTP, we're using port 22. Now, similar to SFTP is SCP, or the Secure Copy Protocol, which is a secure method of copying files between remote devices, just like FTP or SFTP. It utilizes the same port as SSH, just like SFTP, and it's compatible with a lot of different operating systems. To implement SCP, you can initiate it via a command line utility that uses either SCP or SFTP to perform some secure copying. The important thing here to know for the Network Plus exam is not when you would use SCP over SFTP, which is a little bit more complex, but rather to realize that SCP is a secure method of copying, as is SFTP. That's how you're going to see this pop up on the exam. Now, in contrast to all of this secure communications, I want to talk about Telnet, or the Telecommunications Network, which is a terminal emulations protocol. What this means is that it's only simulating a session on the machine it is being initiated on. When you connect to a machine via a terminal by using Telnet, the machine is translating your keystrokes into instructions that the remote device understands, and it displays those instructions and the responses back to you in a graphical or command line manner. Telnet is an unsecure protocol, which is why we don't use it as much as SSH anymore. And this is important to keep in mind. So when you send the password over Telnet, it's actually in what we call plain text. Whereas, as we mentioned with SSH, it transmits the password encrypted. So if someone is reading the packets that are going back and forth, they won't be able to hack your system if you're using SSH, whereas with Telnet, they'd be able to read your password. Now, Telnet uses port 23 by default, which is important to know. However, you could configure it to use another port as long as the remote machine is also configured to use that same port. With Telnet, you can actually connect to any host that's running the Telnet service, or daemon, which again, the word daemon is a Unix version of service. SMB, or the server message block, which by the way is also known as CIFS, or the Common Internet File System, is a protocol that's mainly used to provide shared access to files, peripheral devices like printers most of the time, and also access to serial ports and other communication between nodes on a network. Windows systems used SMB primarily before the introduction of something called Active Directories, which we'll talk more about a little bit later. This is currently what's used in Microsoft networks. Now, Windows services that correspond are called server services for the server component and workstation services for the client component. Now, for example, the primary functionality that SMB is typically most known for is when client computers want to access file systems or printers on a shared network or a server. This is when SMB is most often used. Samba, which you may have seen if you've ever dealt with a Mac or a Linux computer, is free software that's a re-implementation of the SMB or CIFS networking protocol for other systems. Even though SMB is primarily used or was primarily used with Microsoft systems, there are still other products that use SMB for file sharing in different operating systems, which is why it's important that we still familiarize ourselves with it. LDAP stands for the Lightweight Directory Access Protocol. And this is what defines how a user can access files, resources, or share directory data and perform operations on a server in a TCP/IP network. Now, this is not how they access it. This simply defines how a user can access it, meaning that what we're really talking about here are users and permissions. So basically, LDAP is the protocol that controls how users manage directory information, such as data about users, devices, permissions, searching, and other tasks in most networks. We're going to deal with this a little more in depth later on as well. Now, it was designed to be used on the internet, and it relies heavily on DNS, the Domain Name Service, which we talked about is a way of converting, say, google.com into its IP address. We're going to discuss DNS in greater detail in another module. Now, Microsoft's Active Directory service, which we just mentioned, and Novell's NDS and eDirectory services, Novell being another networking operating system, as well as Apple's Open Directory directory system, all use LDAP. Now, the reason it's called lightweight is because it was not as network intensive as its predecessor, which was simply the Directory Access Protocol. No need to know that, but I just wanted to explain the reasoning behind that lightweight in there. Also, it's important to know that port 389 is used by default for all the communication of the requests for information and objects. Finally, zero-conf, or zero configuration networking, is a set of standards that was established to allow users the ability to have network connectivity out of the box, or plug and play, or without the need for any sort of technical change or configuration. Zero-conf capable protocols will generally use MAC addresses, or the physical addresses, as they are unique to each device with a NIC, or network interface card. In order for devices to fit into a zero-conf standard, they have to fit or meet 4 qualifications or functions. First, the network address assignment must be automatic. If you recall from A+, and this is something we'll talk about a little later, this is what we use when we're using DHCP. Second, automatic multicast address assignment must be implemented, which is also related to the DHCP standard. Third, automatic translation between network names and addresses must exist. This is what we talk about when we deal with DNS. Finally, discovery of network services or the location by the protocol and the name is required, meaning that it must be able to find all of this information when it goes on the network automatically. This is what allows users to be able to purchase a router from the local Best Buy or electronics store, take it home, plug it into their ISP or internet service provider connection, and automatically have it work automatically. Another implementation, by the way, of this is a configuration in networking called UPnP, or Universal Plug and Play. So to recap what we talked about interoperability services, which allows, for instance, a PC and a Mac to communicate flawlessly over a network. We then talked about the network file service, SSH and SCP, SSH being a secure shell, working on port 22, and SCP being the secure copy protocol, similar to SFTP, the secure file transfer protocol. We looked at Telnet, which is sort of a plain text version of SSH, so it's been replaced by it, and SMB, or the server message block, allowing us to share files and resources between different types of systems. Finally, we described and defined LDAP, or the Lightweight Directory Access Protocol, which defines users and their ability to access all this stuff on the network. And then we explained zero-conf, or zero configuration in networking, which allows us to plug up a device and have it work almost instantaneously.
Welcome to Module 5, Lesson 1, Ethernet Standards. Pretty meaty subject this, because there's got a whole bunch of standards and information as well as history to fit in. What is Ethernet? The history, why the name, just in case you wanted to know, I guess. Introduction of Ethernet standards. The IEEE standard as well, 802.3, which you'll need to be familiar with, which defines Ethernet. The IEEE as well, what they do and their remit, purview. Baseband and broadband, some history really of the early days of Ethernet networking, which depending on how old you are, you may be familiar with. Some of the naming conventions, the early days, the early specifications, thicknet, thinnet. And some of the standards here which we're going to run through, which you'll need to be familiar with because you could be asked a question. So that's a good reason as any. Ethernet is the first high-speed LAN technology that interconnected computers, high-speed laser printers. Obviously in the early days there needed to be some agreed format for internetworking devices to communicate. Actually invented by a guy called Bob Metcalfe back in 1973. It was remarkable in as much that at the time computing was dominated by some very large and expensive mainframe computers, to name IBM as one of the main players at the time. So only a few people could actually afford to buy the mainframes, and the information required in order to use them, operate, support and maintain was only known to a few people at the time. So Bob actually changed the name of his first network from Alto Aloha network to Ethernet, thankfully, otherwise we'd all be referring to it as Alto Aloha, which would be a bit strange. Why the name? Bob's experimental network, the physical medium or the cable to carry out all the bits. To describe the important feature, Bob named the network based on the word ether. The old luminiferous ether was once considered the medium for the propagation of electromagnetic waves. So there is some mythical background in it. First standardized by the consortium of DEC, Intel, Xerox or DIX. Later actually standardized by the IEEE. Standards define several aspects that make data transmission possible. This is their job. Term Ethernet is used to refer to both the original DIX Ethernet, which we'll rarely talk about unless we're talking in the context of exams, and the 802.3 specification, which specifies Ethernet old and new. So 802.3 is an international standard for local area networks and metropolitan area networks that employs the carrier sensor multiple access with collision detection, the Ethernet protocol frame format for communication. The IEEE is the Institute for Electrical and Electronic Engineers, largest professional association for the advancement of technology. It has more than 400,000 members spanning more than 160 countries. So what do? They provide cited publications, they develop on new and emerging technology standards. They also have conferences that various network engineers can attend to swap ideas and advance the technology. Fortunately, I'm not the points aren't sliding in as they should be, so all the information is appearing at the same time, sorry. So the IEEE's leading developer of international standards. They include the 802 standards, which are for LANs and MANs, and wireless local area networks also, which we'll refer to usually as Wi-Fi. You'll see the little stickers on Wi-Fi devices, and when you go to cafes they may well have a Wi-Fi sticker to say they give wireless access. So Ethernet's the most popular today. It's everywhere, basically making communication possible for pretty much everyone. Mainly popular because of the fact it's economical to use, it uses high speed, it's reliable, and it's easy to install and maintain. Also free to use the standards like TCP/IP. If you used a custom solution by another creator, then you'd obviously have to pay to use all of their specifications and standards. So the early Ethernet ran over what was known as coaxial cables. Modern Ethernets don't do that anymore because of the limitations of speed and troubleshooting. They use a mixture of copper and fiber depending on the location and how much, what the budget of the various devices or local government authorities have. Baseband and broadband is the term synonymous with Ethernet. The band is actually referred to the bandwidth in context of the transmission. Broadband is a broadband system. A whole band of transmission medium is shared, dividing it into pieces called channels. Each channel will have the portion of the whole band. Multiple channels will serve as multiple signal carriers, each carrying its own data on the same transmission medium. So basically we're all sharing the same medium. The local ratio, I think, for my broadband here is 30 to 1. So 30 users will use one connection to the local switch provided by the telephone company. Baseband, in the baseband system, the entire band of the transmission medium will be used as a signal carrier. Naming conventions. The Ethernet standards use a naming convention that helps us determine a few things: the speed of the transmission, the signaling type, and the length of the cable. Cable type used as well. For example, 10base5, really old standard this. It was been phased out in the late 90s, I think, when I was just getting into networking really. So 10base5 is named for the following. 10 is the transmission speed, which is 10 meg. Base means the type of signaling is baseband, and 5 indicates that the maximum length of the cable can be up to 500 meters. This is for the segment, so you could have another segment after 500 meters, and the signal would all have to be replenished. Okay, so 1000 base TX, the following is true. 1000 indicates, 100 base TX. 100 is the speed, which is 100 meg. Base stands for baseband again. T indicates that the standard is twisted pair. X at the end indicates that the cable is capable of full duplex communication. 10base5, real old standard again, based on 802.3. The original standard uses a thick coaxial cable as its physical medium. It was actually called ThickNet for short, and you can see the picture of it there. To actually connect into the cable, you use these big plastic devices called vampire taps, and they physically screwed in to the cable and pierced it. Very awkward to use and hard to troubleshoot. It ran at 10 meg, either RG8 or RG11. It had little resistors on the end to stop the signal bouncing off the back of the cable and coming back, and they ran at 50 ohm. RG stands for Radio Government. The standard determines the type of coaxial cables. The distance was up to 500 meters. There were a few pros and cons to using ThickNet. You have protection against electromagnetic interference, which can seriously degrade your signal. Disadvantage, there was loads actually. Difficult to work with, very difficult to troubleshoot. Cable was very thick, so trying to expand it around an office without people tripping over or hitting the head off them was quite awkward as well. ThinNet is based on the 10base2 standard. So 10 meg baseband, and 2 stands for how long the you could get the connection, which is 200 meters. It was actually 185 was recommended, but you couldn't shorten 185, so they called it 10base2. Being cheaper than ThickNet, it was called CheaperNet. Before we had any type of networking, we used to use floppy disks. Big thick floppy disks, not even the small ones that you might remember. That was called SneakerNet. 10BASE-T was one of the first modern standards introduced in 1990. It ran over 10 meg over 2 pairs of twisted paired telephone wire, and it allowed your network to use the existing telephone cabling, which was pretty handy. Really easy to install, reduce costs. The cable could just be run off and you could cut it to whichever length you required. And also obviously it could use a network switch, which the thick and thin net couldn't use a switch or hub. T denotes twisted pair wires. 10BASE-T is category 3 cable. We used to call it Cat3 for short. In fact, every category is called a Cat for short. High category cables can be used with the 10BASE-T Ethernet. So examples are Cat5, 5E, 6, 6A and so on. This changes every few months as a new category introduced. Higher categories of the UTP cables have higher specifications and they can handle higher data transmission speeds. The 10BASE-T supports a maximum cable length of 100 meters. 100BASE-TX I mentioned earlier, 100 meg over 2 pairs of Cat5 twisted pair cabling. You can get 100 meters before you have to terminate the cable. It would normally then go into a switch. It's called Fast Ethernet. So 100 meg, obviously 10 times faster than 10BASE-T. Became widely used because of its compatibility with 10BASE-T. So imagine back in the day you would have your the core of your network running at 100 meg, and then if you didn't have the budget, you would have your individual PCs connecting at 10 meg into the network switch or hub. They used Cat5 cables, a lot easier to upgrade because it used the same cabling principles and same pinouts and termination. 100BASE-FX, F is usually designates fiber optic. Fiber standard for 100 meg Ethernet is 100BASE-FX. So this is a 802.3U specification. It's 100 meg Ethernet over 2 multi-mode optical fibers. One's used for the transmission and one's used for the receiver, as designated in the diagram there. The 100BASE-FX standard supports the maximum cable length of 400 meters in half duplex mode. Half duplex is pretty old-fashioned now, to be honest. Or in full duplex mode, which means it can send and receive at the same time, then up to 2 kilometers. Half duplex mode is what I've just said basically. It's like a walkie-talkie. A device can either send or receive data at a given time, but it can't do both. Full duplex, it can do both. So it's like having a telephone conversation. 1000BASE-T, now we're talking. 10 times faster than 100. It's IEEE 802.3AB specification. It's 1000 megabit per second Ethernet network, uses 4 pairs of Cat5 cable or better. Speak to your cabling provider to find out what cable you can use, minimum standards. 100 meter length of cable. It's referred to as gigabit Ethernet, 1000 bits. Dead easy to install, runs on Cat5, inexpensive cables. As an example of a Cat5 cable, which I'm sure you've seen many times, even if you've got a home computer. So the Cat5 cables have 4 pairs of twisted wire, which is 8 individual strands. The 10 and 100BASE-T only uses 2 pairs. All 4 pairs are used by the 1000BASE-T. Popular gigabit Ethernet. The 1000BASE-T is the most widely used version. You've got the 802.3 standard that specifies other versions of gigabit Ethernet. Here are some of your options. 1000BASE, CX, LS, LX, SX. You need to know some of this information, but I think one of the questions they could ask is which one of them is fiber optic, and the answer is LX. It's a question I've seen before. I think I was actually asked in a Cisco exam, not CompTIA Network Plus, but good to know anyway. So 5 kilometers to 550 meters, depending if it's single or multi-mode. SX is implemented over multi-mode fiber as well, so LX and SX. 1000 base TX is gigabit over Cat6 cabling. Supports a maximum cable length of 100 meters. Uses only 2 pairs of wires for the data transmission. Now the 1000 base TX you don't really see much anymore, is a bit of a commercial failure, mainly because of the 1000 base T. The cost was so affordable. You had to upgrade all of your cables from Cat5 or Cat5e to Cat6, which is a lot of inconvenience and expense for companies and downtime, because of all your core devices would need, the connections would need to be changed as well. Normally have to schedule downtime for this. 10 gig base T, 10G base T, 10 times faster than 1000 base T Ethernet. Operates at 10 gig. It's an 802.3AN specification. 4 pairs of Cat6A cable or higher. 100 meters maximum. It's an augmented version of category 6, which you can see 6A isn't the same as 6. Frequency is at 500 megahertz. Next standard is 10G base SR. This is gigabit Ethernet over fiber optic cables. I don't know why they don't just put a F in all of the fiber specifications. It's a little bit annoying, to be honest. 802.3 specification. It's 10 gig Ethernet over multi-mode fiber. The SR stands for short range. The cable length is 300 meters. You're going to need to make a note of all of these in case they, for some reason, want you to remember this. Generally, most of us will just speak to the sales advisor, or just look on the online at some documentation. 10G base ER. 802.3 AE. Gigabit over single mode fiber optic cabling. ER stands for extended range. You got up to 40 kilometers, which is quite a nice distance. Well, amazing distance, in fact. SW, that was designed for use over a particular type of technology, SONET or SDH. Again, multi-mode fiber, 300 meters again. Alright, so we've covered a few of the basics of Ethernet here, the history, the name, the standards, the IEEE, what they do in brief. I recommend you have a look in your own time at Wikipedia. The popularity, which is nearly always the fact the standards are free to use and it's affordable, and everyone else is using the same standards. Baseband and broadband, the naming conventions, and then some of the different standards here. You'll need to know the different standards, which uses single and multi-mode, how long you can have the segment lengths and that kind of thing. Alright, so that's the end of the presentation. Thanks for watching.
Network infrastructure and design, network models, the OSI model. So we're going to discuss two different models coming up here, and the first model I want to talk about is the OSI model in this module. Now from this lesson, you're going to have a thorough understanding of each of the layers in this module, and there are 7 of them, and we're also going to talk about how those layers communicate, some of the devices that operate at specific layers, specifically layers 1 through 3, and some of the protocols that operate on some of these layers as well, specifically the upper layers. We're also going to have a better understanding of what the OSI model is and why we use a layered approach. So this model is going to teach us everything we need to know about the OSI model. We're going to begin by explaining exactly what the OSI model is and what the purpose of it is as well. Then we're going to go through and explain each layer, from layer 1, the physical layer, to layer 2, the data link layer, layer 3, the network layer, layer 4, transport layer, layer 5, the session layer, layer 6, the presentation layer, and finally layer 7, the application layer. We're also going to discuss some of the protocols and devices that operate at each of these layers, and we're also going to understand how communication begins and ends through these layers. Now, early back in the 1980s, late 70s, when networking and communication between devices was a lot simpler, a lot of brilliant individuals from the ISO, organization we've seen previously, or the International Organization for Standardization, came together and they came up with a way to outline, standardize, and characterize the functions of a communication system, or the methods by which computers are going to communicate in a network environment. So they came up with this OSI model, and I love it because I know the ISO made the OSI. And they did this in terms of abstract layers. So what we mean by these abstract layers, and here they are, again, from the top down, application, presentation, session, transport, layer, data link, physical, and just so we don't get confused, the first layer is actually here at the bottom, and the last layer is here at the top, and viewing this, we call this a top-down approach as opposed to a bottom-up approach. And these abstract layers outline the functions of the communications process, but they hide exactly, specifically how they're implemented in each layer. In other words, this really attempts to simplify, and sometimes oversimplify, exactly how everything in the network is communicated. So, let's say that we want to establish a highway. More so, we really want to build a brand new type of vehicle designed specifically to be driven on this very specific highway. And we're going to have to do it from the ground up. So let's call this vehicle a bus. Not only do we want this bus to be able to run on any of the existing highways that are out there, but we also want the bus to be able to use the already existing bus stations as well. So in order to do this, we need to understand exactly what we already have, meaning what the standards are already in place for a highway. We also need to know everything about bus stations and everything about the infrastructure of the highway system that already exists. Regardless of whether we actually have to build the highway, we still need to understand everything that relates to highways and their designs, to the materials, the limitations, and so on. So this way, when we're designing our brand new bus, we can ensure that it still can drive and operate on older highways, not to mention new highways, and that our bus is going to interact properly with the other buses and other vehicles that are on the road. The other benefit here is if I'm designing this bus and I break it down into different layers, 7 of them, I only have to worry about one part. For instance, there might be someone who is responsible for, say, the wheels, and there might be someone else who's responsible for, say, the body, and there might be someone else who's responsible for the highway, and someone else who's responsible for the bus stop, and so on and so forth. This way I can fragment everything out and give everyone specific jobs, and if a problem occurs with the bus, then I can go to the specific person with who is most familiar with that section or that layer. This is the benefit to a layered approach to creating something. So that being said, let's talk about the very first layer, layer 1. So layer 1 is the physical layer. This is the actual physical media, the cables, the wires. This is the means by which the bits go from one point to another. So for the actual cable, the infrared connection, the radio frequency, even Wi-Fi, all of these reference the layer or the pathway that the data is going to take. So to take a look in this in the way that we were talking about it with our bus and our highway setting, if our main concern is building our buses, we need to look at all of the other vehicles on the road. We need to understand their size, their shape, other characteristics, and so on. So that way we understand how our bus can use the same tracks the other vehicles are using. So here on layer 1, we have the path, the road used for communication. Again, this is the wire, the Bluetooth, fiber, copper, the Wi-Fi. whatever means there is that physically the bits, the ones and zeros, are going over this media. So the terminology for the information is considered simply the bits because we're actually transmitting the raw ones and zeros. We're not dealing here with what the information is. We're dealing with it at the most electrical, basic sort of standpoint. So this is simply the media, and this is called physical. And as you can imagine, this is also the very first place that data is going to enter into the computer, right? It goes over the cord and into a NIC. All right? Now, what happens then? Well, then we get to layer 2, which is called the data link layer. An easy way to remember that the layer 2 is data link is because it's the only one that has 2 words. It also has, and this is not as important for the Network Plus exam, but it's still good to know, there are 2 what we call sublayers, the MAC sublayer and the LLC sublayer. This layer in total, and so these 2 make up this data link layer. And this layer as a whole is responsible for allowing devices to share the same medium, the medium being the physical layer. So here we see a few things happening. First, we see a certain level of error correction and error detection on the physical layer. We're going to see this a little more on later layers as well. Also, and probably more important, we see access control, which I've denoted here, and I'll get to this in a minute, by the stoplight. So this function is performed by this MAC sublayer. Again, I wouldn't worry too much about that. But the most important thing here is that we have physical addressing, or the MAC address. So anything that looks at MAC addressing, and by the way, MAC addressing is oddly enough performed by the LLC layer, allows a device to look at a certain extra layer of information. So, whereas with layer 1 we saw physical, if you remember we talked about hubs, hubs just forward bits. They don't look at the bits. So they're going to operate at layer 1. Here at layer 2, we start dealing with MAC addresses. As a result, this is where devices like switches are found. And that's why switches are often called layer 2 devices. There are more advanced types of switches, but I want you to remember, again, a switch is a layer 2 device. Now, if we look at this in a slightly different way, here's where we have to be able to have access control on our highway. So this is where we have to be able to have proper on-ramps that are only going to allow authorized vehicles to enter onto the road. And we also need to establish standards for how the road is going to be used by everyone, perhaps with signs. And here we also need to remember this is where we establish how everyone is going to share the road, who's going to access the road, and a certain level of checking for damage on the highway and vehicles. For instance, people sort of going on and making sure there aren't potholes. In this layer, we refer to the data as frames of data because they're beginning to get framed. We're no longer just dealing with the ones and zeros. We're dealing with them in a frame or in a sort of larger context. Now, the next layer is layer 3, or the network layer. Here's where really a lot of exciting stuff happens, okay? First, the third layer is different from the second layer in that the data link layer transfers data between devices that are within the same network. Okay, so if you remember, we're dealing with switches. Switches only deal with devices on the same network. But here on layer 3, the network layer can allow us to transfer data to and from devices that are on different networks. It does this by a specific kind of addressing, specifically IP addressing. And when we deal with IP addressing, or the Internet Protocol, we allow what's called routing. So the main job of the network layer is really about this routing. It's about routing and routers. So knowing this and that IP addresses are used for routing, we come to the conclusion that the kinds of devices we're really going to find in this layer are routers. So routers are what we call layer 3 devices, and that's what you're going to see on the test. Now, for the information to actually reach the destination, this IP address has to be mapped to a physical address on layer 2. So the protocol that does this is called ARP. What ARP does is it maps, for lack of a better way of describing it, maps MAC addresses to IP addresses. By the way, ARP stands for Address Resolution Protocol. This protocol actually operates slightly on the network layer and slightly on the data link layer, because obviously it's dealing with MAC addresses and IP addresses. Now it's important that you consider that, remember we talked about UDP versus TCP, UDP being connectionless and TCP being connection oriented. That's when we're dealing with ports, and we'll talk about that more. We talked about that in A+, and we'll talk about that a little more later. Well, everything in the network layer is connectionless. This means that it manages the transfer of data in a connectionless mode. It just sends the data, but it's not going to wait for a reply to ensure it got to its destination. This means we're sort of using a best effort here. This is like dropping something in the mail and just hoping it gets there. We're not using certified mail at all. On layer 3, the information, remember layer 2 we had frames, well now we have something called datagrams. So this is, now we're moving up, right? We had frames, now the frames are packaged into datagrams. So, if we keep with our method of talking about the bus metaphor, okay? From the third layer up, we're going to concentrate on the bus itself. So we've been talking about the road, right? We talked about the road itself, the physical layer, and then we talked about how people are going to share that road, which is layer 2, the data link layer. Now layer 3, the network layer, this is the bus itself. Layer 3 through 7 concentrates on the processes that affect this container, in our case, the bus. Since we're basically designing our bus, this layer is determining the best path that our data is going to take. So in a manner of speaking, this is like the bus driver on a specific route, who's going to be constantly updating us with routing information. So it's saying, here's our first destination, here's our second destination, here's our third destination. Just in case a route is blocked or if there's a faster or better route available, layer 3 is where those protocols are going to operate to find the shortest and most reliable path to our destination. Here on the fourth layer, also called the transport layer, some crucial functions are taking place. Now, one of these functions is reliability. It can be said that the TCP protocol, what you might have heard in TCP IP, if IP was on the layer 3 perhaps, then layer 4 is TCP, the TCP portion, operates on this layer, or at least close enough to the transport layer to be considered a layer 4 protocol. Just a sort of secondary side note, and we'll talk about TCP and IP a little bit more in depth in the next module. They have their own model. The OSI model is sort of a theoretical model. It was never actually implemented as it was created. That being said, we still use it in discussing a lot of stuff, which is why we need to talk about it. So the reliability is guaranteed by, in here, the connection-oriented protocols that are on layer 4. So the transport layer has mechanisms that keep track of these segments, and when segments fail, the transport layer resends them. There's also this acknowledgement feature, such as like a certified letter would have, that ensures that when a message is received by the destination, the transport layer is notified, for instance, by a message received successfully, what we call a ACK packet or acknowledgement packet. Besides these guaranteed delivery features, we also have what's called data flow control. This function ensures that during the data transfer, the receiving end doesn't get flooded with too much data at any one time. Later in the lesson, we're going to talk about different data flow techniques and flow control techniques that are used. Now, the transport layer is where something else called sequencing of data occurs. Basically, when data is transmitted, it's either broken apart or fragmented to be able to send it across the medium. And when it's fragmented, each fragment or piece is labeled with a specific number, so that when the receiving end receives, when the receiving end of the transport layer receives this data, it can be reassembled and put back together in the proper order. This is really important, especially when data is received out of order, as I just demonstrated. Now, in essence, this layer is much like the standards and the laws that we have in place on our highways. They ensure that vehicles get us to where we need to be safely and on time. Now, some of the other protocols you may have heard of that operate on this layer are SCTP, some tunneling protocols, and more importantly, here when data is sort of partitioned out, it's called a segment, as opposed to a datagram or a frame. Now, the next layer is, I think it's one of the easier ones to memorize. It's called the session layer, and layer 5. And it's pretty simple because the sole purpose of this layer is to establish, maintain when it comes time to shut down or conclude the communication session. Now, while the OSI model assigns the responsibility of this termination of sessions to the session layer, some other models have performed this on a different layer, and we'll talk about that a little bit more. Some of the protocols you might see on here are, for instance, RPC, which stands for Remote Procedure Call, and TLS and SSL as well. So this layer manages how and for how long and in what way a device is going to establish a connection. During the communications process, if the layer is not yet completed with its functions, the rest of the network just has to wait. So in keeping with the analogy of the bus, and in order to understand how the session layer fits in, let's take a look at exactly why we're using our buses. Is it for transporting people, or is it for transporting top secret documents from the main office building to the remote office? This why is going to determine several things for this layer, right? If it's determined that we need several connections to take a private highway, for instance, it might be determined that we need a private bus to take special documents to maintain security or take a special highway, for instance. So the session layer is what's responsible for determining what type of data and how we need to connect this session. Continuing on to the next layer is the presentation layer, or layer 6. This layer is responsible for taking the data from the application layer, which is the next layer we'll talk about, and translating it into an intermediary language that the rest of the network can understand. And it's also going to perform it in reverse on the receiving end. Also in this layer, data encryption and compression takes place, sometimes called the syntax layer because of its data encryption abilities as well as its conversion to a network relatable format, or a format that applications can understand. Now, what this really means is because the applications is going to have its own syntax or its own language, the presentation layer is going to try to map between those languages. Now, if the mapping is available, then the presentation layer is going to convert the data into data units for the session protocol, and after that, it sends down the stack, down the rest of the layers to do everything else it needs to do. Now, some of the protocols that operate at this layer are anything that's dealing with compression, for instance, PNG, JPEGs, TIFF, a lot of these sort of picture file extensions that you've seen. This layer also performs code conversions. They're going to take raw application data and compress them into more manageable forms for transmitting. Now, regarding the translation capabilities of this layer, think of like two different systems that are very different from each other. One perhaps using TCP/IP, which we know, and another using IPX/SPX, which don't worry about, but it's another sort of protocol suite. This layer is what makes communications available. Because of this, we also know that a gateway device, if you recall from the devices we've talked about, is a device that's going to operate on this layer. because it's converting between two different types of networks. This is the biggest difference between a gateway and a router, which, as you recall, operates on layer 3. A transceiver, by the way, and you remember a transceiver is that device that is on a NIC. It's going to allow you to talk, for instance, between a copper and fiber network. Also might work on this presentation layer, depending on how we define it. Other people might actually say it works on a physical layer. Now, to put this layer in perspective, the presentation layer is like having a double-decker bus with a tour guide on a microphone who's translating everything that can be seen and heard to the passengers. The tour guide's also going to help repack the tourists' luggage for them, which is like compression. And it's also going to add another level of security for VIP passengers who might come on board. This is just like encryption. Here, the formatting is simply making sure that the passengers are briefed and ready for their tour, and making sure that they, or the data, is ready for the application. So again, we're really packaging this up for presentation to the application layer. And the terminology for data at this point is going to be actually called data. So this is where we're moving up in the world. We're no longer talking about segments or datagrams or frames. We're here now talking about data. It's packaged in a way that an application can read it. Finally, at the topmost layer, we have the application layer. This is the layer that's closest to the user. And it's the only one that the typical end user is going to be interacting with. Now, even though it's called the application layer, this doesn't mean that the application itself is on this layer, but that the application layer provides utilities and services that an application could use for accessing network resources, like some of these that we've talked about. SMTP, which allows you to get email. DNS, which is going to translate between an IP address and a fully qualified domain name. FTP, which is going to allow for file transferring. NTP, Network Time Protocol, which is going to keep time up to date. And HTTP, which allows us to browse. So, for example, let's say you have a file that you'd like to transfer to a remote computer, right? What method are you going to use? FTP. Now, the application layer provides the FTP services to the application you use, which is some sort of FTP client. The FTP client itself does not exist on the application layer. Simply, the protocol does. This layer is the one you've probably dealt with the most, and you're probably likely already familiar with without even realizing it. For example, you utilize this layer every time you check your email, browse, etc., and so on. Now, some of these might not fit perfectly into the application layer, and that's because, again, this is a theoretical model. When we talk about the TCP/IP model next, we'll see this working in a lot more of a practical way. Now, because we all know we have many different applications on every one of our computers, one of the purpose of the application layer is to regulate the communications between these applications and manage when they request services and resources. So while it might seem easy to lump all applications together when talking about this layer, the only applications that this layer is actually going to manage are those that have a communications component. So, Solitaire would not qualify for this, right? But Internet Explorer, which has all of those browsing and protocols, FTP, DNS, etc., is going to deal with this. So this layer is also responsible for network access, a certain level of error recovery, and it's also capable of some data flow measures. There's a lot of redundancy here. As this is the seventh and the final layer, this is where the information or process either starts or finishes. So an application is going to create what it needs to be sent here and then unwrap the data once it's sent from one computer to the next. So to finish off our analogy of the bus, this is sort of like the bus station. Here's where all the people wait in line to get tickets to use the bus. They're going to dictate, the bus station is going to dictate who has access to the resources being these buses, and it's going to receive all the incoming drop-offs and process them, as well as control the flow of people in and out of the station, and it's going to notify people if there are problems on the highways and so on. Just as users are typically mostly going to interact with the application layer, the bus riders are really only going to interact at the bus station layer, right? They're not going to be interacting with mechanics of building the bus or maintaining the bus or dispatching individuals or any of that stuff. In most cases, they're not even going to be interacting with the individual driving the bus. So this is really where users are going to be doing most of their interacting. Now, after going through each of these layers, we can now begin to have an understanding on how they're grouped together. For instance, layers 5, 6, and 7 are what we call application support block. When we look at each of these layers individually, we can very easily see that the functions of each play a very specific role in the application management, support, and keeping them consistent. The remaining 4 layers, from the transport layer down to the physical layer, are what we call the network support block. These layers and the protocols and devices that operate on them are all network related, whether it's for routing or switching on the network or ensuring data delivery on the network and so on. Perhaps even making sure that the actual bits, all the way down to those bits of data being communicated. Now, as technicians, and specifically for the exam, you really want to know which layer relates to which support blocks. And also, this is going to help a great deal when we discuss the next networking model, which is the TCP/IP layer model. So, just to sort of go through this again, we start here at the application layer, and we work our way down until we get down to the physical layer, which is where the data can actually be transmitted over the network, and then it builds its way back up until we get to the last application. So if I'm browsing, let's say this is me, right, and this is a web sort of server, I send a request. The request goes down all the way, goes over the network. It might even hit a couple routers along the way, or switches rather. So we're hitting some switches, and then we hit some routers, and then we hit some switches, and then it's going to go all the way up again to the web server, and then the web server is going to send that data back, etc. And so we go, this really follows on each end how data is being sent and received. So before we wrap this up, there's a couple ways to remember these, and I'd really highly recommend committing this OSI model to memory. There's 2 ways we do this. One is called the top-down approach. This starts with layer 7 and ends with layer 1. Now, the reason you want to just remember whichever mnemonic device I'm about to tell you, just remember which one you're remembering so that way you know how to write it. A great way to remember this one is all people seem to need delicious pizza. Now, again, all as application starts at 7, so we're starting with the user, and we're going down to physical, to the hardware. Now, the other way I like to remember this is, please do not throw sausage pizza away. That's my particular favorite. Now, here we're taking a bottom up approach because we're going from the bottom up. So realize that this, you're starting with the physical layer and going up to the application layer. So however, whichever one of these you memorize, you use to memorize this, just remember to commit it to memory, and when you get to your exam, write it down immediately so you can just look at it. And remember, this is 7, 6, 5, 4, 3, 2, 1. This is where hubs would function. Again, they're just forwarding the same information, just like this is where a cable would function. Data link is where most switches are going to function. And on the network layer, that's where we're going to see routers function. This is the most information that I see on the exam, and so if you commit this to memory, I think you'll be set. Okay, so just to recap one last time and review everything we've discussed. First, we explained the history and the purpose of the OSI model. Remember, the important thing to realize here is that it's a layered model. And the reason it's layered is to make it easier not only to develop things for each layer. Instead of having to develop something for the entire system, I can just develop one little device, such as a router or a switch. And also, it's going to be easier to troubleshoot and fix anything that goes wrong. We then talked about layer 1, the physical layer, right? And this is where cords, for instance, the media exists, and where all the bits are going to go from one place to the other. We're really here dealing with the ones and zeros, the electrical bits. Also, remember, hubs exist here as well. We then talked about the data link layer. This also had two sublayers, MAC and LLC. And this is where we see MAC addressing, or physical addresses, start to occur. And that means that here is where we're really going to deal with switches. The data here, by the way, is put into what we call frames instead of just dealing with bits. Now, the next layer is the network layer, and this is where we start to see routing. And this is thanks to a new addressing system. Specifically, the one we're going to see the most is IP addressing. This means here is where we're going to start seeing routers. And don't forget, here we start seeing terminology for packets. And the one we mentioned too was datagrams. We also mentioned that this is where we see connectionless, or connections that don't sort of have a definite got sent or delivery receipt. We then looked at layer 4, which is where we see TCP from the IP suite, right? And this is the one that's going to start looking at guaranteeing our delivery. Layer 4 is also where we ensure reliability and flow control. Here, information is called segments. When we get to layer 5, or the session layer, we see that we're really establishing and maintaining a session. This is where we're going to start and gracefully end our communications, such as SSL communications. When we get to layer 6, this is where encryption and compression occur. This is also where we start seeing the term data. Finally, we talked about the application layer, or layer 7. This is the layer that's closest to the user. And this is where you're really going to see the interaction. This is where we saw a lot of the stuff such as SMTP, FTP, HTTP, and so on. This really governs everything. So if we go back through this with our metaphor, remember the physical layer are the highways. The data link layer are how we're going to share the roads. Remember we thought about a stoplight. The network layer is where we start determining the best route to get from one place to the other. The transport layer tells us, for instance, the rules of the road. The session layer is what type of highway we might need to take. For instance, I might need to take a special private highway if I have important documents. The presentation layer is like the bus driver, who is going to pack up our bags for us and also communicate and make sure that we know where we're going. And the application layer is going to be like the bus stop. Now, the OSI model is, in actuality, pretty obsolete, but we need to understand the theory behind it before we can get into something that's a little more necessary. For instance, the TCP/IP layer model. Network infrastructure and design, network models, the TCP/IP model. Whereas in the previous module, we talked about the OSI model, a mostly theoretical model that's in use in computer networks. In this module, we're going to talk about perhaps what is considered to be one of the most common, or at least the most widely used model, the TCP/IP model. Now, while it's important that we memorize and familiarize ourselves with the OSI model, it's also really important that we understand this TCP/IP model and the differences between it and the OSI model. As technicians and administrators, it's really important that we're familiar with each layer, as well as how data transfers between all of these layers, and how all the protocols that are used in TCP/IP relate to one another and in the layers. So, the objectives of this module are first to explain the purpose and depth of the TCP/IP model and to compare it in some ways with the OSI model. We're also going to talk about what data encapsulation and fragmentation are. These are really key to how large amounts of data are able to be transmitted and transferred over the internet, the largest network in the world. And then we're going to talk about the 4 layers of the TCP/IP model, beginning with the 4th one, and then the 3rd, the 2nd, and the 1st. Finally, we're going to talk about protocol binding and something called an MTU black hole that doesn't really occur much anymore, but that Network Plus wants you to be familiar with. So, as mentioned before, the TCP/IP model is perhaps the most widely known or used networking model. It's another networking model that's most commonly defined using abstract layers, just like we had with the OSI model. Now, the entire purpose of this model is to allow for conceptualization of how a computer network functions in maintaining hardware and protocol interoperability. Also, it's commonly called the DoD model for the Department of Defense, which funded much of the research that went into it. TCP/IP was permanently activated in 1983, and it's been in use just about ever since. Now, it wasn't until 1985 that this model was actually commercially marketed, but it is now the preferred network standard for protocols and so on. Now, this means that using these 4 layers on this model, the bottom being the network interface layer, the internet layer, the transport layer, and then finally the application layer. And if you know or remember the OSI model, you'll see that there is some resemblance. Understanding this model and understanding how data flows is actually how the entire world is allowed to communicate and connect to the network. So this is necessary for every computer in the world that is currently using the internet, and for the most part that's on any network. We might find other smaller, lesser known protocols that do operate outside of this, but I think you would be hard-pressed in today's day and age to see that. So technicians and engineers will probably sit and talk about technologies implementation of these 2 models for hours on end. And the reason is because there's quite a bit of history and brilliant thinking that went into the creation of both of them. The TCP/IP model was, in fact, created before the OSI model, and it still makes it easier to represent how communication and network-related protocols are defined and relate to one another. However, it's still more common to hear technicians and administrators use the OSI model when they're troubleshooting or referencing networking devices, and there are many similarities between the 2 models. The first similarity is the obvious use of the layers to describe the functions of these communication systems. Although in TCP/IP we have 4, whereas in OSI, as you recall, we have 7. Some of them even have similar names, as you can see from application and transport, and then we see network or internet and network interface, which is very much like physical. In some ways, some people consider the TCP/IP model to be a smaller version of the OSI model. However, this leads to some misconceptions about the position of relationships of certain protocols within the OSI model. Because these are 2 very different designs and they have different purposes, there are some recognizable similarities, but they're still, at their core, different. So the purpose of this OSI model was an attempt to simplify and standardize networking. TCP/IP's original purpose, as opposed to the OSI, is more attempting to sort out the internet protocols into comprehensive groups according to their functions of the scope and the sort of network that's involved. Now, one of the similarities between the two models is they both have interchangeable network and transport layers. Also, each layer of the OSI model directly correlates with the TCP/IP model. Now here you can see the application layer, the presentation layer, and the session layer of the OSI model correspond to what we know as the application layer of the TCP/IP stack. This means that everything in the OSI model that fell into application, presentation, and session are actually done in the application support block. Next, the transport layer of the OSI model corresponds directly to the transport layer of the TCP/IP model, the network layer of OSI with the internet layer of TCP/IP, and that is easy to remember since internet is really short for like internetworking. And the data link and physical layers of the OSI model correspond directly to the network interface layer of the TCP/IP. Now, some of these correlations, it should be mentioned, aren't precise and exact. They're sort of approximations, and that's because they are two very different models, and therefore they were created differently and weren't necessarily created with the one or the other in mind. That being said, TCP/IP and OSI were built with knowledge of one another, and so we do see this overlap. Now, the TCP/IP model outlines and defines the methods data is going to flow in a communication system. It does this by assigning each layer in the stack specific functions to perform on the data. And ultimately, each layer is completely independent of all the other layers and more or less is unaware of the other layers. For instance, the topmost layer, the application layer, is going to perform its operations if the processes on the communicating systems are directly connected to each other by some sort of information pipe. The operations that allow for the next layer, the transport layer, to transmit data between the host computers is actually found in the protocols of lower layers. And from there on, each data layer will complete its specified actions to the data and then encapsulate the data, where it's then passed down the stack. In the opposite direction, when data is traveling back up the stack, and we saw the same thing with OSI model, the data is then de-encapsulated. So when it's going down, we call that being encapsulated. And when it's going back up, we call it de-encapsulated. So we really need to understand how all of this works together in order to get a really strong picture of TCP/IP and be able to speak about the layers in general. So let's talk about encapsulation. Each layer is responsible for only the specific data defined at that layer, as we've said. Now, these layers are going to receive the data package from the layer above it when sending, and the layer below it when receiving. This makes sense. If I'm receiving data, it's going up, so the data is coming from below, and if I'm sending, it's going down, from the application down to the networking interface. Now, when it receives this package, each layer is going to add its own packaging, which is called a header. This header is used by the corresponding layer at the receiving side for specific purposes. The exact purpose is really going to depend on the layer in question. But this header is going to be added to the beginning of the data so that it is the first thing received by the receiving layer. That way, each layer on the receiving end can then remove that header, perform its operations, and then pass the remaining data up the stack, up the TCP/IP model. On the lowest layer, a footer is also going to be added. And this is going to add to the frame by adding more supplemental information. This extra data at the end of the data package is going to assist the receiving end on ensuring that the data was received completely and undamaged. This footer is also what's called an FCS, or a frame check sequence. And as the name implies, it is going to check to make sure the data was received correctly. Now, on the receiving end, this process is reversed by what's called de-encapsulation. In other words, the data is received at each layer and the headers are removed to allow the data to perform the related tasks, where finally the data is received by the application layer, and then the resulting data is delivered to whatever the requested application was. Now, just like with the OSI model, and we'll talk about later, this application layer doesn't mean the actual application itself. It's simply the layer that provides access to the information from an application. Now, just like the OSI model, there are a few mnemonic devices that can be used to help in remembering these layers in order. And the one that I use the most, going from the top down, is called All Things in Networking. Again, that's application, all, transport, things, internet, in, network interface, networking. So now we have a better understanding of how the data is going to proceed from layer to layer through encapsulation, going down from application to transport to internet to network interface, right? And then through de-encapsulation, which goes the opposite way. Let's take a closer look at these layers, starting with the topmost layer, the application layer. So here on the application layer, much like the application layer of the OSI model, we find what's considered the highest level protocols. Higher level meaning these protocols such as SMTP, FTP, and so on. These protocols are not necessarily concerned with the method by which the data arrives at its destination, but simply that it just arrives, period. Here in the application layer, we also provide the functions that relate to the presentation and the session layers of the OSI model, as we've already pointed out. It does this typically through the use of what are called libraries, which are collections of behavioral implementations that can be utilized and called upon by services that are unrelated. So this means that the application layer of the TCP/IP model encodes the data and performs any encryption and compression that's necessary, as well as initiating and maintaining the connection or the session. As we can see here, these are just some of the protocols that we find at the application layer. We can also further group some of these applications based on the specific type of function that they provide. For instance, if we're looking at protocols that are dedicated to transferring files such as FTP or TFTP, which if you recall is the trivial FTP. Then there are also protocols that can be categorized by supporting services. So some of those are going to be, for instance, DNS, the domain name service, and SNMP, which is for management purposes, or even BootP, or the bootstrap protocol. Now, just like the OSI model's application layer, this TCP/IP application layer is responsible for process-to-process level data communication. This means that the application itself doesn't necessarily reside on this layer. What it more means is that it defines what the application or what type of application can be utilized depending on the protocol. So for example, SMTP specifies that outgoing mail communication with the mail or exchange server, and IMAP specifies the incoming mail communication with the mail server. Also, remember that only those applications that are network relatable are going to be managed at this layer, not necessarily all application. So this layer's role is more towards software applications and protocols and their interaction with the user. And it's not as concerned with the formatting or transmitting the data across the media. For that, we have to move lower down into the model and get to the transport layer. Now on the transport layer of the TCP/IP model, we have two main protocols that we need to be familiar with. First, we have the Transmission Control Protocol, or TCP, and the second is the User Datagram Protocol, or UDP. Let me just write those out here so that you can see what these stand for. Again, now on this layer, three things are going on. Data verification, error checking, and flow control. Now, our two heavy-hitting protocols are done in very different ways. So TCP/IP, as we've talked about in the past, is what we call connection-oriented, which means there's a guaranteed delivery, whereas UDP is connectionless, which means it's just a best effort delivery. UDP doesn't have any means of error checking. That's one of TCP's areas of expertise. So to put TCP and UDP in perspective, I've always thought about it as if, say, a grade school teacher needs to send a note to a student's parent because the student hadn't turned in their homework for more than a week. Now, the teacher can send the note one of two ways. The first is through UDP, or the uninterested, doubtful preteen. Now, this UDP is certainly going to make it home as quickly as possible, but whether the message gets sent to the parent or not really isn't UDP's biggest concern. Getting there quickly is. So UDP is going to have you that quick, but not necessarily guaranteed. Now, meanwhile, the other method, TCP, or teacher calls parent, this is the way the teacher has a guaranteed delivery of the message. But if parents aren't home, the message cannot be delivered, or something happens during the communication process, TCP will wait and attempt to send the message again. So, whereas UDP is quick, TCP is guaranteed. And so that's sort of the give and take there. Now, while our story is a generalization, it really touches on the two most important characteristics of these protocols. Now, there are a few other specifics about TCP that are really worth mentioning. Firstly, and most importantly, we have reliability, like we just mentioned. How it accomplishes this is TCP assigns sequence numbers to each segment of data, and the receiving end looks for these sequence numbers and sends what's called an ACK, or acknowledgement message, which is something important that you do want to be familiar with, and you might also see that as a SYN-ACK, which is the synchronization, and that ACK message is sent when the data is successfully received. Now, if the sending transport layer doesn't receive the ACK or acknowledgement message, then it's going to retransmit the lost segment. Secondly, we have data flow control, which is we've already mentioned. This is important as networking devices are not always going to operate at the same speeds, and without flow control, slower devices might be overrun with data, causing network downtime. Thirdly, we have something called segmentation, and segmentation occurs at this layer, taking the tedious task away from the application layer of sectioning the data into pieces, or segments. These segments can then get sent to the next layer below to be prepared for transmittal across the media. So the final consideration for TCP is, in order for an application to be able to utilize this protocol, a connection between port numbers has to be established. The devices try to create this session using a combination of an IP address and a port number. Now, this combination is called a socket. In the future modules, we're going to look at referencing TCP and UDP, as well as going a bit more further into explaining how they function and interact with different protocols. But what you see here is the IP address on a specific port number. So we know, based on this port number, what the connection is trying to attempt. And whether or not it's TCP or UDP, we know whether it's connection-oriented or connection-less. The internet layer of the TCP/IP model corresponds directly to the network layer of the OSI model. Now, the data terminology on this layer, as I think we discussed when we talked about the OSI model, is a datagram. Now, as the internet layer relates directly to the network layer, which, if you recall, was layer 3, we can a little more easily understand a few things that happen on this layer. First, it tells us that this layer is responsible for routing. If you recall, layer 3 devices for OSI are routers. This means that it ensures the typically fastest and best path from the source to the destination. This layer is also responsible for data addressing. And if you recall, with data addressing, we're dealing with the second part of TCP/IP, which is the Internet Protocol, aptly named since it is on the Internet layer. Now, the Internet Protocol is responsible for a couple main functions. The first of those functions is what we call fragmentation. It's important for us to understand something called MTUs, which are maximum transmission units. so that we know why fragmentation has to occur. Now, the MTU is the term, as the name implies, that's used to define the largest size of increment of data in bytes that can pass through the given network device, such as a router. Now, often data is going to need to pass through networks with MTUs that are less than the MTU listed on that device. Generally, even not just match to, but the lower it is, the more it's preferred, because then we can make sure that it's not going to have a problem. So network devices are going to send and receive messages or responses to datagrams that are larger than the device's MTU. In these instances, when there is a datagram that's larger than the MTU of a device, the transmitting internet layer fragments the data, or the datagram, and then tries to resend it in smaller and more easily manageable blocks. So once the data is fragmented enough to pass through the remaining devices, the receiving end's internet layer then pieces together those fragments during the reassembly process. Now, in the header of those fragmented datagrams, if we go back just a bit, you'll see right here, the header, there's a specific field that's set aside for what we call 3 flag bits. The first flag bit is reserved and should always be 0. The second is the don't fragment, or the DF bit. Now, either this bit is off, or 0, which means fragment this datagram, or on, meaning don't fragment this datagram. The third flag bit is the more fragments bit, MF. And when this is on, it means that there are more fragments on the way. And finally, when the MF flag is off, it means there are no more fragments to be sent, as you can see right here. And that there were never any fragments to send. So as we see here, our initial datagram that we wanted to transmit had an MTU that was too large to send. It was 2500. And it was too large, therefore, to go through router B. And so then we fragmented this datagram and added those bits to the headers of the fragments. So that's how this all works, and that's why fragmenting is so important. Now let's take a look at a networking problem that used to plague network engineers and technicians that has to do with MTUs for some time. And this is also something that's specifically called for on the Network Plus exam. Now, a black hole router is the name given to a situation where a datagram is sent with an MTU that's greater than the MTU of the receiving device, as we can see here. Now, when the destination device is unable to receive the IP datagram, it's supposed to send a specific ICMP response that notifies the transmitting station that there's an MTU mismatch. This can be due to a variety of reasons, one of which could be as simple as a firewall that's blocking the ICMP response. And by the way, when we talk about ICMP, we're really talking about the ping utility as well. Now, in these cases, this is called a black hole because of the disappearance of datagrams. Basically, as you can see, I'm sending the data gets here. The device, the router here, says, wait a minute, I can't fit that 2500 MTU through my 1500, sends a response, but for some reason the response hits this firewall and doesn't make it back to the router, and so the data is lost into this black hole. Now, this is called a black hole because this datagram disappears as if it were sucked into a black hole. Now, there are some ways to detect or find this MTU black hole, and one of the best ways is to use the ping utility and specify a syntax that sets the MTU of the ICMP echo request, meaning you tell it, I want to ping with this much of an MTU, and so then we can see if the ping's not coming back. If it's coming back at one MTU and not another, then we know, oh, this is what's happening right here, and we can determine where the black hole is specifically occurring. Now, on the bottom of the TCP/IP stack is the network interface layer. Now, this layer is completely dedicated to the actual transfer of bits across the network medium. The network interface layer of the TCP/IP model directly correlates to the physical and the data link layer of the OSI model. Now, the data type we're going to be talking about on this layer are what we call frames, as opposed to datagrams. Now, the major functions that are performed on this layer, on the data link of the OSI model, are also occurring at this layer. So we're really talking about switching operations that occur on layer 2, which again is that data link layer. And so this is where we see switches operating. Which means that we're really dealing with MAC addresses. Okay? Now, a MAC address, again, is a 48-bit hexadecimal, universally unique identifier that's broken up into several parts. The first part of it is what we call the OUI, or the Organizational Unique Identifier. This basically says what company is sending out this device. And then we have the second part, which is the NIC specific. And then we have the second part, which is specific to that device itself. So this is the manufacturer, and this is for the device. You can literally go online, search for this part of the MAC address, and it'll tell you what company is creating this device. Now, the easiest way to find the MAC address in a Windows PC is by opening up the command prompt and using ipconfig all, which we've talked about in A+. This brings up the internet protocol information, the IP address, and it also brings up the MAC address or the physical address that's assigned to your NIC. So now that we've covered the MAC address it's really important to understand the parts of an Ethernet frame. And remember, we're talking about frames at this juncture. So the preamble of an Ethernet frame is made up of 7 bytes or 56 bits, and this serves as synchronization and gives the receiving station a heads up to stand by and look out for a signal that's coming. The next part is what we call the start of frame delimiter. The only purpose of this is to indicate the start of data. The next two parts are the source and destination MAC addresses. So the Ethernet frame, again, this is everything that's going over this Ethernet, over the network. We have the preamble. It says, hey, pay attention now. This that says, now I'm giving you some data. And then we have the destination and the source MAC addresses, so that way we know where it's coming from, who it's going to. And this takes up 96 bits or 12 bytes. Because remember, this is 48 bits right here. So if we double that, that's going to be 96. And then the next type is what's called the frame type. This is 2 bytes that contain either the client protocol information or the number of bytes that are found in the data field, which happen to be the next part of the frame, which is the data. This field is going to be a certain number of bytes, and the amount of data is going to change with any given transmission. The maximum amount of data allowed in this field is 1500 bytes. We can't have more than that. Now, if this field is any less than 46 bytes, then we have to actually have something called a pad, which is actually just going to be used to fill in the rest of the data. And the final part of this Ethernet frame is called the FCS, or the frame check sequence. And this is used for cyclic redundancy check, which is also called CRC. This basically allows us to make sure that there are no errors in the data. Now, similar to the way that an algorithm is going to be used to ensure integrity of data, the CRC uses a mathematical algorithm, which sometimes we're going to refer to as hashing, which we'll talk a lot more about when we get to Security Plus. That's made before the data is sent, and then it is checked when it gets there. That way we can compare the two results bit for bit, and if the two numbers don't match, then we know the frame needs to be discarded. We assume there's been a transmission error, or that there was a data collision of some sort, and then we ask the data to be resent. Now, this layer, by the way, this network interface layer, is also responsible for the network access control, and some of the protocols that operate on this are what are called point-to-point protocols, ISDN, which is which we've talked about, also a type of network, and also DSL. So these are some of the things that exist at this, and this makes sense because, again, we're dealing with the physical bits, bytes of data. So now that we've taken a look at each of the layers in the TCP/IP model, there's still a couple things that we still need to define. Now, we've discussed how some of the protocols that we've seen relate to the OSI model as well as the TCP/IP model. And we found that some of the protocols function much more smoothly when they're put into the context of an outline of one of these models. So the next definition I want to make sure to cover is something called protocol binding. This is when a network interface card receives an assigned protocol. It's considered binding that protocol to that NIC. So just as we learned how the data is going to be passed down from one layer to the next, it's very important that we have these protocols bound to the NIC. We can have multiple protocols actually bound to one network interface card. Now, of course, the most easily recognized, we can most easily recognize these when we're looking at the IPv4 and IPv6 configurations in our network connection properties or adapter settings in Windows. For instance, you use a specific protocol more than others, and you're confident in the stability of the connection, you can change the order of binding to potentially speed up your network, since what it basically does is it's going to give a list of each protocol that exists, and it's going to hit each protocol one after the other. So if there's one that you use more, you can set that at the top so it doesn't have as far to go. So as we can see here, we have several default protocols, and they're going to be tested in order for that available connection. And the first protocol that's found to have a matching active protocol on the receiving end is going to be the one we use. Now, while this might sound like a pretty decent method of doing things, it also opens your computer up to utilizing a lesser protocol, which is potentially going to give you a slower speed. So the graphical interface or properties menu for your network interface card is where you're going to be able to configure all of this stuff such as TCP/IP, DNS server assignment, DHCP, and so on and so forth. So after all of this, it's really important to understand that all of this organizing, categorizing, defining of these protocols, the assigning of rules and roles, all of this, the internet didn't just happen overnight. It's not even necessarily the way we did it on purpose. These standards and these models are going to continue to expand and change, and eventually we might even have a brand new model that we're going to have to learn about. But in the meantime, these models are here to stay, and they're going to remain really important, and especially in the future, you have to understand the historical roots of the network so you can be able to define not only how to go forward in the future, but also how to prepare yourself for our Network Plus exam. So let's just go back over everything we've talked about one last time. We covered in a lot of stuff here, right? First, we explained the purpose of the TCP/IP model, and we compared the TCP/IP model with the OSI model. Remembering that the top three layers, if we look at this, if we do the 3, 2, 1, and then we look at 7, 6, 5, 4, right? 2 and 1, physical and data link, are going to go straight over here to that physical layer 1 of the TCP/IP model. Then the network layer is going to correspond directly to the internet layer. The transport layers are going to be the same. And session, presentation, and application all go over to the presentation layer in TCP/IP. We also talked about defining data encapsulation, and we walked through how fragmentation works on the internet layer. And the reason we need to do that is because of the maximum transmission unit. Finally, we talked about the fourth, third, second, and first layers of the TCP/IP model. And on each model, we outlined some of the important aspects of each layer, such as the application layer, which again is the way that the application is going to process all of this information. The transport layer, which is in charge of reliability, and it is where TCP, which is connection oriented, or UDP, which is connection less, live. And this is also going to deal with flow control and also segmentation. We looked at layer 2 as well, which is the internet layer, and the fragmentation that happens there. And network 1, the network interface layer, which is equivalent to all that physical stuff that we've talked about. We also looked at how the terminology changes. Remember, on layer 4, we're talking about data. On layer 3, we're dealing with segments. On layer 2, we're dealing with datagrams, also called packets. And we broke down then on layer 1 frames and an Ethernet frame and all the information that goes into that. Finally, we defined what an MTU black hole was, and we finished off everything by talking about protocol binding, which is binding certain protocols to specific NICs and in a delineated order. Network infrastructure and design, Ethernet, and implementing a wireless network. So, in the previous modules, we were introduced to many networking standards, models, and technologies. Now, this module is going into Ethernet a little bit further, and specifically the implementation of a wireless network. So, the module objectives are first to outline the different types of Ethernet networks that exist. And then we're going to go into the explanation of WLAN, or wireless LAN architecture. Then we're going to define and describe the characteristics of an antenna and of different types of antennas, which is actually pretty important for the Network Plus exam, specifically wireless antenna performance factors. And then by the end of the module, we're going to have a complete understanding of the 802.11 standard and its associated modes. We're going to talk about the beacon frame, and we're also going to talk about what determines where you place your wireless access point, or your WAP. And we'll finish by talking about how to properly implement a wireless network. So an Ethernet network is perhaps one of the easiest networks to plan and implement. Depending on the size of your network and the equipment being used, there are a bunch of different kinds of small Ethernet network implementations that you can use. Some of the typical equipment that you're going to find in an Ethernet network might be a hub, an Ethernet cable, which can either be what we call straight through or crossover. And we've looked at that a little bit more in depth previously. And a switch, and a router. So a network can also contain a combination of these or all of them. Generally, so much we're not going to see hubs a lot anymore, but they're still mentioned on the exam. So a very simple Ethernet network that involves a hub is called a hub network. Now, to create this network, all you need is 2 devices, a hub, and an Ethernet cable. This type of network is not capable of reaching the internet, and it's typically only going to be used for file sharing or printing. And you're not going to want to have a lot of devices either, because it's quickly going to become very slow due to the fact that hubs, as you remember, operate on layer 1 of the OSI model, and therefore broadcast every input data out to everything else. Now, the next type is also very easy to implement, and this is considered a crossover network, or a peer-to-peer network. And the reason is because there is no device sitting in the center. A crossover network only needs the 2 devices and the crossover cable to connect them. And the reason we must use a crossover cable is because we're switching, if you recall, the 1, 2, 3, 6 pins, we're switching these pins so that way on one side the data is sent, on the other side it's received. Of course, newer devices might not always need this crossover cable anymore because a lot of modern NICs have auto switching capabilities which will automatically determine and switch these pins for you. Now, another Ethernet network is one that uses a router to connect devices to the outside world or to the internet. And a switch can often be placed in between the router, which leads out to the WAN, and the internal network, or the LAN, in order to alleviate network congestion and to allow for more devices to be added. Now, just so we remember, a switch operates on layer 2, although there are switches that do routing, and those are called layer 3 switches. And then the router, as we just mentioned, operates on layer 3 of the OSI model. Now, another point about Ethernet networks that is important is that Ethernet uses destination and source access points to assist in keeping tabs on all the multiple channels that are used in network communications. These are called SAP, or service access points. And in the previous modules, we discussed how data flows through these layers in the network models. Well, here, these access points are used to map the network layer communication, or IP, through the physical layer, or layer 1. Now, the access points allow a single physical connection to be utilized for many logical connections for TCP/IP. This would be like a NIC. Because these access points are going to be on the local side only, they're selected by the server managing those services. Now, to keep with TCP/IP as an example, when a user is accessing a website, for example, a connection is made with the web server, and the computer downloads that website. Along with the website are references to parts of the page, such as files that are associated with the web page, sound, image, other things like JavaScript, and these files are stored on the web server. And when the user interacts with the website, the access point ensures that the computer can differentiate between the Ethernet frames for the images, and those for sound files, and those for other types. Okay, so in a lot of the previous lessons, we've been talking about the methods of connecting our devices, mostly through physical means. And we defined that many technologies are commonly used in both wired and wireless networks, otherwise known as bounded and unbounded networks. So here we're going to discuss specifically WLAN, or wireless local area networks, in greater detail, starting with the architecture. There are several components that we really need to define. The first component is what's called an STA, or the station. The wireless STA is any device that has a network adapter card, or a NIC, that conforms to the 802.11 standard. And you remember the specific standard for wireless is 802.11, as opposed to 802.3, which is Ethernet. Now, the next device is called an AP, or an access point. Look familiar? Now, this is very different from the service access point I just talked about, because an AP in this sense, it is a device or a software implementation that allows wireless devices to communicate with each other and to connect to a wired network. An access point, or AP, also sometimes called a wireless access point, offers wireless devices some higher levels of security as well, and can act as the bridging component between the STA and the backbone of the network for access. So the next component that we need to identify is the WDS, or the Wireless Distribution System. This device is the authority in terms of access control to resources and ensures that devices are mobile. This allows multiple access points to be interconnected wirelessly, which allows the APs to be connected and extend the wireless range of the network without having to connect the access points directly to the backbone. And again, the backbone would be the internet, or the rest of the network if we're talking about a LAN. Now, the system has three types of AP stations. We have something called a remote base station, which is the access point that connects directly to the wireless clients or devices. A relay base station just relays or repeats the information between other stations or devices and a main base station. Now, the last thing I want to talk about is the main base station, which is connected to the wired or Ethernet or backbone network. Using these components, there are a number of different ways we can actually configure a wireless LAN. The service set is what defines how your network is configured. Now, there are 3 standard ways that WLANs, or wireless LANs, can be configured. The first configuration is what's called a BSS, or a Basic Service Set. The BSS, in its simplest sense, is comprised of an AP, an access point, and an STA, a station. Although many stations with a single AP is also considered a BSS. So I only need one station, but I can have multiple. The trick here is that I have only one AP. Now, client nodes, like these, may not be necessarily explicitly aware of each other. Using a BSS, we are easily able to extend our network coverage area and the distance between our wireless devices by forwarding packets through a wireless access point so that we can gain access to the wired network. Now, WLANs can also be configured in what's called an ESS, or an extended service set. An ESS is comprised of 2 or more BSSs, basic service sets, and the purpose of an ESS is to allow mobile devices to maintain a constant connection to the network while you're roaming. So each BSS in an ESS, or an extended service set, is going to have the same service set identifier, otherwise known as an SSID. This makes multiple BSSs appear as if they're only one. So as an example, if you think about when you walk through an airport, pretty much wherever you sit, we have a decently strong wireless signal. Theoretically, of course. So thinking about what's that signal, it wouldn't be easy for a single access point to provide you a signal that's that strong for that much space. In fact, it's pretty much impossible. So instead, there are many access points, APs, arranged strategically to allow full coverage throughout the airport, and combined, they make up this ESS, or extended service set. That's why we see the same network name no matter where you are within that network range. Now, the BSSs can either operate on the same channel or on separate channels, which effectively increases the throughput by having separate channels that they're not going to overlap on. Finally, we have what's called the IBSS. This is an independent basic service set. An IBSS is created when there isn't a controlling access point, but instead there's what we call an ad hoc network. And as the name implies, this means that this is a makeshift, or an improvised, in technical terms, wireless network that combines network elements to make a network with minimal planning, where all the devices on the network are essentially equal in status and are free to talk with any other ad hoc devices that are in range. This ad hoc configuration, which is also called, by the way, a peer-to-peer configuration, is where STAs are performing their own AP functions, as well as their own client operations, independent of any sort of central device. So if you've ever connected 2 computers directly together in order to, say, transfer files, or perhaps you've connected your smartphone directly to your computer in order to transfer files without the use of an access point, you're using what's called an IBSS, or an ad hoc wireless network. Many aspects of antennas and their characteristics that are a little outside of the scope of the Network Plus exam, but there are still a few basics that are important. The first of which is to define what an antenna actually is and how it functions on a fundamental level. So an antenna is a physical device that either transmits or receives electromagnetic waves and then converts those waves to and from a high-frequency signal. Now, the antenna's physical characteristics and dimensions are going to dictate these frequencies that it can transmit or receive. And depending on the purpose of the antenna, there are different types that can be used. For instance, the radiation pattern is different on some antennas versus others. Now, another term we really need to understand is the term gain, which describes the intensity of an antenna in a specific direction related to the hypothetical intensity of a given standard, which is the ideal. In other words, we always have a hypothetical versus the reality. Now, this is achieved by focusing on what's called the RF, or the radio frequency, in a more manageable or concentrated plane. This is what we see as strength on your computer, right? If you've seen this thing and you have different number of bars, that's what we're really talking about here, is the gain. In most cases, we want more gain, which is better, but there are certain legal limits, and adding power can potentially have some negative ramifications. So gain can also come from an external source like an amplifier, which means that it amplifies the signal, making it stronger, and it's measured in decibels. Now, while this explanation is very simplified, the antenna gain is how it's affected by things such as the size and shape of the antenna and the amount of electrical power that's applied to the signal, and it's all kind of complicated, which is why there are people who specifically are RF or radio frequency engineers. So what you really need to remember about all this is, first, the physical characteristics of an antenna affect its gain. Second, a higher gain is usually good but potentially dangerous. Third, more gain can be achieved by using an amplifier. And fourth, we're going to measure it in decibels. So now that we've defined some of this terminology when it comes to antennas, let's take a look at some of the wireless antenna types. Now, wireless antennas can be fairly organized into two general broad categories. The first category is directional. Directional antennas attempt to focus the radio waves into a narrow beam going in one specific direction. Because the signal is being focused, it typically means that these antennas are going to have a higher gain, and for the same reason, a relatively narrower transmission beam versus other types, as you can see. These characteristics allow for a couple of benefits, such as a focused beam, which ensures a better signal quality, and a smaller transmission beam, which means that there's less area of interference. Now, directional antennas are really commonplace in implementations of point-to-point networks, which makes sense because I have this limited sort of area in which the waves are going to be traveling. And perhaps most commonly, you've seen them in dish networks for satellite TV and the internet. Now, the next category of antenna are called omnidirectional antennas. This type of antenna emits the radio waves in all directions on the same plane equally. In some ways, these are called donuts because the wave comes out in a donut-looking shape. Now, because the signal is being transmitted in any direction, such as on a wireless router, these antennas have a relatively low gain when compared with a directional antenna. Now, where these antennas lack in gain, they make up for it because obviously they have a greater coverage area. As the donut wave implies. The good part about this greater coverage area is that transmitting and receiving stations don't have to have a specific alignment with one another. They can be in any direction from the antenna. These antennas are really going to be used in distributed networks and multi-point networks as well. So omnidirectional antennas are implemented everywhere, from cell phones to radio broadcasting antennas to walkie-talkies to GPS to mostly our wireless networks at home and in a lot of offices, etc. So now that we've talked about a lot of the different types of antennas and their characteristics, the last thing I'd like to mention about gain is the more gain the antenna has, the smaller the effective angle of use needs to be. So the next thing we need to do is outline what's going to affect the performance of these antennas. So the physical layer of the network, the transmission of bits from one point to the other, there are a lot of things that can hinder the data while it's in transit. These things that are going to impede our signal are going to depend on the type of data in transmission. So for infrared data transmissions, the antennas need a line of sight or LOS, just like your remote control. Almost anything that obstructs this LOS is going to affect the signal. This could include stuff like smoke, smog, fog, dust, even pulses of light and bright sunlight can very easily change the maximum transmitting distance. And obviously, if anything is standing in the way, we're going to be in big trouble. Now, for microwave transmissions, the signal is also considered LOS, or line of sight. This typically doesn't mean that we need to be able to see the receiving station with our naked eye. It just means that the signal has to have an unimpeded path from the source to the destination. Most commonly, satellite, the ground station has to be within the footprint of the orbiting satellite. Generally speaking, distance is the performance factor that's going to affect these microwave transmissions the most. Now, the factors that are going to affect radio transmissions, which are the ones we use in Wi-Fi settings, mostly start with the antenna itself. So the signal characteristics of an antenna can affect the maximum transmitting distance. Also, performance can be limited if there are any objects that are very electrical or give off a lot of magnetic fields near or around the transmitting or receiving stations, and this is going to cause problems to arise. We can also have normal ambient noise or environmental conditions which can affect the distance these signals can travel. Finally, the greatest factor that's going to affect Bluetooth transmissions is the distance between the devices, just because of the technology we're using. As most Bluetooth devices are what we call Class 2 devices, this means that we have about a 10 meter, which is equivalent to around, although a little more than 30 feet, and this is due to power limitations. Now, depending on the type of Bluetooth device, it may operate on the 2.4 gigahertz frequency, which, by the way, is the same as Wi-Fi, and so that's why we're going to have a problem. And sometimes we're also going to see it on the 4.6 gigahertz frequency. And for those that operate at 2.4, obviously, not only does radio operate at those or Wi-Fi connections, but also phones and so on. So there's a lot of potential for having devices on the same frequency that are going to impede its communication. Now, one other term I want to talk about is a term called latency. This is, we've mentioned it a couple times in previous modules, but I haven't really defined it. Latency is basically the time delay in a given system. Depending on what system you're measuring, it might mean slightly different things. So the system we're most concerned with is the network latency, which can be measured in either one-way or round-trip latency, and I'm sure that you can understand the difference there. The latency is the amount of time it takes for data to go from a source to a destination, and we're just dealing with round-trip, it coming back as well. So the round-trip adds the two one-way totals and doesn't include the processing time of the packet. So only because it's sent and then takes a certain amount of time to come back doesn't mean that is all latency, because some of that is how much time the computer is spending processing that information. Obviously, we want lower latency, and to measure it, we can generally use the ping utility, which is going to tell us in milliseconds how long a packet took to go there and come back. Now let's look at some of the 802.11 standards and see which specifications have the least amount of latency. So these 802.11 standards cover the proper implementation, setup, and performance minimums and device specifications for wireless local area networks. And these all fall under the 802.11 specifications. They also specify the method for which those wireless networks, as carrier sense multiple access with collision avoidance, or CSMA-CA, which we've talked about, are going to operate. And it also designates the 2.4 gigahertz frequency as the band for the sped spectrum devices that are going to utilize for reliability. Now, over the years, there have been several standards in this family that have been ratified. The original was 802.11, just plain old. It was named for its release in 1997, so the 1997 is part of that. And it was specified to operate at the 2.4 gigahertz frequency band and was rated for data bits at about 2 megabits per second, which, as you imagine, would not be very useful for us now, and therefore it is very obsolete at this point. The 802.A standard, which was released 2 years later, was designed to operate at the 5 gigahertz band, and it had a 54 megabit data rate. Now, while it would seem that this standard would sort of lead the charge in wireless standards, at the same time that 802.A was released, there was also 802.B, which was released. And 802.B operates at the 2.4 gigahertz band, and essentially was a direct extension of the original 802.11 1997 standard. Now, even though the data rate was faster with 802.11a, there were some initial downsides to that standard that kept it from being the most popular. First, this higher frequency had a lesser range, and so you could travel less distance. Also, when 802.11b came out, it was a lot cheaper than 802.11a, and that made up quickly with consumers, and so it quickly became the de facto standard. Now, its popularity grew rapidly, and though it operated at 2.4 gigahertz and therefore was open to, was really susceptible to a lot of interference, it still was the one that almost everyone used, and so that's sort of where it went because range was such a big deal. The next standard, which was released in 2003, was the 802.11g standard, and this specification used the 2.4 gigahertz frequency again, but the data rates took a major leap up to 54 megabits per second, just like 802.11a. Now, since it used the 2.4 band, it made it backwards compatible with 802.11b, so it was very easy to integrate, and it therefore became the preferred standard. Now, after 802.11g took over the market, it wasn't until 2009 that we finally got the 802.11n standard. And it was released with something called an MIMO, which was a type of antenna, or multiple input, multiple output. And it had multiple antennas, and that greatly improved the network performance. Also, this amendment was specified for both 2.4 gigahertz and 5 gigahertz bands. And so these improvements made the standard really popular, especially because it was backwards compatible, not only with G, but also with B and even A. And it was rated for a maximum of up to 150 megabits per second. Now, the range of these wireless standards is also specified. The original 802.11, 1997, and A have a range of about 20 meters. B and G have 100 meters, and N is approximately 70 meters. So we lost a little bit of distance because we added that 5 gigahertz band in. But for most people, this didn't really matter, since we could use, again, an extended service set and simply add several 802.11 devices. Now, while you might have heard of some newer standards available, and even some that are just coming around the corner, these four are the ones you really need to know for the exam, and so those are the ones I really want to concentrate on. So if we look at these in a little more organized manner, and we can recap the important parts. The 802.11 standard, 1997, worked on a 2.4 frequency, had a range of 20 meters, and had a 2 megabit per second data rate. 802.11a was at 5 gigahertz, 20 meters in range, 54 megabits. It's compatible with 802.11n. 802.11b operated at 2.4 gigahertz, had a 100 meter range, 11 megabits per second, and is compatible with G and N. 802.11g, also 2.4 gigahertz, 100 meters, and it was 54 megabits per second, so it's increasing the speed, and was compatible with the previous and the next one, which is 802.11n, which not only operates at 2.4 gigahertz, but also 5, has a slightly less range, but it does have a higher megabit per second data rate. Some would even claim that this goes up to 600, depending on your theoretical, and it's compatible with all of the previous versions. Now, there are two modes that are supported by the 802.11 standard. The first is what we call infrastructure mode. This is the mode that's configured to use wireless access points to connect workstations to a cable backbone. The network using the infrastructure mode is going to either use a basic service set or an extended service set. The other one we have, which we already mentioned, is called ad hoc mode. This is for those peer-to-peer configurations. And again, it's referred to as an independent basic service set or an IBSS. Now, the configuration of this mode is designed with each wireless workstation able to communicate directly with one another without having to go through a central device. Now, earlier in this module, we talked about the service sets of many kinds, and we talked about frames in previous modules. Now, keeping those in mind, it's important to understand how these devices, such as laptops and smartphones, know what wireless networks are available when we access them. Now, this comes by detecting and receiving what are called beacon frames. A beacon frame is a management frame that's 50 bytes long, and it contains information about the transmission process, such as the SSID, or the service set identifier, which is essentially the name of your network. The SSID is that text string that identifies the network. It's 32 bytes long. Might be, for instance, Bill's network or something like that. Now, the beacon frame is used to start and maintain the wireless communications session, and it's sent in regular intervals from the access point. And those intervals can be manually changed or set by an administrator, and we can even turn them off so that way, or hide them so that's not being broadcast. Now, when it comes to installing a proper wireless network implementation, we need to be familiar with the typical process and the steps to maintain the highest level of functionality. Now, much like a lot of different processes, the basic steps to take are pretty much the same. They begin with planning. So there are a few things that are helpful to collect before the planning process. We need to collect information about the floor plan of the building, where we want to install, and so we can design a topology and figure out where to put access points. We need to establish requirements for how many devices are going to connect, which 802.11 standard we're going to use, what type of security is going to be required, and so on. Now, all of these are crucial to proper planning. Without this information, it's just going to be easy to choose the wrong devices or the wrong technologies. Also, if the research isn't done beforehand, you're going to find yourself performing a lot of rework at the end. Now, once this information is designed and gathered, we can start to establish the type of access points and the number of APs needed. Knowing the number of users on the network is going to help us determine, for instance, how many access points. And we want to balance the number of users with the access points in order to make sure that we have a good load balance. The next step is to assess the building to see if anything around might cause interference. Specifically, it's important to install anything that's going to be on the 2.4 gigahertz band. Now remember, some of the things that can cause interference are Bluetooth devices, other wireless networks, heavy-duty machinery, and so on. We also need to determine the exact placement of the access points. Are they going to be placed in the ceiling or somewhere visible or somewhere like a secure room? And when we determine this, we need to make sure that we're looking for obstacles that are going to impede, like thick walls, doors, metal shelving, proximity to large electrical equipment. And if those obstacles can't be moved, we might want to choose a different location for our access point. So now that we've planned, the next part is the fun part, the actual installation. Here we need to configure the device to connect it to the network. And some of the standard things we're going to do are connect the router, change the administrator default settings that the device came with, and configure DHCP services and encryption levels, such as whether we're going to use WPA or WEP. And also, are we going to use one of the three channels? Are we going to have them auto check or what? Another thing we might want to do is create what's called an access control list, which means we can allow only specific computers to get access to our network via MAC addresses, which are, again, the physical addresses on a computer or on a network card. Next, we need to configure the client workstations, and we need to test for functionality. Now, it's important here because not all operating systems can use all the different standards. They might even require a software update of some sort. You might want to make sure to test the wireless device by walking around a building and make sure you can stay connected and that you can connect in the first place, anywhere you need to. And then you also need to take the device outside and make sure that no one can get in from the outside. So it's actually quite difficult to just start one of these from scratch. The last step in the process is to document every single step that was made, and it's always a good idea to baseline for future testing and implementations. Now, being able to successfully accomplish the two phases, the planning phase and the installation phase, needs to be a part of your skill set and needs to be something you understand for the Network Plus exam. So just to recap everything we've talked about, the first thing we did was we outlined the different types of Ethernet networks, whether that means it's a hub network, a router network, or a peer-to-peer network. We also explained WLAN architecture, looking at the difference between a basic service set, an extended service set, and an independent basic service set. We defined and described the characteristics of antennas, looking at gain and the types of impedances that could occur. Then we outlined the 802.11 standard, including A, B, G, and N, which are the different modes. We also talked about which frequencies these live on, whether 2.4 or 5, and how fast, or the megabits per second, that each one provides. You want to make sure to commit to memory that table that we displayed on an earlier frame. We also talked about defining beacon frames, which broadcast the SSID and tell computers how to connect to the wireless network. Finally, we outlined what factors are going to result in where you place your access point and how to properly implement a wireless network point from the planning and implementation stages.
Welcome to Module 5, Lesson 5, IEEE 802.11ac. Actually, we're going to look at a little bit more than that. The N standard, 802.11n, AC, channel bonding. Now, the 802.11, it's a specification for wireless LAN, WLAN communication. It uses MIMO, which we shorten from multiple input, multiple outputs. I'm sure you can see why. So in this technology, the transmitter and receiver use multiple antennas. I've put a little diagram on the bottom here from IEEE Media that will demonstrate. At the bottom, certainly you can see 3 channels in use simultaneously. Multiple channels on the top part of the fig, you can see. You can select from, but it's only using 1. So in this standard, the N standard, multiple antennas provide independent paths in space between the transmitter and the receiver to send or receive streams of information at the same time on the same band. What MIMO does is increase the number of data streams sent from an access point to a client, which you can see in the bottom part. In 802.11 MIMO, 4 spatial streams can be sent to a single client at a time. Again, if you want to read further, you can look up the specification. There's a few wireless speciality books if it's something you're interested in doing. It's certainly an interesting field. The 802.11ac is an enhancement of 11n. Obviously still wireless networking. It's designed for high throughput wireless LANs on the 5 GHz band. There's a few advantages to using that. It uses a multi-user form of MIMO. In MIMO, the access point sends multiple streams of data at the same time to different clients over the same frequency spectrum. In 802.11ac MU MIMO, 8 spatial streams can be divided among up to 4 clients. I think the MU is multiple user. Yeah, multi-user MIMO at the bottom, and you can see the stream can be broken up. You've got a few options. You can have a higher stream to one client and lower bandwidth stream to another client. Support streaming of HD videos, which is really handy, and to multiple clients because of low latency, high throughput, and reliability. It operates in the 5 GHz band. I already mentioned that. Theoretical data rate of 600. This has been improved on all the time, so maybe check up on the standard before exam day. You've got less interference than in the 2.4 GHz band, which is where you get the increased performance. More channels available for data transmission, greater number of non-overlapping channels than you do in 2.4 MHz. I think there's a couple of disadvantages as well, but I'm not sure I put them down here in the slide. So in the US, a 5 GHz band has 25 non-overlapping channels, whereas 2.4 GHz has only 3. Channel bandwidth are the following: 80, 160, 20. It's worth making a note of all of these in case it's asked in the exam, and 40. Obviously needs to comply with the standard. You can see this particular adapter's got it written on it. It's got AC standard written on it. To comply with the standard, it has to support the 20, 40, 80 MHz channel bandwidth in the 5 GHz band. The 160 MHz channel bandwidth is optional. 80 MHz channels are formed by combining the following: 2 adjacent non-overlapping 40 MHz. 160 MHz are combined to 80 MHz. I think you can see how this works. So here I've put a slide from Wi-Fi Jedi website. They've combined 2 channels here, 2 20 MHz channels, and made a 40 for channel bonding. So channel bonding was first introduced with 802.11n. In channel bonding, 2 or more channels adjacent to each other are combined to increase bandwidth, as you can see in the figure put there. Benefits: 802.11ac benefits because it supports the following channels: 20, 40, 80 MHz. Although 160 MHz channels are supported as an option, its availability depends on your geography, where you are. Wider channel bandwidth increases the data rates. So 11AC uses 8 spatial streams and 160 MHz bandwidth to achieve a maximum data rate of 6.933 gig. Data rates vary on the following for 11AC: your given bandwidth and the number of spatial streams used. Probably worth writing out this table here if you want the information, or you can do a screen capture. 802.11ac with 1 spatial stream and for a bandwidth of 20 MHz can achieve a data rate of 86.7 MHz, and so on and so forth for the others. Their data rate increases both vertically and horizontally. Alright, so we've covered NAC channel bonding. That's all for now. Thanks for listening. Welcome to Module 5, Lesson 6, Network Segmentation. Quite a bit to cover, and some of this is a little bit esoteric, to be honest, so it's conceptual. It can be a bit hard to get your head around in that sense. What is network segmentation? What is physical segmentation? Logical? The uses, why bother? And critical situations. So we're hitting a few of the syllabus topics here in the Network Plus syllabus. So in a sense, network segmentation concerns dividing a computer into network or subnetworks, not in the sense of subnetting in the context of IP addressing, but dividing our network down. So each portion of the network is called a network segment. It can be characterized by a physical boundary or logical. So physical, something you can see; logical, something that the network can see but you couldn't see physically. You would have to log in and check the configurations. So a physical or logical boundary separates various network segments from one another. Physical's a bit easier. The computer is divided into segments, for example with switches, routers. A group of physical access and assets is part of a specific network segment. So a bit harder to do with switches because you would normally need it to add configuration, because switches are designed to broadcast to other parts of the network if it doesn't know where that part of the network is or a particular device, whereas routers do the opposite. Computer network is logically virtually divided into network segments, so this is from the logical standpoint. So we can do it with virtual LANs or VLANs. Virtual segmentation is done on different connections of the same physical switch. So you could have 10 switch ports and the first 5 ports are in one logical part of the network, in one VLAN, VLAN 10 for example, and the other 5 in VLAN 20. And you could have multiple VLANs depending on your capabilities of whatever switch you're using. Through network segments are isolated, although secure communication can be established between them to share network resources. We cover network security elsewhere, but you can actually have internal and external network security. It isn't just, for example, VPNs connecting from remote offices. So why would you bother? In a sense, it enhances the security of the network. You can isolate critical parts of your infrastructure from unauthorized access. For example, if you've got a special service server, you can restrict access so that users don't access it and they don't have direct access, so they'll be in a different VLAN, for example, or just it wouldn't appear on the network. And you normally, or may well have, depending on the size of your network, a different team or department managing that part of the network. It can be used for reducing network congestion, so you're dedicating certain parts of bandwidth for certain segments of the network, and you can even have a high-speed department. For example, the company I used to work at, we had a design team who all used high-speed, high-resolution files and graphics, and they needed a fast connection, so they had their own logical segment. You can also limit traffic, as I said, faster connection for some, slower for others, and the available bandwidth is increased or reduced accordingly. Also useful for load balancing. You can distribute the traffic load based on for the network. Certain devices can be placed in certain segments. Network segmentation is also done for the PCI, the payment card industry. That's different from the PCI bus technology, which we discuss elsewhere. The PCI compliance standards were created by major card issuers, and you may come across it if you have to take online payments, depending on the processor you use. Even if you've got a small network for your business or shop, you may have to, or you will be affected by PCI compliance. So this is to ensure that the payment transactions are done in a secure environment. If someone processes, stores or transmits credit card information, it must comply with the PCI Data Security Standard, which is the DSS. This is mandated by Visa, MasterCard, American Express, Discover and JCB, obviously because people will try and capture credit card information, so it needs to comply with these standards. Network segmentation is actually not a PCI DSS requirement. It's done to isolate the traffic that stores, processes or transmits the cardholder information from the rest of the network. Reduces the scope of the network environment subject to PCI compliance. If you didn't have your network segmented, then your entire network would have to comply with all of the various PCI DSS requirements. If you segment the card processing part of your network, then only that part of the network needs to comply. So it's going to make your life a lot easier. Uses: the footprint of sensitive information is confined, and this is what I mentioned a moment ago, and you can protect it using firewall or your intrusion detection or protection systems. Reduces the audit cost as well. The audit's done for a specific network segment as opposed to your entire network, and again the best example is when you're getting audited for the purposes of PCI compliance. This is one of the topics for the syllabus actually, network segmentations, critical situations. Numerous situations where the network segmentation is critical. So the SCADA, the Supervisory Control and Data Acquisition, and the ICS, the Industrial Control Systems. So again, you'll see this on the syllabus when you look. The ICS refers to several control systems that are used in the industry, in various industries. This is an industrial control system, so you may not have heard of this and may never come to deal or support or manage this unless you're part of the industrial network infrastructure. The industrial facilities are electrical power grids, water distribution, oil, natural gas pipeline systems. They're dependent on electrical, hydraulic and mechanical equipment. This equipment is all monitored by sensors that transform the physical stimulus, for example something's broken or stuck or doing too much or too little of what it should be doing, and this is changed into an electrical signal. In a basic SCADA system, when industrial operations are performed, the information from the sensors is sent to a controller or a number of controllers. The controller is a type of computer that receives the information from the sensor. Now, what happens with this information just depends on the environment and what's required and the sensor type. This sends the information to computers with the SCADA software. So this helps the systems monitor, interact and control a variety of equipment. Prevents outside attacks. The SCADA systems are segmented from the rest of the network, and in addition they have the firewalls installed. You'd need probably help from a specialist design company and probably installation as well, because it's kind of outside the purview of the normal network engineers' roles. Old and outdated computer systems, often referred to as legacy. These may well be running applications, and you could see this a lot if you do any network consulting. You'll go to companies that are just running old software and they want to keep it because it still works, and it's due to the cost and all of the heartache of having to upgrade and translate all of the data. These systems can't be taken out of service usually, but because of the age, they're more vulnerable to attacks. Because of the lack of support, and the support means there's no more security patches. So basically we'll come back to segmentation, and it's important to segment these from the rest of the network. When there are servers in the network for public access, we'd normally restrict access. This is classic example is at a public library where customers come in and want to use the systems, but obviously you don't want them to have visibility to the back-end systems where customers' data is kept and people can get books and make payments and all that sort of stuff. So you'd segment the servers and resources used by employees on a private network, public access to the public. Network segmentations, critical situations. If a private network is restricted only to employees, it's less prone to outside attacks, probably stating the obvious here. In a public network, even if the server is compromised, it won't actually affect your internal private network. So you could do your troubleshooting and resolution without worrying about affecting your critical business systems. Testing, patches and updates for applications should be carried out in a test environment. It's often called a test bed, where you've got a copy of your devices. You could even be running them virtually. And it's all done in order to prevent or foresee problems on your live equipment. A honeypot is a decoy server set to lure attackers, studies their methodology and how they break into the systems, gathers forensic information, and it can be used in the event that you actually prosecute somebody. Designed to be a little bit more easily exploited than the actual production server, so this would probably be the first device discovered by the attackers. Has attackers' activities logged to gain insight into their sneaky little methods. Okay, a honeypot is a network segment that contains more than one honeypot, or honeynet, sorry. So the honeynet would normally look like a normal operational network for the attacker, and it'll make the attacker spend more time in the system, which gives you more time to analyze what they're doing and where they're coming from. Alright, so we've covered segmentation physically, logically, uses of it, and critical situations. That's the end of the presentation. Thanks for watching.
Network routing and IP addressing, IP addresses and conversion. So welcome to this module. We're going to cover IP addresses and conversions. And in some of the previous modules, we talked about a lot of the technologies and theories and protocols that make up computer networks. And so here we're going to discuss some of the more important aspects of networking, specifically the IP address. So this module is going to begin by introducing us to some of the specific protocols that are found within the TCP/IP protocol suite that you need to know about for the Network Plus exam. And these are TCP and IP in a little more depth. We mentioned them briefly when we talked about the TCP/IP model. And then we're going to describe UDP, which is a connectionless protocol. Then we're going to look at ARP and RARP, two versions that allow us to basically, or two protocols rather, that basically allow us to map MAC addresses to IP addresses, and which are basically responsible for routing in general. And after that, we're going to look at two management protocols, one called ICMP, which I introduced to you in previous modules, and I said it was related to the ping utility, and we're going to learn a little more about that. And then IGMP, which is slightly different, has to do more with multicasting and unicasting. And then we're going to continue by outlining IP packet delivery processes, and we're going to finish off the module with a bit of an introduction into binary and decimal conversions, so that later on we can talk a little more in depth about IP addressing and how something called subnetting works, which is going to require us to understand the difference between these two ways of writing our numbers. And after we have covered all these topics, we're going to have a fundamental understanding of IP that's going to prepare us for some of the more in-depth topics, as I just mentioned, in the following modules. So let's begin by taking a look at two of the most important protocols that make up the suite, TCP and IP. Now, in previous chapters, we briefly described these two, but we still need to take a closer look at them to assure that we have a complete understanding of the many different protocols that are found in our protocol suite. So first, for those applications and instances that depend on data to be reliable in terms of delivery and integrity, the Transmission Control Protocol, or TCP, and I'm just going to write out Transmission Control Protocol, is a really dependable protocol and provides a number of features. First, it guarantees that data delivery, and besides guaranteeing that delivery, it also has a certain amount of reliability. It also offers flow control, which, as we've mentioned in the past, assists a sending station in making sure it doesn't send data faster than the receiver can handle. This function also is going to assist in the reliability of data because it ensures that there isn't any data lost due to overloading the receiving station. Now, TCP also contains something called a checksum mechanism. And what this does is it assists with error detection. And the level of error detection isn't as strong as that of some of the lower layers. And you recall that this is in the transport layer of the TCP/IP stack. But it does catch some specific errors that may go unnoticed by other layers. And by the way, this checksum, basically, it's sort of has a number that it creates based on the data, and it can check that number at the beginning and at the end to make sure we haven't lost anything. Now, this protocol attempts to alleviate MTU, if you recall what we talked about with MTU there, mismatches on the data link layer by establishing maximum segment sizes that can be accepted by TCP. This is also going to reduce what we talked about earlier, that MTU black hole. Now, further examining IP, or the Internet Protocol, which is aptly named and exists at the Internet layer, unlike TCP, IP is characterized as being connectionless, or a best effort delivery, which is also like UDP, which we'll see in a second. It outlines the structure, then, of information, which is called datagrams or packets, and how we're going to package this stuff to send it over the network. Now, this protocol is more concerned with source-to-destination navigation, or planning, or routing, as well as host identification and data delivery, solely by using the IP address. So this is slightly different from TCP, which is doing stuff in a much more different way. Now, IP is used for communications between one or many IP-based networks, and because of its design, it makes it the principal protocol of the internet, and it's essential to connect to it. So, unless we are using IP address in today's day and age, we will not be able to connect to this big thing called the internet. Now, the terms connectionless and connection-oriented relate to the steps that are taken before the data is transmitted by a given protocol, whatever that protocol might be. With TCP, we're looking at connection-oriented, and of course with IP, we're looking at connectionless. And for instance, the connection-oriented protocol is going to ensure a connection is established before the sending of data, meaning it is oriented towards a connection, whereas a connectionless isn't going to. It doesn't matter if there is a connection established already. So the next protocol, which is also connectionless that we want to talk about, is something called UDP. Now, since we have many applications and their functions depend on data being sent in a timely manner, TCP and its connection-oriented properties hinder their performance. In these cases, we're able to use something called UDP, again, the user datagram protocol. And UDP is connectionless, just like IP is. And that means it's a best effort delivery protocol. So with TCP, if packets get delayed or if they're needed to be resent due to a collision, the TCP on the receiving end is going to wait for the lost or late packets to arrive. Now with some sensitive data delivery, this is going to cause a lot of problems. And UDP is what we call a stateless protocol, which prefers the packet loss over the delay in waiting. So UDP is only going to add a checksum to the data for data integrity. It's also going to address port numbers for specific functions between the source and the destination. Nodes such as UDP port 53 for DNS, which is one that you should remember from an earlier module. Now, UDP's features make it a solid protocol, and it's used for applications such as VoIP or Voice over IP and online gaming. This makes sense because we don't care if every single little packet arrives. What we want is the speed with which UDP is going to deliver stuff. Obviously, if we miss a couple packets in voice, that's okay, they drop, but we don't want to have to wait until the next packet arrives. That's going to actually cause much more of a delay. And so we're going to use this one in more VoIP and online gaming purposes. Now, the next protocol we want to be familiar with is called ARP, and it's also necessary for routing. ARP, or the Address Resolution Protocol, and the Reverse Address Resolution Protocol, are request and reply protocols that are used to map one kind of address to another. Specifically, ARP is designed to map IP addresses, addresses that are necessary to TCP/IP communication, to MAC addresses, which are also known, as we've discussed in the past, as physical addresses. And again, IP addresses work on the networking layer, or in TCP/IP, the internet layer, whereas MAC addresses operate on the network interface layer of TCP/IP, which in OSI would be the data link layer, layer 2. Now, in TCP/IP networking, ARP operates at the lowest layer, the network interface layer, in total. Whereas in the OSI model, we say that it actually operates between the data link layer and the physical layer. And this is because it wasn't designed specifically for the OSI model, it was designed for the TCP/IP model. Now, ARP and RARP play very important roles in the way networks operate. If a computer wants to communicate with any other computer within the local area network, the MAC address is the identifier that's used. And if that device wishes to communicate outside of the local area network, the destination MAC address is going to be that of the router. So the ARP process works by first receiving the IP address from IP, or the Internet Protocol. Then ARP has the MAC address in its cached table. So the router has what are called ARP tables that link IP addresses to MAC addresses. We call this the ARP table. So it looks in there to see if it has a MAC address for the IP address listed. It then sends it back to the IP if it does have it, and if it doesn't have it, it broadcasts the message it's sent in order to resolve what we call resolve the address to a MAC address. And the target computer with the IP address responds to that broadcast message with what's called a unicast message, and we've discussed that contains the MAC address that it's seeking. ARP then will add the MAC address to its table, so the next time we don't have to go through this whole process. And then it returns the IP address to the requesting device as it would have if it just had it. Now, RARP is used to do the opposite. That is to map MAC addresses of a given system to their assigned IP addresses. And it sort of works in reverse from all this. Now, that's a very general overview of ARP and RARP, and if you were to go into Cisco certifications, for instance, you go a little more in depth into this. But for Network Plus, this is really where we need to stop with this protocol. So the next protocol I want to talk about is ICMP, which is also called the Internet Control Message Protocol. It's a protocol designed to send messages that relate to the status of a system. It's not meant to actually send data. So ICMP messages are used, generally speaking, for diagnostic and testing purposes. And they can also be used as a response to errors that occur in the normal operations of IP. And if you recall, one of the times that we talked about that was, for instance, with the MTU black hole, when that ICMP message couldn't get back to the original router. Now, many Internet Protocol utilities are actually derived from ICMP messages, such as tracert or traceroute, pathping, and ping. And we'll talk about these in a little more depth, and if you were around for A+, we definitely talked about these two quite a bit. ICMP is actually one of the core protocols of the IP suite, and it operates at the internet layer, which, as you recall, is TCP/IP second layer. Now, ICMP is a control protocol used by networked computers and operating systems. And the most common utility that we're going to see is what's called ping, which we've talked about, which uses what are called ICMP echo requests. And they reply to determine connection statuses of a target system. So I could ping a specific system to see if it's on the network. Of course, there are some reasons why the ICMP, as we've talked about, might not make it back to me, or it's configured not to respond, perhaps through a firewall. Finally, we need to talk about IGMP, or the Internet Group Management Protocol. It should not be confused with ICMP. It's slightly different. It is used to establish memberships for multicast groups. Now, multicasting is where a computer wishes to send data to a lot of other computers through the internet by identifying which computers have subscribed, or which ones wish to receive the data. We looked at this earlier and determined that routers determine a multicast group. Now, in a host implementation, a host is going to make a request for an IGMP implemented router to join the membership of a multicast group. Now, certain applications, such as those for online gaming, can use IGMP for what are called one-to-many communications. The one being the game server, and the many being all of those end users that have subscribed to the gaming session. So those routers with IGMP implementation periodically will send out queries to determine the multicast membership of those devices within range. And then those hosts that have membership are going to respond to the queries with a membership report. Now, the process of delivering an IP packet is simple. It begins with resolving the name of the host to its assigned IP address, like we talked about with ARP. And the connection is established by a service at, if you recall, the transport layer. Now, after the name resolution and connection establishment, the IP address is then sent down to the internet layer. And the next step is where the IP looks at the subnet mask, which we've talked about in A+, and we'll talk about more, of the IP address to determine whether the destination is local to the computer on what we say is the same subnet, or whether it's remote or on another network. After this determination is made, then finally the packet is routed and delivered. Okay, so we now understand TCP/IP a little more fully, some of the protocols that are dealt with in great detail, and how IP packet delivery works. So let's talk about binary and decimal, which are going to be really important when we get into what's called subnetting. And it's just good to know as an IT professional anyway. Specifically, understanding binary, or how to convert binary, which is the number computers, the way computers talk, to decimal, which is the way that we deal with numbers, and decimal to binary, pertains to a lot of different aspects of, as I just mentioned, networking. So to begin with, binary, as the name implies from bi, is what we call a base 2 system. More commonly, we used a base 10 system, decimal. Now, this means that we have 10 possibilities for every place value. We have between 0 and 9. You add that up, there are 10. Now, with binary, there's only 2 options, either 0 or 1. So we can either have a single 0 or a single 1. And that's what we call a binary digit or a bit. So the binary number has place markers that are similar to the base 10 system. For instance, if we have a decimal base 10 numbering system, the second place mark designates the tens. If we imagine that there's a period or a decimal right there. The third designates the hundreds, and then we move to thousandths and 10,000ths and 100,000ths and so on and so forth. And in each one of these, we can have anywhere from 0 to 9, and that's 10 options in each one of those spots. Now, in a base 2 numbering system, which is binary, we have only 2 options, a 1 or a 0 in either one of those places. And in computers, especially in a lot of IP addressing, we really deal with the difference between 8 different places. So we're going to call these 8 an octet. So this 8-place binary digit is referred to as an octet because there's 1, 2, 3, 4, 5, 6, 7, 8 of them. And you'll see these numbers pop up over and over again. So this is really as far as you need to know for binary, although you can go even further. So if we look at this octet from the right side to the left, the first place mark is what we call 2 to the 0 power, right? If we were talking about this in tens, this would be the ones place. Why? Because it's 10 to the 0 power, which is ones. Anything taken to the 0 power is 1. Next, we have 10 to the first power, which is going to equal 2. If you recall, we call this the tens place. 10 to the 1 power means 10 by itself is 10. Then we have 10 to the second power, which is 4. And if you recall, in decimal, this is 10 to the second, which would be 10 times 10, which is 100. You can see where this is going. So 2 to the third is 8. 2 to the fourth equals 16. 2 to the fifth equals 32. 2 to the sixth equals 64. And 2 to the 7 equals 128. So each one of these place markers is equivalent to this number, whether it's turned on or off. Now, to help clarify this a bit, each place here has one of 2 options, correct? Because it's base 2. If it's off, that means it's a 0, as you see right here. And the number means it's not being counted, so we don't count any of these numbers we've just calculated. So if all the bits are off, that means that we have a number of 0. If all of the bits are on, then this means we add each of the numbers together. So we get 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which equals 255. Now, believe it or not, you can create any combination of numbers from just binary. You don't need decimal. And we're going to see that in just a second. So, for example, let's say the binary number is 000000111. Well, in this case, the 128, 64, 32, 16, and 8 bits are all off. The only ones that are on are 4, 2, and 1. And if we add those together, 4 plus 2 plus 1 will get 7. 4 plus 2 is 6, plus 1 is 7. If we take another number, say 011001110, then this is going to equate to 102. Why? 64 plus 32 equals 96, plus 4 equals 100, plus 2 equals 102. So it's pretty simple. You just take the number with the ones under it and add them together. So now that we've converted binary into decimal, a number that we all know, let's go ahead and see if we can convert the other way, decimal to binary. Now, for this process, we're going to use the same exact chart that we just saw with the binary conversion. And this chart is going to help us visually represent all the binary digits, which is why I like it, and they're placeholders, and it makes it a lot easier. So for decimal to binary, we simply go from left to right and break down the number until we reach the 0. So let me break that down a little bit. For instance, if we take the number 128, right, this is pretty easy to convert. We plug it into this chart. How many times does 128 go into 128? One time. If we take all the others and we subtract them, we're going to have 0, right? Because now 128 minus 128 is 0. That leaves us with our binary number 1000000, which is equivalent to 128. Now, if we take a look at a different number, let's say the number 218, this is going to take a little more math. Does 128 go into 218? It certainly does. So 218 minus 128 has a remainder of a certain amount, which is 90. Does 64 go into 90? It does. We now have a remainder of 26. Does 32 go into 26? No, it doesn't, so we put a 0. Does 16 go into 26? Yep, it does, which leaves us with a remainder of 10. Does 8 go into 10? It does, which leaves us a remainder of 2. Does 4 go into 2? It does not, so that leaves us with 0. We still have our 2. Does 2 go into 2? Yep. And then do we have anything left over? Nope, we're at 0 now, so we have 0. If we now add all those up, this is our binary number 110111010. Now, while this might seem like a fairly long process, it's important to understand how this works, because when we get into subnetting, it's really going to become important so we can have a better understanding of networking in general. So, just to recap everything we've talked about, we described these protocols in the TCP/IP suite. First, TCP, Transmission Control, and IP, Internet Protocol. One is connection-oriented, and the other is connection-less, meaning that it just is worried about delivery. Remember, IP is what is responsible for that IP addressing. UDP is also connection-less, similar in some ways to TCP, but it's not connection-oriented. Then we had ARP and reverse ARP, Address Resolution Protocol, which job is to map IP addresses to MAC addresses. We talked about ICMP, which is what we use when we're dealing with the status of a system. Internet Control Message Protocol. And then we talk about IGMP, the Internet Group Management Protocol, which is more dealing with multicast groups. We then talked very briefly about the IP packet delivery process, which was pretty simple, right? It's packaged, it's sent, we determine where it needs to go. Once it's determined where it needs to go, it's sent there. Finally, we explained the binary conversion, which is going to be really important for IP addressing, including how to go from binary, which is a base 2 system, to decimal, which is a base 10 system, and back again. Network routing and IP addressing, IP addresses and subnetting. So having discussed IP addressing and routing in general, we're now going to further examine IP addressing and the methods of logically, not physically, dividing up our networks. This way, we can keep not only better track of all the devices on the network, but also organize them for security, performance, and other reasons. After we complete this module, we're going to have a better understanding of how our network devices are identified, both by other devices and by individuals such as ourselves, since we're not computers. So first, we're going to identify what a network address is versus a network name. One, the network address is for other devices. A network name is really for us, since it would be difficult for us to remember all these numbers, much like using a phone number in a cell phone. Next, we're going to describe the IPv4 addressing scheme. And IPv4 is important to know because even though we have a newer version, IPv6, IPv4 is still deployed in most situations, and it's covered to the most extent on Network Plus. When we get to IPv6, which is different, version 6, there are a lot of benefits to that, and we'll describe it later, but really understanding IPv4 is really important. After we take a look at that, we're going to look at subnetting and a subnet mask. You might have seen this, and these are the numbers, and we've probably mentioned them in the past, such as 255.255.0.0, and so on and so forth. And we're going to describe how this allows us to separate out the network ID from the node ID, or the device's ID or address from the network's address, much like our zip code versus our street address. After that, we're going to describe the rules of subnet masks and their IP addresses, and knowing binary is really going to help us understand all of this stuff. After that, we're going to apply a subnet mask to an IP address using something called ANDing, which again gets back to binary, and might even remind you of something you learned in high school, this ANDing principle, which is really going to come in handy. And again, this is something that we only have to do now with IPv4. IPv6 doesn't have to do it, and we'll describe why. Finally, we're going to take a look at what are called custom subnet masks, which are slightly different from these default ones, the 255.255.255s, and so on. So, having said all that, let's get into it by looking at network addresses and names. So let's begin by looking at how nodes on a network are identified, specifically on the internet or network layer. If you recall, the network layer is layer 3 of the OSI model, and the internet layer is layer 2 of the TCP/IP model. So to begin, a network address is assigned to every device, and I think we've discussed this, that wants to communicate on a computer network. The network address is actually made up of two parts. The node portion that belongs to the specific device, and the network portion, which identifies what network the device belongs to. I think I've just described this as a zip code, which describes the sort of network or the area you're in, versus your street number and your street address, which is specific to where you live. This address is what is used by devices for identification, and as it's only made up of numbers, whereas a network name is made up of letters and such, the real reason being readability. We would have a lot of trouble remembering. We already have trouble remembering a phone number, but if you imagine remembering a whole binary number or a set of numbers where there's infinite possibilities, unless you're using it a lot, it's easier to remember a name, such as the conference room laptop or resource server 1, than it is to remember an IP address, which might be something like 132.168.56.43. Especially when there are a lot more computers involved, the names become a lot easier. So the network named is actually mapped to the address or the IP address by one or another naming services, and some of these we've discussed. Now, as devices only communicate with each other by their network address, the naming services are really crucial to the operation of a network. There are 3 different network services used that you should be aware of. The first, DNS, which we've mentioned before, also called the Domain Name Service, is a naming service that's used on the internet in most networks. It's what allows, for instance, you to type in google.com, which we would call a fully qualified domain name, and it will translate that to the IP address of Google, whatever that might be. The next naming service is Windows specific, and it's called WINS, or the Windows Internet Naming Service. It's really outdated, and it was used on Windows networks. The only reason I mention it is you might see it mentioned in a test question, and it might help you. But you're really not going to see it used in the field much anymore. And finally, we have one called NetBIOS, which is a broadcast type of service that has a maximum length of 15 characters. And it was used, or still is used to a certain extent, on Windows networks as well. A good understanding of all of these network identification aspects, addresses, and names is important at this very fundamental level. So now that we sort of have a general overview of these, let's take a look at some of the specific type of network addressing, specifically IP version 4. Now, IPv4, IP version 4 addresses is a very important aspect of networking for any administrator or technician or even just IT guy to understand. It is a 32-bit binary address that's used to identify and differentiate nodes on a network. In other words, it is your address on the network or your social security number. With the IPv4 addressing scheme being a 32-bit address, and you can see if we counted each one of these up, remember a bit is either 0 or 1, and we can count up there are 32 of these. This means that there are theoretically up to 4.29 billion addresses available. Now, that might not sound like we're ever going to hit that, but in fact, we've already gotten there. And so part of the problem is, how do we share 4.29 billion devices with 4.29 billion addresses with even more billions of devices in the world? So this 32-bit address, which is why we've had to develop another one called IPv6. But anyway, I digress. The 32-bit address is broken up into 4 octets. This makes it easier for people to remember and to read. And you can see those here. And if you've ever seen like a 192.168.0.1, those are the 4 octets. This system and structure of these address schemes is governed and managed by 2 standard organizations. One is called the IANA, which stands for the Internet Assigned Numbers Authority, and the other is called the RIR, or the Regional Internet Registry. I wouldn't worry about memorizing these, I'm just mentioning them so you know sort of who's coming up with all this stuff. Now, every device on the network is going to have its own unique address. So there are 2 types of addresses in general. One is called class-full, and these are default addresses, and the other are called classless, which are custom addresses. We're going to talk about the classless ones in a later module, and we're going to define both of these in greater detail a little bit later on. As a network address, it's also made up of 2 parts, the network portion and the node portion. Let me just erase all this writing here so you can see exactly what I mean. In order to tell, now in this section, you can see the network portion are the first 2 octets, and the node portion are the last 2 octets. But that is not always the case. In fact, if we were to just take those away for a second, and this is how the computer looks at them, we can't actually tell which is which. And that's why we need something called a subnet mask. The subnet mask allows us to determine which is the network portion and which is the node portion. That way, we know, for instance, where the area code of the phone number begins and the rest of the number ends. So the network portion would be like the area code of your phone number or the international code. It tells you which network that is on. The node portion tells you exactly which phone on that network we're going to try reaching out to. So we're going to further logically, again, not physically, divide a network into smaller subnetworks called subnets. Now, this logical division is beneficial because of 3 reasons. 1, it can effectively increase the efficiency in packet routing, because if I know that my information is destined for a specific network, I don't have to bother with asking, let's say, 5,000 or 5 million or 5 billion computers if I'm meant for them. I can go directly to the network where I want to go, just like with area codes and phone numbers. The next is it allows for better management of multiple networks within a single organization. For instance, if I'm a network administrator, it might be easier to have separate subnets so I can organize who's on which subnet, so that way not only are things going to be routed more efficiently for that person, but it's easier for me to manage on paper and in my administrative duties. And finally, it potentially offers a certain level of security, since I'm only going to be able to access easily information that's on the same network or subnetwork that I'm on. Now, a subnetted IPv4 address is actually comprised of 3 different parts: the net ID, the host ID, and the subnet ID. Now, if a device on a subnetted TCP/IP network wants to communicate, it's going to need to be configured with an IP address and a subnet mask. And we'll look at these in just a second. The subnet mask is what is used to identify the subnet that each node belongs to. This also allows us to determine which network it's on. Connectivity devices such as routers or upper layer switches, and we're talking about layer 3 devices here, and remember, layer 3 devices look at IP addresses, not just MAC addresses, are used on the borders of these networks to manage the data passage between and within the network. That's how we're going to get better routing efficiency, easier management, and potentially make it more secure. Because if I have any one network and I have let's say a switch, we'll put this as switch, and it has 4 computers on it, and then I have another switch, and these are layer 2 switches, okay? And each of these, let's say we have our different subnets, then I'm going to divide these up by a router, which now is going to make sure that data that's going here kind of gets bounced back unless it's meant for this guy. And this way we're really reducing the traffic on it. Now, a subnet mask is, like an IP address, a 32-bit binary address broken up into 4 octets in a dotted decimal format, just like an IP address. And it's used to separate the network portion from the node portion. And I'm going to show you how that works in just a minute, and it involves a little bit of knowledge of binary, which we've already talked about. So the subnet mask, and that name mask sort of lets you think of it as being put onto the IP address, is applied to that IP address and removes the node ID. The subnet mask therefore removes an entire octet of the IP address by using 8 binary ones, or 255 in decimal format, meaning that this 255, if we add it up in binary, would be 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. And then this would be 1, 2, 3, 4, 5, 6, 7, 8. So meaning that a 255 equals 8 ones, which is the reason why an IP address can never be 255. And if this is a little confusing, that's okay. We're about to clarify that in just a second. So IP addresses, IP address assignments, and subnet masks all have to follow a certain set of rules. I'm going to describe the rules and then I'm going to apply them. So if some of this is a little confusing or over your head, keep paying attention, keep with me, and I think it's going to clarify itself. The first is that the ones in a subnet mask will always start at the left, meaning the first octet will always be 255, or 8 binary ones. So my subnet mask, I'm always going to start at the left when I'm writing it out. This says that the first octet is going to be 255, which means 8 bits. Now the zeros of the mask will always start at the 1 bit, or all the way on the right, meaning that I'm going to have zeros from the right and ones from the left. And the ones in the mask have to be adjoining or consistent or continuous or contiguous, whichever word you want to use, meaning once there is a 0, we cannot then go back to ones. So we're not going to see like this sort of thing happen. In fact, we have to have continuous ones from the left and continuous zeros from the right. This is the only way a subnet mask is going to work, and I'll talk about why in just a minute. Also, if there is more than one subnet on a network, every subnet has to have a unique network ID, and I'll explain this in a bit, but it makes sense. If I have different network IDs, then I'm not really, if I have similar network IDs, then I'm not really dealing with multiple networks. I'm dealing with the same network. Now, assignment of IP addresses have to follow a few more rules. So these are the subnet masks. First, there cannot be any duplicate IP addresses on the network. This means that every network, every device has to have its own unique IP address. We cannot have more than one device with the same IP address. If we do, they're not going to be able to communicate because the switches won't know where to send packets. Next, if there are subnets, every node must be assigned to one of them, meaning that every address, every IP address has to be assigned to a specific network. Now, the address of a node cannot be all ones or all zeros. Remember, all ones would be 255. All zeros would be just 0.0.0.0. So I cannot have an IP address that is either 255.255.255 or that can be 0.0.0.0. And you'll see why when we get to the mathematics of this in just a second. It's because then I would never be able to determine a network ID from a node ID. Finally, and this is something you sort of have to remember, the IP address can never be 127.0.0.1. We talked about this in A+, but that's because this is what's called the loopback. It's a reserved IP address specifically for yourself. It'd be like saying me, myself, or I. I cannot have a 127.0.0.1 IP address assigned to a device because every device calls itself 127.0.0.1. Now, besides understanding these rules, which are a bit abstract, I think, we need to know how to apply them and how to apply a subnet mask to an IP address. I think it's going to make some of these rules a little clearer, so let's take a look at those. Now, when a subnet mask is applied to an IP address, the remainder is the network portion, meaning when we take the IP address and we apply the subnet mask, and I'll show you how to do that in a second, what we get as a remainder, what's left over, is going to be the network ID. This allows us to then determine what the node ID is. This will make more sense in just a minute. The way we do this is through something called ANDing. ANDing is a mathematics term. It really has to do with logic. The way it works is, and you just have to sort of remember these rules, 1 and 1 is 1. 1 and 0 is 0. And the trick there is that that 0 is there. 0 and 1 is 0, and 0 and 0 is also 0. So basically what ANDing does is allows us to hide certain certain bits from the rest of the network. And therefore we're allowed to get the IP address, or rather the network address, from the node address. So let's take a look at this for just a second. Let's say we have an IP address 162.85.120.27, and we have a subnet mask of 255.255.255.0. Now, let's take a look at how this works when we move it into binary. 162.85.120.127 equals this in binary. And if we wanted to write out these places again, if you remember, we had, this was a base 2, right? So these are the place settings. I'm just going to write these out real quickly, and then I'm going to erase it all. Okay? And so we get 1, 2, 4, 8, 16, 32, 64, 128. And it's good to sort of commit these to memory. Therefore, the reason this is 1, 1, 1 is we take that 128, we add it to 32, and we add it to the 2, because those are the bits that are on. And when we add 128 plus 32, we get 160 plus 2 gives us 162. So it works out, and you can see my math is correct here. I'm going to erase all this now. Try to remember this AND thing in here for a minute. Now, if we convert 255.255.255.0 into binary, we've already talked about this, we're going to get all these 1s. And then, because this is 0, we're going to get 0. Now, if we apply the ANDing principle, this is what we're going to get. Anything with 1 and 1 turns into a 1. Anytime we see a 1 and a 0, we're going to get a 0. And if we apply this out, here's what we get. Now, because we have all these zeros here, it's basically going to block all these 1s from coming down and coming through. Right? They all turn into 0. So, if we convert this back into a decimal, we now get 162.85.120.0. Basically, and this is pretty simple to see, we can see that the 162 drops down, the 85 drops down, the 120 drops down because of this ANDing that we just talked about, and the 27 gets blocked by these zeros. And so we can determine that the 162.85.120 is what we call the network ID. Now, by looking at it this way, we can see then that the network portion of the address is going to be the first 3 octets, as we just pointed out, and the node portion is going to be the last octet. So this is the first step in subnetting, and it tells us a lot of things about the networks. Just by knowing the IP address and the subnet mask, a technician can now discern a lot of things, such as what portion is the network ID, what portion is the node ID, and therefore what is my first usable IP address, and what's my last usable IP address that I could start to give to devices. I can also determine stuff like what we call the default gateway, which we'll look at in a second, and the broadcast address, which we'll also look at, not in a second, then in the next module. Now, there are 3 default subnet masks, as you can imagine. And these have to do with what we call a classful IP addressing system, and we'll talk about that next, the next module. But the default subnet masks are 255.0.0.0, just going to go with the class A, and we'll talk about that. 255.255.0.0 and 255.255.255.0. What you can see is, if you have a default subnet mask, then you know immediately, just by looking, what the network address is and what the node address is. As you can imagine, if I have this as my network address, I can have a lot of networks and only so many nodes. This one, I have more nodes, a little bit less networks, and in this one I have a lot of nodes but fewer networks to divide them up on. Now, it would be great if all subnet masks were as simple as this. We wouldn't even really ever have to break it down into this binary sort of coding, because you could just look at it and say, oh, it's 255, I know they're all going to be 1s, I know that's going to AND out, and therefore I know it's going to end up right here. But unfortunately, this is not always the case. Sometimes we have what are called custom subnet masks. Now, by using a custom subnet mask, we can actually further divide or subdivide our IP address, and in these cases, it can be a little more difficult, and so converting to binary is actually necessary to break it down. Custom subnet masks are created by what we call borrowing bits from the host portion to use to identify the subnet portion. So you can see we've just borrowed a bit, this one, right over here. Now, keeping in mind that the subnet mask rules allow us to borrow bits from the node portion and give them to the network portion, the bits from the left to the right of the portion, like this, are switched on. Now, turning this bit on means we now have different values for the subnet mask. Instead of just 255.255.255.0, we know this is no longer 0, right? So this is actually now going to be 128. And we can have a number of these, and if you keep adding over to the right, so 128, and then we added 64, we get 192, and so on and so forth. So we can actually have a number of custom subnet mask values in the last octet, and those are these. And so you can see, in this case, it's not really going to make much of a difference when I do all the binary bitting, because you see that the 0 and the 0 is still going to become a 0 here. And so all of this is really going to look the same, and so our network portion is actually going to look the same as it did before. We have the same network ID as we did before. But let's say that this was actually, this number, by the way, is the same as the one we had before, 162.85.120.27. If this was instead 162.85.120. I don't know, 128, we're going to have an issue because this is going to be on. These would say let's be off. And when they come down, this is going to turn into a 0 as opposed to that 1 dropping down. And so it's going to change what our IP address in the end looks like. And so we actually need to do some backward engineering to get to our subnet mask. Now this is all really complex, and when we get into, if you ever get into Cisco, you'd really have to know this. But for our purposes, you really don't need to know this that in depth. Alright, so just to recap what we talked about here. We got a basic understanding of a lot of things, not too in depth, and you might need to rewatch this video to really get it, and maybe even do a little bit of exercises on your own. First, we talked about the difference between a network address and a network name, remembering that the 3 network name services that match a name, such as Bill's laptop, to an address, which would be something like 192.168.0.1, we can use either DNS, the domain name service, which is the most popular one, something called WINS, which is specific to Windows, or NetBIOS, also a Windows-based naming system. The one we want to be most familiar with is this. This one's not really used anymore. NetBIOS is still used in certain instances, especially in older networks. We then talked about the IP version 4 address and the things that it requires, including, and remember, a IPv4 address is that 32-bit broken up into 4 octets. The reason it's called an octet is because we have 8 times 4 gives us that 32, and we break it up. So for instance, 192 is going to break down to a certain amount of bits. Okay? We also talked about defining subnetting and a subnet mask, which the most important thing it does is distinguishes our network from our node ID. In other words, what's our area code, and then what is our phone number. We can have the same phone number in different area codes, but they go to very different people. We also talked about the rules of subnet masks and IP addresses. We can only have one IP address on any network, and we can not use 127.0.0.1 because that is what we call the loopback address. As far as for the subnet mask, remember that all 1s have to be continuous from the left, and 0s have to be continuous from the right. Our defaults are 255.255.0.0.0, and then 255, I think I just said 255.0.0.0, 255.255.0.0.0, and 255.255.255.0. Those are our defaults. And so we talked about applying a subnet mask using something called ANDing. And we looked at how that divides up, again, the network ID from the node ID, and we saw that in practice. Finally, we talked very briefly about custom subnet masks, something that we don't have to get very much into. But we talked about how if we had 255.255.255. For instance, 128, we could have these sort of subnets, or these, we could break it down even further, and therefore we could start to do a lot more stuff. And in the next module, I'm going to talk about this in a lot more detail and why we would want to do it. network routing and IP addressing, default and custom addressing. So we described in the previous module subnetting, how to determine the network from the node ID, and we talked specifically about IPv4, and we're going to continue talking about IPv4 a little bit more. First, by defining the default IPv4 addressing scheme. Now, some of this we sort of touched on in the previous module, and some of the stuff we're going to talk about right now is going to probably help clarify that. And so it might even help to go back and watch the previous module after watching this one. After that, we're going to talk about the reserved or restricted IPv4 addresses. One of the ones we've already mentioned is what we called the loopback, or 127.0.0.1. That's an example of a reserved IP address, or restricted IP address. And so we're going to talk about those in more depth, and some of the ones that, some of the ranges that are restricted and why they are. Then we're going to discuss what are called the private addresses. And we're going to talk about these specifically because these are different from public IP addresses. One you might be familiar with is the 192.168 private addresses, rather. And this is going to explain why every router that you purchase at electronics store has this as its default. Not everyone, but a lot of them have this as the default IP address, and yet we talked about how you can't have more than one IP address with any device. And so we're going to describe why with private IP addresses this is the case, and we'll talk about some other private IP addresses as well. Then we're going to talk about the IPv4 formulas, and that's what allows us to determine how many hosts and networks are permissible based on the type of IP address, the class that it's in, and the subnet mask that's applied. And this will help us also determine, and we'll talk about in a second, why we might want to use custom subnet masks and custom IP addresses. So then we're going to talk about what the default gateway is. This gets back to actually this right here. It is the device which any node needs to know in order to get out to the network and to the rest of the world. Finally, we're going to talk about custom IP address schemes, VLSM, and CIDR. These are a little more in depth, but these really get back to the subnet masks and why we can apply those, how we can apply sort of specific subnet masks to things. And we'll look at this thing which you might have seen, CIDR, which has to do with why there might be a slash after an IP address, which really gets to the number of bits it has. And we'll talk about that in just a minute. Now, aside from being an aspect that's covered in many areas of the Network Plus exam, understanding the classes in a default IP address scheme is really important for us. And this gets back to right here. So let's talk about, remember we talked about classless and class full. We're going to talk about the classes that exist in an IP address right now. So as we learned in previous modules, the IPv4 addressing scheme is again 32 bits broken up into 4 octets. And each octet can range from 0 to 255. Now, the International Standards Organization, ICANN, which we've mentioned in a previous module, is in control of how these IP addresses are leased and distributed out to individuals and companies around the world. Now, because of the limited amount of IP addresses, the default IPv4 addressing scheme is designed and outlined with what are called classes. And there are 5 of them that we need to know. Now, these classes are identified as A, B, C, D, and E. And each class is designed to facilitate in the distribution of IP addresses for certain types of purposes. Now, the first class, a class A, allows you to have, is designed for really large networks, meaning that it does not have a lot of networks because we only have a few of them, and that is because a class A range goes from 1 to 127 in the first octet, meaning that the remaining octets are reserved for nodes. And so we see that we don't have a lot of networks. We only have 126 networks, 1 to 127. But we do have up to 16 0.7 or 0.8 around about million nodes that can be on this network. And so we have so many nodes for so few networks. And so this is really for very large networks. And there are some specifically reserved addresses in this as well, and we'll talk about those in just a minute. Now with Class B, here we have 128 to 191. And these are called Class B. They allow for a lot more networks and fewer nodes, which makes sense. Now, the default subnet mask for a Class A, which might make this a little clearer, 255.0.0.0, whereas for a Class B, it's 255.255.0.0. Now, as you can tell, the class is actually determined by the very first octet, the number in the first octet. And it's important to then, therefore, memorize these numbers because you'll see on your exam, they'll ask you which class is this IP address a part of. If it's between 1 and 127, you know it's a Class A. If it's between 128 and 191, you know it's a Class B. If we get to a Class C, now we have a lot of networks and not a lot of nodes. And you can see that these are 192 to 223 in the first octet. And the default subnet mask for this is going to be 255.255.255.0. And if you remember, that gives us only this octet for nodes and all of these octets for networks. This is usually one of the most recognizable for home networks because we have the 192.168.0.1, for instance, that is going to obviously fall into this Class C. Now, there are two other classes. They're not very common, but they're important to be able to recognize. There are Class D IP addresses, which are only used for what we call multicast transmissions. And these are for special routers that are able to support the use of IP addresses within this range. You don't really need to worry about this for much application unless you're dealing with a lot more advanced stuff. And these deal with 224 to 239. Finally, we have Class E, which is from 240 to 255. And these are really for experimental reasons. So we're really not going to see these in much play. The ones you really want to be familiar with are these first three classes, A, B, and C. Remember, 1 to 127 is a Class A, 128 to 191 is a Class B, 192 to 223 is a Class C. If you can remember those ranges, I would commit them to memory. You'll be good to go for the exam. Now, within each of these classes, there are a number of addresses that are not allowed to be assigned or leased for specific reasons. These are what we call reserved and restricted IP addresses. Now, we've mentioned the 127.0.0.1 or the local loopback or the local host IP address before, which can't be assigned because it's reserved for me, for myself, for I. This means that this address is used when I want to address myself. So if I wanted to, for instance, assign myself my own name via DNS, and my name was me would link up to the IP address 127.0.0.1. And that way it's going back to myself. Now we're really going to use this for mostly diagnostic purposes if I want to double check to make sure, for instance, that TCP/IP is running correctly. And it's also going to be used for programmers and such like that. Now the address 10.0.0.0 is also restricted, and it's not available to use because, again, this a host address can never have all zeros. Conversely, the addresses that have all ones, for instance, 255.255.255.255, cannot be used for addresses. Obviously, this one can't because it would sort of ruin the use of a subnet mask. But even if I had something like 192.168.0.255, I can't use that because that's what's called a broadcast address. And so it's just simply reserved for that. This means that if a message is transmitted to a network address with all ones in the host portion, or 255, that message is going to be transmitted to every single device on the subnet. It's called a broadcast, and we talked about broadcast before. Finally, the address 1.1.1.1 cannot be used because this is what's called the all hosts or the whois address. So these basically, whereas 127 is for me, 1.1.1.1 is for everyone. So these we can never use. The important one I really want you to remember here is this one, and you're going to want to remember that, for instance, 255 in the host portion can never be used. Again, not only because that's going to ruin a subnet, as we've talked about, but also this is reserved for what's called a broadcast address. Now, there are portions of each class that are allocated either for public or private use. Private IP addresses are not routable. This means that they are assigned for use on internal networks, such as your home network or your office network. When these addresses transmit data and it reaches a router, the router is not going to route it outside of the network. So these addresses can be used without needing to purchase or leasing an IP address from your ISP or internet service provider or a governing entity. So this is how I could create an internal network in my home, and I don't need to go register it, and I might not be able to access the internet, but I don't need to register it. If I want to go out to the internet, then I can share using devices and resources we've talked about previously and we'll talk about later, a public IP address with all of the internal devices that are configured using private IP addresses. Now, since these are not able to be used externally to our network, these IP addresses can be used by as many devices as necessary, as long as we never double over one IP address per device. So the Class A private IP address range, remember we talked about 10.0.0.0 because we cannot have zeros, right? Remember 10.0.0 and 255 we actually cannot assign, but any address in between that, so 10.1.126.5 would fall into what's called a private address range, and you might see this in your home router as well. So this makes it easily discernible from other addresses in its class. Anything that has the 10 to begin with cannot be used on a Class A network or any network except privately. We also have a Class B private exchange, which is 172.16.0.0 through 172.31.255.255, and Class C, which is 192.168.0.0 through the 255.255. This one you might have seen the most. This one I'm guessing you've seen the least. This one's probably the second most common, the 10 dot. So if you have an internal network at your home, you might have your address on your computer right now, for instance, if it's not connected directly to the network, if it's connected to a router, might be something like this, or like this, or even like this, all right? That's because these are each private addresses. It's important that you commit these to memory as well, because these will appear on the exam. And remember, the important thing with a private IP address, as I mentioned right here, is they're not routable, and I don't need a lease to use them. So when tasked with subnetting a network, you need to understand how to calculate how many hosts and how many networks are available. If we want to determine the number of hosts that are available, we apply this formula, 2 to the x minus 2. And this is where x equals the number of node bits. And that's after we break it down from decimal to binary. Now, the reason for the minus 2 here is because, again, we cannot use a .0.0.0 address or a .255.255.255 address, which would mean all zeros or all ones in the subnet. And so we need to make sure, rather in the bit, right, when it's broken down. And so we need to make sure that this is the case. We also need to know the number of networks, and to do that, we're going to do 2 to the y minus 2, where y equals the number of network bits. So let's take a look at this. If we have the IP address 162.85.120.27, and we have a subnet mask of 255.255.255.0, by the way, we can look at this and we automatically know that 162.85.120.27, this looks like a Class B IP address. And the 255.255.255 is actually our default class C subnet. So this is not the default that we're working with here. So we need to figure out some information here. So let's break it down into bits, and I'm going to do that here, and if you wanted to check my math, you could. Now the number of network bits is right here, the Y, and the number of node bits is right here, the X. So if we pop this into our equation, the number of possible hosts we have is 254, and the number of possible networks is over 16 million. If we go back to that table we saw a few slides ago, we'd see then that that's why we have a default for Class B and Class C networks, is we can see how many networks are possible and how many hosts are possible. Now, why would I want to know this? Well, let's say that I have to divide up my network, and I want to have a certain number of networks and a certain number of hosts. Well, if I only need 5 networks, but I need 30,000 hosts, I'm going to be in major trouble here, because now I have to divide this up so much, I'm wasting a lot of networks, and I don't have enough hosts. So we want to determine how we can do this to reduce the amount of waste. And we're going to talk about that in just a bit. Going back to something called a default gateway for a second. For any device that wants to connect to the internet has to go through what's called a default gateway. This is not a physical device. This is set by our IP address settings. It is basically the IP address of the device, which is usually the router or the border router that's connected directly to the internet. If, for instance, we had other routers in here, this is going to be the gateway. And so 3 things need to be configured on any device that wants to connect to the internet. We've talked about it. We need to have an IP address, a subnet mask, and this is the new one, a default gateway. So this is the device that's used when I want to communicate with the internet. And it's not used when communicating with devices on the same subnet. This is why it's called a gateway. Think about it as your gateway out to the network. Most often, and more often than not, as I mentioned, this is going to be the router. So if you have at home, for instance, a router that's 192.168.0.1, that is also your default gateway. And if you went in and did an IP config all, something we'll take a look at later, in command prompt, you'd be able to see then your default gateway is this address. Basically, it means, hey, I don't know, I want to get up to the internet. I don't know how to get to Google. I'm going to ask my default gateway. The default gateway then takes care of everything else, and then the information comes back, and it sends it out to you again. Now, there are a couple different ways of implementing custom IP addresses. We previously described how we could use custom subnets, and with that method, a custom subnet mask and an IP address is what we call ANDed, if you recall. And together they allow the node to see the local network as part of its larger network. Now, each customized subnet is configured with its own default gateway, allowing the subnets to be able to communicate with each other. Now, another method of doing this is called VLSM, or Variable Length Subnet Mask. And by using this, we're going to assign each subnet its own separate customized subnet mask that varies. Now, the VLSM method allows for a more efficient allocation of IP addresses with minimal address waste, which I was just talking about. So, for example, let's take a situation in which a network administrator wants to have 3 networks, and I have a Class C space. Now, just so you know, some of this is very outdated, and we're not going to see it used a lot of the time. That being said, Network Plus really wants you to know about it, so we're going to cover it. So, I know I need to have 3 different networks or subnetworks. And I know on the first network, I want to have 4 hosts. On the second network, I want to have 11 hosts. And on the third network, I want to have 27 hosts. Now, in order to accomplish this, I could use the subnet mask 255.255.255.20.224. And for each of these subnets, if I was to add this out, right, 1, 2, 3, 4, 5, 6, 7, 8, that's 255, 1, 2, 3, 4, 5, 6, 7, 8. That's 255, 1, 2, 3, 4, 5, 6, 7, 8. That's 255. Let's write 224 in bits. All right, let's go through our calculation again here. I'm just going to do this because it never hurts to do this a couple times. So let's write all of these out. Great. All right, we have 1, 2, 4, 8, 16, 32, 64, 128. Now we remember that subnet masks have to have continuous ones. So that's 128. 128 plus 64 is 192, plus 32 is 224. So then if we broke this down into bits, this is what it's going to look like. Okay? So let's write that out here. And if we do our calculation, we know we need to have how many hosts? Well, we need 4. So let's do our calculation. 2 to the 1, 2, 3, 4, 5 power. Right? We're going to figure out how many hosts. That equals, we already know, is 32. Minus 2 means that we can have up to 30 hosts on this subnet. So I'm wasting, in effect, 26 addresses on this subnet, 19 on this one, and 3 on this one. I'm not really doing a good job because I've had to apply the same subnet mask to every single IP address. And in doing so, I'm wasting a lot of my possible addresses. Now, if I used VLSM instead, I'm just going to erase all this. I could do 255.255.248.240 and .224. Now remember, 248, if we wrote that out, I'm just going to really quickly. All right, and you can double check my math here. If we do 248, that is going to be 1, 1, 1, 1, 1, 0, 0, 0. All right, and then if we do our calculation, 2 to the 3, because we have 3 host bits, what does that equal? 8 minus 2. Well, now we have a possibility of 6 hosts. So what is our waste? 2, because 6 minus 4 equals 2. A lot better, right? If we do the same thing with the next one, and you were to do the same thing I just did, that would look 1, 1, 1, 1, 0, 0, 0, 0. We did the calculation. Again, 2 to the 4, because now we have 4 bits, minus 2, which equals 16 minus 2, which equals 14. So now I'm only wasting 3 bits, because 14 minus 11 equals 3. And finally, 224 is the same. Remember, that was 30 bits, or 30 hosts rather. 30 minus 27 is 3. So doing this variable, we are a variable subnet mask, we're no longer wasting as many host addresses. So by utilizing this, we're going to appropriately plan and implement a scheme, and it allows us to use our space much more effectively. Of course, the negative aspect of this is it's a lot more harder to scale, and if I want to add nodes to these customized networks, I might have to go around and change all of the subnet masks as well. Now, CIDR, which is CIDR, which stands for classless inter-domain routing, is also commonly called supernetting or classless routing. It's another method of addressing that uses the VLSM, but in a different way as at the 32-bit word. So the notation is much easier to read because it combines the IP address with this dash after it. For instance, the number is what denotes the amount of ones in the subnet mask from left to right. So if we look at this notation right here, we have 192.168.13.0/23. Well, the 23 means there are 23 ones from left to right in the subnet mask. Okay, and now if we were to convert that, this allows for a possible amount of host addresses, 2 to the 9th minus 2, which equals 510 addresses. So this allows for more than one class-full network to be represented by a single set. Basically, we can now break it up further into smaller subnetworks. If we look at 3 of the most easily recognizable ones, I'm just going to erase this so we can get a better look here. The /8, the /16, and the /24. We can see that these translate basically over to the basic Class A, Class B, and Class C networks, right? Because /8, Class A, that means it's 1, 2, 3, 4, 5, 6, 7, 8, dot 0, dot 0, dot 0, which would mean 255, dot 0, dot 0, dot 0, which is our default subnet mask for Class A. Because, again, this is my network ID is the first octet, and the node ID are the last ones. And you can see that that would fall out for the next ones as well. So because of the ease by which it is we can subnet networks this way, because of readability and efficiency, CIDR notation has become extremely popular and widely adopted. Most of the internet, in fact, has become classless address space because of this, meaning that we don't really use classes, and when we get to IPv6, we're not going to see it at all. Now, again, this is very complex. The important thing I just want you to remember on this whole thing is that if you see this dash after an address here, you know exactly what the subnet mask is, and then you can backwards engineer or forward engineer the IP address or the network ID or node ID. So just to review some of the points that we covered here, we started by outlining the IPv4 addressing scheme. We looked at the 5 classes. The 3 I really want you to be aware of are A, B, and C. Remember, A is anything in the first octet that's 1 through 127. With Class B, we're looking at anything from 128 to 191. And with Class C, we're looking at anything from 192 to 223. Anything else here, we're really looking at experimental and stuff that we don't really need. Remember these ranges for that first octet. It's easy then to determine what class we're looking at. Okay, so we also described the reserved or restricted IP addresses. For instance, we can't have anything with a .0.0.0 or with a 255.255.255 because these are our multicast addresses. And we also can't have anything with 127.0.0.1 ever or 1.1.1.1 because these are both, one's the local host, one is the whois address. We then looked at private IP addresses. Remember, we had 3 different ones each for each class. For Class A, it was anything 10.x.x.x. With Class B, it was 172.16.x.x through 172.31.x.x. And the one you're probably most familiar with is the Class C, which is 192.168.x.x. Remember that you can see what class they're in by looking at this. And most importantly, Class A private IP address can allow for the most networks, the most nodes, the fewest networks. Class C is going to be the complete opposite. I'm going to allow for the most nodes, the most networks rather, but the fewest nodes, okay? And again, remember these ranges because they will come up. What does make a private IP address? It is not routed past a router onto the public network, okay? We also talked about the IPv4 formulas, which allow us to determine how many hosts or how many networks are allowed on a network. And that is where the X or the Y equals the number of host or network bits. We defined the default gateway, which is what I need to get out to the WAN. It's what a local device, a node on the local area network, needs to go to this default gateway. And finally, we define the two custom IP address schemes, the one which allows me for variable subnetting, and the other, CIDR, which allows me to use a slash and then put a number, that number representing the number of network bits in the subnet mask. Right? So the most popular, of course, 24 would be for a class C, 16 would be for a class B, and 8 would be for a class A, because if we had a /8, that would mean the subnet mask is 255.0.0.0. Network routing and IP addressing, data delivery techniques, and IPv6. Now, we've talked a lot about IP addressing when it comes to IPv4, or the Internet Protocol version 4. But fairly recently, IPv6, or IP or Internet Protocol version 6, was released and has now begun to be implemented across the world in every network situation. So in this module, we're going to discuss the core concepts that are involved with IPv6 addressing and some of the data delivery techniques as well. So at the completion of this module, we're going to have a complete understanding of the properties of IP version 6 or IPv6. And we're going to be able to differentiate between IPv6 and IPv4, which is the one we've been talking about up until this point. As a reminder, IPv4 is that IP address that is 32 bits and divided into 4 octets. And we're also going to outline some of the improvements in the mechanisms of IP version 6 and why we needed to have another version of IP addressing. We're also going to cover the different data delivery techniques, as well as what a connection is, different connection modes, and we touched on these briefly, such as connection-oriented and connection-less, and their transmit types. Finally, we're going to go further into data flow, or flow control, which we've talked about a bit, and we've mentioned a bit, buffering, and data windows. These are all techniques that allow data to be sent over a network in varying ways. And finally, also, we're going to talk about error detection methods. That way we know when data arrives on the other end, we can double check it to make sure it is the data that was in fact sent. So, in the last module, we learned about the IPv4 addressing scheme, and we talked about some aspects of how it's implemented. Now, IPv6 is the successor to IPv4, and it offers a lot of benefits over its predecessor. The first major improvement that came with this new version is that there's been an exponential increase in the number of possible addresses that are available. Several other features were added to this addressing scheme as well, such as security, improved composition for what are called unicast addresses, header simplification and how they're sent, and hierarchical addressing for what some would suggest is easier routing. And there's also support for what we call time-sensitive traffic, or traffic that needs to be received in a certain amount of time, such as voice over IP in gaming. And we're going to look at all of this shortly. So the IPv6 addressing scheme uses a 128-bit binary address. This is different, of course, from IP version 4, which again uses a 32-bit address. So this means, therefore, that there are 2 to 128 power possible addresses, as opposed to 2 to the 32 power with IP address 4. And this means, therefore, that there are around 340 undecillion, I'm going to write that out, so that's a word that you probably haven't seen a lot, undecillion addresses. And to put that another way, it's enough for 1 trillion people to each have 1 trillion addresses. Or for an IP address for every single grain of sand on the earth times 1 trillion Earths, give or take a bit. So if the 128-bit address were written out in binary, it would be 128 ones and zeros, because that is binary. And even in decimal form, that's pretty hard to read and keep track of. So because of this, we use what's called hexadecimal as the format in which IPv6 is written. And if you imagine from the name, binary is a base 2 system, meaning that we take everything to the power of 2. So we have the ones place, and then we have the 2 place, and then we have the 4 place, and so on and so forth. With decimal, which is a base 10 system, we have the ones place, the tens place, the hundreds place, which is 10 times 10, the thousands place, and so on. With hexadecimal, though, we're looking at a base 16. So every single digit has a possible 16 different options. So we'd have a ones place, which we always start with a ones place, and then a 16s place, and then so on and so forth. Now, the way we do this is that every digit, as opposed to decimal, where we have 0 to 9 options for every digit, and binary, where you have either 0 or 1, with hexadecimal, we can either have 0 to 9 or A through F. If we add this up, we have 10 options here, 0 through 9, and then A through F, we have 6. So a hexadecimal number is going to be a combination of anywhere from 0 to F. A would be 10, B would be 11, C would be 12, and so on and so forth. So when you see this written out, that's what that means, okay? Now, the address is broken up into 8 groups of 4 hexadecimal digits. And these are separated by colons. Now, I'm going to show you this in just a second, but there are also a couple of rules when we come to readability. So the first rule is that, let's say this is our hexadecimal IPv6 address. You notice, first of all, 1, 2, 3, 4, 5, 6, 7, 8, right? There are 8 groups of 4 hexadecimal digits each. And, of course, each one of these digits has 16 possible values. Okay, so let's look at 2 rules. And these are also not only readability rules, but what we call truncation rules, meaning this is how we can shorten an IPv6 address, since they can get quite long. The first rule is that any leading zeros can be removed. So if we imagine any leading zeros, I'm going to circle them right there, right here, right here, and if we wanted, we could even consider these leading zeros. And therefore, if we rewrite this out below, you'll see we're going to remove all the leading zeros. And that allows us to shorten our address. Now, we could also, if I was just going to take this one step further, I could also shorten these zeros if I so wished, and just leave 1 0 there. Now, no matter how you write out the address, the rules are put in place in a way that you can always go back to the main address. And so you don't have to worry about, you can sort of pick and choose. There are best practices, but the computer is always going to be able to figure it out, okay? Now, the second rule is that successive zeros, or successive sets of zeros, can be removed, but they can only be removed once. So, any sets of successive zeros, and here we see 1 set, or 2 sets rather, of successive zeros, can be removed and replaced with a double colon. Now, the reason we can only apply that once is, let's say these zeros we had another set of zeros over here, and we truncated those. We can add up, right? We know there's 1, 2, 3, 4, 5, 6 sets here. So we know that this represents 2 sets of missing zeros. But for instance, if we had, 2 other sets here and we removed those, we might not know whether it's supposed to be 1 set and 3 sets or 2 sets and 2 sets and so on and so forth. So we can only do this once, because when we add them back, there's no way to know, where that would sort of lie. Now, I'm just going to erase this for a second, because we can even truncate this more. We've applied this rule. So this applies this rule. This one has applied this rule. But we can apply both rules, right? So we can remove these leading zeros here and actually write this out as 2001 D8 88 A3 double colon, which means that those are successive zeros, 3E 70 7334. Now, I just want to sort of follow up and explain, write out what I was just talking about with why we can't have more than 2 sets of successive zeros, okay? Let's say that we have zeros here as well, okay? So I'm going to rewrite this out. We have 0, 0, 0, 0, colon, 0, 0, 0, 0, colon, 0, 8, A3, colon, 0, 0, 0, 0, 0, 0, 0, 0, 8C, 3E, 0, 0, 7, 0, 7334. Okay, let's first apply our first rule, which is that leading zeros can be removed. So we rewrite this, and we're going to get this. Okay, now we're allowed to remove 1 set of successive zeros only, which is the second rule. Okay, but let's do it twice and just see what happens. So let's say we have a double colon here, 8A3, and then we have another double colon, 8C3E, 70 7334. Now, let's say we want to expand this back out to its full version. Well, if we have these successive zeros here, we don't know if this would be written out 0, 0, 0, 0, dot 8A3, because from what we're seeing here, theoretically, we could put 3 zeros here and 1 0 here, right? Or we could do it the other way around. So the reason we can only do it once is because then mathematically we know exactly how many belong when we do that, all right? So hopefully that helps clarify the reason behind the successive zeros being removed. All right, now what this also means is that if you remember a loopback address, an IPv4, the loopback was 127.0.0.1. Well, we also have a loopback when it comes to IPv6. That's all these zeros to 1. But because we can apply all of these rules, we can truncate this to simply this. All right? So this is important to remember. These rules are important to remember. The other thing I want you to remember is that hexadecimal is 0 to 9, A to F. So they might show you something and say which of these is not a valid IP. If it has a letter, say a G or an H, then you know it's not going to be valid. And here we can check. Here's a D, that's good. Here's an A, that's good. C, good. E, good. So this is good to go, right? If we had an H or a G or an X, for instance, then we would know that the IPv6 was incorrect because there's no hexadecimal symbol X. So the IPv4 addressing method is really different from IPv6 addressing, and it's comparatively it's lacking in many areas. First, as we've talked about, we're using a 32-bit binary address in IPv4 versus a 128-bit binary address in IPv6. And of course, this greatly increases the number of possible IP addresses. I think around February of 2011, all of these IP addresses had been leased. And so there weren't any addresses left. I think we had something like 4.8, 4.7 billion, right? And all those were gone. And so we were depleted of all of our IP addresses. So this is why we had to transition to IPv6, because now we have that undecillion address, which again is if there were a trillion people, they could each have a trillion addresses. Now, another major difference between these two is that IPv4 utilized the classless interdomain routing notation, if you remember, which had that slash and then a number of bits. Well, in IPv6, this isn't necessary, and IPv6 actually has a subnet size of 2 to the 64th power. Now, if you remember that the total IPv6 is 2 to the 128, then what you realize is that the first half of the IPv6 address, so if we were to write one out again, let's say 208A, A364, 92BF, 1000, right? Okay, so then we're going to have 4 more on this side. The first 4, which again is the first 64 bits, that's the subnet. So now we've integrated the subnet into the IPv6 address, which is the benefit. Now we don't have to sort of have this extra written out CIDR thing. So it's been standardized. It's always 2 to the 64. We always know the subnet or the network node is on the first section and the node ID is on the second section, the other 2 to the 64. So this really helps simplify things to a great extent. Now, obviously, one of the issues is we're going to underuse a lot of the addresses. We're going to underuse many of our addresses because we're never going to have to really use this many subnets, or perhaps not even that many networks, right? But there are so many other benefits that it has with routing and efficiency and simplified management that it sort of makes up for it. And so that's why we're going to make that sacrifice. Now, in terms of domain name systems, with DNS, when we talked about, for instance, a google.com going over to, say, whatever that IP address is, I'm making this one up, obviously. It's not a real one because we're in a private IP. But this was called an A record, right? So a server would have something, or a DNS server would have something called an A record, and that A record had this information in it. All right. Now, when we're dealing with IPv6, we're utilizing a quad A record for this mapping. Now, it can also use the same A record, but this quad A record can be used as well. So if you see 4 A's, what we call a 4A record or a quad A record, then you know we're using IPv6. It's one of the differences. And again, these are the records that are used to map IP addresses to what are called fully qualified domain names. Now, while comparing these two schemes also, IPSEC, which stands for IP security, is another aspect that we need to consider. In IPv4, IPSEC is optional. It's widely used for secure traffic over IPv4 communications. But when we dealt with IPv6, IPSEC was designed for it. And so it's required from the original specification, and therefore all communications that are working over IPv6 are automatically falling under IPSEC. So it can be considered in some ways optional, I guess, but it is required use from the get-go because it was built into IPv6. Now, the IPv6 scheme can also handle a much larger packet size. The packet size for IPv4 is 65,535 octets payload. When we get to IPv6, we're dealing with a 4.295 billion octets of payload. So obviously these are a lot bigger. These are what we call jumbograms. As a result, you can imagine that if we want to deal with IPv4 and we're on an IPv6 network, we're going to have to make up for this. Now, if you recall, when we were talking about Ethernet, we also were talking about the header sizes and all the information that was contained in there. Well, the header size for IPv4 and IPv6 is also very different, which actually makes these two protocols not compatible with each other. So IPv6 is not compatible with IPv4. And so the way we're going to communicate with an IPv6 over an IPv4 network, if we need to, is by tunneling the packets. In other words, we take an IPv6 packet, and we literally wrap it around, or we wrap around it an IPv4 packet. And so we tunnel the IPv6 packet inside of the IPv4. Now, this allows it to communicate, but this is also what we call a dual stack. In some cases, we can have what's called a dual stack, where we have an IPv4 and an IPv6, and so we can choose which one to go over, and then this tunneling is not going to be necessary. Now, we don't really want to tunnel because obviously the payloads are so much different in size that it's going to cause all sorts of trouble. So what we'll try to do is create this dual stack in which we have one network and the other, and they're both operating sort of side by side. If we can't do that, then we have to use tunneling in order to move the IPv6 data over an IPv4 network, which might be necessary even if the IPv6 data is traveling through an IPv4 network. All right, so we've compared these. Let's talk about some of the improvements that IPv4 did not have that IPv6 does. Starting with some security and privacy measures. If privacy extensions are enabled with IPv6, then we have something called an ephemeral address, which is created. And this is used as a temporary and random address that's used to communicate with external devices, but the external device doesn't know the true address of the internal device. And so this improves the privacy and security for the user. And this is what we call a privacy extension. And it does have to be enabled from sort of a router point of view. Now, another improvement is a better composition of what we call the unicast address. What this means is that IPv6 uses a unicast addressing structure to replace the classful addresses of IPv4. This offers a lot more flexibility and efficiency with addressing, and depending on the category of the unicast address used, there are different functions for each, meaning that there are different types of addresses that are used, and that way the computer automatically knows what the function is. The first is called a global address, which is sort of like the public or routable addresses in IPv4. If you recall, most addresses could be routed. Those are what we call global addresses. We also have site local addresses, which are essentially like the private addresses or non-routable addresses that are not routable to external networks. If you recall, these were, for instance, the 10.0.0.0 through 10.255.255.255, and then the 172.16 through 32, and then the 192.168. Those are the private addresses. Well, in IPv6, we call them site local addresses. We also have something called link local addresses, which are basically comparable to a PPPoE addresses in IPv4, and we're going to talk more about what those mean in just a little bit later. But just to give you a little heads up, and we have talked about it with A+, if you were around for that. This is automatic private IP addressing. And we need, because every device needs an automatic IP address, if it's not given one by a server, then it's going to give itself one, what we call a PPPoE address. And so in IPv6, these are called link local addresses. And finally, there are IPv6 transitional addresses, which are basically going to be used in the time being until we phase out of IPv4. These are used to route IPv6 traffic across IPv4 networks through tunneling, much like I've just described in the previous section. Now, a mechanism built into IPv6 addresses is a field located in the IP header that's designed to guarantee network resources be allocated to services that need time-sensitive data, such as voice over IP, right? We need that is time-sensitive because I'm talking and I want the person to hear almost as soon as I talk. And so this time-sensitive stuff is built into IPv6, one of the reasons that we use it. Now, another improvement with this scheme, IPv6, is called hierarchical addressing. This eliminates the random allocation of addresses, so connectivity devices such as top-level routers are assigned a top-level block of IPv6 addresses, and then segments are added to those with blocks of addresses that are assigned at that level. So basically, it looks like a hierarchy from an IPv6 standpoint. You remember we looked at this sort of topology earlier. Now, IPv6 scheme also has a much simplified header, and it's going to make addressing a lot easier to read. This improves the speed packet routing on an individual packet basis. So obviously, if we're going to simplify how information can get read, it's going to simplify how routing can occur. Now, data in transit is susceptible to a variety of things that could cause it to be delayed, lost, or damaged. And these things can occur on the transmit side and quite commonly on the receiving side as well. So the method the data is delivered makes a huge difference in whether the data is going to arrive at the destination correctly and efficiently. So depending on the method of delivery, there can be error detection, which would mean we detect that there are errors, and error correction, which means we not only detect but we fix the errors when these recovery mechanisms are used. Now, an important aspect of the data delivery begins with the actual connection itself. So depending on the type of connection service used is going to give us an idea of what sort of delivery options are available. So, a connection in terms of networks is the logical joining of two network devices through a specified medium that is established and maintained for a period of time during which the session exists. In other words, the connection is what allows data to be transferred between, say, my computer and a server computer. Now, in networking and specifically in IP networks, there will be connection services that attempt to provide data integrity and reliability. Now, there are generally three types of connection services that we see when we discuss certain protocols. And we've talked about these in some way, shape, or form, but it doesn't hurt to sort of go over them in a little more specific detail. The first is an acknowledged connectionless service. In these, the connection isn't created. However, when data is received by the destination, there is a acknowledgement of receipt. So website communications use this type of service. A great metaphor to think about this would be, for instance, a delivery receipt with regular mail. So it's not certified. We're not going to get a signature, but what we do is we get a receipt that it has been delivered. Now, with unacknowledged connectionless services, there's no acknowledgement sent unless the application itself does this. This could also be considered simplex communications, which we'll talk about in just a second. So this is just like regular mail. We send it, we drop in the mail, there is no acknowledgement, okay? Acknowledged at least has an acknowledged that data has been sent, but there is no connection made, right? There is no established session made between the receiver and the sender. Finally, we have connection-oriented services. And by the way, when we talked about these connectionlesses, you recall this is like UDP, which is connectionless, and IP. Here, connection-oriented, we're looking at TCP. Now, these are where error detection and correction are available, as well as some flow controller packet sequencing. In other words, this would be like certified mail. Now, there are also three types of connection modes that we're typically going to use. There's simplex, half duplex, and full duplex. With simplex, this is one-way communication only. This is sort of similar to FM radio broadcast, right? You turn on your radio, you tune in, and you can receive, but you cannot send data. Now, we also have half duplex. This is two-way communication, but only one at a time. This is like a pair of regular walkie-talkies. Only one device can transmit at any one time, which is why we have to use those code words, right? Over, 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 and out. So this is like a walkie-talkie. Finally, we have full duplex, which is two-way and both ways simultaneously. This is similar to the telephone, in which we can talk and listen at the same time. In some ways, we have trouble understanding each other as a result of it. Now, in networking, devices are designed to receive and transmit data at different speeds, and with different sizes of packets as well. So certain devices are not going to be able to handle as much data as others at one point or another. We talked about this briefly with MTUs and MTU black holes. So flow control is the managing of amounts of data and the rate at which the data is being transmitted over a network connection. Flow control is necessary to help prevent devices from being overflowed with data. Now, some devices, when there's too much data is received, are going to potentially shut down to prevent certain attacks, or simply are going to drop packets that are too large because they're going to cause delays. On the other side of the scale, if too little data is being received by the device, it may just be sitting idly by waiting for the remaining packets. In this case, it's simply a matter of efficiency. So there are two main types of flow control that are covered on the exam: buffering and data windows. Buffering is a flow control technique where a portion of the memory, either physical or logical via software, is used to temporarily store data as it's being received in order to regulate the amount of data that's being processed. Buffering may be used to maintain data consistency as well as minimize overloading. Now, RAM uses a type of buffer when data is being read from its cache, right? So remember we talked about RAM, and that was what we called cache. Now, with buffering, there is a potential concern because what if the buffer becomes full? Well, when receiving node's buffer reaches a certain capacity, it actually transmits a squelch signal. I'm going to write that out just not only because it's a great word, that says, stop transmission or slow down your transmission so I can catch up. Now, a common place we're going to see this type of flow control is when we're streaming movies. You might have seen buffering when you're using movies, for instance, on YouTube or on Netflix or any of these sites. The idea is, if there's a problem with our communication, we have a little buffer of data, so that way we're not going to see a dip in quality of the film. Now, another type of flow control is called data windows. The data window refers to the amount of data being sent, and it can either be a fixed amount or it can vary. And these are fixed length windows or sliding windows rather. If you think about the window, and I put the data inside of it, we can either have a window that is a specific length, like this, or a window that can possibly get smaller based on the data. And that's what fixed length and sliding windows are. So to go a little more in depth into these, with fixed length windows, the size of the packet of the data being sent is determined by the sender, and the rate of transmission is determined by the receiver. So the size is typically going to be pretty small, and overall this is going to be fairly efficient. The other thing to remember is that the packet size is always going to remain the same. It's never going to change. So if I need to send 10 packets, they're all going to be exactly the same size, or as much as I can draw them as such, and so on and so forth. Now, with a sliding window method, it's a bit different. The sender begins to transmit data typically with a small number of packets, and with each transmission, it waits for an acknowledgement or ACK packet receipt. Now, with each receipt, this contains the current maximum threshold that can be reached, and then the transmitter is going to begin increasing the number of packets by a specified amount. In other words, it's going to start sliding that window from here over. Now it's going to continue to increase this over and over and over until we reach a maximum potential. At this point, we're going to start getting some congestion, and so the receiver is going to send another ACK saying, listen, you need to slow down now, and this is a good rate. This method is really going to allow for minimal data traffic congestion and a lot of throughput. And depending on the amount of traffic, the size of the window can really vary dramatically. And so this really gives us a lot more flexibility. If you imagine if I have a home that has a whole bunch of regular windows, I'm going to want sliding windows. Now, if I have a home with all these similar windows, everything built the same, then I can use a fixed length window. But this one's going to give me a lot more flexibility. Now, error detection and correction is an important aspect of how we know our information arrived at the destination unhindered and unaltered. One method achieves this by attaching supplemental information at the end of the footer that pertains to its contents, and the receiving station is going to look at that data and compare it to the data it received. If the data matches, it's going to consider it error-free. If not, the data is going to be requested to be retransmitted. Now, when an additional correctional component is added that allows the data to be rebuilt in the event of an error, this is going to become an EDAC, or error detection and correction. Now, parity check is a process where an extra bit is added to every word of data. And the receiving station can look for the bit on this word-by-word basis. And remember, we're talking about words. We're not talking about language. We're talking about words as far as data goes. And so it can look at these, and therefore it can determine any errors that are built in. Because parity adds this extra bit to every word, this method takes a little bit of overhead. So it does add not only extra resources, but some more data in there. Now, with something called CRC, or cyclic redundancy check, a code is added to every block of data through a mathematical operation, which is also referred to as hashing. Now, this code is added to the end of the block, and then it's transmitted. When the receiving station applies this hashing method, this mathematical operation, to the code, then it should get the same data. And if it doesn't, then it knows there's a problem, and it can request it to be resent. Like parity, CRC is also going to add a certain amount of overhead because it takes data and calculation time. All right, so now just to review some of the topics we talked about. We talked about the IPv6 addressing scheme. Specifically, we talked about it's a hexadecimal, 128 bits, divided into 8 sections. We also compared and contrasted IP version 6 with IPv4. We saw that IPv6, for instance, has IPSEC built in and has a whole bunch of other improvements and mechanisms, such as data delivery, time sensitive, and so on and so forth. The important thing I really want you to know about IPv6 is that it does not require a subnet, and we need to recall all of the truncation or readability rules, which include removing leading zeros and combining successive sets of zeros, but only once. We also explained the different data delivery techniques, and we defined a connection, the different connection modes, whether they're acknowledged connectionless, simply unacknowledged connectionless, or connection-oriented. We also looked at the different transmit types, including simplex, which is one-way, half duplex, which is like our walkie-talkie, and full duplex, which in effect doubles our bandwidth. We also explained flow control, buffering, and data windows. We use buffering a lot when we're talking about videos. In data windows, remember we talked about the fixed and sliding windows. Finally, we outlined error detection methods, including parity, which adds an extra bit to every word, and CRC, or cyclical redundancy check, which uses hashing, a mathematical operation, so that we can ensure the data that was received was also the data that was sent.
Welcome to Module 6, Lesson 4a, IPv6 Concepts. Now, we actually covered IPv6 earlier, however, as per usual, some new ideas have been added to the syllabus. So what I'll do here is I'll review some areas that you've already covered with Josh, just with my own take, and then we'll go into the new stuff. So IPv6 addressing, address types. New is a neighbor discovery protocol, which is part of IPv6 built in. The EUI64 addressing is new. Tunneling types is new. So IPv4, which is obviously the precursor to IPv6, created a long time before we had home computers. The computers were pretty expensive and big, probably the size of any room in your house. So nobody foresaw that people would be using home computers, just like when the telephone was created. I think one of the first comments was, why would I need to phone anyone? So there we go. So it was just, the scheme was designed just to cater for commercial enterprises only, so we didn't think we were going to run out. Lack of a simple auto configuration mechanism. So eventually we had DHCP was created, which works well. Obviously it's got some drawbacks. IPv4 has no security built in. Again, nobody realised that well, there was no such thing as hackers, obviously, when IP was brought out, because it hadn't been invented yet, so nobody thought that we needed to have it built in. IPv4 is hard to use with mobile devices, especially when we're using the cellular networks. IPv4 needs massive routing tables required over the internet. Internet service providers have huge tables for routing all the IP traffic. There's only around 4 million addresses available. We actually ran out of IP4 addresses some time ago, and around 50% of the traffic going over the internet at the moment is IPv6, which is why we need to know about it. So IPv6, there's that many addresses. I don't even know what the numbering system is called for calling out that many, but for every person alive, there's many millions of available addresses. Now, NAT can be used with IPv6, and you'll read some documents about NAT-PT. Not really used. There's no need to NAT because there's just no shortage of addresses, really. Security is built into one of the fields in the IPv6 packet. We have address auto configuration, which is a major part of IPv6. And it's plug and play as well. So things like when you enable IPv6 on an interface with most devices now, it actually self-configures an IPv6 address. We do not have broadcast on IPv6. We'll come to that later. It's built to work plug and play with mobile devices, again, which is handy. So the addresses, there's several RFCs. One of the main ones is 1884, if you want to read it. It's 128 bits. Each of these bits is divided into 8 groups of 16 bits, and then each of those bits is separated by a colon, which is a dot on top of a dot. Hex numbering is used because it's just a lot easier to write out that many bits using hex than it is in binary. It would take forever. The addresses, when you're typing them out on interfaces, is not case sensitive, so you could use caps lock or lowercase and the address will work fine and be accepted. Here is an example of an IPv6, and you can see, if we just come over here, so 8 groups of 16 bits, which we'll go into a minute, divided here by the colon, and another 16 bits, 16, 16, 16, 16, 16, and so on. So if you wrote the address out in binary just for the, don't know why I should have said D here, sorry, EEDE, but if you change the hexadecimal here, so this is the hex, into the binary value, it's 1 in the, if I go 1, 2, I know you already know how binary works, 4, 8, so 1 in the 8 column, 1 in the 4, 1 in the 2, so 8 plus 4 is 12, 8, 9, 10, 11, 12, 13, 14, so the E is number 14 here, 14 here in hex. Now we've got the D, so we've got 1 plus 4 plus 8, so 8, 9, 10, 11, 12, 13, so D is 13, and then we're back to another 14, 16 bits, 2 bytes in total, so 4 bits, 8, and then another 8, 16 bits, so that's 2 bytes. We can compress the address, so you can remove the leading zeros. Leading zeros are numbers that appear beforehand, so this is a leading zero, this is a trailing 0, so we can't remove these because they've got numbers prior just before. So if we get rid of the leading zeros, for example here, 0, 0, 0, 1 becomes a 1, 0, 7, 8, 9 becomes 7, 8, 9, and this is to save space and for when we're writing out the addresses. 0 ABC becomes ABC, and you can get rid of the trailing zeros here and just have 1 0. So this address is legal to write that out. You could possibly have questions in the exam asking you to choose the correct compressed address. You can use a double colon once to represent consecutive zeros. So here we go, we've got all these consecutive zeros here for some reason. Well, we've got rid of them just by having the double colon here, and we've got a double colon here between the 1, 2, 3, 4. So what we've done is just compress all of these zeros, and we've done it again here, and then we could have put it in the second set of zeros, but just to save space we've got rid of all these zeros here. So practice this, work out your own numbers because this is a typical exam type question. Main IPv6 address types: global unicast, unique local, linked local, and multicast. You'll note we don't have broadcast, that isn't a legal address. And we also have anycast, which I'm not sure if I mentioned here. So the global unicast, this is allocated by the ISP, and then you will get a mask associated, whatever the mask may be. These are routable on the internet, so you can send them out of your company, and they're legal, they're legally recognised. The numbers range from 2000 to 3 FFF in the first 16 bits. Current allocation, there's trillions of these addresses, so the current allocation is come in from 2001. This will last quite some time, obviously. There's a 48-bit provider prefix, and if you check the images of the address packet, you'll see the 48-bit. There's a subnet ID. You can subnet inside the organisation if you wish. Subnetting IPv6 is a topic, but it's not in the CompTIA. It is in the Cisco CCNA, and then the rest is the host portion of the address. Now, I'm sure most equipment can actually do this, but Cisco routers can self-generate this part here. So what you would do is, if you configure an interface, you would basically configure whatever the address is, .b, whatever, and then the host portion here, the interface would self-configure. So I've issued, this is on my Windows computer by the looks of it. I've just issued an IP config all /all, and I've seen the IPv6 address that's been allocated here. I think Windows self-allocates these addresses also. Link local address. The prefix for link local addresses are FE80. These are only valid between the link between two IPv6 interfaces. So you've got an internal router, and say for example an Ethernet connection here. Then these addresses will be valid, and these two IPv6 routers can communicate with one another using this link local address. What it can't do is this address in here, it can't be used to reach another device out here. Now if you've got another device, the link local addresses of these two facing interfaces, so for example fast Ethernet here, fast Ethernet here, they will communicate between one another here. Automatically created once IPv6 is enabled. Now these are used for routing protocol communications. IPv6 protocols mentioned in the syllabus, but I don't think, I've left it out for now because looking at all the official guides, there's no questions yet. I will add it later on if that changes though. Traffic isn't forwarded off the local link, certainly not using the link local address. So here's a configuration for a Cisco router. I've enabled IPv6 routing. I've gone to the fast Ethernet interface. All I've done is turned on IPv6 for this interface here, the fast Ethernet 0/0. I've typed end, and then I've said show me this interface. It's down, I haven't connected it to anything, but as we can see, this address, this link local address, has been allocated, self-allocated. This is an important bit here, FFFE, as we'll see in a minute, but basically this is my IPv6 address. I haven't had to write it out manually at all. I've already shown you the Windows one. Unique local, it's an IPv6 version of private IP addresses, so you can use all of these on the inside of your network. You wouldn't be able to route with them onto the internet. Don't think these are used anymore. I think they've actually been depreciated. If you get a question in the exam, here it would be something like this: what prefix is link local addresses taken from? FC00 /7 for your subnet mask. These depreciate site local addresses. So it's site local addresses that have been depreciated, overtaken by link local, a unique local. So you'd use this on the inside of your network if you want to do any internal routing. What you couldn't do is use it out on the internet though. Multicast addresses are still used very much in IPv6. This is the prefix, so write it down and put it into your study cram notes. And multicast replaces address resolution protocol for IPv6. Used for duplicate address detection. So when you first fire up your interface, I'll talk about neighbor discovery in a moment, but I'll say, just to save space, I'll say this is the address. Obviously it would be the IPv6 address. This interface will advertise out this address to the network, this multicast address, saying I want to use this address X, and if any of these interfaces are using that address, so this is using Y, that's using Z, it will come back and say no, you can't use that address. But in this case, my example here, nobody's using it. All routers must join the all hosts multicast group of FF02 and then whatever in the middle, 1, so it'll all be zeros and then 1, and the all routers multicast group. This is how neighbor discovery protocol works, so it must be allocated and listening to these two addresses. And if I issue a show IPv6 interface, fast Ethernet 0/0, you can see that it's joined these two groups up here, the F2 and the F1. EUI64 addressing is the new part in the syllabus. So I've issued a show IP interface. Sorry, I didn't do IPv6 because I want to see what the MAC address is, because this is how EUI64 obtains the EUI64 address. So this is how, or one of the ways you can self-generate an interface. It uses the MAC address. The 48-bit MAC address, obviously we need 128 bits. 48 bits isn't enough to generate this address. But what it does, it takes the MAC address, it inverts the 7th bit and adds FFFE in the center. So right in the middle of the MAC address, it's going to add FFFE. Make sure you take a note of this for the exam. So we've got 0011. I'll cover why it doesn't say 0011 here. And then here's the AA here. And then you can see the FFFE has appeared here. It's inserted it. And then it carries on with the rest of the MAC address, BBCCDD. So BBCCD. So this is how it pads out the address. So there's 2 bits. MAC address plus this, but then it does this other bit here, which is inverting the 7th bit. So just to recap what I've already said, we're looking at this part now, 0011. Well, instead of that now we've got 0211. Alright, so going on to the seventh most significant bit. So this is our sample address here. The first 2 nibbles is 1 byte, so this is 0.0. So a nibble, if we have 1, 2, 3, 4, 5, 6, 7, 8. So 8 bits is 1 byte, which we've covered already. Whoops. 1 byte. 1 byte, 8 bits, but what we can do is kind of subdivide it in the middle here, and we can have a nibble here and a nibble here. Alright, so our first 2 nibbles, 1 byte here, is 0, 0, which would have all the binary bits basically. Pretty easy to work out. So this here, if you write it out with a nice font, is 00000000. So what we need to do is flip the 7th most significant bit. So what we've done is 1, 2, 3, 4, 5, 6, 7, 8. So this is the 7th most significant bit, and what we've done is gone all the way over here to find the 7th bit, and we've flipped it. So whatever it was here in binary, we've flipped it. So 1 flip to 0 flip to be a 1. Now if you wrote that out, this part here, you'd have your 0 would become a 2. That's the 1, 2, 4, 8. 1, 2, 4, 8. Okay, so we've enabled this column here, and our 0 has flipped to a 2. And you can see here 0211, and then this is the MAC address. We've got the FFFE in the middle, and then the rest of the MAC address. This is how you work it out. You might get a question on this, so this is why I brought it to your attention, and you just need to practice a few examples. So what would this address be changed to? If you write it down. Alright, so I've just carried it over to the next slide here. So show IPv6 interface, we've got this address here, and we end up with this global unicast address here. And you can see already we've got the FFFE created here. So, and because it might not show you in other vendors, but you can see here there's a clue. It says EUI, so we know EUI 64's addressing. Well, C2 in decimal is 192, or in binary here 1100. 1100 in hexadecimal is C, and if you've just got a 1 in the two column here, so 1, 2, 4, 8, you can see that's a 2. C in hexadecimal is 12, so we've got 8, 9, 10, 11, 12. So I think we've covered hex earlier. So you swap the 7th bit, so 1, 2, 3, 4, 5, 6, 7. This bit has to be swapped if we're doing EUI 64, and then it becomes a 0. If you work this out, 0, 0, 0, 0, the second part is C0. So here we go, C0, and then it carries on as normal, 0, 0, instead of C2. So I know it's a lot to get your head around. Just practice it, watch this over a few times, and then practice some of your own examples. Applying it, enter your desired subnet, and then add the command, the tag, EUI64. This is how you do it in Cisco. You won't be asked about vendors or how to apply it, I'm sure. I'm just telling you how it works. So I've added this address. I want to say we're using this subnet here, this address, and double colon, so I don't care what goes there, /64, and then I add the tag basically saying you allocate using the MAC address plus the 7th bit rule, which will swap the 7th most significant bit from a 0 to a 1 or 1 to a 0. And here's the command on an actual router. So you have to, you can't just say create the entire address for the routable address. You have to add this tag here. Alright, next is the Neighbor Discovery Protocol, which is a major feature of IPv6. This allows other routers on the link to be discovered. There's a couple of messages you need to be aware of, which is RS, router solicitation, like are any routers on the link. This is the router solicitation message, and it's sent out saying what else is here. The router advertisement is the reply you'll get from the routers, IPv6 routers. RA, yep, I'm here. RA, I'm here. It discovers prefixes, so whatever your prefix is on the network, etc. These routers will say we're using this prefix, and then this will be able to auto allocate an address so it can communicate on the subnet. So this replaces ARP. We don't have ARP working on the IPv6 subnets. Also works with duplicate address detection, which I've already mentioned. The device, the IPv6 device, will say I want to use address X. Are any of you using it? And then there'll be a reply if it is in use. So neighbour solicitation, asking for a neighbour's information. The neighbour advertisement, you advertise yourself out to neighbours. The solicitation, ask for information about local routers. These are the 4 types that you need to know about. Router advertisement, advertise yourself as active. These are the 4 types, so make a note of them. DAD I've already mentioned. The neighbour advertisements are sent to check if your address is unique. This is the address it's sent to, which is the same as the broadcast address, but we're multicasting in IPv6. No reply means your address is available to use. The amount of air seconds should vary from vendor to vendor. I haven't read the RFC actually, but if you really wanted to, you could read it. So you can see the advertisement is going out with this address. Reply if you are this address using the ICMPv6 packet, and then the advertisement here, I am this address, so basically you can't use it. DHCP version 6 is used for IPv6. This is for auto allocation of addresses. Also used with it's used in conjunction with DNS for IPv6. Here's the RFC if you've got some spare time in your hands. Allocates IPv6 information to hosts. Obviously, the IPv6 is the gateway, the DNS server, and other DHCP information. Host can request it with an outgoing router advertisement message. Allocated and requested using UDP. Bear that in mind because some people think it's TCP. It's port 546 and 547. The other subject you need to be aware of now is if you're running IPv6 on your network and then IPv4. Nobody is going to come into work one day and have IPv4 taken off and only running IPv6. You're going to have a transition period where you're running both of these protocols. So what's going to happen is somehow IPv6 host reaches an IPv4 router, and what you're going to have to do is tunnel the IPv6 information inside an IPv4 packet with a header and the trailer running IPv4. There's a few versions. ISOTAP, 6-to-4 tunneling. Dual stack is when you're running both at the same time. There's a static tunnel, I think. Yeah, that's different to GRE. You don't have to know the config, so don't worry about it. Generic routing encapsulation has been around a long time, but you can use that for tunneling. Automatic is another type you can choose from. If you want to study more, I recommend everyone needs to do about 4 hours study into IPv6. This is for interviews, technical jobs, technical interviews, and just to do your day-to-day job. You do need to understand it. There's a course on howtonetwork.com. It's 16 hours in total, but I broke it down into, I think the beginner course is about 3. There's an intermediate with loads of routing, and then maybe, I think, 5, or I'm trying to do my math now, 6, 12, 7 hours extra, which is advanced. So you could just do one part, and then when you come to do something a bit more difficult, do the second part, and if you want the third. But you really do need to know IPv6. I've been talking about this for about 4 years now, and it's becoming more and more urgent. So I used to recommend it, and now basically the level of understanding and the level of adoption is basically you have to know it. It's just like not knowing IPv4 now if you go into an interview. So please do learn it. We've covered IPv6, address types, neighbor discovery, EUI64, and then tunneling. That's all for now. Thanks for listening.
Network routing and IP addressing, IP assigning and addressing methods. So having discussed both IPv4 and IPv6 and the difference between these different types of IP addresses, we now want to talk specifically and in more depth about how IP addresses are assigned to a specific node or client or server. So in this module, we're going to look at the 2 different ways that IP addresses are assigned. This involves defining the first, static IP addressing, static meaning that the IP address is always the same, and dynamic IP addressing, which means that the IP address can change. We also want to talk about the strengths and weaknesses of each of these addressing methods, and we want to compare the features of one and the other. We're also going to identify when we want to use dynamic IP addressing as opposed to static IP addressing. and define, when we're talking about dynamic IP addressing, the terms DHCP, the server and protocol that are responsible for allowing dynamic IP addressing to work, something called the scope, which lets the DHCP server know which IP addresses are up for grabs, and then the lease, which, just like the lease on an apartment, lets both the server and the client know when a IP address can be used and for how long. We also want to talk about when static IP addressing would be preferred, and as you can probably tell from the way this is worded, we generally want to use dynamic IP addressing, as we'll talk about. But there are certain instances in which a static IP addressing is the best method for us, and we'll talk about those as well. So first, let's talk about static IP addressing. It's done manually, and that's what this really means. Static means manual assignment, which means that I literally have to go to the computer and type in what the IP address is and how I want to use it. So there are two major flaws with this. First, it can be very time-consuming because it has to be done manually and each address has to be entered individually by hand. In addition, this takes a lot of time and it's prone to a lot of errors. Human error is often a factor when we're configuring addresses for a large amount of systems. And if you can imagine, I'm working in a system of, say, 5,000 computers, then I'm going to be typing in IP addresses a lot. Now, while this may be a worthwhile method when assigning a very small amount of addresses, it's obviously not very practical when I'm talking about large quantities. And the other major flaw is that it has to be reconfigured every time the addressing scheme changes. So for instance, if I was going from IPv4 to IPv6 on my internal network, I'm going to have to rechange everything once I've switched over. Or let's say I want to change my naming system. Maybe I want to go from a class C to a class A IP addressing system if I'm on IPv4. And in this case, I would have to then reconfigure everything on each computer, and you can imagine the amount of time that that's going to take. So due to its many flaws, we're really not going to use this method, static IP addressing, which means, again, manual assignment. The way you can remember that is that static does not change, right? It remains constant. And the word static, meaning not changing, is what tells us that. So we're only going to use that in specific instances, and I'll talk about that a little bit later. So as a result, it's very rarely used except in very specific instances. I'm guessing you've never had to enter the IP address on your SOHO router or at your computers at home, and that's because we're going to use this other method, being dynamic addressing. Now, as the name dynamic implies, the IP address can change, which means that it is automatically assigned. Now, this is a lot more useful of the two that we have for many reasons. It's done automatically through a protocol called Dynamic Host Configuration Protocol, or DHCP. So you ever hear DHCP, that is what is referred to when we're talking about dynamic IP addressing. This is part of the TCP/IP suite, and it allows a central system to provide IP addresses to client systems. Now, since it's done automatically, there's no possibility of human error, and it's also a lot more efficient than static IP addressing. As a result, it's a lot more common of a method. It also eliminates the need to reconfigure a system if the addressing scheme is changed. So it's far more commonly used because of all these reasons, like we just said. It's more practical and more efficient because I don't have to change every computer. All I have to do is tell the DHCP service computer, we'll talk about that in a second, that we're changing everything, and all the underling computers automatically are going to change. So if we move over real quickly into our Windows system, and let's go into our network Properties. And we'll go ahead and go to Change Adapter Settings. I'm going to right-click on this and go to Properties. Now, we'll see over here, if I click on TCP/IP4 and go to Properties, it says Obtain an IP address automatically. So, through DHCP, the IP address is being automatically obtained, just like DNS is also going to be given out automatically. Now, if I wanted to do it statically, I would have to manually assign an IP address, a subnet mask, and a default gateway for each device. So you can see where we're not going to want to do that. So let's talk a little bit more about DHCP, or the Dynamic Host Configuration Protocol. This is the protocol which assigns IP addresses, and it does this first by assigning what's called, or defining rather, what's called the scope. The scope are the ranges of all of the available IP address on the system that's running the DHCP service. And what this does is it takes one of the IP addresses from this scope and assigns it to a computer or a client. So for instance, let's say that we're dealing, for simplicity's sake, with a 192.168 Class C network. So the scope might be something like 192.168.1.10 through 254. This means that of the IP addresses it's going to assign, it's not going to take anything in front of the 10. So this gives us .1 through .9 to use for static IP addressing. So what this ensures is that the DHCP server is not going to assign an IP address that we have already manually or statically assigned to another device. We'll talk about why we would want to do that in a minute. But this ensures, again, that the scope, that the DHCP is not going to assign an IP address outside of its scope. Then what it does is it takes this available address and assigns it to the client for a set amount of time, and this is called a lease. So the lease says how long the IP address is going to last. Now, the reason that we had leases is because, remember, if I turn off my computer, it no longer needs an IP address. It also means that, let's say I'm taking a computer away, if it has a lease of forever, then that computer now has one of my available IP addresses. So sometimes we'll have an IP address with a 24-hour lease, or maybe a 2-day lease. But whatever that lease is, at the end of that lease, it's going to have to again ask for another IP address. This is also the way that we can share a limited number of IP addresses with a lot of computers or nodes. So when we had the internet, we used to dial up to our ISP, or internet service provider. What this would allow is it allowed our ISP to provide us with one IP address that only lasted for a certain amount of time, and then when we disconnected the IP address, or disconnected from the server and therefore didn't need the IP address, it could assign it to someone else, and it didn't have to worry about us coming back on and wanting to use the same IP address. Because remember, one of the rules is you cannot have two devices with one IP address. All right? Now, let's talk about how this works from the client's point of view. Basically what happens is I have a DHCP server here, and it has what's called a trusted connection to the switch. We've defined what a switch is previously, and we'll talk a bit more about them later as well. But it has a trusted connection. This computer, say, comes online and says, "Hi, can I join your network? Can I get an IP address?" It sends its request through what's called an untrusted connection to wherever the DHCP server is. Now, the DHCP server at some point finds this, because this is generally a broadcast, because again, it's not a unicast, it's a broadcast, because this computer coming on doesn't know where the DHCP server is. So it sends a broadcast message out. The DHCP server then responds and offers a lease on an IP address, at which point this untrusted or unassigned connection becomes a trusted one. Now, when the lease goes out, it's again untrusted, and so it needs to repeat the entire process again. Now, so far, we've been pretty fair to DHCP and expanded on the benefits for dynamic addressing. But there are some exceptions when a network is configured for DHCP, and we don't want every single device to be automatically assigned an IP address. For instance, the DHCP server itself needs to have a static IP address. This is because we don't want the DHCP server to be changing addresses. And what's going to happen is if we have a lease, theoretically, the DHCP server could change its IP address. And since every computer on the network needs to know where to go, that's going to have to remain the same. This is going to go the same with the domain name server, so the DNS server, which allows us to convert between, say, google.com and the IP address. So we don't want to have to find this every single time, and we have to set it as something specific, meaning static. We're also going to put our web server as some static IP address. This is the reason why, if you wanted to get an account with your ISP or internet service provider, and you wanted to run a web server from your computer at home, you would need to ask for a static IP address, because that's the only way that someone can link through DNS to your web server. And so our web servers always has to be static, because when I type in google.com, I always want it to go to one of a few different IP addresses. Finally, printers are something else that we want to have be static, because the printer we don't want to move around. We want to be able to lock it in when we install it on the computer. Same with any servers. Also, routers, the gateway computer, or the gateway device that allows us to get out to the network, we need that to remain the same. So that's why when we define the scope, and in previous example we defined it as any IP address between 10 and 254, we don't want it to change, because we want these 9 IP addresses to be ones that we can assign. Now, sometimes we're going to make this a little larger, so that way we can assign a lot more static IP addresses. So also maybe a wireless access point we might want to be static, etc., etc. And all of this, again, is done through a web interface or through some sort of router device, or through a terminal or something. So this is not something we're physically hardwiring onto the device, because, again, that's a MAC address, physical address. But this is something that we want to set through a software of some sort. Alright, so just to recap what we talked about, we defined static IP addressing. Again, static means that the IP address does not change. It also means that it had to have been manually assigned. Okay? Now, we also talked about dynamic IP addressing, which DHCP allows us to do. And this means that the IP address can change because it is automatically assigned. One thing I didn't specifically talk about, what we referenced in previous modules too, is that a PPPoE address, that automatically assigned IP address, which if the dynamic IP address system is not working, so the DHCP server, for instance, is down, and it can't get an IP address from the DHCP server, it's going to assign itself its own IP address. If you remember, that was 169.254.x.x. So if you see this is your IP address, then guess what? Your DHCP server is down. We also identify the strengths and weaknesses of each of these. So we define the static, we define dynamic, and then we identify the strengths and weaknesses of each. Remember, the strength of dynamic is that it's easy, and it requires less work if we change anything. Of course, the dynamics, or the downside of it, could be this a PPPoE, or we don't want the IP address to change. We also talked about when to use dynamic IP addressing, which is in most cases. We defined DHCP, which allows dynamic IP addressing to work. Scope, which is basically the range of IP addresses. And the lease, which is how long the IP address is going to be sent out for. And then we recognize when static IP addressing is preferred. For instance, when we're dealing with printers or routers or even the DHCP server itself, which we cannot have change.
Welcome to Module 6, Lesson 6, DNS, Domain Naming System. We're going to cover a lot of stuff in this presentation, but I'll try and get through as quickly as I can. We need to know what DNS is, what are domains, the fully qualified domain name, the DNS root servers, so what happens, or how does the system actually, how do we interrogate it and how does it update itself. What are DNS records as well? This is stuff that's actually in the syllabus. Now I'm sure you've already heard of domain name system or DNS. You can see in the output here the image we've got .com, .org, .us. There's actually loads and they're added quite rapidly, and as each country has appealed for their own top level domain, more and more have been added, so there's lots of countries now that you can register domain names for. Some of them are protected. For example, if we go to .com.au for Australia, you actually have to have a business number. So even if you live in Australia, you must have it's called an ABN, Australian Business Number. So you can't just have anyone having a .com.au. Other countries have got restrictions, some haven't. So it just depends on where you are. So it's the name of a computer. It's got an IP address on the internet. Now these can actually be shared. You can have some of the same domain names. If you buy cheap hosting, they'll all be sitting on the same IP address. But this DNS can deal with this. So yep, that's just what I've said. If you for example, I used to host with these, but not anymore. What were they called? HostGator. I'm not recommending these, by the way. You could have this guy's website, somebody else's, another person's, but they're all sharing the same IP address. But that's easily taken care of. So what is it? It resolves the name associated with a server to its IP address. So you can see on my home computer here, I issued a ping cisco.com. Well, this URL is sitting on a server somewhere. I'm probably spread among quite a few servers actually, but somewhere from my home, wherever I am, I've got to get through to my ISP, and then obviously we've got a whole bunch of other hosting companies wherever they may be, and then finally we get to the building that Cisco own, maybe Palo Alto or somewhere else. But there has to be a resolve between this and what actually comes back, because TCP/IP doesn't ping names, it pings IP addresses. So 172.168.4.161, that could have changed, but something has to happen before the ICMP packet can be built. And as you know from other lectures, it's got to have inside their source, destination, and data, whatever else, inside the packet. So DNS will take care of the resolve for us. When we try to access samplecompany.com from the web browser, DNS translates the domain name into an IP address. So I've just put an IP address. If you're super smart and got a great memory, you could basically browse the entire internet just using IP addresses. However, if it's something new, for example, if you want to go to xyzsite.com, you're not going to know, obviously, the IP address. And this can change over time, by the way. They can move to another company, assimilate with someone else, or buy them out. So that IP address is used by our computer to communicate with the corresponding server on the network. As a database, DNS knows about the relationship between the domain name and its IP address. It's a distributed database that's spread across the world. I'll come to this more in a minute, but you've got your ISP, which will probably have several thousand of the most common DNS addresses and mappings in there. If there isn't one there, then when you do your search at home, if it's not there, then quite quickly it will be forwarded to, quite possibly, it might not be the one of the root servers which I'll come to, but it might be an authoritative DNS server that will hopefully resolve. If not, then it can carry on. Uses UDP port 53. Just bear that in mind because it could come up in the exam. Just people argue that DNS doesn't use UDP. It does. For our purposes, DNS uses UDP. Now, if you happen to be working for an internet service provider, then TCP is used, but it's used for zone transfer. So all the domain names that will be transferred across. That obviously has to be done reliably. Or large requests. It can also be used if there's multiple. This depends how you've got it all set up. If there's multiple failures looking for xyz.com, then it could also move to TCP. This is because it could be caused by UDP dropouts or fragmentation. But we probably wouldn't need to worry about that for our day-to-day jobs. Our DNS database, or the DNS database, divided into sections called zones. These store name information about one or more domains. When a domain is included in the zone becomes an authoritative source of information about that domain. So as I've already said, we need our routers and multi-layer switches. We concerned about IP addresses to make forwarding decisions, so we had to have this service created. We know this stuff already. Difficult to remember, kind of alluded to it. So the IP address, with the domain name system, we don't need to go through the headache of remembering the IP addresses. I'm flogging the point a bit here. So the DNS naming system is based upon the domain name space. Collection of unique names that denote other kinds of information such as the IP address. Now there has to be certain rules in place, obviously, and these rules have been added to and amended if you've got the time and the inclination to read through the RFCs. And certainly when we come to CNAME records, canonical names, I'm not saying that twice, they had to issue an update on the RFC because people were getting a bit confused about what it did. And this is one of the things about when you create something and you write the rules or the documentation, you presume people already understand stuff because it's in your head. This is why it's handy to get other people to write the documentation and then you read it. And I'm saying that because documentation is included in the Network Plus exam. So the namespaces are hierarchically, there's too many long words today, structured and has rules to that let the namespace be divided into subsets. So in the LAN, the domain is a subnetwork consisting of a group of clients and servers. I'm not talking about the your internal intranet, for example. I'm just talking about the day-to-day LANs of IP addresses. You could have the intranet, or obviously Microsoft also has a naming system, the Active Directory, so we're not talking about that. So internet domain is a descriptor of the logical grouping of names, and it indicates whether the names belong to the following: commercial entities, non-profits. I'm not sure what the non-profit is. Yeah, it's .org, isn't it? Which isn't really the case, because I've got a .org website, so it's not protected. You don't have to be a registered charity. Educational is .ed. I don't think it's .eu. It's .edu. Now, you can't get these as far as I know. Certainly not for USA. You have to be a uni, college, something like that. So I presume you have to have some sort of documentation or number. Government agencies .gov, and so on. You can subdivide a domain into groups called subdomain. So the DNS domain can also contain hosts. These refer to computers and services. So we've got an example here: training.samplecompany.com. So this is the first, obviously the top level domain which we talk about. Then somebody's registered this, but then when you go into your admin panel, you can add these subdomains here. For example, I think it's called racks.howtonetwork.com. I've got the same sort of thing. I created this subdomain which has got its own IP address. Howtonetwork.com is sitting somewhere. Actually know where it is. It's sitting on a server. Say no. IIO. The racks are sitting somewhere else because I've used DNS records. That's sitting in I'll actually remember where it is. I think it's up at Nevada. Just so you get the point anyway. So samplecompany.com, the .com is known as the TLD, top level domain. In case you could be asked this in the exam, this is why I say. The FQDN, the fully qualified domain name, is a complete domain name for a specific computer or host. So it's got the host name and the domain name. So the FQDN for a hypothetical mail server might be mail1, and you probably have this if you're in a reasonably sized company that's got a dedicated mail server, so you're handling all your mail. Most of these services are named, mail1, mail2, whatever, and then your company name. So you're managing all of your incoming and outgoing mail, which is probably a good idea. So you can blacklist and comply with other legal requirements. So mail1 is a host. Obviously you can use more than one server. You can use virtualization, whatever you want, but hypothetically speaking, it's a server. .com is the TLD, as we mentioned. So DNS root servers, these are contain the top level domain registry that maintain the global domains. So at some point, if you register a brand new domain name, you'd register it with your could be with your hosting company. I'll just put HC, and then that eventually will get forwarded to the TLD, and then that will be forwarded to non-root servers. So eventually your ISP will probably get a copy. So as of 1st of August 2018, root server consists of 933 instances. These are operated by 12 independent root servers. If you're interested in more information, you can go to root-servers.org and have a read up, and they've got some maps on there of where all these root servers are. Some examples of global domains are .com, .org, .net, .gov and .edu. Country codes: US, Canada, CN, don't know, Denmark, France, Japan, CN. Oh, that's going to annoy me now. I'll have to look when I finish this presentation. If it comes to me, I'll say. You wouldn't be tested on that, by the way. DNS root servers, also known as root name servers. If anyone says that to you, it's perfectly fine for them to say that. And it describes where the authoritative DNS servers for the top level domains are located. These give answers for a specified set of zones from its own source, so it doesn't have anywhere else to go. If there isn't a response, something's gone wrong, or the domain doesn't exist at the moment, and you'll get some sort of timeout message on your web browser. Non-authoritative servers, these provide cached answers, or cached, I know some people say, that are obtained from another name server. So as I said, you've got the root servers here, and then other companies, large organizations, just to save traffic and time, can query these, and then if they so wish, they could also be queried by other servers, and so on and so on and so on. The DNS is composed of a namespace. This is a distributed database. It contains the data that includes the host names. If you recognize the structure there, it's similar to a file system in Unix. The name server translates the domain name to its corresponding IP address, and we've seen an example of that. Does the response to the DNS query it receives from resolvers or other name servers? I'm going to talk about resolvers in a minute, I think. I'm not sure which slide it is. So the answers to the DNS queries are based upon the contents of the name server database. So obviously the database is full of records of mappings. So x.com, and it will be mapped to, there's a lot more than this, but as a simplified illustration. Cached information is learned by the name server from other name servers. How often they update the cache just depends on obviously their local configurations. Now you can get an authoritative answer. This is based on the contents of the name server database. If it's a cached answer, it's known as non-authoritative. Now on your PC, you can issue IP config, and this has worked for me before, /flush DNS. Say I've moved my website from one hosting company, which I have done in the past, to another. I can force a flush to find out where to see if this it's been moved correctly. Obviously I could put the IP address in, but this is quite a stressful time if you own a business, because you've got your website technically in two places, although this is the old version, and eventually the records will update. But could possibly be asked in the exam, ipconfig /flush DNS, and try it at home if you like. What's the DNS composed of? Resolver is the next part, which I mentioned. It's a software component that comes bundled with your operating system, also in network hardware. The internet applications such as web browsers and email clients need a domain name lookup. So this is a piece of software that issues the DNS request. The resolver accepts the DNS queries, and if the required information is available in the local cache, it returns that data to the client. So your PC will use the resolver, little piece of software somewhere. Then it will go out to the internet and obviously return it to you. Then you can issue the ping, which we already saw. If it's not available, it sends the query to the name server. When the resolver receives the name server's response, it hands the result to the application that initiated the request. So this will be your web browser, email package, whatever you're running. Obviously most of us run our email off the cloud now, like Gmail. So internet application sends a query for translating the sample company. Resolver checks the local cache, so you could actually check your DNS cache on your home computer. If it's not available, then it hands it over to the resolver hands it over to the nearest name server, which will be normally your ISP. Name server determines whether it can provide the data. If it's not available, then it goes all the way off. So PC resolver which basically just checks your DNS cache on your home computer. If not, it'll go off to your ISP. If the ISP doesn't know, it could query another server, but let's just say it goes off to the route there. So this should all happen pretty quickly. Obviously, you know yourself, you've put in a URL and just sat there. We're so impatient nowadays. You sat there, and any more than 5 seconds, you start hitting the refresh button. Alright, so the name server asks the .com name server and finally gets the IP address. Since the sample company has the IP address in its own database, this will be for a new domain, I guess. The name server that requested the IP address now gets an authoritative IP address as the answer, and that's all finally relayed. You can have a couple of query types. A query received by the name server. This is a recursive query. This is received from the resolver. Non-recursive is received by other servers, so they could just be doing an update of their own records. Probably in the exam you'll be asked a little bit about what are DNS records, what do they consist of. Also known as resource records, these have the information that we need to do the resolving. The records map a domain to its IPv4 address. These are A records. So this is the type of question you might get asked. What is an A record? It maps the domain to its IPv4 address. So here's an example. You would put these in when you register your domain name. If you host with the same company that you register, so there's a company called 123reg.co.uk that I used to register my names with and host. So I think it was all done for me there. Now some of these domain names, say in 60days.com, I had it registered here, but it's actually hosted somewhere else now. So I've had to go in and I actually put the name server. That's the only part I've put in, but there's other records that I can manipulate. And as the owner of this domain, I can do that. But just be very careful what you do. If you don't know what you're doing, then you need to ask for help, because things can go wrong. Because as I've told you, you can split your mail to go to one IP address. Your web server could be hosted on another IP address. You've got to have records for all of this. So, example of an A record. First is used to take care of situations when someone tries to access the domain name without typing www. Most of us don't bother now, so it'll resolve correctly. The first one being this here. Sorry. So somebody hasn't put www, and this is a wildcard. So anything before your domain name is just going to go to whatever server they're hosting it on here. The second record we saw is the wildcard. It will direct any subdomains to the hosting server. If you so wish, you can then point it off somewhere else, or you can add it into the DNS records. The quadruple A, I don't think there's any quick way of saying this actually, AAAA, quadruple A, because over in Australia this means the Australian Automobile Association. I know it's AAA we've got over here, so just got to be careful if anyone else is using these letters. This is an IPv6 address that maps the domain to its IPv6 address, obviously, because we need to be we're moving to IPv6 now. So the 128-bit address. There's an MX record, which you probably won't be touching unless you're doing your own mail stuff. To maps the domain name to an email server. If you're working for a big company, they'll take care of that. By looking at the MX record, we can identify the mail server to which the emails are sent. CNAME, canonical name record. Used to specify a domain name or subdomain as an alias of another domain. So it allows the mapping of a domain to another domain. So for example, you can point subdomains such as the mail or your FTP to your main address, And you can do this to make your company look bigger. And I think my FTP certainly just points to my normal server. Yeah, but obviously when you're doing FTP, you need to specify in your software that you're using FTP. So that's how it would work. So there must be an A record for the hosting server before aliases can be added. So CNAME aliases must point to another domain. So if somebody types bar.example.com, there's a CNAME record that basically says that is actually on the CNAME is foo.example.com. Then the search takes place, the DNS search takes place for foo.example.com. There's an A record, so IPv4 record, and it's saying, yeah, this is hosted on this particular server. PTR records, pointers, maps an IPv4 address to a canonical name for the purposes of the reverse DNS lookup. So this is the reverse. So normally we do xyz.com, and that goes to, but the reverse can happen. Somebody could type 192.1.1.1. When you type that in your browser, I think you need to test that actually. It won't stay. So if you type that, you may well see it actually resolves to this. It may depend on your browser software. SOA, Start of Authority record, is the first record in the zone file. It declares it contains the most authoritative information for the zone. Information is the email address of the administrator. You normally have to put something in unless you want it to be private. The name of the primary DNS server. There's a serial number. Time fields when it was all registered and on their last updates. Two of the types of record. Static is when it's done manually here, and dynamic is automatically updated. There's two types of records. And dynamic DNS. This is a process of automatically updating a dynamic DNS record in the name server. What can happen is this is almost in real time. Could well be used if you're using cloud computing and you're setting up servers, tearing down servers, moving information. Dynamic DNS will update the IP information and the names. So useful when the IP addresses of our devices keep changing. Whenever a client computer using DHCP gets a new IP address, it can use dynamic DNS. Alright, so we covered a lot of stuff. You know the core stuff about root servers and A records and quadruple A records. I think that's the type of stuff they'll ask questions on. We looked at DNS, domains, fully qualified domains, root servers, records. A lot of information, and thanks for watching. Welcome to Module 6, Lesson 7, Proxy Servers. Objectives, we're looking at what a proxy server is, an introduction, the uses of proxy servers, and forward proxy servers, reverse proxy servers. So you may have actually heard of these before, especially if you've worked in an office whereby instead of connecting directly out to the internet, your settings will be such that you'll connect to a proxy server, especially for getting out to surfing websites. The proxy server will do a few things which we will look at in a bit. So it's a mediator or an intermediary between you and some other service. You've got the client computer, the destination server, and then obviously the proxy in the middle. Here's an illustration here which will talk about the caching and web filtering. So it's mainly used for surfing when you want to go out and surf the web for whatever reason. It can filter what sites you can and can't connect to. It caches some of the content, so it's got a copy of regularly visited websites to speed up the surfing experience for you. Makes requests on behalf of the client computer, so you're sending the request out to what you think is the internet, but it's going to the proxy, and then the proxy does it on your behalf. The proxy receives a response from whichever server, say the web server on the internet, and then sends that information back to you. So it intercepts the communication between the client computer and the destination server. I've already mentioned that you don't actually directly connect to the destination. You can have different proxy servers to serve different traffic needs. You might have a proxy server to handle only HTTP, and then if you're doing FTP, then it may handle those requests on a different server. What does it do? It increases performance, so it's mainly due to caching, or you may have quite a powerful proxy server that's doing all these requests for you. Increases security because what the outside servers on the web see is the connection coming from the proxy and not actually the client device or the host device. It also, as I said, caches content, so it can serve up saved copies of a website. It could be a news website or something else that may not be updated too regularly, and then whatever these rules are on that proxy server, it will refresh that content at given intervals. So you've got to be careful. Sometimes you can actually be served up a cache of a web page and the actual live website has changed, so it's something to bear in mind when you're configuring this on your network if you do it. Increases security as well, filters out unwanted web traffic, malicious files before sending that onto the end client. If the client tries to download a malicious file unknowingly, the proxy server can filter it out, and you can have a firewall in between your proxy server and the client, or between the proxy server and the internet, or both, depending on what your requirements are. So already covered that actually. A forward proxy server is a new thing on the syllabus. It acts on behalf of a client computer. It gets the requested information from different servers. Servers on the internet only interact with the proxy server and they don't know about the client's existence, which is the concept we've already been discussing. Now there's something known as a reverse proxy server, and the clue's in the title, I suppose. It acts on behalf of the servers on the inside of an organization. But you can see here, some host on the internet is trying to access your web server internally, and the proxy server will act as the intermediary, deciding what does and doesn't go out, and also obviously it could have cached copies of what's actually on the web server, the actual web server on the inside. So since the servers are behind the proxy server, the following is true. The client is not aware of the server's existence. This is the internet client, wherever that may be, and it treats the proxy server as the origin. It can also be used to balance the load on a server farm, so it can poll different servers at the same time or load balance. Now, the servers are considered to be on the server side of the internet because of the following. They intercept all the traffic coming from the internet. They make it more difficult for hackers, not impossible, but more difficult to get the details of the internal network. Alright, so in brief, we've covered proxies, an introduction, the uses of them, forward proxy servers and reverse proxy servers. Alright, that's all for now. Thanks for watching. Welcome to the lesson on Network Address Translation, or NAT for short. I'm going to look at what it is, IPv4 addresses, IPv6 addresses, benefit of having NAT or using it, source network address translation, destination NAT, and port address translation, or also called PAT, or NAT overload. So what is NAT? It basically translates in private IP addresses into public IP4 addresses. The private IP4 addresses, was it RFC 1918, I think it is. These provide addresses that you can use internally on your network, but they can't be routed over the internet. So all of a sudden you've got a problem. So this helped solve the issue of running out of IPv4 addresses. However, then we had to resolve the issue of not being able to route those addresses. So NAT is a router function. Actually, these routers and firewalls can do NATing. So normally it's enabled at the boundary where your local area network meets your internet connection. You don't need to bother NATing usually internally on your network, no particular reason. We use NAT with IPv4 addresses. IPv4 has approximately 4.3 billion. Unfortunately, the drastic growth of the internet due to affordability of user equipment basically meant we were running out of IPv4 addresses. So NAT was a temporary solution to a permanent problem. IPv6 is the replacement, obviously, for version 4. Now, this is the long-term solution. There is a version of NAT available for IP version 6. I don't even think Cisco include it on their syllabus anymore. The reason is there's an almost inexhaustible number of available IP version 6 addresses. I think something like millions per every person in the world, so it's pretty much inconceivable that we're going to be running out of them anytime soon, certainly within our lifetimes anyway. So benefits, as well as using it so we don't run out of addresses, it actually hides our internal addresses on our private network from the internet, which is pretty handy, so it's a security feature. These are the private addresses, which hopefully you're already familiar with. You need to know this range of addresses because this is a favourite exam topic for CompTIA and also Cisco and Microsoft. These addresses, you can arbitrarily assign them with a DHCP server inside your network, or you'll have a DHCP server somewhere usually. I wouldn't let end users assign their own IP addresses. So let's say we have a LAN with computers that are assigned these private IP addresses, and internally we've got PC1. The data packet goes to our router. The router will NAT to this address for a routable address which you've added to the configuration somewhere. And it's one of the addresses you've been allocated. The packet goes out to the internet somewhere, comes back. Your router will have a table, a NAT translation table, and it will recall which address is on the inside, which is on the outside, and then re-NAT it so it populates the packets with the correct header and then forwards it back to the PC on the inside of your LAN. So in this case, this is in longer version of what I've said really. In this case, the howtonetwork.com server, the server on the right there, has seen that it's coming from a routable IP address. It just wouldn't get routed by your ISP otherwise. You can tunnel addresses, but you still need to tunnel them inside a routable packet. Source network address translation, a bit of a strange term this, but CompTIA are coining it. Basically it means the source on the inside of your network is being NATed out to a routable address, so you're initiating the connection from your source. So you've got a 192 network and it's been translated to a range of addresses on this router. Probably not a good idea to have one routable address because you can only ever have one connection live from the inside to the outside. So I've covered that, and since the source private IP address is replaced with an external public address, it's called source NAT. To be honest, I've only heard the term NAT used in all my years on networking, but you need to be familiar with this because they've put it in the syllabus for some reason. Okay, so I've covered this. The other thing is destination NAT. This is where the connection has been initiated from outside the network, and say you've got some sort of internal web server that serves members of the public who want to find out more about your company. You normally have this off a DMZ on a router interface also, or a firewall somewhere. So this time the packet has come from the internet, and it's hitting your router, and your router has a mapping. So this will be a permanently featured address, a mapping inside your router or firewall. Now, if you look at this image, it probably would make more sense just to have a routable address anyway on the inside of your network somewhere in the DMZ, the demilitarized zone, which is a safe zone for external hosts to access, that isn't on the same interface as your local area network. That would probably be a better idea, but otherwise this destination NAT is an option here. So I've mentioned DMZs. Through our public-facing server, although our public-facing server has an internal IP address, the user on the internet obviously cannot connect to it, which we've already covered. So DNAT, destination NAT, is the solution there. You can use destination NAT for load balancing the traffic coming to servers from the internet. So you could have 3 servers load balancing, lots of web connections coming in, and there's different types of device you can actually use for this. And so it's all getting load balanced to one routable IP address, but 2, 3, 4 or more non-routable addresses on the inside of your network. So when the user sends a packet, it changes the destination public IP address to one of the internal private IP addresses. The last thing is PAT, which is actually used more often than NAT. Port address translation. Normally, when you have a small company, you'll be allocated a single IP address, but you still want to do NATing. So what this does is it uses your one IP address, but uses port numbers after the IP address for source and destination. So this is the solution. Normally, for this solution here, you'd have static IP addressing 1-to-1, but you can't afford that for whatever reason. So you've just got one IP address externally, but several hosts on the inside. So what we have is a port number, for example 192.168.1.3, and then a port number. Your connection would go out on a specific port number, for example port 80 if you were doing a web connection, but it would come back in and then get changed to a random port number, or you can configure a range of usable port numbers that are outside the well-known port numbers of 0 to 1023, I think it is. When the internal host with a private IP address initiates this session, it will generate a TCP or UDP port, and that's just unique to that session. So you can see here internally we've got port 15345, externally 20201. To be honest, it would normally be a well-known port number such as FTP, DNS or web traffic. This port mapping is kept on a table inside the router. It does expire after a while just to clear the table, but normally more than enough time for you to complete all of your sessions. But that table expiration time can be altered on the router. Alright, so NAT, IPv4, IP version 6, which is a solution to address depletion, but we don't really use NAT much at all with IP version 6. Some of the advantages, remember security, and also you get to use lots of addresses on the inside of your network, and up to, and one address or more on the outside of your network. Alright, so that's all for now. Thanks for watching.
TCP/IP, TCP/IP simple services. In the previous module and lesson, we discussed the way that IP addresses are assigned. Now, in this next lesson, we're going to be talking more about the TCP/IP suite. And specifically, in this module, I want to discuss some of the simple services that are in the TCP/IP suite, what they do, and what some of the output might look like for some of the services, and why we might not see output for some of the other services. Now, you might see this on the exam and you might not, but either way, it's a good thing to know about just in case. Now, first, we're going to talk about all of these different simple TCP/IP services, and in some cases, we're going to demonstrate them. And just to give you an overview of what these are CARGen, or CHARGen, or character generation, the daytime service, the discard service, the echo service, and quote of the day service. Now, some of these happen in the background, are sort of embedded into other protocols and services that we might have seen, but these are important, again, to know about in a sort of general way. So, the 5 simple TCP/IP services are listed here, along with the description of what it is they do. CARGen, or character generation, or CHARGen, or whatever the preferred way that you want to pronounce it is essentially what you get anytime you choose the option send test page to a printer. It's made up of ASCII characters, and ASCII again stands for the American Standard Code for Information Interchange. So this is usually used as a debugging tool when you're creating or troubleshooting printers or print test pages. And so what it does, it literally just generates characters, and we'll look at this in a little bit. The next one is the daytime service. The daytime service is usually used for checking errors or changes that happen within a system's internal clock. It presents a message with the exact time that a change was made or an error occurred. And we'll look at this format in just a minute. But basically what's important here is that the output from this can be used for instance, the event viewer. It's sort of what provides information to that. And if we're going to see it in a text-based mode, you will see exactly what that's going to present in the next slide. Now, the discard service, so we've talked about character generator and daytime. The discard service is basically used for messages and information that are not important and therefore should be disposed of. It discards these messages automatically when they enter this port, or the port that discard is working off of. Now, this can be useful when you're configuring a system and using test messages that you don't want necessarily to display. So note that because the messages are immediately discarded, there's really no response message that's issued, and therefore I can't show you an example of one. But just realize that discard is going to usually be used for network setup and configuration, and is going to make sure there is no response or acknowledgement. Now, echo, or the echo service, sends an exact copy, or an echo, hence the name, of any message that enters its port to a place in the system where the message can be monitored. So this is often useful for when you're monitoring things that are going on in a network. Because the echo service simply echoes and copies and forwards any messages it receives, there's really no way to show what an example would look like, because they each look very different from each other. But basically, in many cases, we're going to get some sort of message that happens internally. And we want the computer to tell us that message once again, so we can see what's going on internally. And that's when we're going to use the echo service. Finally, the quote, or the quote of the day service, sends a short message that's been selected by the administrator of the system to a client's device. Now, this service is used primarily for checking the connection to client devices, so it's really similar to like echo. The content of the message is not what's important. What's important is that it is sending something, and that way we can make sure that the service is working and that the troubleshooting is sort of easily solved. Now, as it mentions here, it can be taken from a specific file right in here, which is where random quotes can be taken of. If you remember, or if you know the hosts file, it is also located in this folder. So let's take a look at this character generator and some output that it might give you. Now, this is what a test code page would look like. These characters are used, and they are the 95 printable ASCII characters, as you can see from here. And basically what's happening here is that when I, for instance, and this is someone going into Telnet, so they've Telnetted in, they've connected, and now I've told it basically to create some characters, and that's what it's doing here. And it's using all of the characters that are available to it in ASCII. And you would usually use this when you're setting up a printer, testing a connection to a device or printer. It doesn't really have much of a function otherwise. You can see that the content is not very important, but all it's doing is basically creating characters or content for us to test with. The next one is the daytime service report. And this is what it looks like. And you can see that it's presented in the following order. It's going to show us the day of the week, the month, the day, the year, the hours, minutes, and seconds in that format. And finally, and very importantly, the time zone. The reason the time zone is important is, let's say that we're looking at this daytime in an email. And sometimes the headers are going to use this same format. All right, that's provided by the daytime service in TCP/IP. Well, I can see that, oh yeah, it was sent at 1845, which that's military time, so this would be 6:45 p.m. in sort of our lingo. But by knowing the time zone, I can actually determine where in the world it was sent from. And therefore, for instance, this was sent on Pacific Standard Time, which is in the U.S., then I would know that this is 3 hours later, or 9:45 in the Eastern time zone. Now, none of the other, as we've mentioned, none of the other services have any sort of output I can show you. But just to recap what we've talked about, we described and demonstrated really briefly the TCP/IP simple services. And these again included character generator. We're really going to see this a lot when we're dealing with printers. It's just generating ASCII code. We looked at the daytime service, which is presenting the day, the time, and also don't forget the time zone, which is really important. We looked at the discard service, which automatically deletes messages that we don't need, and so there's really nothing there. Echo simply repeats or echoes any services or messages that are happening internally. And finally, the quote of the day takes a random quote selected by the administrator or taken out of a etc. folder in the system 32 quotes area. So that would be, if we had the root, which would be like system 32, and then etc., and then quotes, that's where it's going to draw something from. And again, this is also used for troubleshooting purposes. I showed you examples of these two because they're the only ones that have their own format. All of the others, the form is not as important. All it does is take other information and sort of regurgitate it. Now, in the next module, we're going to take a step further and talk more about some of the TCP/IP tools and commands and get into the operating system when we do so. TCP/IP, TCP/IP tools and commands. So in the last module, we talked about the simple services that TCP/IP provides, and those you may or may not see on the Network Plus exam. However, in this module, we're going to talk about some of the most essential tools when it comes to the TCP/IP suite, and I can almost guarantee you're going to see these on the exam. So we're first going to discuss and demonstrate all of the TCP/IP tools. And some of these tools include the ping command, and some of these we might have seen previously as well, perhaps in A+. And some of these also I'll go into the operating system and show you. So we're going to see the ping command, which basically tests for connectivity. We're also going to look at the trace route command, which basically traces a ping route. And remember when we were talking about protocols previously, we mentioned the ICMP protocol, the control messaging protocol. And that is what a ping and a trace route command use, or these types of packets. So we're also going to look at a protocol analyzer, not necessarily a command line tool, but something that allows us to analyze the protocols, or rather the packets that are going in and out of a network or a system. We'll look at a port scanner, sort of does the same thing. We'll talk about the difference between these two. We'll also look at something called NS lookup, and if the NS doesn't ring a bell with you, that is like DNS or name server lookup, how we convert between an IP address and a fully qualified domain name, such as Google. We're also going to look at the ARP command, which allows us, just like DNS, which does a name to an IP address, ARP is what is responsible for routing and allowed us to convert between an IP address and a MAC address, or physical address. So you can see where this is really going to come into handy when we're talking about routing and switches. Finally, we're going to look at the route command, which can present us with routing tables and is specifically more or less used when we're dealing with routers, not so much in Windows. Alright, so first the ping command. The ping tool and the ping command are extremely useful when it comes to troubleshooting and testing connectivity. Basically, what the tool does is send a packet of information, and that packet again is ICMP, through a connection and waits to see if it receives some packets back. This is not unlike when you used to see the radar screens on a TV or program. We're talking about with submarines, for instance, and you would see basically a submarine here, and you'd hear a ping coming off of that. So it gets its name from that sort of sound. So the data literally bounces or pings right back if there's an established connection. It can be also used to test the maximum transmission unit, or the MTUs, and remember we talked about that when we dealt with an MTU black hole, which was in a previous lesson. Now this is the maximum amount of data packets that can be sent over a network at any one time, or the maximum size of that data packets. So using this, you can test the time it takes in milliseconds for data to travel end-to-end or to other devices on the network. And this can also be done on the local host, and you remember the local host is 127.0.0.1. That's the IP address for it. And we can test this all by opening the command prompt and typing in ping and then the IP address. So let's take a look at this for just a second. If we're here and we have our command prompt, and I wanted to type, for instance, ping 127.0.0.1, which would be the local host, I can tell that my time is less than 1 millisecond, which makes complete sense, since there should be no loss of data. It should take no time, and you can see that no loss of data right here, right? Because we're sending it there and back, and obviously we're dealing with ourselves, the local host, or the 127.0.0.1, so it shouldn't be an issue. And if we do that, notice that when I use localhost, I'm using my own name, and it's also giving the IPv6 IP address here. Now, if I clear the screen for a second, I can also, for instance, ping google.com. And you'll see that it actually sends, first it figures out what the IP address is, and then sends that, and it gives us the time that it takes to get there and back. It also gives us some statistics. For instance, it was sent, 4 of them were sent, 4 of them were received, 0 lost. And so we know that on average, this is taking 13 milliseconds to get from us to Google. And if you imagine that this was a local host, or rather a local server on my network, and I was rebooting that server, this could help me tell whether the server is back up again. And one of the things I might want to do with that, and I'm just going to use the local host right now, is use the /t switch. And what this will do is it'll continually ping the same IP address over and over again. Now, so for instance, if I was waiting for a server to come back online, this would be an easy way for me to tell whether it's come back online or not. And I could exit that by pressing Control-C. All right. So the next one I want to talk about is trace route, which actually goes hand in hand with ping because it also uses that ICMP data packet or protocol. It basically tells us the time it takes for a packet to travel between different routers and devices. And we call this the amount of hops along the network. So it not only tests where connectivity might have been lost, but it's also going to test the time that it takes to get from one end to the other end of the connection. And it's also going to show us the number of hops between those computers. So for instance, between me and Google, there might be 4 different computers. And so each one of these is called a hop. And we can measure how far the packet is traveling before it gets back to us. Now, I can also use this to test where a downed router might be or where in the connection a downed router might be. So if we go in here for a second, and let's take a look at the command prompt here. And let's say I go to trace route google.com. Now what's going to happen is it's going to start saying all the different hops. It's going to tell me how long it takes to get from one place to the next. And we can see also where it's, so right here we're still in New York. You can see NYC. I can probably guess this is someplace in my ISP. And now it looks like it's starting to go out, get further out, and we can see that the amount of time it's taking is also more and more. So between me and Google, you can see how far we're having to go until we finally get to the google.com web server, which would be right here. And we know it took about 10 hops. Now you can see it has a maximum of 30 hops, and we can actually set that in the switches if we need to, but I wouldn't worry about that for the exam. And just to show you what it looks like if I'm tracing the local host, you can see it only takes 1 hop, obviously, because, or not even a hop, because it's myself. It should be no route to get to me. Now, going away from the command line for a second, I want to talk about what's called a protocol analyzer or a network analyzer. And this is an essential tool when you're running a network. It basically gives you a readable report of virtually everything that's being sent and transferred over your network. So these analyzers will capture packets that are going through the network and put them into a buffer zone. Now this buffer zone, just like the buffer zone we're dealing with YouTube or Netflix and buffering of video, is going to hold on to these packets. And we can either capture all the packets or we can capture specific packets based on a filter. It can then provide us with an easy, readable overview of what is contained within each packet. This allows the administrator total control of what does and doesn't pass through the network, and can also stop potentially dangerous or unwanted pieces of data to pass through the network undetected. And so what you can see here is if this is our cloud or our network, we're going to call this a TCP/IP network just because this is basically our WAN. And here, let's say I have one LAN and another LAN. I'm going to have a protocol analyzer or network analyzer in between my network and my LAN. That way I can analyze exactly what's going on. In some ways this might also take the form of a firewall. Now this is different from what's called a port scanner. A port scanner does exactly what it sounds like. It basically scans the network for open ports, either for malicious or for safety reasons. So it's usually used by administrators to check the security of their system and make sure nothing's left open. Oppositely, it can be used by attackers for their advantage. So if I'm on the internal, I might use a port scanner to scan my firewall to see what's going to be allowed through. I might also put my port scanner over here and have it try to come in. Alternatively, a hacker could use a port scanner to go through and scan for open ports. If there are any open ports, it can then use those to try to get into my system. So I can use it either as a white hat or as a black hat. White hat means a good hacker, black hat means a bad hacker. Now let's get back into our command line for just a second here. The name server lookup, or NS lookup, and again, whenever you see NS, as in DNS, domain name system, you can think that it has something to do with name server or name system. It's used to basically find out what the server and address information is for a domain that's queried. It's mostly used to troubleshoot domain name service related items, and you can also get information about a system's configuration. Now DIG actually does the same thing, but it's a little more detailed, and it only works with Unix or Linux systems. So here's an example of what the NS lookup would look like, and you can see we have NS lookup here, and then what did we do? Well, we asked it for Wikipedia's name, and up it pops the IP address. And it also tells us whether it's authoritative or non-authoritative. Authoritative would be a DNS server that's somewhere out on the internet that is definitely has all the information. Non-authoritative means it might be a local one. So if we were to look at this for a second for ourselves, let's do NS lookup to go into the utility. And now we could, for instance, look up google.com. And it'll tell us all the different IP addresses that are available for google.com, yahoo.com, maybe even microsoft.com, cnn.com, etc., etc. So you can see all these different ones that are coming through. Now notice that cnn.com actually wouldn't let us out, and neither would microsoft.com. That's because they're actually blocking, they're filtering out the type of ports or protocols that are going to be allowing that are going to allow like the ICMP ping. So if we were to go out of this for a second, and by the way, you do that as Control-C, and if I tried pinging Microsoft.com, you'll notice that it actually doesn't come back. And that's because they're actually shutting out ICMP packets from going in. Now, another one related somewhat is what's called ARP, or Address Resolution Protocol. We actually talked about this previously, and it's really used to find the media access control, or MAC address, or the physical address for an IP address, or vice versa. Remember, this is the physical address. It's hardwired onto the device. The MAC address is the system's physical address, and the IP address is the one, again, assigned by a server or manually assigned. In a way, this would be like your phone number, and this would be like your social security number, which is given to you by the government. The way it does this is we're actually going to send out discovery packets in order to find out the MAC address of a destination system, and once it establishes that, it sends that MAC address to the sending or receiving computer. Now, the two computers can now communicate using IP addresses because they can both actually resolve to IP addresses. So basically, I want to send something, right? So what I'm going to do is I'm going to go out, hit a router. The router uses ARP in order to get the MAC address to the sending computer, and now we can talk directly. Because now I know what your MAC address and IP address equal. Finally, the route command is extremely handy and can be used fairly often. It basically just shows you the routing table, which is going to give you a list of all the routes, network connections, and so on, that the user has the option to then edit. Now, the reason you might want to edit it is if, for instance, in your router, you want to tell it to use one route instead of another. So an example here shows us the gateway, the mask. So draw these really quickly. And the interface, the metric, as well as the interface, and these are all numbers. So these might not mean a lot to you, but if you had a guide and you knew where they were going, if you knew what your interface was, for instance, is it a wireless interface or was it your wired interface, that would prescribe a specific number. The gateway is going to say what gateway you need to get out, and the subnet mask. And you could actually add specific information to this to create your own routing table. And this you would do really not so much on your computer, but more if you're working on a router, say a Cisco router, so that you can tell it exactly where you want information to be routed. So just to recap, we discussed and demonstrated several TCP/IP tools, including ping, which we're really going to use to test connectivity. And remember, you want to hold on to the /t switch, which is going to do it indefinitely. Traceroute, which is going to measure the hops and can also tell you where a connection has been lost. A protocol analyzer, which is going to look at, or network protocol analyzer, which is going to look at all the protocols coming in and can actually filter them in or out. A port scanner, which can be used to show open ports, either as a security precaution or if I'm trying to infiltrate your network. The NS lookup, which is that name server, could also be DIG, by the way, which is on Unix systems. And this is going to allow me to get my IP address to a fully qualified domain name. ARP, Address Resolution Protocol, which is specifically going from IP address to MAC address. It sort of really allows routing to occur. This is really a principle in routers. And finally, the route command, which allows us to edit the routing tables and would be really useful if I was using one of my servers as a router. You're not really going to see routing or route command on the Network Plus exam, but I guarantee you'll see all these others mentioned. So now that we've finished up this very brief lesson on TCP/IP, the tools and the simple services, we're going to go into LAN Administration and Implementation a bit more in depth. Local Area Network, Administration, and Implementation. So in previous lessons, we've discussed a lot of the tools, the networking fundamentals, the theory, and so on. And now we're going to get into a little more of the practical side, and that's in creating and maintaining a local area network, wide area network, and so on and so forth. This module is certainly just an overview of a local area network and some of the best practices that go along with it. As we get more in depth over the coming lessons and modules, we'll talk more about the specifics and what we need to do. So in this module, we're going to talk about an overview of a LAN, kind of go back over what it is, and also when we'd probably want to use one. And then we're going to identify the steps to setting up a LAN, including using a network plan, having backups, creating proper documentation, auditing, and security. So first, what is a LAN? Well, there are two types of networks, as you recall. One is a LAN and the other is a WAN. A LAN stands for, again, a local area network. And a local area network is really any sort of local or geographically specific network. WAN stands for a wide area network, and we're going to talk about that in more depth in the future. So because LAN is restricted to one geographical location, such as a school or a small office building, it's a lot easier to administer and requires a certain specific set of skills. Since it's so localized, it also has higher speed capabilities than a WAN, and it's often a lot less expensive. So here's an example of a local area network. The internet connectivity comes from the server, which is going to also go out to the WAN, which would generally be represented by a cloud, the WAN being the internet. And we can see that there is a switch here, which connects each one of these PCs. Wirelessly, perhaps has a PC connected through it, thanks to a wireless access point, perhaps connected to the switch or router. By the way, here the server is acting as a router, and we might also have a network-connected printer. A very simple but effective LAN here. Now, at the heart of every network is a server. And the server is really what powers the internet connection to every device that's on the network and provides devices on the network with resources and other sorts of information. Now, in some cases, we're not going to have a server network, but we're going to assume here that we're talking about a very technical network, okay? And the first step to implementing a local area network is to generally set up the server, or if we don't have a server, to set up the router or the SOHO router in a small office, home office. Remember, the server is really going to serve up resources. It's going to serve up DHCP server, so on and so forth. So the word server doesn't necessarily mean a freestanding personal computer or a more powerful computer. It's really just the device that's at the center of our network. Now, usually we're going to do this with some sort of professional setup. Sometimes we'll have someone else come in, and sometimes we're going to do it ourselves. Now, the network topography and design is also pretty important. We need to figure out how we're going to set up the network. We talked about different topographies previously, so we probably are going to want some sort of star network, if you recall what that is. We might, for some reason, have a ring if we have a really intense local area network, although this is usually going to be used in a WAN setting. So really what we're going to see usually is a star. And as you can see, everything is hardwired, and this is a bird's eye view of how we're going to connect this network. So you can see, we see each device plugged in. We see where every device plugs in. For instance, this printer plugs up directly to Mike's PC. So if we were having a problem with the printer, we know that actually the PC could be the problem, not necessarily this cord here. And so knowing where everything is set up and how everything is set up is really important as you go forth, and of course important before I start to create a huge network. By the way, your network and your plan are probably a lot more complex than this, but try drawing out your network at home and see if you can do it as well. Now, backups are extremely important when I have especially an enterprise setup. The loss of data that can occur could take us out of operating, and if I'm talking about a network that is running bank information or healthcare, then I really need to potentially stop and avoid this critical loss of data. And so regular backups are key. Now, there are a lot of different ways to do this, and we'll talk about specifically some of the difference between incremental backup and a differential backup, which we've discussed in A+ as well. But there are some other surefire ways that we want to do this. First, all users on the network need to be regularly saving and backing up their own work. Then we might want to have an outside service also taking care of our backups. So I might want to have the backup going out to a cloud or to a WAN. In this case, I probably have, and this computer is representing my LAN, all of the information going to a central service and then going out. If I have a server and all of the devices are hooked up to this server, then they're going to feed the server with the information. Once that information is on the server, then I can make sure that that all goes out to the cloud. The important thing is to centralize where your information is being saved. If I have, for instance, data being saved to various computers, and those computers don't have a central place to store all their data, then backing up simply the server is not going to do it. I'm going to have to go back up every individual computer, and that really doesn't work. So what we really want to have is a centralized backup system, and sometimes we want to have redundancy in this system by not only backing it up locally, but backing it up out to the WAN, or alternatively having tapes that we're going to take off-site in case, God forbid, something happened to my backup plan. Now, it's also important that we document our network, and once we've documented it, we need to continually audit where our network's weaknesses and strengths are. So we want to keep track of everything that's on the network, including the hardware, the software, diagrams that we have, numbers, serial numbers, etc. We also need to audit the network for security strengths and weaknesses. We might do this by using a port scanner, by having some sort of centralized virus scan program like we'll see in a minute, and maybe even by hiring an outside security firm to try to hack into my system so I can see where the weaknesses and strengths are. All this information is going to be key in recovering in case of major data loss. And that's the reason I want to always just keep a nice long paper trail. Sometimes you might want to print this stuff off too, because again, the computer goes down, I can't access anything that's digital, or throw it up in the cloud, then I don't have to worry about it. Now, when we come to management and troubleshooting, we always want to make sure the network is running smoothly. And since you're the administrator, you're the person who has to be monitoring and managing everything that's going on. Now, when there are issues, you want to troubleshoot and solve the issues where they arise. Using the OSI model can be really helpful in this case because you can determine where the issue is occurring. For instance, if I'm having a trouble getting out to a certain website, but everyone seems to be getting out to information, then maybe the DNS is the problem. If, for instance, new devices can't get on the network, but if I manually assign them an IP address, it does work, well, then probably my DHCP server is getting funky. Again, this is just an overview. We're going to talk about all this in more specifics as we go forward. So I need to take a look at what the error is, figure out what the problem is, and get to the root issue, especially because what I'm really going for here is what's called 5 nines, which means I want to be up 99.999% of the time. That's like 5 minutes of downtime per year. That 5 minutes, however, can be really a big issue. This also means I want to be updating with Windows updates, and I want to be providing as much information as possible to my network and my network staff, and even the individuals who are using the network as possible. Finally, when it comes to security and virus protection, I want to make sure to audit and prevent the attacks before they can happen. So I'm going to audit it, and once I audit, I can see what sort of the issues are. If I notice that there's no virus protection program, then I'm going to want to use some antivirus software. If I notice that there are open ports getting out to the server through the firewall, then I'm going to want to use that. If I notice there isn't a firewall, I'm going to want to have to put a firewall up. So basically all the things I can do, there's no one-size-fits-all practice. What you really have to do is use the skills that you have in order to audit the system and then prevent the attacks before they happen using a number of different tools. You might even use something called an IPS or IDS, which would be intrusion protection or intrusion detection service or scanner. All right, so just to go back over this was a very broad overview of what a local area network is and some of the things that we need to do in setting up and maintaining a LAN, including creating and having a network plan, performing regular backups, providing documentation, holding on to that documentation, auditing our network to identify weaknesses, which is the main reason for an audit. We also might want to use the audit to identify bottlenecks or slow issues that are going to cause speed issues, and so on. And then, of course, having proper security such as virus scan programs, intrusion detection, prevention systems, firewalls, and so on. We're going to talk all about this and more in the coming lessons, but this was just a broad overview to get us sort of set up. Local area networks, switching. So in the last module, we talked about local area networks in general, what they do, how we set them up, how we administer them. But in order to have a functioning local area network, one of the most important developments that we had was called switching. If you recall earlier on, we talked about the OSI model. And if you recall, the OSI model went from level 1 all the way up to level 7. Now, level 1 was the physical layer, and on there, we talked briefly about a device called a hub. Now, the problem with the hub was whenever data went from one computer into the hub spouted all of that data out to all the other computers on the network. This created a lot of broadcast traffic because the hub itself worked on the physical layer. All it did was repeat all of the bits that went into it out to all the other devices. But now we have something, and we've had for quite a while, a thing called a switch. And this allows for switching, which operates mostly on level 2 of the OSI model, which, if you recall, is the data link layer. Switching allows us to have a fully functioning local area network because it allows devices to talk using the MAC address, or the physical address of the computer. So in this module, we're going to talk more in depth about what a switch is, how a switch operates, which I just touched upon a bit, and then I'm going to talk about a couple advanced switches you need to know about for the Network Plus exam. These are the multi-layer switch, also called a layer 3 switch, or a smart switch. And then we're going to talk about a content switch, which, as the name implies, deals with the content in the packet, not just relaying the packet of data itself. So, a switch is an extremely important part of a functioning network. So let's think for a minute about a light switch. A light switch essentially has two pieces of wire attached to it. If we look at like so, I'll put the little switch right there. And when the switch is flipped in one direction, the circuit is completed. When it's flipped the other way, then the circuit is sort of broken, and so the light turns off. In a way, an Ethernet switch follows the same principle, except it's not only attached to one single wire and cable, but to many. Some switches can even have upwards of 200 cables attached to them. Now, these Ethernet switches are used to connect many, if not all, of the devices on a network, and it establishes a flow of data between them. This switch, like a light switch, makes a connection between two different cables and allows the data to flow specifically between those two devices. Now, LAN switches are used to send data from a single device to another. Sometimes, and sometimes even multiple devices. There are devices, as I said, called hubs, but these do something different. So what the switch really does here is it allows data sent from one device to go specifically to the other device that it's meant for. And it does this because it knows the MAC address that it wants to send to. Now, it doesn't necessarily know where that MAC address is on the network. All it knows, and it puts this into the packet, remember we talked about that, it puts it into the header of the packet, the address, which would be sort of like the phone number or the social security number of the computer that wants to receive the data. The switch then has a table that says in each port, so if we had port 1, 2, 3, 4, and 5, it would say the MAC address connected to each port. And so when port 1 sends data meant for a MAC address, it knows, oh, I'm going to send that to port 5. Now, it could also do this for multiple. For instance, I'm going to send it to port 2 and port 5. The key difference here, as I pointed out in the very first slide, was rather than a hub, which broadcasts out to all devices, the switch creates a single switch between two specific devices and closes a connection. What this does, in effect, therefore, is reduce broadcast traffic and allow the network to run much more efficiently than a hub allowed. Now, there was a time when networking devices only served one purpose, and their functions were specific to that type of device. But over years, things have evolved. So now devices can do multiple things. Now, we see this multi-layer switch, or what you might also see as a layer 3 switch or a smart switch, What it does is it is not only a switch, it's also a router. This is the reason why it's called a layer 3 switch. I brought up the OSI model on the very first slide. Layer 1, physical. Layer 2, data link. And if you recall, layer 3, let's use our mnemonic device. Please do not throw sausage pizza away. So this is the network layer. And if you recall, we mentioned briefly that routers, which we'll talk about in more depth later, operate on layer 3. That's because IP addresses operate on layer 3. So a switch can not only look at the MAC address, but a multi-layer switch, one that operates not only on layer 2, but also on layer 3, can also look at IP addresses. So because this switch operates as both a router and a switch, it can send information between several different networks. So here, for instance, I have network A and network B. And let's see, this PC wants to talk with the server on network B. In the old system, unless the server was actually connected directly to the switch, there would be no way for the two networks to sort of speak to one another. But because we have a device here that's perhaps operating as a switch and a router, it can route the data onto a different network using an IP address. In some ways, you could think about this as the advent of the area code. When we had a phone number, which was only 7 digits, such as 7235411, we could talk to anyone within our local network if we knew this number. When we added the area code, we were allowed to then dial out to other states. And then we were allowed, by putting an international code, to dial out to different countries. So we're allowed to go then outside of our specific network. And in this way, we're not just dealing with MAC addresses, we're dealing with IP addresses. And as we've talked about, IP addresses are assigned by, for instance, a DHCP server. And so as a result, they're more temporary, they're not hardwired onto the device, and it not only allows for routing, but it makes it a little more complex to figure out where a device is at any one time. We'll talk more about that in the next module. The important thing here to realize, though, is that a multi-layer switch operates both as a router and as a switch, because it works on layer 3 and layer 2, which means it not only reads MAC addresses, but also IP addresses. Now, the next type of switch I want to mention is something called a content switch. The name content should give away what we're about to talk about here. Now, these are not really used as much as we see in today's networks because they're quite costly. But a content switch will actually analyze the data it receives and forward it based on its content only. So rather than dealing with simply an IP address or a MAC address, it actually looks at what's inside of the packet. If we have a MAC address here, and then we put an IP address on the outside of that in order to tell it where to go, it's actually going to look inside and look at the data and determine where that content is going to go. These switches are also sometimes called load-bearing switches because they can evenly distribute data based on the type of data there is and the appropriate destinations, which can alleviate stress on a single server or device. So for instance, if I erase all this for a second, let's say we have, for some reason, and let's say we have a router right here, which allows us to connect out to the internet, and then information comes in straight from the router to the content switch, and we don't know where the information is set for. Or let's say we have 6 different clients or servers, it doesn't really matter, that each could operate under the same sort of IP address. For instance, we're going to put them all together or group them. The content switch can say which one it's going to go to based on the type of information it's receiving. So for instance, email is probably going to go to one computer, whereas web is going to go to another, whereas the FTP might go to another. And the packet itself doesn't have to know which computer it's going to. The packet just has to have an IP address and or a MAC address, and then the content switch itself, based on the content, is going to send that over. Another way to think about this is if I'm dealing with some sort of firewall, and I want the firewall to put certain types of data into a filtered area that needs to be scanned for viruses. So this is really going to help me alleviate certain processes and also help keep my network safer. And we'll talk about other devices that do this as well. But when we're dealing with the content, we're dealing with further up on the OSI model. So we're not just dealing with layer 1 or 2 or 3 even. We might even be dealing with layer 4 to some extent. So just to recap, we first talked about what a switch is. A switch, again, allows for a direct connection between two devices. Or more. The important thing here to realize is that the devices communicate directly because the switch creates a circuit between those two devices within a box based on ports. Now, how it does this is it creates a table defining which ports are connected to which MAC addresses. Again, a MAC address is the physical address that's built into a device when it's made. This is different from a hub, which just broadcasts everything. So if we were to create an analogy, we could say broadcast, which would mean all the data going out to every other device, is to a hub what unicast or multicast is to a switch. We also looked at some advanced switches you need to know about. The first is a multi-layer switch, which operates on layer 2 and 3. Our usual switch, because it's only dealing with MAC addresses, is dealing with the data link layer, which on the OSI model is layer 2. A multi-layer switch is also operating on layer 3. It also routes. So it is not just a switch, it's also a router. A content switch is even going further up the OSI model and analyzes the content in a packet to determine where to send it. This is also why it's called a load-bearing switch, because it helps reduce the load on a specific node by sending the data out to several different devices that can all deal with the same content in a device. Now, we're going to talk further about routing in the next lesson.
Spanning tree protocol. So what is spanning tree? It's defined by the IEEE 802.1d standard, and basically it allows switches to communicate in order to prevent loops on our switch network. It runs a mathematical algorithm. It finds out and blocks which ports would be the possible causes of layer 2 loops. Basically, a loop will occur on our switch network when there's more than one path for a frame to take, and this could cause obviously confusion, as I'll illustrate in a moment. So it's a real simple illustration here with our diagram. So switch 1, for example, will receive a frame on its fast Ethernet 0/1, and it will flood it out of its next interface, fast Ethernet 0/2. And remember, if there's 24 interfaces, then it would be flooding them out of all 24. Now switch 2 would receive this, and the address would be for host A, and it would be firstly received by switch A, switch 1, and recognised that host A was connected to Fast Ethernet 0/1. Unfortunately, that address would come out of the bottom of switch 1, go around and reach the bottom of switch 2. Switch 2 then thinks that it knows the way to get to host A, and the direction to go is through Fast Ethernet 0/1. It will send that out of Fast Ethernet 0/2, and it will send that out as 0/1. Now we have a problem in that the ports on the switch all think that they can reach host A, when that isn't in fact the case. Now there's no time to live field in layer 2 frames, so that would go round and round around the network until every single switch thinks it knows how to get to host A, and it would bring your network to a grinding halt. So there's a mathematical algorithm was created, and it's based on two key components. The bridge ID. For bridge ID you can basically read switch ID, it's the same thing, and the path cost. So these are contained inside the frame. The bridge ID is an 8-byte field consisting of the bridge priority and the MAC address, the base MAC address of the switch. The default bridge priority is 32768, and then this is added to the MAC address. Now I've issued a show version on a switch, and it showed the base MAC address among other information, and each one will be different. So the path cost is used to calculate the proximity to neighbour switches. The higher the bandwidth, the lower the default port cost. So we can see the 10 gigabit connection here has got the lowest port cost allocated to it. So there's a 4-step path selection process. So the lowest route bridge ID, the lowest path cost to the route bridge, the lowest sender bridge ID, and the lowest port ID, and it will go through these 4 steps until it makes a decision. This all happens after the exchange of bridge protocol data units, which are called BPDUs. So let's have a look at our diagram. We have 3 switches here, and just to keep things simple, we've given them the MAC addresses of all A's, all B's and all C's. They're all connected, so we could possibly have a loop here unless something is done to close down one or more of the ports. So there's a route bridge election firstly, then there's route port selection, then there's a designated ports election. The bridge with the lowest bridge ID is selected as the route, and remember it's a combination between the priority and the MAC address. In this case the lowest MAC address is going to be the one with all of the A's, because that's a lower number in hexadecimal. So route port is the port closest to the route bridge. Now the route bridge will not have any route ports because it is the route bridge, so its ports will all be known as designated ports. You can see switch 2 and 3 has elected its closest port to the route bridge as Fast Ethernet 0/1. Every bridge except the route bridge must elect the route ports, and each interface adds a cost. So as the frame goes through different interfaces, the cost is added. You can see Fast Ethernet 0/1 is 19. As it gets to Fast Ethernet 0/2, that port cost is added again, and 19 plus 19, costs have been 19 each, comes up as 38. So Fast Ethernet 0/1 wins. The designated port election. A designated port sends and receives traffic on the segment to the route bridge. Only one designated port per segment. You can see there's a segment at the bottom here. Fast Ethernet 0/2 on switch 2 and 3. The tie goes to the lowest route bridge ID, lowest route path cost, lowest sender bridge ID and lowest port ID. And you can see on switch 2 and 3, the lowest out of the 2 would be the switch with the number MAC address BB, BB, and so on. The port states for STP can only be one of the 5 following. It's forwarding, it's learning, it's listening, blocking, or disabled. Alright, so we've covered a fair bit there. I only wanted to give you a taster of STP, and there could be a lab on this. I haven't decided yet. Obviously you'll be digging into a lot more detail when you actually come to do the CCNA. Thanks for listening. Welcome to Module 8, Lesson 2B, Power over Ethernet, or PoE. What is PoE? The benefits, components, the power supply equipment, we love our abbreviations there, PSE, end span, mid span, power devices, modes in PoE, standards, how does it work? What is it first? PoE is a technology that allows a device connected to an Ethernet cable to receive the following: electrical power and data. Now obviously a device connected to an Ether cable was already going to be receiving data because that's what Ethernet was designed for. However, what it wasn't initially designed for, and some very clever people found or realized a way and tested it, is to deliver power. And it's got all sorts of uses. We're talking in the context of networking. However, I recently bought a guitar effects board that plugs into the back of my amp using a Ethernet cable, and I thought it was going to come with a power supply, but as soon as I plugged the Ethernet cable in, it actually powered up the pedal board. And the pedal board offers a whole bunch of effects. It can record about 5 minutes of music, loop it, add other tracks on to that loop, and a whole bunch of stuff. So very clever technology, and it's got a multitude of purposes. And it's just one of those things, when it's invented, you think, why didn't somebody think of that earlier? The power devices that support PoE only operate from the power it receives through the Ethernet cable. Now, obviously there's a finite amount of charge or power that you can push through the cable because it's quite a thin strand of metal. But obviously avoids the need for additional electrical wiring, i.e. your power supply unit and all the wires that come with that. And as we all know, every single power device has got a different socket, a jack on it, and it just makes it very awkward to keep a track of which is which. And then obviously your power supply can die, making our lives a misery. So what is it? We're supplying electrical power through the electrical Ethernet cable in order to power devices. I know I'm stating the obvious here. The course is designed for beginners as well. Very handy for voice over IP telephony. Very useful indeed because it just saves those extra wires and cables. Wireless access points, network cameras, very big in the field of security, especially industrial security in shops and warehouses. Since the devices can consume the required power from the Ethernet cable, there's no need for the separate local power supply. If the device is an outdoor wireless access point or a WAP it supports, then we can do the following. We can send it electrical power and we can send data through the cable. It eliminates the local power source. It's saving you money, no need to upgrade the existing Cat5 or Cat6 cabling, which is another lifesaver and a wallet saver for companies. No need to purchase the power outlets, electrical wiring. I'm not sure if I talk about that in a moment as well, but it's just another thing that wouldn't possibly go wrong. I can't remember if I've put this in a slide somewhere. So you've got one less point of failure there. Very easy to install. Basically you just plug and play. You can install it even at locations that are hard to reach because there's no need for local power. Increased reliability, less risk of power interruptions caused by human interference because the device is essentially powered. A lot of the time our networking equipment has redundant power supplies as well and backup generators, especially if it's an ISP, so they'll keep working. Enhanced operational support, monitoring and remote management we can do through SNMP, so we can power the devices and perform different operations over the network. Very handy. I know I could remotely reboot different devices on my remote rack if I couldn't reach it and I didn't want to pay a tech to go and power cycle stuff. I could just send a message for the power unit to reboot if I needed to. Alright, two basic components, your power supply equipment and your powered device. Your PSE is the unit that adds electrical power to the Ethernet cable. You've got end span and mid span. The end span refers to a switch that supports PoE in addition to its switching role, so it can do both. These switches are capable of sending electrical power and data to the device. Midspan refers to a standalone inline injector that provides power to the Ethernet cable, so it's not built into a switch. This is situations where a switch doesn't have the built-in PoE. It could be an older model or a cheaper model for whatever reason. So you can pass the data coming from the switch to the inline injector and can output the same data, but it adds power to the points of the cable there. The power device supports PoE, receives the power via an Ethernet cable. Now in PoE there's two different modes for combining the following: data and power over the Ethernet cable. The two modes are not very imaginative, unfortunately. Mode A and Mode B. I suppose it could have been 1 or 2, or Jack and Jill. Mode A, the electrical power and the data are combined on the same wires over the Ethernet cable. This is called phantom powering. Mode B, the electrical power and data are carried on different wires, which is more common. You separate the data and power inside the Ethernet cable. So in the Ethernet cable, if you got a pair of wires carrying only the power, then the other pair of wires would carry only the data. First international standard was 802.3 AF. It was ratified a long time ago, June 2003, and it defines a power supply of up to 1.54 watts of DC. Uses 48 volts. There's a growing demand for more power over Ethernet cable, so the standard was updated. 802.3 PoE+. This was adopted back in 2009, and it defines the following: a power supply of up to 34.2 watts of DC power using 48 volts. Both the IEEE 802.3 AF and AT are now included in the Ethernet standard, so they've all been combined together. As we know from earlier presentations, the Ethernet cable has 4 pairs of twisted wire. This is Cat5e and Cat6. And we already covered earlier that 10 base T and 100 base T Ethernet only use 2 pairs of wire to send the data. So this leaves us some spare wires, 2 pairs of spare wires. So electrical current flows in a loop powering the electrical components such as bulbs and fans. The loop is an electrical circuit. Since the electrical current flows in the loop, we need 2 conductors to deliver power over an Ethernet cable. Typically we use 48 volts. That's sufficient power to transfer over the cable, and it's safe for users, so it's not going to injure anyone. Now if you plug a PoE device into one that isn't designed for use with PoE, then you could cause damage and fry it, in other words. And the PSE sends a lower voltage to a device to detect the characteristic signature of a compatible PD. If it detects a signature, then it knows the 48 volts can be applied. The PD lets the PSE know how much power it requires to operate. So this is to save a surge basically on the line now, too much power has been sent. The requirement of power is classified in the power classes shown below. Probably worth making a note of these, write them down just in case it comes up in the exam. Difference between the following: power supplied by the PSE, power received by the PD account for lost power. Now there is a maximum distance which matches in with the Ethernet standards, and maximum supported distance is 100 meters. There's a new standard which increases the power available, uses a wide range of the following devices: thin client terminals, point of sale stuff in shops, video conferencing. So I think that's all we need to know. We've covered PoE, the benefits, the components, the PSE, end span, mid span, the power device, the modes for PoE, which was A and B, the standards, and how does it work. So that's all for now. Thanks for watching.
Local area networks, routing. So in the previous module, we discussed switches. And as you remember, they're very important for the functionality of a local area network. Now, when we talk about connecting several different local area networks together through the internet, we have to deal with how a switch, which again is based on MAC addresses, the physical address on a computer, can find the MAC address of a computer halfway across the world. And the way it does this is by assigning each MAC address an IP address. Now, when we start dealing with IP address, we deal with a completely different type of device, one which is called routing. And the process of routing is what really allows the internet to work. And so in this module, we're going to talk more about the devices that allow routing to work, called routers. So first of all, we're going to define what a router is, and then we're going to talk about how it functions, which is also called routing. Then we're going to identify something called static routing. Just like we've talked about dynamic versus static IP addresses, we also have dynamic and static routing. Obviously, one is more resilient than the other, but there are certain instances in which we want to always go to the same location, and that's why we're going to have static routing. Then we need to cover some terms that you might see when you're dealing with routing. These terms are hop counts, costs, latency, and convergence. So we're going to cover all those terms so you have a good idea in case you see them on the exam what they're referring to. So a router is essentially like an extension cable. An extension cable connects two sources of power, and in this case, a router connects two networks together in order to make a larger network. In networking, the router is used to connect two networks together and give a clear route for data to travel between these two devices. Now, in smaller settings, such as houses or a small office, home office, or SOHO, the router connects the devices to the internet. So, for instance, you have your computer, and you have a laptop, and perhaps you have some sort of Apple TV device, or some device that's connecting to your TV and the internet, and all of these connect through what you call your router. Now, this SOHO router is actually doing several things. It's not just a router. But one of the things that it does is it allows you to connect all of these devices in your internal network, otherwise known as your LAN, out to the large WAN or wide area network that exists in the world. This is called the internet. So in a larger scale environment, the routers are used to make bigger network pieces. So if you can imagine that instead of just having my own home, I have, say, a number of buildings across a city or a number of buildings across the world. And I want them all to talk to one another and be able to locate one another as though they're sitting right next to each other. This is where routers are going to come into play. This is also why routers do a lot more and are more expensive than switches. And it's also why we need fewer of them. Now, in modern networking, the router is either going to be a dedicated device or it could be a server with a routing functionality, meaning it's a large computer with two or more network cards or NICs in it so that you can have traffic going in and then traffic going out. Now, when a router receives a packet of data from a client device, it reads the information in the packet's header and determines what the destination of the packet is. Now, after it finds out what the destination address is, it looks at a routing table in the router in order to determine where the packet is going to go in its next route. So, for instance, let's say this PC here, which for sake of ease we'll call PC1, wants to talk to PC2. Now it has an IP address in mind, and so what it does is it goes perhaps through a switch, but eventually to the router at the end of its LAN, and it says, hey, I'm looking for this specific PC. Now this router has what's called a routing table, which sometimes we're going to call an ARP table, because ARP, again, the Address Resolution Protocol, is what allows routing to occur. It's this protocol that we've talked about, which allows for a table that would say, for instance, 1 goes to IP address 192, whatever, etc. And so this router would look for this information. If it doesn't know it, it's going to say, I don't know it, but I'm going to go to the next router that might. Goes to this router, and this second router says, oh yeah, I know where that computer is, and then can forward the packet onto the computer. It also tells this router, the first one, which we'll call, let's say, router A and router B, where that destination was, so it can add it to its ARP or routing table. And if you imagine, this is only what we call one hop, because there is one hop between these two routers. But you can imagine in the entire world, if I'm traveling from, say, here in New York City all the way to Australia, for instance, I might have to take several different hops. And also, if you imagine, there are probably many different routes that I can take to get to a specific computer. If we imagine that the circles are the two computers, and the squares are the different types of routers, and we have them connected like so, well, there are a lot of different routes that a packet can take to get from point A to point B. And so we rely on routers to tell us which path it's going to take. It could take this path, or it could take this path, and so on and so forth. And so, depending on the number of hops and a number of other things we'll talk about in just a minute, it'll determine where the packet needs to go in order to get from point A to point B. Some other things it's going to determine too are what if there's a cut in the line. Well, now it can't get here. And so instead it'll say, well, let's try one of our alternate routes as well. Now in the previous slide, I talked about how routers might talk to one another in order to automatically update their routing tables. This way, two routers always know how to communicate with each other, or one computer on one side of the world can always get routed, or the information sent from one computer on one side of the world can always get routed to the information on another side of the world. But in some instances, we want to tell a router exactly where to send information destined for a specific network. Now, it might not always be the most practical way, but sometimes it's necessary. So static routing is when routes and routing information are entered into routing tables manually. Now this can be time consuming, and because it's prone to human error, it can be error ridden and can cause some problems. So this is why it's only done on very small systems or on ones that are very internal and controlled. Now in order to statically add a route, we're usually going to use something called the route add command. Now this is the sort of thing you might use if you were adding a route to a Cisco router, or to a Windows machine, for instance, that was acting as a router, or even a Windows machine that's at the edge of a network and needs to go out to another. The way it works is we use the route add command with the network name, the mask or the subnet mask, and the IP address of the gateway. So this tells us if we want to get to the network 192.168.2.1, we need to go to the subnet mask 255.255.0 and the gateway 192.168.2.4. Now all this information would automatically be done dynamically by most routers, but in some cases we're going to want to add it statically. Now this isn't something I've necessarily seen come up on the Network Plus exam, but I did want to clarify it and go over it just briefly in case you ever saw it in the field, since this might be something to do, something that your administrator or your boss asks you to do for whatever reason, or maybe something you want to play around with. If you need more information, simply Google the route add command. But again, I don't think you'll see it on the Network Plus exam. Finally, I mentioned that there were some important terms we had to mention when we talk about routing. The first is the hop count. This is the number of hops it takes to reach a connection or before an appropriate connection is made. If you remember when we used the trace route command, remember that was trace route, it went through a number of hops or a number of routers until it got from our computer to, for instance, Google's. So, if our computer and the destination computer are represented by these two circles, and let's say we have our internal router. So for instance, perhaps we are in a 10.0.0.x network, and then they're on their own network as well. Let's say that this is a, for instance, 124.68.24.3 network. Now we need to get from ours to theirs. And so let's say there are a number of different routers in between. Well, in this case, we have 1, 2, 3, 4, 5, 6 hops between us and the destination. So if there are an infinite number of hops, that means that the destination is unreachable, or that for some reason we're getting caught into some sort of loop. So the hops keep coming back to itself. Another way that you can see this as I erase this is, for instance, we have a system that looks something like this. And these are each routers. So what might happen, as I draw out all the connections, is the route might go from here, 1 hop, to here. And then instead of going to the destination, it simply goes like this. Because this could be a valid way of getting to the router, right? We could hop here, and then we could go over there. But instead, it hops, and then this one sends it along this route. So we move here, and basically we create a loop in which the destination is never reachable. Now this could be because of some sort of poor routing table, and what you would need to do is basically tell one of these routers that the destination goes over here. The next term is what's called the cost. This is the number of, or these are the numbers rather, that are associated with traveling from point A to point B. Generally, this means hops and several different links along the path. The lower number of hops, the better we are. So the cost would be how many hops total we need to travel from point A to point B. Generally speaking, we're going to look at the lowest number of hops possible. But there are some instances in which we could want to go more hops or have a higher cost through hops in order to save on something else, for instance, latency. Latency is the time it takes for a packet to go from one location to another. So to give you an example of what I was just talking about, sometimes we go route specific, which means that it's going to choose this route because this is only 2 hops. However, let's say that instead of traveling this, let's say this was a dial-up connection right here. And this was a broadband connection. Well, obviously, even though we have to go 1, 2, 3, 4 hops, as opposed to 3 on this one, we would want to take the 4 hops because the latency is going to be less. And so the cost would be determined based not only on hops, but on latency as well. Now, convergence is the process of routers discovering the network structure has changed. In this way, it updates the routing tables to the knowledge of the networks. So for instance, if we have 2 different paths that a route could take, it could either go like this or like this. We would want to know if one of the connections had been severed. And then this routing table would be updated to know, don't go on this route, instead go on that route. The process of this happening is called convergence. So, although this module might have been short and a brief overview of routing, we went over some key things. First of all, we talked about a router. This is the device that generally allows us to connect our LAN out to a WAN. It does this by operating on layer 3 of the OSI model, which again is responsible for IP addresses, as opposed to switches which work with MAC addresses and therefore operate on layer 2. We also talked about how a router functions. In this case, we talked about the fact that a router has what's called a routing table, which can sometimes be called an ARP table. The ARP table tells it where an IP address goes to get to a specific place. So it maps basically IPs to MAC addresses. And then the routing table would say how many routes you take to get to a specific node on the network. We also looked at static routing, which is manually updating the routing table, so that way you can tell it where to go. We also talked about some key terms, including hop counts, which would be like the number of places we're going to go. If we're going to take a trip, this would be, for instance, the miles. We looked at the cost, which basically means we're going to take several things into consideration when determining our trip. For instance, if one has a highway, whereas the other are a bunch of local roads with stoplights, then even though it might be more miles to go on the highway, we're going to go there as opposed to this one with the stoplights because we know we'll get there faster. Finally, convergence is keeping all these routing tables up to date. That way we know which route is the most effective at any one time. In the next module, I'm going to talk more about how all this works in dynamic routing and the protocols that are involved with it.
Welcome to Module 8, Lesson 3A on Routing Metrics, or if you're in the UK, Routing Metrics. So this is a little bit esoteric in as much as you're better off configuring routing and playing with this and doing hands-on labs, which you don't do for the CompTIA Network Plus. But if you're doing a CCNA exam for Cisco, for example, you'd actually have examples where you could see this being affected as you configure the different routing protocols and add more hops or other devices. But we'll do our best. We're going to look at routing metrics, the MTU, metric costs, latency, load, reliability. So routing metrics, tables on a router, and it's actually the same for servers as well. The routing table can contain a field known as the metric. Now, a metric is a value, and that value can be made from a number of different factors depending on the routing protocol. This is used by the router when it runs a mathematical algorithm to work out the best path to get from A, which will be the local router, to B, which is the remote router. Now, I issued a show IP routes on a router in the image here, and I just highlighted D, if you did look at the table there, is short for EIGRP on Cisco routing tables. It'd be different if you're using Juniper or a different device. But just for your information, the different numbers there are the routing metrics that EIGRP is calculated based upon the location of the different networks, which are 34, 4.4.4.4, the 23 network, 24, and the 12 network. Don't worry too much about that, but I just wanted to show you that you can actually see it in a routing table. And the number 90 before the routing metric there is the administrative distance that is allocated to the protocol. And for EIGRP, it's 90, internal EIGRP. So if a router has different routes to the same network, the routing metric helps the router decide which of these routes to choose, because you could have 30, 40, 50 plus ways to get from A to B, and the routing table would just be too big and the router would crash. So it chooses the best path and inserts the best path in the routing table. Alright, each routing protocol uses a different metric. I think you probably need an overview just for the Network Plus. So we've got two routers, router 1 and router 11. Between these two routers, you've got 9 other routers that connect to different networks. And you can see the different routers there, path X, Y and Z are the different paths in order to get to router 11. And of course you could make it more complicated by connecting all of the routers in between the paths, which may well be the case. So you want to get from router 1 to router 11, and there's 3 different paths to choose from. For sake of convenience, as I've said, X, Y and Z are the different path names. Routing protocols will choose a route with the lowest metric. Now if we use RIP, Routing Information Protocol, it only uses hop count. It doesn't care about the speed of the link or if the link's reliable or anything like that. It's a fairly old routing protocol, and it was built for quite small networks because all networks were small at the time. And so you can see there that there's one path has got 3 hops, one has got 1, 2, 3, 4 hops in the middle if you're not counting the source and destination. The other has 2, routers 9 and 10. So that's going to be the shortest amount of hops. 2 hops, 4 or 3. So if RIP chooses the route between router 1 and 11, it will choose the best path as path X. It's got the lowest hop count. Now I've introduced a problem here. I've actually shown you the speed of the links, and the speed of path X is only 56k. Which is crazy slow when you compare it to path Y, which is 1 meg. However, RIP won't understand this. Now you can configure it and do extra configurations to force it to take path Y, but by default it won't choose path Y because of the hop count. So different routing protocols use different metrics, and since the link speed affects the throughput, routing protocols such as ERGRP, which is an advanced routing protocol, take into account. Now it can take into account Cisco's version of ERGRP only uses 2 of the possible values that are usable within ERGRP. Cisco have their own version of ERGRP. Now, considering ERGRP can actually use 5, but we've only listed the 2 used by Cisco devices here, which are bandwidth and delay. Now, considering the link speeds, path Y is better because we want to take the faster route there. Router metrics can be based on the following factors: the MTU, the cost, latency, administrative distance, shortest path bridging. The MTU is one factor, as I've mentioned, stands for maximum transmission unit. This is the largest size of the packet that can be transmitted across the link without that packet being fragmented. Fragmented means it gets chopped into different sizes and numbered, sent, and then reassembled on the other side of the link. And obviously this can introduce the scope for errors, and obviously there's delay while this fragmentation takes place. Also overhead involved because of the acknowledgements. Each packet is sent and received as it goes along, and it could be requested to be retransmitted also. Largest packet you can send by an Ethernet network, because of the way the technology is designed, is 1500 byte. Now cost, I actually did an output here of a router running OSPF, or an interface running OSPF here. And you can see the other information is irrelevant for our purposes, but the cost has been allocated as 64. Different interface speeds are given different costs by OSPF. Total cost, so this link and the other link and all the other links between the hosts are added up together, and then the best cost, which is the lowest one, is installed into the routing table, and the other costs can be put into the topology table for use if the best path goes down. So you can have second best, third best, and so on. A routing protocol can also use delay or latency as a metric. Delay refers to the delay of the links across the route. So is there any delays to the packets being sent and received? Load, I've actually issued a show interfaces serial 0/1 on this router, and you can see some of the metrics that are allocated to this particular interface. The MTU is 1500, the bandwidth is 1544, so 1 meg. Delay and 20,000 milliseconds. Reliability 255 out of 255 is the best. It means it's very reliable, and if there's problems then the number goes down, like 10 out of 255 is very bad. The transmission load is low, it's the lowest, 1 out of 255. Receive load is 1 out of 255, which is an arbitrary value. So load is the measure of traffic consuming the links. We don't want our packet to be travelling along a path with high traffic. So the path with the lowest load would be the best path, if we're using load as a metric, of course. Reliability is in there also, which I've discussed. We want to take into consideration the reliability of the path. Reliability metric has a value that denotes the number of times any of the following occurs. The link goes down or had errors at a certain period of time. The routing protocol may use the following: one metric, as in RIP, multiple link characteristics to calculate a metric. For example, ERGRP, which is bandwidth and delay of the line. ERGRP uses characteristics to calculate a metric for best path. I've actually done a output of a Cisco router here for ERGRP, and you can see the different metrics here. Some won't be used, but you can actually affect this if you want in the configuration. Normally best to speak to a Cisco engineer before you do this. So some of the delay characteristics are delay, bandwidth, reliability, load. You can see others in there, but again it's bandwidth and delay of the line is usually used. Summary: so far we've covered routing metrics, the MTU, metric costs, latency, load, reliability. So that's all we need to know for now. Thanks for watching. Welcome to Module 8, Lesson 3B, Routing Tables. Another hard one to put in perspective if we don't configure live routers, but we'll do our best. We're going to look at routing, the routing table, static routes and a static route example, and dynamic routing protocols, only an overview really, and then an example, and physically connected networks. So routing is the process of sending a packet from a source network to a destination in another network. We actually have to differentiate between routing and packet switching. Routing is a process where the router actually decides the best route to get from A to Z, and then switching in the context of sending IP packets is actually pushing the packet out of the correct interface. I just wanted to highlight the difference between the two. But obviously we're looking at network plus level stuff here. So there's two aspects: determining the optimal route, which is the routing part, and then pushing the packet through the network, which is the switching part. So routes are based on networks. We don't really we don't want to concern ourselves with host on networks, because if you can imagine, even an enterprise network for some large company could have thousands of hosts. It'd be pointless every router having thousands of hosts listed. So what it wants to do is focus on networks, and then it will switch the packet to the correct network, another router, and then finally the host addressing and the MAC part of the address will be taken care of by the LAN switches. So a route is not based on the host because the packets are routed through the networks. It doesn't use the physical MAC address of the hosts. So here's an example. We've got a few different. I've shrunk down. Each switch would have, it could have 12 or 24 hosts connected, but I've just added one. And you can see we've got 3 different networks listed: a 192, a 10, and a 172 network. So the MAC address of the destination host is only used for the final delivery. So the switch, if these are layer 2 switches, which for my examples they are, it won't understand the IP address portion of the packet. It'll be concerned with looking inside the frame, and it will match the MAC address to the correct port and then deliver the frame to that particular port. This is what our switches are concerned with, whereas all the routing between the 3 routers in the diagram here, they're concerned with which network or which port which network is connected to of the router. So the switch down here on the right, if you issue a show MAC address table on a Cisco switch at least, you'll see a mapping, and you'll see which MAC address, and each one's unique, is connected to which physical ports. And on this particular one, they're all in the same VLAN because we're not worried about inter VLAN, any VLAN stuff here. So gigabit 0/2, 0/2, 0/2, and fast Ethernet 0/1. If you see more than one host connected to one port, it means it's a trunk and it's connected to another switch somewhere. So this switch down here would be connected to another switch via a gigabit Ethernet port, and it's learned a few host addresses that are connected to that. Alright, so when we send packets out to the internet, the following is true. The routers have a database of routes stored in a table called a routing table. It could actually be a database consisting of one route or just connected routes. Depends how we configure stuff really. The routers use this information in the routing tables and they make a decision based upon the next hop. This is what routers all do. They send a packet to the next hop unless they are the last hop in the journey. So there's a routing table here. You can see there's a network been learned, and if I just put the text here, the routing table contains the following: the network ID. Here the network is 3000, and it's actually found a host on this network. Destination network address and subnet mask. I'm not sure how this has been configured because I pulled this one off the internet. You can actually see at the bottom 10.10.23.0 is a network found by OSPF. It will have the next hop and gateway. So if we go to the bottom, 10.10.23.0, 110 is the administrative distance for OSPF, 20 is the cost, and it's been learned via the address 10.10.12.2, which will be another router interface somewhere connected. It was actually learned 1 minute and 17 seconds ago via the fast Ethernet 0/0 interface. Alright, so the router has enough information that if it wants to send any packets to any host on the 10.10.23 network, it knows where to send it, and it also knows how fresh that route is. Alright, the metrics used to decide which route is to be taken if multiple routes exist for a given destination network. So we can see some metrics here. In fact, squared in the yellow highlighting, you can see 2 routes have been learned to the same network. The reason is the metric is exactly the same. So it must be exactly the same cost to reach the destination via 2 different IP addresses, 172.24.122 and 172.24.134. So as long as the costs are the same, then ERGRP is configured to load balance over those. I think with Cisco ERGRP automatically load balances over up to 4 links, and you can change that value up to 16. But this could change depending on your platform. Alright, so the administrative distance, when a router is running 2 routing protocols such as RIP and SPF and everything else is equal. So for example, RIP and OSPF, it will use the AD, administrative distance, to determine which route to choose. I've configured 2 routers up here, just connected via gigabit 0 and 0/1. The top network for the top link is 192, the bottom, and it's using RIP. The bottom is OSPF and it's 172. And at the end we have another network, a 10 network, that is advertised via RIP and OSPF. So RIP, I know the administrative distance is 120, OSPF is 110, so routes to get from router 0 to the 10 network should use OSPF. And if the OSPF network goes down, or the interface is running OSPF, then the RIP network could be chosen. This is a part of the output from a show OSPF. You can see 120 is the AD, /1 is how many hops, and underneath 110 is the AD, /2 is the cost, because OSPF uses a cost, not a hop value. So it's the calculation is used looking at the speed of the link is put into a formula, and each link between source and destination is added to the cost. So the cost is only 2, which is the gigabit Ethernet speed there, and it'll be the speed of the interface that the 10 network's connected to. So if I try and trace traffic going from router 0 to the 10 network, you can see it's traced and it's used the next hop address of 172.16.1.2, which is the gigabit 0/1 of router 1. So that's basically the preferred path. If for some reason that path went down, it would start using the next best AD, which is RIP. Routing table, routing information is populated through a few different means. It could be a connected route, actually, a static route, I said connected there, or a dynamic routing protocol. What you configure depends on your network. If it's a tiny little network, or if it's in a remote office somewhere, then you'd probably use a static route to just send all traffic to the next hop router. So this is the show IP route, and I've highlighted in red the connected routes for router 0. It's a 172.16 and the 192.168.1 network is showing as C connected. R in Cisco at least stands for RIP, O stands for OSPF, and L stands for local. Static route is a route that is manually added to a router by administrator. So you can see here router 1 on the left has got a default static route, which you can recognize it because it's all zeros. I'll give you an example in a moment. If router 1 receives traffic destined to any network other than a local one, i.e. one that's connected, it should really know where to send that traffic. If there's no entry listed, then by default routers will drop the packets. Since R2 is the next hop for router 1 to reach the internet, what we could basically do is put a static route on router 1 saying send any traffic to any network over to R2 and let R2 worry about where to send it. When R1 receives the traffic for a network that's not available, it will now send it out of its interface using the default static route. I've actually configured a static route here on a Cisco router, IP route 0000 and then 0000, so any IP address and any network go out to our gigabit Ethernet interface. Instead of G00, I could have put an IP address for the next hop router, as long as the router knows how to get there. And for the R2, you can do the same thing. You could add a static route. As long as you know your next hop, which would be your ISP router, let your ISP take care of any routing decisions. Alright, dynamic routing protocols. This is a routing protocol that dynamically builds routing information such as the following: the network, the next hop, and it will build a topology table, and from the topology table it will choose the best route to put in the routing table, and the topology table can supply second, third and fourth best routes and so on. Static routing does not do well in large networks because you would have to manually add 5, 10, 15, 20 routes per router. So you can imagine you're going to have a lot of work there if you decide to change the IP address or even add one device. So you'd want your routers to automatically learn the routes, update any changes without you having to worry about it, and this is where routing protocols make our life a lot easier. Once you've configured which networks you want to advertise, depending on which protocol you're using, the routing protocol will go ahead and run on automatic settings unless you change the settings for whatever reason. The routers use the routing protocols to learn about available routes, to build a routing table, and the routing protocol communicates with the same routing protocol on another router. You can't have RIP on one router communicating with OSPF on the other because they work in entirely different ways and use different protocols and ports to send their information. So this information is placed in the routing table. So as an example here, router 1, 2 and 3, you've got some different networks connected. PC1's default gateway, because PCs won't do the routing, will always be router 1. You'll just send all traffic to whatever the IP address is of the router there. Normally, in fairness, the PC is connected to a switch and then a router, but this is just a simplified diagram. So if router 1 has 2 routes to the internet, then it will choose the best one depending on the routing protocol. Unless you've changed the settings, you can obviously manipulate things. If RIP has been used, then it will choose a hop count, and it will choose the lowest hop count, so it will be router 1 to router 3, even though it's 128k the link there. If OSPF is being used, then it will choose R2. That might not be correct actually. If I look at the diagram, you'd have to add up the speed of the links, but the speed between router 2 and router 3 has been put as 128k. So that isn't quite correct. Say you've got a 1 meg link between router 1 and 2 and then 2 and 3, then OSPF should choose the that link, even though it's more hops, because it's only looking at the costs. So dynamic routing protocol also allows a router to reroute around a failed link, and this is where the topology table will come in. It will have a ability, or most advanced protocols do, to have some backup routes in the topology table that will quickly take over. Physically connected networks. A router's interface is physically connected to a network. It obviously knows how to reach that network. Since R1's interface is directly connected to these networks, it already knows how to reach them. Alright, so we've covered routing, just in an overview, the routing table, static routes, an example of a static route, dynamic routing protocols and an example, and then physically connected networks. Now, your physically connected networks, you don't have to advertise, but obviously if you want traffic to be able to reach that network, then you're going to need to add a dynamic or static route. But that's all for now. Thanks for watching.
Local area networks, dynamic routing, and protocols. So in the previous module, we discussed what a router is and how it functions, and we discussed static routing, which is the process of manually creating a routing table. So in this module, we're going to define in more depth dynamic routing, which is what allows routing, just like with DHCP and IP addresses, to be dynamically upkept, and which is going to allow for a much more flexible network. Now, although the title of this entire lesson is local area networks, in some ways we could extend this to wide area networks. So we're going to talk about dynamic routing, and then we're going to talk about two different types of dynamic routing. These are distant vector and link state. Now, we sort of alluded to the difference between these in the previous module when I was discussing hops and simply relying on the number of hops to get from one place to the other, versus looking at, for instance, if one link was a dial-up or broadband, or if the link was even shut down completely. And so there are two different types of protocol sets we're going to look at. There are distant vector protocols. These are the protocols that allow distant vector routing. And then there are link state protocols. You'll see them listed here, and we'll talk about each one in depth. And if the acronyms are already starting to freak you out, don't worry about it. What we want to do is just know which ones are distance vector and which ones are link state. So as you can tell, if you can remember that these two are link state, you'll be fine for the Network Plus exam, which again is multiple choice and will ask you to recognize it. But we'll go over them in a little more depth than that. So dynamic routing uses a series of protocols to establish the routing table, as opposed to the route add command. All of the routers pass information about themselves along to the other routers, and they use this information to establish a routing table based on certain specifics of the other routers. Now, there are two different types of protocols that are used, like I just mentioned. There are the distance vector protocols, which in some ways are older, and the link state protocols, which are newer. The reason being that distance vector looks just at the number of miles we have to travel, and the link state also looks at the traffic. So it can tell us if, although we'll have to go further miles, it's going to be quicker based on traffic, just like our GPS system. So let's talk about distance vector first. In distance vector routing, the routers on the network are only aware of the routers that they are directly connected to. So if this is one router, let's call this router 1, and there's a router 2, a router 3, and a router 4. Router 1 is only aware of routers 2 and 3. So these routers don't know anything about the rest of the routers on the network, unless, of course, they're directly linked. Now, they can share route information with these directly connected routers, but the flow of communication is limited as a result. The spaces between distance vector routers are known as, we just talked about this, hops. Now, each router along these paths represent a hop. For example, a network with 5 distance vector routers has 4 hops from the first to last router. If we have 1, 2, 3, 4, 5 routers, there's 1, 2, 3, 4 hops. It's also important to notice that convergence, that's the updating of all of the information to the router table, is going to take longer with this set of protocols than with link state, which we'll look at in a second. This is because the routers don't have the knowledge of the entire network, so it takes longer for them to become aware of a change in the network. So there are 4 main distance vector protocols that are still in use today. The first one is called the Routing Information Protocol, or RIP. Routing Information Protocol version 2. There's the Border Gateway Protocol, or BGP. And finally, the Enhanced Interior Gateway Routing Protocol, or EIGRP. You can see how these two sort of have some similar names in them, and these two are obviously related. RIP, or Routing Information Protocol, is limited to only 15 hops. Originally, it required the information that updated every 30 seconds. And on a small network, this wouldn't have been a problem. But if we're talking about a very large network, which is where networks went, there was going to be a large amount of traffic being sent between routers at any one time. And so this became not very useful because of speed. And also, the protocol itself was just not very secure, and it was very vulnerable to attacks. And it didn't support authentication of any sort. Now remember, we want something like authentication, which would be a username and a password, so I can make sure the router contacting me is the one that I wanted to talk with. So RIP2 came out, and this featured authentication, so it added it for better security. And it also was designed to reduce traffic flow. But it only supported 15 hops because it had to be backwards compatible with the previous version. And since the previous version was only 15 hops, so is this one. So again, not very useful for very large, intense networks such as the internet. Now, BGP is often associated with the internet. And the reason is because it can be used between internet gateway hosts, as this name implies. So it examines the routing table and decides what is the best route for data to travel based on the connections, the distances, and certain addresses. Now, the Enhanced Interior Gateway Routing Protocol, or EIGRP, draws upon information that its neighboring routers have. So it would look at all the routers that it's a neighbor with. Now, routers configured with EIGRP would use that information to determine the best path for data, all determined by what all these other routers know. So that's one of the benefits, is it went outside of itself. So here's an example of basically distance vector routing. The router on the top left, over here, has no idea what's going on with the routers over here. It can only make a routing table based on the routers it's connected to, just like the one on the right can only make a routing table based on the routers it's connected to. Therefore, these two are unaware of each other's existence because they're not connected to each other. Now, of course, they can still communicate because there's probably a router someplace that one of these is connected to that will connect them. But you can see how this is going to make for a lot less efficient routing. So unlike those distance vector routers, routers configured with link state protocols are aware of every other router on the entire network. They use each other to build an enormous network map. And then this network map is shared with each other. Unlike distance vector, link state routers will update with less frequency, so there's less traffic on the network. Now, if a change in the network's topography occurs, then they automatically update with each other and share the map with each other. So instead of simply updating at a certain interval of time, they're going to update whenever there's a change. Now, though this seems like link state has a better set of protocols, link state routers also require more powerful system components, such as better RAM, etc., than distance vector. And that's why we still see distance vector used quite a bit. In some cases, we don't need link state. So it offers quicker convergence as a result of this automatically updating, but this also means it needs more power. So there are two protocols I want to go over with this. The first is the Open Shortest Path First, or OSPF, and the second is the Intermediate System to Intermediate System protocol. These are really similar, and they both use a shortest path algorithm to determine the shortest way for the data to travel. However, we're generally going to see this one, the OSPF, on medium networks, and ISIS on larger networks. Another benefit of this is because it knows all of the routers on the network, it doesn't just think about distance, it also looks at what type of connections we have. It looks at the state of the links, and therefore it can give you, in some cases, the best route available, not just based on the number of hops, but on a lot of different factors. So here we can see what a link state protocol might look like. The two different groups aren't connected directly. However, they're both aware of the entire network layout, as you can see, if we imagine that this was a map inside of the router, and then they can then share that network layout with all of their other routers. In this way, they create a massive network, a massive routing map on their network, and can communicate much more efficiently and quickly. So we've just talked about dynamic routing, which means basically that the routers build their own network map or routing table. This is much more efficient than static routing. We also compare distance vector to link state. Again, distance vector is focused very much on hops and isn't aware of all of the devices on the network, only direct connections. Link state, on the other hand, looks at other features, so for instance, traffic, latency, etc., and has a huge network map. Of course, the downside is that distance vector is going to be a lot more efficient with the resources it has in the router than link state, which requires perhaps better or more powerful system components. We also finally talked about the different protocols. RIP version 2, BGP, and EIGRP were our distance vectors, and our two link states. Again, OSPF is for medium networks, and ISIS or ISIS is for larger networks. We still see all of these used, but these are newer, perhaps faster at convergence, although perhaps not the most ideal for our network or necessary for the network we have. So now that we've talked about switching and routing, I want to talk about something which is a little not so much complex, but allows for more organization within our network, which is called VLANs or virtual LANs.
Welcome to Module 8, Lesson 4A, IGP and EGP. Alright, so we're going to look, this is an overview really to put things in context, dynamic routing protocols, interior gateway protocols, autonomous systems, BGP in brief, not actually how the protocol works much. So we can classify dynamic routing protocols into interior and exterior. The interior protocols, these are the ones that we'll be using mostly as network engineers on a day-to-day basis, unless we end up working for an ISP, an internet service provider. So in order to understand what we mean by the inside of a network, we actually need to understand the term autonomous system, which we generally shorten as an M2AS. So an AS is one or more networks that are governed by a single administration. So it could be a company network or a large company network. And you can see here we have 3 different ASs. Now these ASs could actually all belong to the same company. And inside you've got a different administrative domains. For example, the large cloud AS200 could all be running OSPF. And you could have bought a company on the top left there that is running ERGRP, or just has a different set of administrative principles and rules. In this particular example, you can see AS100 on the top left and AS300 on the top right are actually ISPs. These are internet service providers. So even though it says here that the AS within is under the control of a single authority, you could have various teams managing different parts of the network. However, it's all under the same administrative control. AS is actually defined in one of the RFCs, 1930, if you wanted to Google that, but it'd probably be a fairly long and boring read, I think. According to the definition of the AS, it's a set of routers under a single technical administration, uses an IGP, Interior Gateway Protocol, and common metrics to route packets within the AS. You would generally use an Exterior Gateway Protocol, an EGP, to route packets to other autonomous systems. The RFC says that the AS has a single and clearly defined routing policy, which makes sense if your company is running the administration. Now routers within an AES use an IGP, which I've already said. So here's an image from Microsoft's TechNet. You can see there's two different autonomous systems here. They're running an IGP, an Interior Gateway Protocol, doing all their OSPF, routing, whatever they need to do. And then in order to communicate with another autonomous system, it's running the EGP between the two border routers there. You can further divide IGPs into distance vector, link state, or hybrid. Some of the common ones are RIP and RIP version 2. OSPF is an advanced routing protocol. ISIS. ERGRP is a hybrid, which uses parts of the distance vector and part of the link state. IGRP is pretty redundant now, to be honest. It's not very rarely used because of its age, and it's not very flexible at all. Exterior Gateway Protocol is a routing protocol used to route between ASs, which we've already mentioned. If you're going to route between autonomous systems, it's referred to as inter-AS routing. So an example is BGP, which is mentioned in the syllabus, is used for inter-AS routing. So to route between AS 1, 2 and 3 here, we've got an exterior gateway routing protocol. There is actually a routing protocol called interior BGP, which you can use to route within an autonomous system. I don't think that's mentioned in the syllabus in any detail, but BGP is used to route between autonomous systems, exterior BGP. Now each AS is actually given a unique number. You have to apply for these numbers to your service provider or your internet registry, whoever that may be. And as I said, I've already said this, it needs to be a unique ASN. The ASN is actually supplied by the Internet Assigned Numbers Authority, and they'll split the numbers between whoever governs the numbers within your country. All organizations within the network don't need the ASN. The network that has a single connection to an ISP and a single prefix, which is a subnet mask, doesn't need the ASN because the prefix of that network is managed by the internet service provider. So you may not actually need to worry about any of the exterior routing. You could be running OSPF all through your network, send your traffic to your internet service provider, and let them take care of any exterior routing. BGP is Exterior Gateway Protocol, and it routes packets between the ASs, which I've already said here. It's an example of some different ASs, and on the bottom you've got AS1, which has the prefix 192.0.20 and the subnet mask of /24, 24 bits. According to the RFC, BGP is an inter-autonomous system routing protocol. It actually uses TCP, so it uses a reliable transport method as opposed to other protocols. It listens on TCP port 179, and you can see we've captured a BGP message with a packet capture program. Looks like Wireshark. There's an open message, and you can see the destination port there is 179, and it's using TCP. Current version is 4. If you could look further down inside the BGP packet, it says version 4. That's the current version in use today. Alright, so CompTIA, they actually list it as a hybrid protocol. I'm not sure why they do that. It's a path vector routing protocol. So you can see the paths here. AS1 at the bottom is sending the NLRI is network layer reachability information, i.e. how to get to that particular network and prefix. Router 3 appends its path, which is AS3, and then when the network 192.0.20 is sent to AS5, it's appended with the paths 4, 3 and 1. As a reply is sent, the different paths are removed. So AS4 will remove path 4 and send it to 3, we'll remove 3 and back over to 1. Alright, so we've covered an overview of dynamic protocols, interior routing protocols, what an AS is, BGP. That's all for now. Thanks for watching. Welcome to Module 8, Lesson 4b, Routing Loops. We'll look at what a routing loop is and distance vector routing protocols, split horizon, and poison reverse, which are a couple of the solutions to prevent routing loops on a network, layer 3 loops. So, routing loop is a network problem where a packet gets routed between two or more routers endlessly. Now, this is a different solution to layer 2 loops where we have a spanning tree protocol and some advanced versions of that are there to stop layer 2 packets circulated, because layer 2 packets don't have a time to live value. So this happens when the routing table has incorrect information. As we know, during the routing process, routers forward packets to various destinations. These are based on the entries in the routing table. Now, if one of these entries is incorrect, for example, a network goes down, then a routing loop can occur. So here's an example. I'll go into more detail in a bit, but router D is advertising 192.168.2.0, which it advertises out of both interfaces there. It goes to router B and router C, both of which advertise to router A. Now, router A unfortunately has two ways to send the packet to router, or two paths to see 192.168.2.0, which isn't necessarily a problem. However, what router A does is advertise the fact that it knows how to get to that network to router C, to router B, which then forwards it to router D. Now, router D is hearing from other routers that they know, or they have a route to get to 192.168.2.0. Now, if that network goes down, router D will be sending packets to that network either to router C or router B, because it's heard from those routers that it knows how to reach that network. So this is how a routing loop can cause havoc on your network. So I'll go into a bit more detail with another example here. Obviously have a detrimental effect. Increases packet loss, utilization of the links, CPU utilization on your routers, because it has to process every time the packet's received. So in distance vector protocols, slow convergence causes routing loops. This is when other parts of the network are stabilizing their routing tables slower than other parts of the network. Any change in the network is updated in the routing tables. So during the process, the routing tables have inconsistent entries due to slow convergence. This could be due to bandwidth or processing speeds on your router. The network is said to have converged when all routing tables are consistent. So this means every router's got the same picture of the network and they all agree on which networks are where. So here we've got router C advertising the 10.1.1 network. When the network's converged, all routers will agree that that network exists and they will agree on how to reach that network. So A will send it out of the right-hand interface, B out of the right-hand interface, and then C is directly connected. Now, if this network goes down or the interface goes down, router C will remove that route to the network from its routing table. But before this update is sent to router B sends a periodic update to router C saying it knows how to reach the 10.1.1.0 network. So this update makes router C think that router B has an alternative path to get there, obviously through some other series of routers. It doesn't have a picture of the entire network. Well, it's got this directly connected network and it believes what it hears from other routers. So it will mark this route to get to the 10.1.1.0 network as reachable through router B. A periodic update from router C will contain that network, which we've already said. Router B assumes it knows how to reach that network mentioned in the update. Now when router B receives a packet destined to the 10110 network, it will forward it to router C. When router C receives a packet, it sends it back to router B, and this is where the loop is happening. So unlike switching loops, in a routing loop, the packet will last until the time to live value, which is TTL, in the packet header reaches 0. So you can see the time to live field in this particular packet here, which is a BGP packet capture. Once the time to live value reaches 0, the routers then drop that packet. Distance vector protocols, we've got a couple of solutions. Split horizon and poison reverse. So this is split horizon. The rule is that if an interface learns a particular route, it doesn't advertise that route back out of the same interface. Now, this causes problems when you come to configure a hub and spoke network, and there's ways around it which we're not going to cover here with ERGRP and OSPF in particular. You can change this rule or turn this rule off and set ways to get around it so routing works. So router A learns about router C from router B. What it won't do then is advertise the network back out of the same interface to router B, because this would breach the split horizon rule, and basically the networks attached to router C can be reached via B, so it doesn't need to be re-advertised back to router B and cause confusion. Poison reverse is a form of split horizon. It uses a method known as route poisoning or poison reverse. It allows the router to set a distance to the network as infinity. This is for the how many hops, for example, in RIP. This allows the network to converge. So perhaps you've had some instability. The network attached to router E, network 5, has gone down. So router E will quickly advertise that with an infinite distance, which is known as route poisoning. So we've looked at loops, distance vector, routing protocols, split horizon, poison reverse. That's all for now. Thanks for watching.
Local area networks, VLANs, and SOHOs. So we finished talking about switching and routing, how networks communicate with one another. And so now we want to talk about two other terms that we see a lot when we talk about local area networks and that are important to know for the Network Plus exam. The first is called VLAN, or Virtual Local Area Network. It has to do with segmenting a physical local area network into two or more virtual or logical local area networks. And we're also going to discuss what they do and how we define memberships in VLANs, since this is not a physical distinction, but a logical one. We're also going to discuss a SOHO network, also called a small office home office network. We've probably seen this term in the past because we deal with it when we talk about SOHO routers, which are those routers like the D-Links and the Linksys that you have at your home that allow you to get, for instance, wireless access. Although these provide many different things, they're distinct from a regular router, a SOHO router, because a regular router just does routing, whereas a SOHO router does several different things. Now that's an example of why a small office home office is such an important term when it comes to Network Plus. So virtual local area networks, or VLANs, are a type of local area network configuration. They're actually somewhat of a misnomer. Though the word virtual is really the focus of the name, they're really more segmented than virtual. A VLAN can be described or defined as a group of computers that are connected to one another, although they function as though they are on different networks, even though they sometimes aren't. So the computers that are segmented together are usually ones that are in the same department as the others. For example, we might have an office building with 4 floors, and the accounting employees could be on every floor. A VLAN would allow them to all be connected to one another, even though they're really sort of sharing the network with every other department. In other words, if we had the accountants and then, let's say, the managers, they would all be connected to the same physical network in the building, but we could segment them into separate virtual local area networks, so that way they can communicate with one another and other folks can't communicate with them. They would therefore think that they were connected physically to one another, or all plugged into the same switch, even though we're really using 4 different switches, one for each floor. Now, there's some very clear benefits to having VLANs set up. First, the security is increased. This is because when we segment a network, there are virtual boundaries, and that makes attacking the entire network very unlikely. It also makes sure that accounting people are going to have a harder time getting into the management people's information. So again, even though they're physically connected, all the same, we're giving them a virtual segmentation so that they are separate, and therefore it's slightly more secure. They also increase the performance by freeing up bandwidth and reducing and splitting up traffic from the network. If accounting, for instance, uses a lot of bandwidth and management doesn't, well, we don't want management to suffer because accounting is using QuickBooks and the servers so much. Therefore, by segmenting it, we can make sure all of the traffic that accounting is using is staying on their segment, and management's performance doesn't suffer as a result. We can also group users that often communicate and share data, and so this network becomes far more organized. This is not just from security and performance perspectives. Organization is just from a logistical perspective as well. I can put someone in a VLAN and automatically they're going to have all the benefits that come with being in that segmented area, independent of their physical location. Finally, it also makes the administrator's job a lot more easier, because when everything is segmented up, things become easier to deal with. I don't have to create a specific set of policies or security for one individual when I can simply put them into a VLAN and let it all sort of work itself out. So here's an example of what a VLAN might look like. As you can see, there are 4 floors to the building with computers on each of them, and the computers are all connected to the same network. I've very much simplified this. In fact, we would probably have a switch on every floor. Remember, this would be called the IDFs. And then they would all come together, like we see here, in one central MDF. But for all intents and purposes, they're all connected to the same physical network. However, we only want the accounting employees to share data with themselves, not with the graphic designers or the marketing folks. And we want them to have their own segmented network as well. So with VLAN, we can actually segment out the accounting folks into their own virtual network, even though they're on the same physical network. The same could go for the graphic design folks and the marketing folks. They're all split into segments with similar employees, and we would actually give these VLANs numbers. For instance, VLAN 1, 2, and 3. Now, there are 3 different ways that VLAN membership can be assigned. A membership is a way that the device is assigned to that specific VLAN. For instance, the 1, 2, or 3 that we just mentioned. The first method involves protocol-based VLANs. In this way, computers are assigned to VLANs using networking protocols that are in place, such as the IP address. The IP number is only used to determine the membership, but has nothing to do with the routing of the VLAN network. So for instance, we could say all IP addresses from 1 to 100 are in a specific VLAN, and all of the ones from 101 to 200 are in another. Another thing we can do is what's called port-based VLANs. This requires that ports on the network switch are assigned to specific VLANs. So as you saw previously, we had accounting and marketing and graphics all in sort of different physical locations, but they were all plugged up to a central switch. So what we would say is, for instance, any computers plugged up to ports 1 through 3 are in VLAN 1, and the ports plugged up to 4 and 5 are in 2, and 6 and 7 are 3. Now remember, a lot of switches can have perhaps 200 ports, so this can get a little complex. Finally, there's MAC address-based VLANs. In this way, you've heard of the physical address, and you know that we can use this to actually filter out using what's called an ACL, or access control list, certain MAC addresses from a wireless access point. Well, it works the same way with a VLAN. Depending on the MAC address of the computer that is being connected, it will automatically place it into a specific VLAN. Of course, the benefit with this is because the MAC address is the physical address of the computer and is always hardwired onto that computer, I can move the computer into any different port, and it can get any different IP address, and it will always remain in the same virtual local area network. Now, the other term we want to talk about is a SOHO network, or a small office home office network. This is, generally speaking, as the name implies, a small or home office network that serves between 1 to 10 users on the network. Now, you can have more users or less users, although I guess you wouldn't have less users than 1, but generally speaking, it's really going to designate a very small network. Although they're smaller in physical size and generally smaller in the number of users, they're going to accommodate the network in the same sort of way, meaning we're going to use some of the same protocols and devices. They're just going to be built differently because they don't need to be as powerful. So, for instance, here is a small office home office network. You have 2 PCs in it. Perhaps I have one in the living room, or one in the bedroom, and one in my home office. And maybe even we have a laptop as well. So maybe we have 3 different computers, one's for the kids, one's for my wife, and one's for me. Now, we have what's called a small office home office router. Now, it's called just a router to many of us, but really this is a small office home office router because it does several things. It has a built-in DHCP server. For a lot of us, it also is wireless. So it's a wireless access point, or WAP. It also has plugs on the back, so in some ways it acts as a switch for us, although that's built into a router, so I'm not going to write that separately. It does something called network address translation, which allows the IP address coming from our internet service provider on our modem, which might be, let's say, 126.43.17.3, to be shared among 3 different internal devices. So that way, when information comes in from the internet, it knows which device to send it out to. It also does a couple other things. For instance, it might have a firewall and do some other stuff we've mentioned as well. No matter, and it might even allow for VLANs actually. But no matter, you can see that this one device is taking on several devices that we've talked about previously. If this was your only experience with a router, then you might think all routers operate this way. In fact, they don't. We just call it a router because that's probably the most important function it does, which allows us to get out to the network. But there's not floors and floors and floors of stuff going on here. And this router wouldn't do very well, just because it's not built to, if I tried plugging 100 computers up to it. So the real important thing here is, as you go forward in your career, you'll probably be seeing more and more of this. And if you're going to be supporting homes or really small businesses, then you want to know that perhaps they don't need a separate switch and router. They just need one device. That being said, if a company is growing really fast, perhaps they need to purchase a separate switch that then plugs into the router. The switch, therefore, can help work with traffic internally of the network, and the router will help get the information out onto the network. But it's important again to realize that even though this is a small office home office, or SOHO, that's not the area or the geographic location, remember? That's just the name of this type of network. That it's going to have all the same principles apply. It's just the devices might be smaller and less able to handle a lot of people. So we've talked about virtual local area network, which is basically segmenting a LAN or local area network into several logical partitions. But physically, everything is exactly the same. We talked about how we do the memberships for these. We can do it based on the port it's plugged into. We can also do it based on the MAC address or based on the protocol, which in some ways would be linked to the IP address. Finally, we talked about a SOHO network, or small office home office network, which the real reason we want to know that is because the devices are going to be less powerful and they're going to sort of converge, meaning that we're going to have a wireless access point that's also a router, that's also a DHCP server. Whereas in a large network, we would separate all of this out. So that sort of finishes our discussion on local area networks and LANs. The next lesson is going to talk about wide area networks, or WANs, which we've already talked about slightly when dealing with routing, but we're going to talk about it in a bit more depth.
VLANs and trunks. We'll be doing some labs on this as we go through the course, so don't worry if it doesn't sink in straight away. A VLAN is a virtual local area network, so it's not something you can see by physically looking at the network. You'd have to look at the configuration of the switches. It defines a broadcast domain in a layer 2 network, so just the same as a local area network using a switch. The switch will forward broadcasts. However, if you have two VLANs on a switch, for example the one on the top right diagram there, the broadcast will stop as far as the VLAN. Reason is you need a layer 3 device, which is normally a router, in order to send information from one network to another. So a virtual local area network, for all intents and purposes, it follows the same rule as a normal network or subnet. So you can separate broadcast domains even though it's on the same physical switch by configuring a layer 2. A VLAN is a logical division of switch ports. So if you had 20 switch ports physically on the switch, you could in theory have 20 different devices, each in its own VLAN. You need a router to pass packets between VLANs. Some switches actually come with a routing module that you can insert, which is a bit beyond CCNA level, to be honest, but just for your own information. So VLANs can span multiple physical switches. So we've got switch 1, 2 and 3 here, and you can see we've got a couple of different VLANs configured. Best to have all hosts in the same VLAN on the same subnet. That's all really I wanted to say on that particular subject, but it's just the best idea. No need for a router to communicate if all the devices are all on the same VLAN. Some of the benefits, or why would you bother? The logical separation just gives you better security, helps with the broadcast issues if you do have one, better utilization of your bandwidth. A VLAN marking, obviously there has to be some way, if you're chopping your network into VLANs, for the VLAN to identify itself. Vendors use different approaches. For example, Cisco created ISL, Interswitch Link, which is a proprietary for Cisco devices, They've actually moved away from ISL now, though many of their switches still support it, and they moved on to IEEE standard 802.1q, called frame tagging. Frame tagging inserts the 32-bit tag field into the original frame. So concept of a native VLAN is something you should be familiar with as a Cisco engineer. A native VLAN on Cisco devices certainly is all allocated to VLAN 1. By default, all devices in a VLAN will be assigned to VLAN 1 unless you configure them to be in a different VLAN. So traffic on a VLAN, on the native VLAN, is not tagged. It's not given the 802.1q tagging. What the reason is we have it is it allows a switch to communicate with a device that doesn't understand 802.1q. It is a security risk, which we'll cover later on. VLAN membership. So you can assign VLAN devices or ports to a VLAN statically as a network administrator. It can be dynamic based upon device MAC address. Switch ports are assigned to VLANs and then devices plug into the physical ports. Access ports connect to network hosts. Network hosts connect to access ports. It works both ways around, that sentence. If you want to connect to another switch and you're using multiple VLANs, then these connections are known as trunk ports. So trunk ports will connect more than one VLAN, switches connecting more than one VLAN together. So special port type carries data from multiple VLANs. It can use ISL, although that's pretty much been depreciated now, so you shouldn't be looking at it for the Cisco exams at least. Frame tagging is transparent to end hosts, so the tag is attached by the switch, sent to another switch, and before it reaches the end host, the tag is actually removed. Trunk port modes, we can manually set the interface to trunk with the command switch port mode trunk. Trunk modes include on, which is manually set the interface to trunk. Off, you can tell it to never become a trunk. Auto, silently wait for a request to become a trunk. Desirable, which means actively seek to become a trunk. Or no negotiate. You'll cover these commands in detail when you come to do the CCNA. I probably won't be doing covering these commands and how to configure them for the primer. Configuring a VLAN, you need to manually add the ports to VLANs, and you need to set your ports to trunk. So here's a configuration. I've just done one side because the configuration is the same for both switches. I've created VLAN 5 in config mode by typing VLAN 5. I've given it a name called RND, so you can name your VLANs. It probably makes it easy for you to manage. Interface fast Ethernet 0/1. I've created switch port access VLAN 5. So this is telling the port that it's a switch port layer 2, and the device belongs to VLAN 5 that's connected to it. I've gone onto my fast Ethernet 0/15 switch port trunk encapsulation.1q to tell it what encapsulation to use. That won't work on a 2960 switch because 2960 will only recognize .1q, and I've told it to become a trunk port. Okay, so you'll be labbing some of this up later on, but for now, that's the end. Thanks for listening.
Wide area networks, implementation, and administration. In the previous lesson, we discussed local area networks, or LANs. These were networks that were restricted to a specific single geographic location. Now, in this lesson, we're going to talk more about wide area networks, or WANs. We're going to define them and talk about how they compare to local area networks. So we're first going to define a WAN. which we've talked about in general before, and then we're going to identify some of the steps we would take to implement one, specifically some of the things that make it different from a local area network or LAN. Finally, we want to identify some of the administrative tasks that go along with or that challenge us as WAN administrators, specifically backup and security. So, a WAN is a wide area network, and though it functions very similarly to a LAN, it is different in that it's the way it's set up and the way it's connected. A WAN is a network that's not restricted to a single geographic location like a LAN. In fact, it's often made up of multiple LANs all linked into one big WAN. And these LANs can be across town from each other or even across the globe. Now, we've talked about some other terms, for instance, CAN, like a campus area network or city area network, and a MAN or a metropolitan area network, but all of these could be, in some way, shape, or form, considered a WAN. And of course, the biggest WAN that's out there is the internet, usually referred to as the cloud because, on network diagrams, a cloud is used to represent it. Now, because of this geographic distance, WANs are generally slower than LANs because they have to, as it makes sense, travel a longer distance to deliver data. Just like if I sent a letter internationally, it's going to take longer to get there than one across town or even across the country. That being said, newer technologies, such as fiber optics and et cetera, are making WAN connections faster and therefore are connecting parts of the globe that have never really been connected before. So here's an example of what a wide area network might look like. Let's say, for example, that a company had 2 branches, one in New York and one in Houston. Each of the branches has their own local area network. As you can see here, the one in New York and the one in Houston. And obviously, these are simplified, so imagine that instead of just 2 PCs on each, there are maybe 5,000, and instead of just 1 server, maybe there are 20. But they each have their own switch to talk locally to one another through MAC addresses. Then there's a router on the edge of each network that connects it out to the WAN, or the internet. Of course, the WAN, if configured correctly, can also connect these 2 LANs as though they seem like they're in the same location, just like they're next door. Now, we could set up our own WAN. In other words, we could have our own cables and wires running through from New York to Houston. And that's going to get really expensive. And so we've come up with technologies to use the existing WAN that's out there, i.e. the internet, in order to create secure connections between 2 locations without having to actually physically lay our own cords. However, the idea is the same. We connect 2 LANs through a WAN. And this allows users in both locations to share data easily. A great example of how this is deployed worldwide would be banks, or for instance, American Express or Chase. You can buy something with your American Express card just about anywhere in the world, and it still takes the money out of your bank or puts it onto your account almost instantaneously. Now, the process of establishing a wide area network can be quite complicated, although it's gotten more and more simplified over the years. So I'm just going to go over some of the basic steps and do it in a really simplified manner, basically what you need to understand for Network Plus. A good way to start with the implementation process to set up what we call a VPN, or a virtual private network. As the name implies, it's not actually a private network. That would be one in which I actually have a cord stretched across the country connecting one computer to another. Rather, this is a virtual private network. So this is a type of WAN, and what it does is it actually allows us to use the public WAN, the internet, and create a tunnel through it called a virtual private network that then makes it seem like the 2 locations are right there next to each other. The benefit of a VPN is that it makes it secure. So once you basically install the settings, you need to put in some administrative policies and rules so not just anyone can tap into your tunnel. Otherwise, it wouldn't be very secure and there wouldn't be any point. We also need to select certain users who are going to be able to get access to it and how we want to allow them to have these remote capabilities. We'll talk about a VPN in a bit more detail, and we've talked about it a bit in the past. Finally, we have to add the user accounts to our local networks so that then they can communicate throughout the WAN. This can be configured using either IP addresses or MAC addresses or domain names. So just to go back over that again, I create the VPN, I give access to the users, and then I connect those users to the network. Perhaps I connect them to the network from home, perhaps from their own internet access at home or their own internet router. But in some way I have to give them access, and that generally involves some sort of special software or device and some sort of authentication, such as a password or a PIN number. Now, being the administrator for a WAN can actually be pretty demanding because it's not restricted to a single location. The job involves a lot more than being a LAN administrator, because you might have a LAN that's all in New York, but if I have a WAN, I could have offices all over the world. So the main tasks, though, are still the same. They're just generally on a much larger scale. In fact, almost every task that both administrators would share is just larger in scale and just a little more difficult for the WAN to admin. So backups are just as important on a WAN as they are on a LAN, if not more so, because data loss of any kind is something that needs to be avoided. It's the WAN admin's job to be in charge of backups for the entire wide area network and make sure that everything goes well. The actual process of backing up everything is virtually identical on both networks. However, with WAN, it's much more difficult because, as we said before, WANs span over 2 or more physical locations geographically and are grouping LAN networks together. So we need to not only back up stuff at the individual LAN locations, but then we need to put all that together into one big, huge backup. Now, of course, one of the main differences we mentioned at the outset is speed. And so when we're trying to back stuff up to a WAN, to the internet, speed becomes an issue. I can back something up really quickly if I plug it into the computer. When I start going over the network, that's a little slower. And then when I start going over a WAN, it's going to get a little bit slower too. So full backups can take days depending on the size of the WAN. And obviously the issue with that is if it takes days for me to back something up and I'm working on it, then by the time it's backed up, it's actually hasn't gotten the backup at all. And so we have to deal with all sorts of stuff when we're doing this. So as you can see here, I generally might have some sort of off-site backup area that all the data would sort of route into. Sometimes what we'll do is we'll actually back stuff onto a local backup, and then the local backup will be backed up to a cloud backup or a WAN backup. So we have to deal with space issues, and we also have to deal with speed issues. Now, when it comes to backups, as you can imagine, that's some pretty important data that's flying over the network. And so I also need to make sure not only my backups, but my entire network are secure. And this is a massive job for the administrator of a WAN. In fact, generally WAN administrators don't do this. They hire someone else to specifically focus on security. Again, the big difference with WAN is that the network is not limited to a single location. So there are many more points for access for people who might have nefarious purposes to get into our network. This means the administrator is not only controlling the security at each physical location, but also the security of the entire network as a whole. Theoretically, if an attacker were to infiltrate one of the LANs, it could infect the rest of the WAN. So we have to have a lot of fault sort of safety measures in there as well. It makes our job really difficult. And we not only have to spread against these attacks, but also the spread of attacks. If one site gets infiltrated, well, I can't do anything about that at that point, but I want to make sure all my other sites don't get infiltrated as well. So here we see the same WAN from earlier, but unfortunately, a virus has been sent by a hacker and it's making its way through the WAN to the other LAN. This is an example of something an admin would have to be diligent about. In some ways, what we want to do is create some sort of wall here, so that way the virus, or the logic bomb in this case, couldn't make its way over and just got stuck and stayed in Houston. While it's still a pretty bad scenario, at least New York hasn't gotten infected. So, in this module, I really briefly talked about a WAN, or a wide area network. Remember, a WAN is comprised of several LANs that are connected over a geographic area. In some cases, we're going to connect them through the use of what's called a VPN. When we have a VPN, or a virtual private network, it creates a tunnel over the internet, which is our public switched network, or our public network, and we create a private network within that using all sorts of protocols we'll discuss, so that way these two LANs can communicate as though they are actually one LAN, or they're right next to each other. We also need to have user accounts, so that way the users can't just, not anyone can get onto a network. They have to have a specific password, authentication, etc. And those users also have to have access somehow, whether that's through the internet or they actually are physically connected through our LAN site. We also talked about some of the administrative tasks that can be difficult for WANs, specifically backup, where we're dealing not only with speed, but also with amount of data. And we talked about security. We're not just stopping intrusions, but we also need to limit the spread of an attack. Wide area networks, WAN Transmission Technologies. So in the last module, we talked very briefly and in an overview sense about the implementation and administration of wide area networks. Now, the reason we didn't get into too much detail is because it gets quite complicated when we talk not only about connecting computers together in a local area network, but in a wide area network. And as a result, the technologies become more and more complex, and just like we have people who specialize in LANs, there are people who specialize in WANs. Since the purpose of Network Plus is to give you an overview of all the stuff, we just want to get you familiar with certain terms, so in case you were to come across them, you would sort of know where to look or what to start with when you looked for more information. Now, in this module, we're going to talk a little more specifically about WAN transmission techniques. Again, we're going to look at this from a mile-high view. So the techniques, then, the transmission technologies we're going to talk about are specifically ISDN, which you might remember if you've been around for a while. It's mostly been supplanted by DSL and cable to this nowadays, as actually have most of these technologies. But some of these are still around, and you probably have heard of them. So ISDN is the first we're going to talk about. We're also going to talk about T-carrier, and if you've ever seen the term a T1 or T3 line, that's what this is referring to. We're going to talk about SONET, which is responsible for a different type of classification. It's also using some optics, which is why it's a bit faster and required a completely different form of rating the cabling and the speeds. And then we're going to look at some technologies that allow the data to transmit over this stuff, these T-carrier and SONETs, including X25 and frame relay. X25 was supplanted by frame relay. And ATM, which is not the thing you put your card into to get money out of, but rather a technology of protocol that allows us to communicate over WAN networks. So the first one we're going to talk about here is the Integrated Services Digital Network, or ISDN. Now, ISDN is very high speed, but it's also high cost. And the reason for that is because in order to use ISDN, a special phone line is required to set it up. Now, the line is paid for monthly, just like with any phone line. And this is where the high costs come in, because the service is pretty expensive to pay for every month. In order to set up a connection, the phone line has to dial the address of the receiving computer, very similar to the process of calling a phone on the other end. And once the connection is established, you can drop it by just hanging it up. So if we were to consider this, for instance, to be our ISDN line, you would notice there is sort of a box here, and that's because we need a special box to allow the ISDN to communicate, and it would then communicate onto the other side to the ISP. Now what's interesting here is this is actually a plain old telephone system line, or by the way, plain old telephone system, or PSTN, public switch telephone network. So this is using old telephone technology, but the difference is, instead of using the one that's already been installed into your home or to your office, it's actually another one that has to be laid down, which is how it's different from DSL. Now there are actually two different types of ISDN. We've talked about these in A+ as well. One is the BRI and the other is PRI. BRI, by the way, stands for Basic Rate Interface, and this one stands for Primary Rate Interface. Primary is a bit faster, but it's also a little bit more expensive. Now there are certain speeds these operate at, generally 64 kilobits per second or 128 kilobits per second. Again, that's pretty slow when we compare it to modern-day DSL or modern-day cable technologies, but this was a dedicated line specifically from you to the ISP, which is the reason why, even though it was a little less fast, it was still used, although nowadays we don't see it used as much because it requires special technology, special boxes, special equipment, and so on and so forth. Now the next technology I want to talk about are called T-carrier lines. T-carrier lines are dedicated digital lines that are leased from the telephone companies, much like ISDN. But they're high speed, and they establish a stable connection on both sides, just like ISDN. Now, these connections are always open, unlike ISDN, so communication can be made between the two ends whenever it's needed. There's no hanging up, in other words. Because they provide such a good, dedicated link, they're also expensive to use on WANs, although they were faster, and so we saw a lot of companies used to have T1 or T3 connections, and they might still do. Now, there are different types of T connections available depending on the speed you require. The first, T1, is the slowest of the four types. Now, like the other three, it does create dedicated ends, and it's secure. And T1s are generally going to be used to connect LANs together. So, for instance, if I have my LAN in one side of the city and you have another one, we might get or lease a line from the telephone company to directly connect them if we don't want to use the internet. Nowadays, we have the internet, so a lot of organizations are going to use that and just get a very fast connection, perhaps a T1 or T3 line between them and their ISP or internet service provider. You might sometimes see this, by the way, referred to as Digital Signal 1 or DS1. So if you ever see DS, it's the same thing as a T line. Now T2, as you can imagine, are slightly faster than T1 lines. They're not much different. They're, for some reason, used a little less. It's probably because the speed is not worth the upgrade, and because the T3 is actually even faster than T1 and T2 put together. So if we add both of those together, we'll get a T3. This is sometimes also called a DS3. And T1s and T3s are the most commonly used T lines that you'll probably see out in the field. T4 is even faster. In fact, it is a combination of all of the top ones, meaning it's faster than all of them combined, but it's also pretty expensive, and for most part we're going to see, if you really want a fast line, a T3, and if not, you'll probably see a T1 out in the field. A lot of companies maybe 10-15 years ago used to connect via a T1 or a T3. Sometimes you'll still see that if it's a very large company. Otherwise, they're going to connect via perhaps a DSL or cable connection, generally commercially. Again, this was before you had cable and DSL at everyone's homes, so now the technology has shifted a bit, but it's important to know about this for Network Plus because they're testing knowledge that you might see, even legacy information, meaning old information that you might run into or encounter at an office or a building. Now, in 1984, if you recall your history, or if you were around then, you might recall that AT&T in the United States held a monopoly on the network carrier industry, i.e. phones. So preceding this, smaller companies were given a chance and a challenge to come up with a system that was going to rival AT&T, the one that they had. So a company called Bell Communications, which you might have heard of came up with this called the Synchronous Optical Network, or SONET. Now, SONET is fiber optic. Okay, so rather than being copper, we're dealing with fiber optics, which uses plastic or glass and delivers information and either voice, data, and video at much higher speeds as a result because it's using light pulses. Now, this achievement was so great that it sparked a new system of defining data rates, meaning that the old systems just didn't, it was so slow in comparison, there was nothing that could sort of counter this. And so we start seeing the OC levels. Like, for instance, one you might have seen is OC9, and that would be really, really fast. Now, don't worry about knowing the specific speeds for the Network Plus exam. That's why I'm not covering them. What you just want to make sure of is if you see OC versus like a T1 or T3, you want to know that the OC is generally going to be faster because, again, look at this word, optical carrier levels. Now, in the mid-1970s, we had something called X25, which was everywhere. And this was technology that was developed as a way to send data over copper wiring. So not that OC stuff, but more the T1s, etc., and ISDNs. During its creation, everyone in the networking communications world had a part in creating and implementing it. You might see X25 or terms used to talk about how they would take data and send it over these technologies that it had. And its format was virtually universal. However, it was really limited by speeds because of the copper wiring and just because of the way that the protocol worked, which I'll write up here. And so it was replaced by something called frame relay. Now, frame relay is a protocol that was developed basically to transfer between LAN and WAN endpoints. In other words, between my LAN and the ISP or my larger wide area network. The way it functions is not important. Just know that it functions similarly to X25, but it's faster and it has a more modern build behind it. They're also both called packet switching technologies, and we'll talk about that later. But frame relay can send smaller packets and it can send them faster. We'll talk more about packet switching in the next module. Finally, I want to talk about asynchronous transfer mode, or ATM. So if you ever see ATM on the test, this is what they're referring to, a wide area network transmission or transfer mode. It was introduced in the 90s as a successor to frame relay, and it was really considered a breakthrough because it was what they call an end-to-end solution that could work either from the desktop or remotely. What this meant is that it could work on a WAN, a wide area network, and within the LAN. However, this sort of proved not really to be true because the technology sort of got, for lack of a better word, pushed out of the LAN market because other technologies came around that were just better. It was actually pretty expensive to use, but it did have some benefits. One of the main ones, just like with the T lines, is it could transfer data, voice, and video. It's also a packet switching technology, something we're going to talk about, and it's pretty fast. And one of the major things we're going to talk about with it is that it used what are called cells. And the cells were 53 bytes long, which is fairly large for a packet of data. And I shouldn't say even packet, because what it really we're talking about is it was replaced by cells. So these cells have proven to work more efficiently for transferring than packets that were used by frame relay. And this is really sort of the legacy of ATM, was using these cells that had a lot more information in them than the frame relay packets, which were much smaller. Obviously, the more information we could cram into a packet, the faster we could send it, the quicker we can get information to the other side of a network or a wide area network. And if we just look at this, this is just to show us that it has, again, voice, data, and video all in one cell, which was sort of the amazing thing that this technology ATM did. Good way to remember it is to think about going to the ATM. You can check your balance, you can get money, you can pull out of your savings, you can pull out of your checking, and so it sort of does a lot of things when it comes to your bank. Same with the ATM cell. All right, so those are all the WAN transmission technologies I just want to briefly go over. Obviously, we took a very cursory overview of them, and you could probably Google and find a lot more information that's going to go over your head, and you don't need to know that for Network Plus. But what I want you to remember again is that ISDN was used. It really either came in that BPI, or rather BRI or PRI modes. PRI was slightly faster. It was either in 64 kilobits per second or 128 kilobits per second. It worked over the existing POTS or PSTN phone system, but it was still relatively slow. We don't see it much anymore, although it was pretty big maybe 15 years ago. The T carriers, the big ones you're going to see are T1 and T3. Remember that T3 is faster than T1. SONET as well was introduced. It replaced the sort of T way of looking at speeds with the OC system. OC is fiber optic, and if you think about the O in there being optic, that's why it was faster. X25 and frame relay, both ways of transferring WAN data. This was replaced mostly by ATM. Both of these are what we call packet switching, which we will look at in the next module. And the important thing with ATM, again, not the thing that you put your money into, but rather a WAN technology. It was marketed as being end-to-end, meaning it could work from the computer to the computer, although nowadays we really use it in WAN technologies from a LAN to a WAN endpoint. And the other thing it really introduced was that 53-byte long info cell, which again could hold video, voice, and data in it.
Welcome to Module 9, Lesson 2A, Leased Lines. I'm going to look at T1, E1, T3, E3, and SONET, Synchronized Optical Networking. These are our syllabus talking points, so I kind of need to cover some of the things I think could come up. It's you've got a lot of choices when you want to connect your small office or even a larger office across to the internet or to another remote office somewhere else that you own. Now, one of these options is a leased line, which is a dedicated telecoms line. Now, you don't install the line, the roads will be dug up, or wherever they put their cables will be all laid by a telecoms company, and you will lease that line for a fixed fee, usually monthly, and you have to sign a contract. This leased line is available to you all of the time, 24/7. So since it's dedicated line, it's not shared with other users. Here's an illustration. It's an image from Wikipedia. At the bottom, you've got remote users using the public switch telephone network. They're dialing in. I suppose nowadays they'd be using broadband and VPNs. They could be working from anywhere. But you've got two regional offices on the left that need a dedicated connection up 24/7. They'll go through the telecoms network using a leased line. Based on the technology, the bandwidth of a leased line varies, typically between 56k and 2 meg. To be honest, it's unlikely you'll be using 56k unless you just wanted to have like some sort of keyless entry system, perhaps for a gym where it just needs to authenticate people. But even then, the costs are so low now that it's unlikely to be that slow. Okay, some advantages we've already said. It's your connection dedicated to you, and you can choose how you allocate that bandwidth if you want to use it mainly for video conferencing or some of the use. Disadvantage: they are quite expensive. Typically used to connect businesses that have a geographically distant offices, so they tend to be somewhere out in the sticks. A bit more difficult to use other connections, for example a broadband connection with a VPN. Always active, and like a dial-up connection. Dial-up's a fairly old technology now, quite expensive. Okay, the telecoms company will charge you monthly for use of the lease line. V varies based upon the distance, speed of the connection, also where you are in the world. Some places the technology is still emerging, some places it's still established. So level of quality is assured. It's not as if you can use more bandwidth at certain times of the day, like frame relay, and less at others. Quite old technology, still in quite prominent use, but the technology is quite old. Originally used to connect your mainframes to remote sites. So a few examples that they mention in the syllabus: the T carrier and E carrier, T carrier 1, E carrier 1, and then T3 and E3. The T1 transmission system, originally developed by AT&T. T1 introduced back in 1961, originally developed to transmit 24 phone signals at the same time over the copper wire. It uses something called TDM, time divisional multiplexing. This mixes up the signal in order to use multiple signals over the same physical link. I don't think they go into any detail on TDM in the exam there. So T1 will give you bandwidth of 1.544 meg upstream and downstream, so synchronous. T1 system is used in America, Japan and South Korea. The E system is generally used in Europe. The bandwidth level of T1 was originally called the Digital Signal Level 1 or DS1. I mentioned before the T1 line has 24 channels. Each channel is called a DS0. And you could have 1, 2, 3 of these channels, or all of the channels, depending on how much you want to pay and how much bandwidth you need. Each channel is capable of transmitting data at up to 64K. The leased line T1, multiple channels provide flexibility. So I've said you could already choose some channels or all the channels. E1 is the European version of T1. However, because of the infrastructure that was in place at the time, you could get up to 2 meg, 2.048 meg. This has 32 channels, and each channel's capable of transmitting data up to 64K. You can add them all up, and then there's a signaling channel also. T3 is equivalent to bundling together 28 T1 lines, so much faster. Also referred to as DS3. Since there are 24 channels, the T3 is capable of carrying 672 T1 circuits. So multiple companies will be using these. It's not likely it'll be one company's. So you get up to 44.736 megabits per second with the T3 leased line if you had the whole line. 30 times faster than T1. E1 is the equivalent to 16, or E3, sorry, equivalent to 16 E1 lines, 512 E1 channels. So you get up to 34.4 meg there. So T3 has more bandwidth than E3. Sonnet, I think, is mentioned in the syllabus, which is why we've got it here. Synchronous optical networking. This can be used as leased lines also, but it uses fiber cabling instead of copper. You get higher bandwidth for that, obviously, because it's using fiber optic. The transmission of Sonnet fiber networks is specified as optical carrier or OC transmission rates. OC1 is a transmission line with speeds of up to 51.84 meg. OC3 you get up to 155.52, and then OC12 you get up to 622 megabits per second. The OC12 is typically used by your ISPs as a wide area connection. You wouldn't be using it in a small company for sure. So we've looked at T1, E1, T3 and E3, and also Sonnet networking. Thanks for watching. Welcome to Module 9, Lesson 2B, Wavelength-Division Multiplexing. Bit of a mouthful, but it's a new objective in the Network Plus exam. We'll look at what is WDM. He said WMD. WDM system, course length division multiplexing, CWDM. Again, we love our abbreviations here. Dense wavelength division multiplexing. So what is it? Basically, the idea is to get the most you can out of what you've got. In this instance, what we've got is a single optical fiber, and what we need to do is get as many signals to cross this fiber at the same time as possible. If you just had one signal passing, then the internet would grind to a halt basically. It allows bidirectional communications over a single fiber, so two directions. WDM, it uses a multiplexer, which is you'll often see it referred to in diagrams as MUX, MUX, and then a demultiplexer at the other side, DMUX, DEMUX. So this, if we could just go back, sorry, the multiplexers at the transmitter to combine multiple optical signals of different wavelengths, and at the other side this needs to be demultiplexed back to the original separate signals. WDM systems mostly used by telecoms companies because of the capacity of the network, and again the idea is getting more out of less, so they can expand the network without having to lay more fibre optic cables, which obviously takes a lot of time and money. WDM, they're divided into two types, and these are based on the wavelength patterns that are used, CWDM and DWDM. Wavelength division multiplexing through DWDM and CWDM, they use multiple wavelengths or light, but they differ in the spacing. I'll show a diagram actually in a moment. So in the following factors: a wavelength and the number of channels, the ability to amplify the multiplex signals in the optical space. CWDM uses a smaller number of channels. It can use 4 or 8 channels with large spacing between the channels. The bandwidth of each channel is 3.125 gigabits. So here's an example of CWDM used for transporting data within 100 kilometers, so within a metropolis area. An example of CWDM is 10-base LX4 network. It can transmit data at up to 10 gigabits per second. CWDM cable televisions actually use this, where different wavelengths are used for the downstream and upstream signals. Dense wavelength division multiplexing, DWDM, uses a large number of channels. It can be 40, 80 or 160, but they have small spacing between the channels. And here we go, here's an example from, I'll put the link in down here. You can see the difference here between the spacing and obviously the numbers. The numbers are shown in the diagrams there. CWDM, you can see the spacing, whereas DWDM, it's very hard to see any spacing between the channels. Okay, the high number of channels was the reason for the name dense wave. Typical DWDM system would use one of the following: 40 channels at 100 GHz spacing, 80 channels with 50 GHz spacing. The bandwidth of a single channel is 100 gig. Used for transporting data over long distances, mainly used as the internet background, so this cable will be laid over long stretches and under the ocean. Interconnects large strategic computer networks and core routers. Alright, so we looked at what is WDM, the system, and CWDM, DWDM, sorry, it's a typo. Alright, that's all for now. Thanks for watching. Welcome to Module 9, Lesson 2C, Multi-Protocol Label Switching, MPLS. So what is it? Label switch paths, benefits, tunneling. It's just an overview really because they mention it once in brief in the syllabus. But an MPLS network, it provides WAN connectivity between two geographically distant offices. So it's one of a number of methods for connecting across a wide area network. And obviously each has its pros and cons, which we'll go into. MPLS is high performance, it's packet switching, a packet forwarding. It uses labels to address packets in a telecoms network. Now, it's called label switching because it makes forwarding decisions of the packets based upon the values of the labels, as opposed to the usual way, which is looking at the IP headers. So this avoids having to look at the routing table lookups and all of the problems associated with routing table lookups. Core concept is labels are assigned or pushed into data packets. Since the packets are labelled, the routers in the MPLS network make forwarding decisions based upon that label. It's done without having to examine the actual packet, it's only the label has to be examined. So say remote office A wants to send packets to remote office B. When the data sent by A reaches the MPLS network, the data will be labelled, just like how we'd label a packet if we were sending it via shipping. And then the routers in the MPLS network will act like a courier service. The routers do not open the packet, they just look at the label and decide where to send it for the next destination. The process continues until you reach the edge of the MPLS network when the label is removed or popped before being forwarded to the remote office B. Here's an example of an MPLS network from netcerts.net. The labels in the MPLS network have the information that tells the routers where to forward the packets. This is a simplified diagram where the IP packet has gone across to two routers and then it's hitting the MPLS network at router PEA, which adds the label, and then the label is finally removed at router PEZ. So there's only three routers involved in the MPLS network here. So as I said, this is different to the traditional routing where each packet's header has to be examined. Each router step by step has to do complex lookups and obviously deal with all the other issues associated with routing. A label switch path, the data transmission in an MPLS network occurs through a path called the label switch paths. This is the sequence of labels at each and every node along the path that establishes between the source and the destination. This is all actually set up before the data is transmitted. Multi-protocol basically means a number of protocols can be used. Really the only protocol left to send over MPLS is IP, IPX, SPX and other such protocols like AppleTalk aren't used anymore at all. MPLS is often referred to as layer 2.5 because it sits between layers 2 and layer 3 of the OSI. Some of the benefits, not dependent on layer 2 technologies such as ATM, SONET and Ethernet. It can be used to carry different types of traffic, and ATM, SONET and Ethernet frames. Tunneling, MPLS can control the entire path of a packet by tunneling through the intermediate routers that span multiple segments. This is a unique feature of MPLS. It's used in provisioning MPLS-based VPNs, which is actually outside the syllabus. Alright, so we've looked at MPLS, LSPs, some of the benefits, and we've mentioned tunneling. We haven't gone into any detail, obviously. That's all for now. Thanks for watching. Welcome to Module 9, Lesson 2D, an overview of GSM, CDMA and WiMAX. Again, we're just hitting a few syllabus topics that CompTIA kind of mentioned in passing really, but they are marked down there. We'll look at what is 2G. You may be familiar with it if you've had a mobile phone, or I think you call them cellular phones in America perhaps. Enhanced rates for GSM, LTE, long-term evolution, and CDMA. So what is it? It stands for Global System for Mobile Communications. You used to actually be able to plug an adapter into your laptop and use a GSM card for accessing the internet, but it was pretty slow. My experience was pretty unreliable and pretty expensive, so not fantastic, but if you were desperate it kind of did the job. Developed by European Telecom Standards Institute, ETSI, and this is the protocols for second generation, the 2G cellular networks, digital, used by mobiles. The original standard was for 2G wireless telephone technology, and it became the global standard for mobile communications. It's been left behind now. So GSM is a cellular network that uses radio signals for mobile comms. The cellular network is a mobile network that is spread across the land area called cells. One or more fixed transceivers or base stations we're probably more familiar with. They provide each cell with network coverage. Obviously, the further away you are from these base stations, the poorer your signal is, until at some point you'll have no signal at all. We commonly call them mobile phones during the cellular network calls. Alright, what is 2G? Second generation, as we've said. They use radio signals, developed as a replacement for the old cellular network that used analog radio signals. So that was real old school stuff. They were quite easily hacked into at the time. If you had the equipment, you could listen to people's telephone conversations with a scanner. The original GSM standard was actually designed for full duplex voice telephony. It was just adopted for data later on. It originally operated at 96 bits per second, which is pretty darn slow. Evolved over time to allow data comms through an enhanced GSM technology called EDGE, or Enhanced Data Rates for GSM Evolution. This was considered a pre-3G radio technology. It's part of the ITU's 3G definition, and the idea is it delivers higher rate bits per radio channel, so it's 3 times faster than ordinary GSM, also used for internet connections. Long-term evolution, LTE, is today's mobile networks use something called LTE. Commonly marketed as 4G, you may have heard 4G LTE. High-speed data rate access based on the EDGE and HSPA network technologies, which are legacy. Download speed is 300 meg, upload is 75, so it's asynchronous. CDMA is code division multiple access. This uses a spread spectrum technology, and basically the idea is multiple users can communicate independently but using the same bandwidth, and there shouldn't, in theory, be any interference on the connection. Represents a second generation 2G digital radio solution. Uses the spectrally efficient technology for mobile communication. Alright, moving on to WiMAX. Worldwide interoperability for microwave access. No wonder they've shortened that one. Technology is based on 802.16 standard, which you can look up in your own time. It delivers wireless broadband services anytime and anywhere. Here's an image from Conic.com of indirect access with the outdoor customer premise equipment connecting through a base station when you've got a poor connectivity, but the signal goes through multiple paths. The 802.16 standard is developed for providing a non-line of sight connectivity, so it would be quite useful in areas where there's a lot of buildings and things in the way, trees and other buildings and antennas. WiMAX is sometimes referred to as Wi-Fi on steroids, similar to Wi-Fi but can provide broadband access to a large area, supports communications over a maximum of 30-mile radius. They're either available for fixed usage or mobile. So WiMAX is the standard, which I've already said. Download speed is up to 37 meg and the upload speed is up to 17. Mobile WiMAX is based on the 802.16e standard from 2005. They got a throughput of up to 100 meg. So we've covered in brief GSM, 2G, enhanced data rates for GSM, LTE, CDMA and WiMAX. That's all for now. Thanks for listening.
Wide area networks, WAN connectivity, and voice over IP. In the last module, we discussed the different types of WAN switching and the different transmission technologies, some of which are going to reappear in this module. That's because transmission technologies and connectivity options are going to go hand in hand. So we're going to talk about some of the WAN connectivity options that we have, including a leased line, packet switching, which is different from circuit switching we've seen in the past. Something called cell relay, which, as the name implies, is related to ATM. And then we're going to discuss briefly voice over IP, which is something that'll come up again, but which is more and more become a necessary part of our networks. That is, making phone calls over our internet network or our Ethernet network, rather than over the plain old telephone system or public switch telephone network. And just to recall, that's either called POTS or PSTN. That was the phone network we used for lots and lots of years until we started getting more into a internet-wide world. So when we talk about voice over IP, I want to bring up a very important protocol called SIP. If you see SIP on the test, it is going to be directly related to voice over IP. Now, one of the ways in which wide area networks can gain connectivity is through a leased line. We've seen this in the past module. A leased line is sold to a company for a set amount of time, thus the word leased. Now, a leased line provides steady, permanently set up connection, such as a T1 connection, or perhaps even a T3 connection or OC9 connection. This connection usually allows data, voice, and internet connectivity to pass through it. Now, typically, these are used for establishing a WAN and connecting two different geographical locations to one network. Though this connection is permanently there, it can only be accessed as long as the customer is paying the lease for it. This is where the disadvantage to it is. This can be pretty expensive to buy a lease for because, again, if I have an office in, let's say, Manhattan, and I have an office in Houston, the idea is I'm leasing a direct line between the two. And as you can imagine, because I have my own line that's going between these, it's pretty expensive. The reason I lease it again is because I'm not a telecommunications company. I can't just lay this cord. I need them to lay it for me, and then I'm going to lease it from them. So the upside to this, although that's the downside, is that it's the most secure connection that we have. Now, in the last module, we talked about T-carrier lines, and a T1 line can be leased and provides a secure connection, so therefore, it is a leased line. Now, we also talked about in previous lessons switching. We talked about how important switches were to the functionality of a local area network. They provide a communication path between two endpoints, and they manage that flow of data so that way we don't have a bunch of traffic going on. In effect, they basically make sure that packet going from one location gets to the other and doesn't sort of interrupt the flow of all the other packets that are going on. Now, in a LAN, these two endpoints aren't very far away from each other. However, on a WAN or a wide area network, these endpoints could be on opposite sides of the globe. And that's why switching is such an important topic to understand. Now, when it comes to a WAN or a wide area network, there are two different types of switching. There's packet switching and there's circuit switching. Packet switching is when the data is broken up into smaller chunks, or packets. And then they're assigned a source and a destination, and they stop at different nodes along the way. Every packet has these assigned to it because they don't always stay in the same path as the other packet, and I'll show you a visual to clarify this in just a second. They're usually going to split up which paths they're going to take in order to avoid colliding with each other and to make it much faster. This principle of packet switching is sort of similar to a torrent. If you remember, a torrent file, if you've ever used one, it contains information about data, like files and folders that can be distributed. Now, if someone torrents a file, the folders and files within that torrent are downloaded to the user's computer. But the torrents are a peer-to-peer sharing system. They work almost exactly like packet switching does. Torrents collect packets of data from wherever the data is available and then reassemble it in the whole file on your computer. In other words, you can be downloading information for the movie you're torrenting, or of course the movie that you own that you're torrenting. We wouldn't want to say to do anything illegal. And what you're doing is you're actually taking that information from, say, 5 or 10 or 100 different systems that are out there. They're all coming down into your system, and then you're compiling it all together to make one movie. This isn't unlike Willy Wonka, where the information goes up into the Wonka vision, gets split up into a whole bunch of little pieces, and then gets brought back to you. Except all the little pieces don't have to be sent from all the same place. So the benefit of this is that it can go a lot faster. That's with packet switching. The downside, of course, is that there's a good chance that the packets can be lost along the way. Now, the second type of switching is called circuit switching. This method of switching requires dedicated physical connections. So whereas packet, we're dealing with data, in circuit, we're dealing with physical connections that allow data to be transferred. Now, it can be difficult to establish these connections, but the results are a lot more reliable than with packet switching. With circuit switching, the connection that's made is dedicated for that purpose only. In other words, I create a switch over which all the data is going to be sent. Once I'm done with that, and the transfer is complete, I no longer need this circuit, and so it might be switched to allow another computer or system to talk to one another. Now, there's a very small chance of the data getting lost along the way because the circuit switching establishes a consistent data transfer. However, the downside is I can't take it from, say, 10 different sources. Instead, I have to have one sender, one receiver, and in this case, because I can't split it up, it might take longer to find that one connection, although once that connection is established, it's a lot stronger. So here's an example of what packet switching might look like. The packets that are traveling across the network are all going on different paths, right? One might be going like this. One might be going like this. The other might be going like this, etc., etc. They're all going to reach the destination on the right, but they're going to do so in a different way if we say that this is the source and this is the destination. This is going to alleviate traffic network because, as you can imagine, I don't have to require everything to go across this one dedicated line. Instead, it can use whichever line has the least traffic on it at that time, and therefore everything's going to get there with the least amount of traffic. However, it's also not the most secure way, because obviously there are a lot more points for someone to enter in and perhaps steal information or sniff information. And this packet, for instance, might have been gobbled up by a hacker, someone who wanted to get the information, or it somehow just got lost. So this is where the issues with packet switching come in. Now, in the last module, we talked about many of the different transmission technologies that WAN has, and one of those, if you recall, was ATM, or asynchronous transfer mode. And imagine that name, asynchronous. That's important because it's not at the same time, it's asynchronous. Now, ATM splits data packets into these cells, and these cells, again, are 53 bytes in order to send them. Now, this made data flow simple, and it did not back up the system and didn't cause too much traffic. So very similar to ATM is what we call cell relay. Cell relay is a connectivity method that breaks data up into equal-sized cells and then sends them to their destination. Now, unlike ATM, these cells aren't necessarily 53 bytes, but they're all even with each other. So they're all sent across the network, and they all are even, meaning they each have the same amount of bytes. Now, the data itself is transferred very similar to a method that we just talked about in packet switching. The difference is that packet switching doesn't evenly break up the packs, which could cause some network traffic. So cell relay is good for simultaneous transfer of data and voice, meaning it allows me to do voice and data at the same time. However, just like with packet switching, it's not very secure, and some of the cells could also be easily lost along the way. Now, as we all know, voice over IP has sort of taken the world by storm. International calling can be really, really expensive. And so voice over IP is a way to make calls through IP packets or using the internet. If you recall, IP packets are part of the TCP/IP suite. They involve giving every single device on a network an IP address, which is just like a phone number in an old system. And this would allow us to save money on international calls. It's by far a cheaper alternative to a phone service because unlike a phone service, there are no monthly bills to pay and there are no long distance charges to deal with. So VoIP uses the existing internet infrastructure that's already in place to make connections for calls. And what it does is it basically puts the information from your voice into packets and streams those across a network. Now, like almost everything in computing, there is a protocol that allows this to work, and that is called the Session Initiation Protocol, or SIP. Write that out. Now, if you see SIP on the test, or if you see voice over IP on the test, you can be guaranteed they're related. The other thing you're going to see when it comes to voice over IP is called QoS, or quality of service. The reason is we want to make sure the quality is pretty good. Otherwise, if we're getting the packet at the end, if we're getting if I say a sentence and I get the end of the sentence before I get the beginning of the sentence, then the quality is not really good and I can't really rely on this. So getting back to SIP for a second, this is the protocol that's designed to set up and maintain internet multimedia sessions such as voice calls. It's also responsible for communication that's used in video and audio conferencing, online games, voice chats on the internet, and so on. So it's extremely important, and without it, basically, VoIP wouldn't function. So here's an example of what VoIP might look like. As you can see, there's both a phone and a computer that are connected to this network on the top end. The PC connects through a modem or perhaps even a network card. And the telephone connects through some sort of adapter, and they both connect through the internet. Generally, there's also one box that everything sort of connects into, and that sends it out into the internet, out to your internet service provider. And again, the important thing here is that everything is being captured into IP packets. So your voice is being turned into, for lack of a better term, data in an IP packet, which can then be sent over the internet. Great. So now we've identified some WAN connectivity options, including a leased line, which is a line that you lease between two places. An example of that would be that T1 or that T3 line. The reason it's leased is we don't actually put it in. The telecommunications company does that for us. We simply lease it for a set amount of time. It's very expensive, and so a lot of companies don't use leased lines unless they require one. What they use instead is a connection to the internet, and then they will have basically virtual private networks and software and other hardware that create a virtual leased line over a public line. We also talked about packet switching, which was important, different from circuit switching, which is sort of what switches do. Packet switching would allow me to send data, and if I had many different routes for that data to take, it could take any one of those data packets, run in sort of any different configuration I wanted it to, and it would all arrive at the end and be put back together. So the packets all basically get broken up, sent out, shuffled, sent in whatever order they need. In the packet, each packet has the source and the destination, and also it has a number basically. So that way, at the end, it knows how to put it back together in the correct order. This is somewhat similar to cell relay. The difference with cell relay, which is linked somewhat to ATM, is that all packets are the same size. We also briefly, which we'll talk about more, discussed VoIP or Voice over IP, which allows us to make phone calls or voice calls over the internet or using Ethernet technology. The protocol that allows this to occur is called SIP, or the Session Initiation Protocol. Again, if you see SIP on the test, you can guarantee that it has to do with VoIP or Voice over IP. Now, in the next lesson, we're going to talk more about remote networking. Obviously, something more and more of us need to do with telecommuting, and also something that would allow us to replace, for instance, a leased line with more of a temporary solution.
Welcome to Module 9, Lesson 4, WAN Protocols and Services. As usual, covering the things we haven't already gone over. So under wide area network still. We're in brief, i.e. the stuff I think you need to know, because there's entire books on some of these protocols. PPP over Ethernet. Dynamic multi-point VPN, which has actually just been brought into the Cisco CCNA syllabus. SIP trunks. Josh talked about SIP trunks earlier. Briefly, he actually wrote it onto one of the slides when he talked about voice, so I'll just cover an extra little bit. PPP, very popular over dedicated and circuit switch links for wide area connection. Now, the typical question you would get, certainly for Cisco, is if you're connecting a Cisco device over a wide area network to a non-Cisco device, what protocol would you use? You would probably use PPP because it's vendor neutral. Anyone can use it, whereas Cisco has their own set of protocols that you can choose from for use over wide area networks. Also works over many different link types, so synchronous, ISDN, asynchronous, DSL, etc. Two components inside PPP. You've got your NCPs, which are your network control protocols. These interface with the TCP or network layer, talking about OSI. And then you've got link control protocols. This manages the data link sessions and connections. That'd be your typical exam type question. The other thing about PPP is it offers authentication built in, which is very useful. Now you've got two types, PAP and CHAP. Unfortunately, if we go over to password authentication protocol, your password, if you sniffed the packet being sent over the line, the field, you would see password. It doesn't encrypt the password. CHAP actually sends a hashed value of characters, whatever they may be. So you don't actually see the password. So this is the one you're going to want to use. No one really is going to use PAP anymore unless it's you can configure it. If for any reason CHAP goes down, you can configure it to it's called a fallback, PPP fallback. But really, you'd probably rather just have your PPP line go down and you troubleshoot it. But CHAP is what you will want to use because it offers the encryption. There's a three-way handshake. This is another typical exam question. And you can see it in the diagram here. There's a challenge, a response, and then it's accepted or rejected. If it's accepted, then the line comes up and you can pass then your data. If it's rejected, then obviously the PPP session won't come up. And I spent some time debugging this when I worked for Cisco systems. Continual authentication, so it doesn't just do it once. I'm not sure, you'd have to read the RFC and see how it's been implemented, but there's regular challenges take place during the session. Usually there's a host name and password. For example, the host name of this router is router B, and you would configure on this side here, you would say the username that's permitted is router A, and I've just used a simple password. So what happens is this router's host name acts as the authentication host name. It calls using its host name here and its password, and in the database over here you've configured that as the parameters that's going to be permitted. You can do it in a lot more complicated ways. The commands on a Cisco router are PPP authentication CHAP, or if you want to use or clear text, it's PAP. Moving on to PPPoE, it allows encapsulating PPP inside Ethernet frames. No surprise really, because the clue's in the name there. Often used with your DSL connections, and it tunnels to your internet service provider. I'm just thinking of questions that they'll ask because you're not going to have to configure this. So they may ask a question, what are the PPPoE stages? There's a discovery, which is obviously the building up the connection between the two devices, and then the actual session where the data is going to be sent across the line. This is the same with most protocols, as you know. Moving on to dynamic multipoint VPN. This allows your remote VPN connections to bypass your headquarters VPN. So in your traditional VPN service, your spoke router over here, say it's in Las Vegas, this is in LA, and this is in where can we have this? Atlanta. Bit of a pain. Your branch office would have to communicate to your headquarters in order for the tunnel to actually take place, but it would be routed from here to here. And obviously, if there's problems in your headquarters office for whatever reason, or the line is congested, your connection won't take place. So the point of dynamic multipoint VPN is your branch offices, your spoke routers can directly make a connection, and it bypasses your VPN's router. You do require a hub and spoke topology, which we spoke about earlier in our topology sessions. Oh, that shouldn't be in there, sorry about that. I left that in from my last slide. Alright, and finally I've got this slide here, this image from mynetphone.com.au, but this explains basically how SIP trunks work. Session Initiation Protocol. If you ever hear SIP or Session Initiation Protocol, which Josh mentioned, you immediately think voice over IP. This is what enables voice over IP to work. SIP trunks enable your PBX to send and receive calls via the internet. So what it does is it takes your your typical phone connection and acts as a bridge between the internet. That's the point of the SIP trunk. So digital equivalent of a phone line enables you to make and voice and or video calls, video conferencing calls via the internet. Acts as a bridge between your PBX, which is your phone system that you'd have at your corporate office there, and IP telephony. Alright, so we covered a lot of stuff, but I think only what you need to know, and it is covered in other presentations as well by Josh: PPP, PPPoE, Dynamic Multipoint VPN, and SIP trunks. And I've highlighted what I think would be the typical exam questions. So that's all for now. Thanks for watching.
Remote access, remote networking fundamentals. In the last lesson, we talked about wide area networks. We talked about how they can be implemented, what their benefits are, how they transfer information, some of the technologies we use, and so on and so forth. Now, in this lesson, we're going to talk more about remote networking access. Remote networking and WANs actually really go hand in hand. And if you think about it, more of what we do now, more than ever, allows us to remote in from home to the WAN, the largest WAN in the world being the wide area network of the internet, and then access our LANs at work. This really allows us to not only get stuff done, but is changing the landscape of how networking, the internet, and security have been created and how we continue to work with them. So we're going to talk about this in this module and in the next couple. But for this one, the first thing we want to do is define what remote networking really is. Then we want to identify some of the technologies that we see in place when we discuss remote networking. These include VPN, which we've already discussed in some broad detail, or a virtual private network. Radius, which allows us to authenticate users once they connect, and TACAX, which allows us to keep it all secure. So these three are used in enterprise settings to allow someone to remote in from home and connect to the network at work. So WANs are networks that are not restrained to one single physical location. They're typically, as we've discussed, many local area networks that are joined together to create one big WAN. However, this isn't the only configuration they can have, and remote networking is something that ties in really well with wide area networks. You see, remote networking is the process of connecting to a network without being directly attached to it, or physically present at the site. In other words, a user or a group of users can remotely connect to a network without actually being where the network is established. So, if I were at home and wanted to connect to a network, say in China, I could actually connect as though I were sitting right in an office in China without actually physically being present. This type of thing comes in handy quite a bit. Now, remote networking doesn't always happen between two very distant locations. In fact, it can be used within the same building, the same room, while traveling, and remote networking not only works on a long-distance level, but on a local network as well. For instance, suppose that I'm an administrator in my office, and I want to access the contents of a user's computer, or I want to restart a server. Well, instead of having to get up, walk up to the 4th floor, or down to the basement, wherever the server is, I could simply remote in to the server and reboot it from there. So you can see that it's a huge time-saving device. However, it also opens up a lot of possibilities for security issues and so on. So here's an example of what remote network connectivity could look like. The user is in China on the right, and they need to connect into the network in New York here on the left. So they're sitting at one physical location, and they connect through a WAN, which we're going to call the internet, the largest WAN in the entire world, and they remotely connect in some sort of way, which we'll talk about, usually through something called a VPN, using all sorts of public networks, and eventually they reach the router at their corporate office, And then it's as if they are actually sitting there connected into the network. They can now access resources on local clients or even on the server, and all without physically being at the location in New York. Now, there are a lot of terms we hear when we talk about remote networking and remote access. Most of them end up being acronyms for the sake of time and convenience. But there are three that I want to specifically talk about here that we're going to talk about in more detail in the coming modules. The first is VPN, or Virtual Private Network. This is something we've talked before and we'll talk about a little bit later, but in essence, it extends a LAN or a local area network by adding the ability to have remote users connect to it. The way it does this is by using what's called tunneling. It basically creates a tunnel through the wide area network, the internet, that then I can connect to and through. So all of my data is traveling through this tunnel between the server or the corporate office and the client computer. This way I can make sure that no one outside the tunnel or anyone else on the network can get in, and I can be sure that all of my data is kept secure. This is why it's called a virtual private network. It's virtual, it's not real, it's not physical, it's definitely private because the tunnel makes sure to keep everything out. Now, the next term we want to talk about is called Radius. Radius, by the way, stands for Remote Authentication Dial-In User Service. I'm going to write that out here. Remote Authentication Dial-In User Service. Now, if you notice there's a dial-in, well, remote can actually be dialing in using a modem. We don't use that much anymore, but this is an older service. What this does is it allows us to have centralized authorization, authentication, and accounting management for computers and users on a remote network. In other words, it allows me to have one server that's going to be responsible, and we're going to call this the Radius server, that's responsible for making sure once a VPN is established that the person on the other end is actually someone who should be connecting to my network. Remember, I don't want to just let anyone connect. I want to make sure the person who connects is someone who belongs to my network. Generally, what we'll do is we'll have active directories, which is what Microsoft uses to create, for instance, usernames and passwords, and we'll link that up or sync it with the Radius server. Sometimes this is done on a separate server. Sometimes it's done on the same server. Either way, once you connect the VPN then goes to the Radius server checks the Active Directory, and now I can make sure that only users of the network are allowed onto my network. Finally, we have something called TACACS, or Terminal Access Controller Access Control System. It's really long, I'm not going to write it out. This is actually a replacement for Radius. There was another replacement for Radius, by the way. It was called Diameter, and if you're a math whiz, you'll notice that Radius is half of a diameter when we talk about circles. But diameter wasn't really used much. TACACS, on the other hand, is a security protocol. It allows us to validate information with the network administrator or server, and the validation is tested when we try to connect, just like with Radius. Of course, the benefit is TACACS is newer and more secure than Radius. So it basically does the same thing. It's just a little more powerful. All right, so this was short, but I just wanted to give us an overview of remote networking, and we're going to talk more about that in the coming modules. So we talked about remote networking, what it is, allowing us to access a LAN basically through a WAN, whether that WAN is the internet or a public switch telephone network. It also allows us to access the LAN from a different physical location. We can also identify 3 remote networking technologies. The first, virtual private network, creates a tunnel over the WAN through which we create a virtual network that is also private. We also talked about radius and TACACS. Both of these allow for authentication, so we can make sure the person who establishes the VPN is actually allowed on our network. Remote access and implementation. We've now talked about some of the basic information when it comes to remote networking, and with that base knowledge, it's going to come into play in this module. We're going to talk more about remote access and how to implement it. Some of the stuff we're going to talk about is overview, and some of it is still pretty basic. Again, you're not going to be able to take this information and just implement a network or remote access to a network. That would take a little more legwork and a little more research. What this is really giving us is an overview of how it all functions and what you need to know for the exam. So we're going to talk about remote access as opposed to remote networking. Remember, remote networking is sort of the act of creating the network to allow remote access. So we're going to talk about what it is, what it does, and the benefits for it. We're then going to discuss the steps of implementing a remote access policy or remote access technologies. So, remote access is a practice that's extremely useful and becoming more and more popular constantly all around the world in every IT situation. As we've mentioned, it's a way for someone to connect to a corporate LAN from an outside location. It's not always used in a corporate setting, but for the most part, that is its main use. However, for instance, perhaps you wanted to remote into your home network or a home computer from the office, or you wanted to remote in from outside your home. These are things you could set up as well. With remote access, you then have the ability to connect to a physical network without having to be anywhere near the network. In fact, you could be on the other side of the world and still connect as though you're sitting at a desktop PC on your LAN. Now, you can imagine how this is even going to take it to another step where we could start to have computers that are on a LAN or a WAN that we don't even control or have any physical access to at all. Instead, all of our computing will be done remotely. This is already coming into play when we talk about cloud computing and things like Amazon's Elastic Cloud, which allows you to set up a virtual computer on a remote system and then remote into it and through remote access and connect to it just like you would be connecting to the computer as though you were sitting in front of an actual computer. Now, this obviously speaks to not only a greatly reduced amount of cost, but also a lot more flexibility. Because now I can set up a computer anywhere in the world, and for instance, if I had 20 computers, I could remotely access them, and I would only need one monitor, keyboard, and mouse. So you can see where this is really going to come into major play. Now, we've already seen this before, but here's another example of what remote access might look like. I'm at home, and I want to access the office computer. So I connect through the internet to the router over at the office through something called a VPN. And now it's as though I'm sitting there working at the office. In fact, if it wasn't for the fact that the boss had to see my face, they would think that I was actually there. So the first step in implementing remote access is assessing it. We need to, before we can set anything up, we need to know what exactly we are going to set up. So first you need to review and determine all the connections that are going in and out of the LAN. This means deciding how remote users are going to connect to the network. For instance, if I want someone to dial in directly, they could use a modem. This is going to go over the public switch telephone network or POTS, the plain old telephone system. Alternatively, let's say I have a T3 connection connecting the corporate LAN out to an ISP. Well, then, as long as people at home have internet access, which today they basically would, and most of them have broadband access, they'd be able to connect back through their ISP to the network. Second, we have to understand and know exactly what applications and systems they're going to need. For instance, I can give them access to their computer, which might be one way to do it. But if I have a lot of people logging in constantly, remotely, and I need to give them access to their computer, that's going to be pretty difficult to set up and quite uncentralized. So what I might do is create one remote access server, RAS, in which everyone can connect and get their profile or information. This also goes with something called virtualization or cloud computing. So basically, they would log on to this very powerful server and they would see what looks like their computer. In fact, if I was basically doing this all the time, I might just do this for when they sit at the office. They just sit at a terminal sort of thing, turn on the computer, and they're connecting actually to a server that's not even located in the building. Finally, I want to determine the number of remote users. If I'm only giving this to, say, the top honchos at the firm, that's one thing. If it's going to be for everyone in the entire operation, I'm going to need to spend a lot more time and resources devoted to setting up remote access. Now, the next thing I have to do is think about the considerations and the things that are necessary for remote access in order to implement. For instance, the first step is to make sure that the remote access solution you create is flexible enough to support all those connections and the users that you've just established. For example, if one remote user is connecting through a T1 line and another one's connecting through dial-up, your solution is going to need to be able to accommodate both of them. Of course, nowadays, that's not such an issue because everyone has broadband connections. But if they're not connecting in the same way, or one person is going to be traveling around while most people are going to be connecting from home, well, those are all things I need to take into account. Next, I need to establish some sort of centralized access point, meaning when they hit that router, if they're coming out of the internet, into the router, I need something here that is going to centralize all of the stuff coming in. I also don't want to just give them access to the network. I might want to send them into a separate network temporarily while I make sure that they get authenticated, perhaps a virtual LAN or a honeypot or something. So it's important, or a demilitarized zone. So it's important that I have some area where they can go and understand what the central device is going to be. In some cases, we could call this a VPN Concentrator, which is basically a device that helps set up VPNs. Finally, I need to consider security when I'm establishing this remote system. As I mentioned, I don't just want to give people access to the network. I want to make sure the people on my network connecting wirelessly or remotely or physically connecting can all connect securely. I don't want someone to tap into their connection on my end or on their end. So it's really important we take security into account. Nowadays, we have a lot of authentication methods that would provide you with, say, a key ring. And on that key ring, you'll have what's called a token. The token provides you with, say, a 6-digit number that randomly alternates every minute. Unless you have the token, and that token is set up with your computer, you won't be able to get access to the internet. These things we've talked about in A+, but I'm just reviewing them a bit more. Now, I also need to have some procedures and policies in place so that people understand how they're going to be able to access and what they're going to be able to do. The policies ensure that the procedures are followed, and the procedures ensure that the safety is used when remoting into the system. So designing these policies is up to the network administrator and perhaps the Central Information Officer, or the CIO, or the Chief Information Officer. Now, it's common to have a system configuration that does not allow users to remotely access the system after a certain time at night. I might want to do this for a number of reasons. However, the policies need to be, whatever they are, well documented and easy to understand. I need to know exactly how I'm going to access stuff. Otherwise, what's going to happen is you're going to say, hey, we have remote access, and suddenly people are going to start calling the help desk saying it's not working properly. We also want to make sure that they're accountable if they don't follow specific rules, policies, etc. So I need to say if someone remotes in or loses their token, they could be possibly fired because that's a huge security breach. Just like I don't want to give my laptop or my token to someone, even if it's someone within the network, if I've been told specifically to keep it. Same with passwords, usernames. Basically, the idea is the more ability I give people, the flexibility I give people to connect, it also makes it much more of a security hazard. Finally, you need to make sure human resources is behind all of your policies. They're the ones who are going to be training everyone, and so if HR isn't behind you, you're going to be in major issues, and they're going to fight you the whole way. Speaking of human resources, I bet it's pretty fair to say that not everyone is going to be qualified or knowledgeable enough to connect to remote access. So it's really important that we train the end users on what's happening on their end and how the connection works. It's a good idea to have the remote users learn about what's actually happening when they connect and how to set up their ends of the connections. Otherwise, your help desk is going to be inundated with calls, and not only that, but you're going to have a lot of people upset when things aren't working properly, even if it's something that they could easily fix. So, like the job of an admin in any other case, it falls upon your shoulders to help users when there's any sort of issue. Now, this can become a lot more difficult when the admin doesn't go over to the user's desk and help them out, or doesn't have the time to go over hundreds of people's desks. You have to connect with the user in some other way, though. Perhaps it's through a handout, or through an email, or perhaps you remotely access their computer, or even give the computers to them set up already to remotely connect, or talk to HR about creating some sort of training program that's going to help support all of this. Finally, once we've set all this up, we need to monitor the network to make sure that the remote access is working as intended. The first step towards doing this is to manage all of the entry points that any of the users could use. It should be kept down to one single access point, and that's important because obviously it's easier to manage one access point than several. If all the users enter the network in the same place, it's going to be a lot easier to monitor them. Next, we need to make sure that the policies and procedures are followed. So when users start using wrong procedures, don't follow the policies, there's a really good chance something's going to go wrong. And it's important to have the remote users follow a strict procedure in order to avoid any problems and to help take the load off of you and the help desk. It's also very important to understand everything that's going on within the network. You have to know where the connections are, what they're doing, what the users are up to. You have to keep track of all of this stuff. And there are different ways to do this, different devices we can deploy, and software that we'll talk about. So just to recap, we've defined what remote access is, what it does, and its benefits. All in all, it allows us to, again, be geographically at a different location and connect to the LAN. We also talked about lots of the steps of implementation, and although this isn't very technical, all this stuff comes up on the Network Plus exam. You have to know what it is you're supposed to do. So remember, we talked about some policies, procedures, training, and monitoring. Now, in the next module, we're going to talk more specifically about how we set some of this stuff up and what we're going to do to make sure it works properly.
Welcome to Module 10, Lesson 2A, Remote Access Methods. So remote access is all about how you can reach various network devices when you're not at the physical location. Go look at RDP, SSH, VNC, Telnet, and management through the HTTPS, and file access, and then out-of-band. RDP. This is proprietary to Microsoft, so they've come up with this software. You may have seen it before when you can, if you check on your Windows machine, you can normally find the button to click that will allow you to connect to a remote computer. And you might use this if you work in a help desk, if you need to support a remote user. You can have remote access and control via screen sharing. This is actually how a lot of scammers will get people to hand over remote control. They'll phone somebody who's a bit naive and say, we've found a technical flaw in your computer and hand over, can you hand over access so we can fix it? Typical exam question would be, what port does it use? It's TCP, it has to be reliable obviously, and the port is 3389. You need to know this kind of stuff if you need to permit this through your firewall, or deny obviously. Now the client side can be Windows, Mac or Linux. There's a few different operating systems that are supported. SSH. This allows remote terminal access. By terminal we mean a window like this where you've got command line access to a remote computer server, or in this case, I'm not sure what this is actually. It could be a Cisco device of some sort. It encrypts communication between the endpoints. So most places now you can't telnet across the network. Because it's all traffic is sent in clear text, you have to use secure shell as part of the policy, the network policy. In order to use secure shell, you have to enable it on your server, router, or switch. It isn't usually enabled by default. The client software you install on your computer, the one I use mostly to get my remote secure shell sessions is PuTTY. It's a free download. If you Google PuTTY, I think it's putty.org, you get taken to. VNC, I used this a while ago when I was on holiday and needed to connect to my work computer. This is platform independent. It's a GUI based, which is pretty handy if you're not too familiar with command line. Desktop sharing. It uses remote frame buffer to remote control a computer. Alright, you get the TCP port basic. The port is 5900, and then there's a number. The number you check the documentation, but there's various numbers you will be using depending on what you're connecting to and how you want to connect. Now, Telnet is TCP protocol. It's used for remote access. I did mention SSH, so really Telnet, you'd use it at home if you've got a rack or something you want to troubleshoot. You would never use this in a corporate environment now. If you went and did some configuration or a network installation for a company and left Telnet open, then I think you'd probably be in trouble legally, because you've left a big hole in their network for other people to connect. It requires client software, just something like PuTTY. You used to have Hyperterminal with Microsoft. They stopped bundling it with the software, I think, about 4 or 5 years ago. You could still enable it, but you had to go into the back end, and I think you had to download some extra software. But it didn't work. It doesn't work too well anyway. It uses TCP port 23. Make a note of that. All traffic is unencrypted, not secure, which is why we don't recommend you use it. I've already mentioned it's banned or blocked. HTTPS management. This gives you the graphical access method for a device. When you first buy, for example, a Cisco router, and say you don't know how to configure it, you can get the router, you basically plug in an Ethernet cable here, you connect your PC or laptop, and in the documentation that will come on a CD-ROM, or you get a little card, it will basically say in your browser window you put HTTP, possibly HTTPS, and then you will put a number. So say, for example, your home router will normally be something like this, 192.168.0.1, and then that will resolve. Doesn't need to use DNS because it's using an IP address. It will resolve them to this management window. On my router, on my home router, you've got a whole bunch of menus here. You can configure the firewall, you can reboot, you can check your DNS settings, you can permit or deny different devices if you want your kids to access the internet or you want to block them. You can configure NAT, firmware, etc., etc. Anyway, you get the idea. So this is a way of managing your device. It's a security issue if enabled by default. I'm trying to remember now. I think Cisco devices it's disabled by default, but sometimes you can have different versions of iOS where all enabled, and then there's some change happens and the command changes, or the default setting changes. This is for routing commands, security commands, how to switch traffic, packet switching and frame switching. So check what device you're on and if it's enabled or disabled by default. Generally you'll want it disabled. Otherwise you've got to configure advanced usernames and passwords. So put the IP address into the browser bar. Remote file access. FTP is used to upload and download large files insecurely. So this represents a problem. SFTP, this is a protocol in its own right, so it's not as if you've got FTP and added something to it. This is its own protocol. So just be careful. It encrypts, secures and encrypts traffic. It uses SSH, which is port 22. So don't think that it's an FTP with some little extra bit on here, security bit. Security issue if enabled by default. This is again, I've done that again, sorry, I've left it from the last slide. Your other file transfer method is trivial file transfer protocol, which I think we've mentioned earlier. If you've got a small file that you want to send over your network, again, please don't use this. This is just what it's used for. If you've got a router and you want to back up the configuration, you've got a tiny little file, like about 8 bytes, whatever, or 8 kilobytes probably. You'll back it up here using TFTP. But again, this file really is sensitive because it's got IP addresses, passwords, and heaven knows what. So really, using TFTP, it shouldn't be done anymore. If you're at home, you've got your little home network and you want to have a play with your software, fine. If you're in a corporate environment, no, I think it's a really bad idea. Out of band access. Out of band, basically, it's not within your normal Ethernet connection. So say you've got a router, you've got a fast Ethernet port here, and then you've got your, again, your PC or whatever you use to connect. So this will be your in-band. Out of band would be something like a modem connection. So you've got your router and you've got your telephone connection here, and then a modem which is connected to your computer. So out of band. Used for emergency access. Normally, if you're connecting out of band, something has gone wrong. It looks like this is a modem here, and you can connect over the internet. So you could connect to the modem, and then there's a modem port here. Normally on Cisco devices, it's got AUX written on it. Again, check your documentation because things change over time. So attach your modem to a port. What you would normally do is this wouldn't be connected. Say you're in a corporate environment, so this is in your corporate network, and you've got a you've got your remote hands. So this is like your help desk team. They're not that technical. Say they're level 1, but you've got people who, if you send them in the instructions to go to rack 1 and find, say, row 3 or whatever, and ask them to plug in the cable, and you'll have the cable sitting there but not plugged in. You'll do the fix, bring the router back up so that all the other ports are working, and then they will disconnect that again. And you'll normally have obviously a ticketing system of some sort where you'll say plug it in and then confirm that they've unplugged it, because it's a security issue. So just be careful. So I've mentioned remote hands. You can use a console. Oh, you can use a console router for multiple out-of-band devices. So say you've got, this is normally, we used to do this when we were practicing for Cisco exams. You had a rack of all of these different routers. Say router 1, router 2, router 3, switch 1, switch 2. And you haven't got Ethernet access for whatever reason. So what you do is you'd have this a console router, I can't fit it all in, a console router which basically connects to the console ports of all these devices. Now console connections don't work over the internet, it's an out of band thing. So what you would do would telnet to this device here, and then through this router here it would have the telnet the software, the client software, that you could configure all of these devices through a command line. And really handy way of connecting to remote racks, but you could have this for your corporate network. This is an example of one. This is the models of routers for Cisco are 2511 and 2521. Now you can see how old this is. This is your Ethernet connection. Look at that, the AUI. So what you do, we've talked about transceivers already, I think, but you'd have this transceiver that's got an Ethernet port in here, so you could connect an Ethernet cable to another device, which then lets you get in at 10 meg. So pretty slow. Old-fashioned serial connection there. That's a DB60. And then your console port for console connections. This is your modem I've talked about. For your out-of-band access. And what this is a bunch of console connections. So you can see one here, they've all got numbers on, and it's numbered 1 to 8 here. And then if you plugged in the second one, if you needed up to 16 devices, then these numbers, I won't tell you how to configure it. I've got a video on YouTube if you want to look that up under my name, Paul Browning. And you could connect these to a load of other devices. So really what you were doing is connecting to this device, whatever this modular switch is, but you're doing it, you're telnetting or connecting through a modem connection to this device, and then from here you're choosing whatever console line is free, say for example 1, and then you can actually configure this device. So it's a slightly longer way of doing things, but that saves you having to configure telnet connections to 16 different devices. So pretty handy. So we covered a load of stuff: RDP, SSH, VNC, telnet, HTTPS for your GUI access here, file access, and then out of band. So we covered a lot of stuff. So thanks for listening. I'll see you on the next presentation.
Remote access, VPNs, and their protocols. In the last two modules, we discussed remote access and remote networking. Both are basically around the same concept. Remote networking meaning that I can create a network that exists in two very different geographical locations, and remote access meaning that I can access a computer or a network from one geographic location to another. So they're both basically the same thing. But how we accomplish this in a secure fashion is what we're going to talk about in this module. And that revolves around this term VPN. A VPN I've talked about a bit in the past, and it stands for Virtual Private Network. And as that term implies, and like we've discussed, it creates a tunnel through the internet, the wide area network, in which we can securely send data between two locations. And why the tunnel? Well, that's what keeps it secure and private from everyone else on the internet. And this is how we've been able to allow remote networking to become so ubiquitous in our world, because I no longer have to have a direct T3 or T1 line between my office and my home. Instead, I can use the internet, which is fairly ubiquitous these days, and create a virtual private network. Again, virtual being the key word there, because it's not actually a private network. It's a virtual private network because of this sort of tunneling concept that we're going to talk about. So what we're going to talk about in this module is first to define virtual private networks a bit more, and then talk about the difference between a VPN client and a VPN server. We've seen the terms client and server in the past, so these shouldn't be too new for you. Then, I want to talk about the VPN protocols. There are two specific ones that you need to know about for the exam. One is called PPTP, and the other is L2TP. Notice the T in there for tunneling. So we're going to discuss both of those and how they all work. All right. So first, virtual private networks. A virtual private network, or a VPN, is nowadays an essential part of networking. It's basically used anytime a network is extended beyond a LAN or local area network. So it establishes a remote connection through a public network such as the internet in order to extend the LAN. And I'll show you a graphic of this in just a second. Once the extension is made, a dedicated point-to-point link point-to-point link, which you might also have seen P2P. A dedicated point-to-point link is created between 2 points using the same IP network, meaning that even though we are on 2 very different IP networks, I might be on my LAN, you might be on yours, we can create a virtual point-to-point connection between the two using tunneling that makes it as though we are on the same point-to-point network, the same IP network, and I'll show you that in just a second. Now, the extension of the LAN, or sometimes the linking of 2 LANs, creates a new wide area network. So you could say that any time a VPN is established and a new LAN sort of added on, a new WAN is created. Don't worry too much about that concept, but the idea again is if I have the office LAN and let's say either another office and then perhaps a remote user, all connecting through VPN over the internet, I now have created, in effect, a wide area network out of 3 very distinct local area networks, but I haven't used any different infrastructure than something that was already there. Now, VPNs are actually a type of remote access, probably the most popular one. They share similarities to all the different remote access. For instance, you might think of dialing via modem, but VPNs are an inexpensive way to extend your network because it uses the internet, so you don't need to purchase a leased line service. Now, remote users just connect using the VPN to their remote office through the internet. And so that's really the key here, is it uses the internet as its platform. So this is what access through a VPN might look like. The remote users connect, let's say from home, through the internet, and then there is a authentication server that verifies that this user is allowed on the network. Once you pass through that, it puts you into a switch, which then makes it as though both of these computers are on this LAN. So in effect, I've created a new WAN without having to lay down any extra line, because I'm again using the internet. Now, say that this was an office building. I could have an office building here, perhaps another one, and these can be any place in the world. And because I'm using tunneling through the virtual private network, I create, in effect, a tunnel which allows all of these to each create a point-to-point connection between themselves and this authentication server that then basically puts them onto this LAN. So any one of these offices is now part of the LAN and in effect then making a brand new WAN or wide area network. Now there are a lot of things we need in order to set up a VPN connection, and some of them are more important than others, but I'm just going to key in on the main things we need. First, we need a VPN client. Now the client is the remote access user. Without this user, there's no point in setting up a VPN, so why bother if no one needs to connect? They are one of the most important clients, or the ways that components rather. And what's interesting about a VPN client is it can either be software or hardware. If it's software, then it's built into the operating system generally, or into the networking package of the operating system. If it's hardware, it's generally either built into the router, or it's a separate device, which is generally called VPN Concentrator. Now the benefit is, if I have, for instance, 2 offices, we'll call them Office 1 and Office 2, and they are located in different parts of the world, but they both connect to the internet, then I don't want each, so let's say each of these offices has, we'll put 4 users for now, but let's say these 4 really represent 4,000 users. I don't want each one of these people to have to set up on their computers a piece of software that's going to allow them to connect through this tunnel. So instead, what I've done is I do something on the network side of the office, for instance in the router or with a device, that automatically creates this tunnel between the 2 offices, and then these members don't have to do anything. Now, if I am a lone user at home, then it's going to be easier for me, instead of buying a device that's going to allow a network to always set up, to just plug in through my computer and put it into the software whenever I need. And if I go into Windows 7 real quickly, go over here into our network and sharing, and say we were going to set up a new network, you can see right here it says set up a VPN connection. And if we go and do this, you can actually say connect to a workplace. Now, connecting to a workplace, what they really mean is setting up a VPN connection. So I'm going to click next. Now you can see I can either dial directly, which is something that we might have done years ago, or the one we're going to use more likely now is through the internet connection, again, creating that VPN. We could call this whatever. Now, one thing we would need here is the server address. We'll talk about that in just a second. But we are the client, and we need to connect to a server. So this is where, for instance, that server address is going to go. Now, you know this IP address wouldn't work because this is a private IP address, but we're just using this for the time being right here. You can use sharing, etc., but for right now, let's just go ahead and click next. Let's say our username. So let's say user, and then we have a password. I'm just going to do password. We can have it remember the password or not. You might have a domain if you're connecting to a Windows computer, and then you click connect. The next thing I need, obviously, is something for the VPN client to connect to, and this is the VPN server. The VPN server not only allows the connection to take place, but is also going to authenticate the client and allow them to connect. Now, this might be done through, again, some sort of device like this VPN Concentrator I've mentioned, or through a separate server that has software hooked up on it. Either way, I need some sort of device that allows outside clients to connect in to the network, basically to give them permission, act as sort of a controller or a gates person. There are different ways of setting this up, and you remember I mentioned something called an RAS, Remote Access Server, and the specific one we mentioned previously was a Radius server, which was a Remote Access Dial-In server. And although this was for dial-up, it still does the same thing, which is it allows someone to remotely access the local network. So we have some sort of RAS, and again, an RAS stands for, let me just write that out, Remote Access Server. Now, the access method is also pretty important. Without a connection, there's no way for a user to get onto the network. So most of the time, this connection comes from the internet. But it's not uncommon for a VPN implementation to actually come through a private intranet as well. So we have the internet, which is the public version, but there's also something called the intranet, if you recall. The intranet is like a private internet. And sometimes we might actually have a private leased line, or we have several different subnetworks within a larger network. And so it's important to know where your people are connecting from. Most of the time, you're not going to see the intranet. It's all going to be through the internet. And sometimes you'll also have people dialing up. So it's all important to know. Even though internet is the most popular, sometimes we're going to be doing it internally through an intranet. And finally, there are 2 protocols that we need to know about and that generally are set up on the server side, and the client needs to be configured to set up through. The first is PPTP, which we're going to talk about in a minute, and this stands for Point-to-Point Tunneling Protocol. The other is L2TP, which stands for Layer 2 Tunneling protocol. And if you remember talking about the OSI and the TCP/IP models, that's what that layer 2 refers to. So let's talk a little bit more about these protocols. The VPN protocols are really important to the security and efficiency of VPN. So the protocols manage, establish, and secure the data that's going on through that VPN connection. So PPTP and L2TP are the two most common protocols that are out there. They function pretty differently, but their jobs are fairly similar. They enable encryption, which means the data isn't sent in its sort of plain text format. It's sent in a way that if you were just to see it, it would look like it's all gobbledygook. And so what happens is it's sent on one end in a code and then received and decoded on the other end. And it also provides authentication. So only those who are allowed on the network actually get on. The authentication, it also establishes the identities of the people in the network so we can audit them. It's a way for the clients and the servers to be on the same page about who is on the network. And like I mentioned, encryption is really for the data protection. So because we're going through the internet, which is public, this is really at risk for attackers. And so the encryption protects that data that's traveling through the network and prevents these issues from happening. Generally speaking, we're going to prefer L2TP over PPTP, just because it's a more advanced protocol and uses a different form of encryption. I think, in fact, Windows 7 and Vista only allows L2TP now. It doesn't even allow PPTP, as we just saw when we looked into Windows. All right, so just to recap what we just talked about. First, we mentioned virtual private networks, which you'll never see referred to as virtual private networks. You'll see them referred to as VPNs. And those basically create a tunnel through generally the internet, sometimes the intranet, to connect LANs together, and in effect then creating one large WAN. Now this can be done between office and office, or say a home user in an office, and either way you have a VPN client, which would be the one connecting to the server. And remember, we have either software or hardware. We looked at the software that was built into Windows. We also have hardware. Generally, the thing that you'll see with there is something called a VPN Concentrator. It could also be, for instance, built into your SOHO router or be built into a Cisco router of some sort as well. We also discussed the two VPN protocols. Remember, these were the point-to-point tunneling protocol and the layer 2 tunneling protocol. Notice that these both, are VPN protocols because of this T, the tunneling protocol. Generally speaking, we're going to see L2TP used more than PPTP, and what these really are responsible for is defining how encryption takes place and authentication, which is something that it works in conjunction with the VPN server to accomplish.
Welcome to Module 10, Lesson 4, GRE, SSL, VPN and VPN concentrators. We'll look at secure sockets for VPN also. What is SSL, VPN concentrators, IPSEC. This is just an overview. As usual, there's whole entire exams for security stuff like this in more detail, like the CompTIA Security Plus, which we host on howtonetwork.com, and the CCNA Security also. GRE stands for Generic Routing Encapsulation, and it was actually developed by Cisco Systems as a tunneling protocol. And a tunneling protocol tunnels something else, another protocol within a protocol. So it allows network users to access a network service that's not supported by the underlying network. So you can actually tunnel lots of different things. You can tunnel IP version 4 inside IP version 6 if the hop-by-hop devices don't support it. Here is an image of a GRE tunnel going across an internet. source interface or IP address, destination IP address of the tunnel, and IP address of the tunnel. That's part of the configuration. You don't really need to worry about that, but the traffic will pass through the GRE tunnel, and the devices actually sending the traffic will only examine the header of the GRE packet, which is wrapping the traditional IP traffic. So we already know we can run a protocol over a network. You can actually run non-routable addresses as well. So inside that tunnel, you could have a 192 address, and as long as the tunnel is going via routable IP addresses, you'll be fine. A GRE creates a virtual point-to-point link and encapsulates a variety of network protocols. I've already mentioned the private IP addresses. It's used in conjunction often with PPTP, point-to-point tunneling protocol, and IPSEC if you want to create a VPN. And there's an image there with the GRE tunnel, also working with an IPSEC tunnel from networkstraining.com. VPN, virtual network, virtual private network is the full term. It's built on top of an existing public network. Obviously very handy if we need to securely connect over the internet from two different network locations. Often used by companies because they don't want to buy a dedicated leased line, so they'll just use existing security technology. You have a secure communications between two private networks. SSL VPN, this is a secure sockets layer, virtual private network. It provides encrypted communication between a client and server. One example is SSL encrypts communication between a web browser and a web server, and your browser will be Google Chrome or whatever you're running on your laptop or PC. The user connects to VPN devices using their web browsers. Traffic between the web browser and the VPN is encrypted with the SSL protocol. So as a result, you've got a secure access to web applications and client-server applications. You'll see this working with the green padlock when you're browsing different websites. Built into all standard web browsers, you don't have to add anything extra on. You don't have to configure or install any client software anymore. You used to have to. That was a few years ago now, and it's all built into the web browsers. The SSL VPN can be accessed from anywhere, including airport, hotel rooms, coffee shops, as long as you've got web connectivity and the user has a standard SSL client that's used with that particular SSL VPN. SSL VPN products, they're usually standalone hardware appliances, and there are software solutions available. Speak to whoever the sales representative is for Cisco or whoever you're using for the technology. You also get common security services such as authentication, encryption, integrity protection, access control, who can access, even how long they can access for, security, endpoint security controls, intrusion prevention, IPS. Authentication, as we know, I'm sure, is just authenticating that particular person to verify they are who they say they are. Encryption protects the confidentiality of the data as it passes through the internet. Integrity ensures that the data is not altered, so there's a whole bunch of ways to offer integrity of the data as it's sent from the source and received at the destination. Access control gives restricted access, and that can be based upon a number of things, and the access control is then associated with whatever privileges you wanted to give that particular user. The endpoint security controls checks the user system for compliance whenever the user attempts to use the SSL VPN. Intrusion prevention checks the data for any potential threat after it's been decrypted. VPN concentrators, these were supported originally when I worked at Cisco by the security team. They provide a remote user with secure access to the organization's resources, and the concentrator is basically an endpoint for multiple VPN connections. So there's maybe lots of home users or people dialing in, mobile salespeople that need to connect from certain places, and the VPN concentrator will be the point where their connection is terminated. Alright, the concentrator is a device that can handle multiple tunnels coming in. VPN, they provide VPN encryption either by using IPSEC or SSL. Again, check with your vendor for the documentation. IPSEC is IP security, provides a high level of security and encryption. It requires client software to establish the VPN tunnel. IPSEC is better for fixed locations, SSL when the remote users need to connect from various locations. For example, they're a traveling salesperson. And nowadays, VPN concentrators are not manufactured as separate devices. They're normally combined with devices that also provide firewall protection. If you go to cisco.com and then click on, I think it's sales or products, you'll see the type of devices that are available and what they do. Alright, so we've covered a fair bit: GRE, tunneling, VPN, SSL, security services of SSL VPN, and a VPN concentrator, and IPSEC. That's all for now. Thanks for watching.
Network management, network administration. In the previous lessons, we've talked about a lot of the technical aspects of networking, including remote networking, remote access, virtual private networks, local area networks, wide area networks, and so on. But there's someone who's required to sort of put all of this into place, and that's where an administrator comes in. So in this lesson and in the following modules, I want to talk about what an administrator is and some of the tasks they have to do. In this module in specific, we're going to start by defining an administrator or network administrator. Now, there can be several administrators at any one site, but we're going to give an overview of what an administrator, no matter what their specific role, is going to do. Then we're going to identify some of the key admin duties, and these might be documentation and monitoring. We'll talk more about these in further modules, and we've probably already mentioned these to some degree. So some of this might be recap. In some cases, it might be overview. But a lot of what's on the Network Plus exam is sort of applying, not just having knowledge, but applying the knowledge in certain administrator roles, since that's what they assume you're going to do with your certification. So there's no doubt that we have used administrator, or admin for short, in hundreds of times by now. So it might be useful to stop for a minute and actually take time to talk about what this term means. So the administrator of a network is the most important person involved in network. They are in charge of everything that happens on the network and know what all of the users are doing. They're in charge of security, and they can be held responsible for everything that happens on their network. So not only are they responsible for sort of creating the network, but if someone misuses the network, the real axe is going to fall on them. More than that, they're in control of all the accounts, the resources, the data that users have access to. The administrator is the only person that has access to everything in the network and can control what others can access. Even if they give access to, say, an assistant administrator, in the end, if that assistant administrator screws something up, it was the administrator who gave them access in the first place. So clearly, this is a really important person and are essential to managing and monitoring the network. Without them, there really wouldn't be anyone with enough knowledge or ability to manage how these networks, and you can see how large they get sometimes. So here is essentially what an administrator's view might be like. They have a view of everything that happens going in, right? They know all of the nodes, all of the servers, and this is very simplified, all of the routers and switches. This is what we might call a network diagram. We might also have printers. And if this is a cloud environment, as it seems to be, then they're going to be aware of all the virtual sort of stuff that is set up. They're going to be aware of all of the user accounts, the network security. They're also going to be dealing with all the remote access. If there is this going out to the internet, are there firewalls? Are there intrusion systems, etc., etc.? So they really have an overview of everything, and they have to maintain everything as well. You can see how complicated this can get, which is the reason why one network administrator might have several under administrators to help them. They not only log when someone comes in or out, they can see when someone visits a specific website, when they're sending or where they're sending data, what the type of data is. We might also have, for instance, an exchange server, which would be for email, in which case we need someone to manage that as well. For instance, what if someone sends a 50 megabyte or 50 gigabyte file by email, or they try to? That's going to log up the entire network. So one of the first duties of an administrator is documentation. There's a couple reasons why this is so important when it comes to managing and running a network. It's going to be the focus of its own module, but it's good to get a basic understanding right now because the process of documenting everything can be really time-consuming, but it's also really worth it. It can save you a lot of time, trouble, and money when things are well documented and no one has to go searching for them, especially if the administrator is out of town or if we switch administrators, we want to make sure that the network can still live on its own. Now, there are no shortage of things to handle for the administrator, and documentation is usually the thing that's going to get pushed aside and forgotten about. But there are some really key items that we can look over that are helpful to be dealt with. First of all, properly documenting information is useful when training new admins. It's not uncommon for the old administrator to leave and then have to train a new one as their replacement. However, the new admin doesn't have time to learn the topography, the cable connections, everything about the network from scratch. So this is where proper documentation is really helpful. It can save the new administrator a lot of time and effort, especially even if you're not leaving, if you bring on someone to assist you, allowing them to look at documentation is going to save the super administrator time from having to teach the new administrator. It's also going to help us when we troubleshoot problems on the network. It can save time and money because we can eliminate the time it takes to test every possible problem because we can now isolate where the potential problems are. For instance, if I have an overview of where things are set on the network and I know one side of the network's not working, then I can automatically sort of go to that side of the network and not have to worry about the other side. Finally, it's also really important when I'm bringing in outside workers to make changes to the network. They need accurate and up-to-date information about the network, its layout, and if they don't have an idea of how my network looks and I just start to tell them to fix things, they're going to have major issues. And one of the things that's really big these days is having a contractor come in because we're sort of going to outsource a lot of our network administrator duties, or sometimes the administrator is not a specialist in something, for instance, security, and so they need to bring in contractors to implement a better security plan. Now, monitoring is also an extremely important job for the administrator. It's necessary to monitor a network for a lot of reasons, and again, we're going to talk about this in its own module, but it's good to understand it a little bit right now. So when you monitor a network, the administrator can almost always find faults in the system and find out where they are. There are tools that help the administrator check all the devices to find out where the faults are and how they can be fixed, and I think we've looked at some of those, and we might look at a couple more. But some of the tools, the ping, trace route, etc., looking at routing tables, looking at broadcast, all this stuff. And also, performance detection is very important when we're involved with network monitoring. When an administrator monitors performance, they're able to find some very useful data. They can discover network usage data, how each user has been using the network, and make sure that the bandwidth is load balanced properly, a term that we have seen a bit, and we're probably going to see a little more. And also we can make sure that there's not too much traffic on the system. Obviously, too much traffic slows things down and makes everyone miserable. Finally, security monitoring is really essential because one thing we don't want is someone outside of our network getting access to all the stuff we set up. It's really going to make your bosses upset too. And we're not just talking about hackers, we're talking about viruses, attackers, any of this stuff. So when we're monitoring security, an administrator can find holes in the system and then take preventative actions in order to stop the attacks before they happen. One thing that's going to help with this are two devices called an IPS or an IDS, an intrusion detection system, and then an intrusion prevention system. These are actually two different things. As you can see from the name, intrusion detection just detects when something happens. Intrusion prevention is actually going to stop it in its tracks. So that was just a broad overview of defining what an administrator does, the person who has a complete overview of the network. And then we looked at a couple of the reasons why their admin duties of documentation monitoring are so important. Documentation for training new people, tech support, bringing in outside resources, and also monitoring, not just for security reasons, but also for performance. Because obviously if we have a slow network, it's going to result in everyone being unhappy and your bosses not being able to accomplish the work they need. Not to mention, if we talk about 1 extra minute in work time, that can actually cost us quite a bit of money in the real world. So having given us a broad overview of this, we're going to talk more about optimizing a network performance based on the monitoring that we do. Network management, optimizing network performance. We're going to be covering a lot in this module. It's all about the optimization of a network and its performance. And there's a lot that we have to do as administrators when it comes to that. We're going to specifically focus on strategies to optimize network speed and efficiency. So first, we're going to give an overview of what network optimization is. And then we're going to define something called quality of service, QoS, which I want to point out right now, you're going to see anytime we talk about voice over IP. Because as the name implies, what we're doing is trying to make sure the service provided on our network has a high degree of quality. And when it comes to voice over IP, we need to make sure the quality is pretty high. There are 2 ways to do this. One is called latency sensitive and the other is latency insensitive, and we'll define that a bit more. We're also going to talk about something called traffic shaping and methods in which we do this, and finally, caching engines, which help speed up network performance as well. So, bandwidth is essentially the amount of data that can be transferred and utilized at any given time. This amount is usually expressed in bits per second. So, if you remember, we see, for instance, megabits per second with the small b. And I want to point out again that this is not megabytes per second. As you recall, there are 8 bits in every byte. So we would really need 8 megabits per second to equal 1 megabyte per second. Just something to keep in mind as you purchase perhaps a broadband connection. Now, how the bandwidth flows is dependent on how many people are using it at once and for what purpose. So everything in today's world is expected to be fast, and we can settle for no less than the fastest. People become really impatient with network speeds very easily, and unfortunately they fluctuate fairly easily too, especially in a corporate environment where there are a lot of people using and taking up the same bandwidth. Just imagine how frustrated workers are going to become with when they can access something really fast 1 second and very slow the next. You can imagine this at home as well. So the purpose of network optimization is really to help control the traffic on a network. If a large group of people are trying to enter a building through one door, the flow is going to be a lot slower than if there are multiple doors. Now, the same principle applies to networks. If the network is laid out and run in an optimal way, there is less chance of blockage. So in addition to network traffic, optimization works to utilize bandwidth in the best possible way so that everyone can use it at the same time. This would be also called throughput. So whereas bandwidth is our ideal or possible, throughput is the actual. In other words, what actually makes it through the bandwidth. So here's a representation of what bandwidth might look like. Imagine the bandwidth capabilities are like tubes. And the bigger the tube, the more that is free to flow through it. So here you can see there's much more ability to flow through the tube on the right because it's a lot bigger than the tube on the left. That being said, only because our bandwidth is, for instance, 90 megabits per second or 1 gigabit per second, doesn't mean that the throughput is actually going to be that. I'm sure that you have at home bandwidth or broadband internet, and it probably says it has up to perhaps maybe 15 megabits per second if you're on a cable. But sometimes you're not always getting 15 megabits per second. You might be getting 5 or 8 megabits per second. And you can test this using different sort of online speed test utilities. But only because we have a certain amount of bandwidth doesn't mean our throughput is going to equal that, which is an important distinction to make. What we want to do is get the bandwidth and throughput to equal as close as possible to one another. So there are strategies used to increase the use and optimization of bandwidth on a network. These strategies are called quality of service, or short-term QoS. Now, they have a lot to do with information and helping it optimize the network. So QoS allows administrators to predict the bandwidth use on their network, monitor the use of it, and then control it. This is done to make sure that there is available bandwidth for any one application that requires it. The applications that need this bandwidth are generally split into two different categories: latency sensitive and latency insensitive. Latency sensitive applications are appropriately named. These are applications that are affected by latency or a delay caused by a device. So latency is sort of the slowness with which bandwidth occurs, or not living up to its full potential. So an application that needs bandwidth because of its effectiveness is impacted by lag time. For example, applications that use VoIP fall into this category, or voice over IP. They're latency sensitive because lag time could disrupt a video or a phone call. Latency insensitive applications still require bandwidth, but for a very different reason. These don't have video or voice transfer, so the bandwidth is just as important to them, but the latency doesn't really matter. These applications are those that are used to transfer large amount of data, like during backup or FTP. Just to cover this one more time, and perhaps say it in a different way, latency sensitive would be meaning that if something, for some reason, I have a huge amount of traffic, then I'm going to start seeing a degradation in service when it comes to my latency sensitive applications, such as VoIP. For instance, I need to make sure that no matter when I'm talking over my VoIP phone, it's still reaching the end person in the same degree of quality. It can't be dropping a lot of packets, because if it is, then they're not going to be able to hear my voice very clearly. With latency insensitive, the traffic can modulate quite a degree, because as long as the files get from one end to the other, if at one point it's transferring at 90 megabits per second and the next it's transferring at 1 gigabit per second, it's still going to get over to the other place, but it doesn't really matter if I don't receive the packets in a sort of steady stream. So in this case, the latency doesn't really matter as much as the fact that it simply gets from one place to the other within a certain degree of time. So a very important QoS strategy to help to help control the flow of data through a network is called traffic shaping. Its main purpose is to reduce latency, which it does by controlling the amount of data passing through a network. Data traffic is sort of split into different categories and put in something called a queue. A queue, by the way, would be something like a line. Basically, I'm going to put certain types of information into one queue and certain into another. And those queues are going to be given priority. So my voice application is going to have the highest priority, whereas maybe my FTP will have a bit of a lower priority. Now, there are quite a few different ways to use traffic shaping, and each method has its own benefit and needs to be chosen based on the circumstances of the situation. Now, here are a couple of the common methods, actually 3. First is shaping by application. This is a strategy that involves the administrator allowing only a certain amount of bandwidth to be used by a certain application. For instance, an admin only allows a VoIP application to use, for instance, 6 megabits per second, and it can't use any more than that. So in some ways, we set a limit to the bandwidth that's going to be used by a certain protocol or a certain application. The next, which is called shaping network traffic per user, allows the administrator to limit the bandwidth that any individual user can use. Now, shaping by application is something that we're going to be seeing a lot now on airplanes and trains. We don't want to let, for instance, people use Netflix and YouTube on the plane because there are other people who need to be using email. And so we're just going to say, if you want to do bandwidth for video, we're not going to allow that as much as bandwidth for, say, email or for text messaging, for instance. But when I'm talking about network traffic per user, I'm allowing specific users to have a certain amount of bandwidth. So some users might use more bandwidth than others, and sometimes it isn't all for work reasons. For instance, let's say that Anthony from sales is constantly streaming video or audio to his computer. This is using a lot of bandwidth. So now the discipline part of this may not be up to the administrator, but he or she can certainly limit the amount of bandwidth Anthony is allowed to use. So if each individual, for instance, Anthony, is limited to 256 kilobits per second, it's not going to access what he can access, just how fast he's able to access it. So whereas this is really doing it, shaping by application based on the type of information, shaping the network traffic per user is on an individual basis. In this way, I can give each user, let's say Anthony, Maria, Amy, each a certain degree of bandwidth so that no person can use one more than the other. Of course, a downside with this is if Amy's only using, let's say, 10 kilobits per second to send emails, and Maria is on the video team and is trying to use all of her 256, she might be able to use some of Amy's, but because of the way we've shaped this per user, Maria doesn't get any more. And sometimes what we'll do is give people in certain roles at the company a little more traffic or bandwidth allowability than some of the others. For instance, accounting probably doesn't need as much as our graphics team. Finally, we have something called priority shaping, which is the way to allow more bandwidth to those who require it most, sort of what I'm referring to here. For example, in a school system, the teachers need more bandwidth than the students. So the network admin shapes the traffic. Again, we have that great term, priority shaping, so that it's dedicated more to the teachers, but the students can still use it at a slower speed. So when the teachers don't need the bandwidth, the students are able to access it at faster speeds. So we're really taking this sort of concept and allowing it to be a little more flexible. Now, another technique used is something called a caching engine. Caching is essentially temporary storage, although the storing of what is changing every single time. In the case of caching engines, the temporarily storage of data is actually web data that can be used in the future. So this is happening through something called a proxy server. Basically what's happening is, without going too far in depth into it, is that a proxy server caches web data for future uses by others. So if I have, let's say, 3 users, and the first user, and I have a proxy server in between them before it goes out to the internet, and the first user requests CNN, the proxy server, which holds a cache or sort of copies of everything, will first say, hey, I have the latest CNN or I don't have the latest CNN. It'll then go out to the internet, get the latest CNN, and hold that in its proxy. Now, when the second user, 5 seconds later, says, hey, I want the latest CNN, the proxy server does not have to go out to the internet. We can basically cut out this entire process. And instead, it just returns what it has already cached. It can do this with as many users as possible. And what we'll generally say is that every minute or every few seconds, it's going to update, the proxy server is going to update its information. That way we can make sure that it's still the most up-to-date information, which is one of the downsides of using proxy servers and caching, is that sometimes it's not going to have the most up-to-date information, but it certainly speeds things up by cutting out this whole process of having to go out to the internet by keeping it locally. Now this all saves bandwidth, because obviously I'm not having to go out to the internet, and therefore I can reserve that bandwidth speed that would have been used for video or something else that's new, instead of having to use it for information that I'm gathering over and over and over again. You can imagine in a corporation of thousands or hundreds of thousands of people, this is really going to save us a lot of time. All right, so just to recap, we talked about network optimization. There were a couple terms we mentioned. First was bandwidth. Bandwidth is the highest possible speed that we have on our data connection. We also talked about something called throughput. Whereas bandwidth is the ideal or potential speed, throughput is the actual speed, how much is actually traveling. And what we want to do is get these two to equal one another as much as possible. However, we also want to make sure to make good use of our bandwidth so that everyone can get information they need when they need it. So then we talked about something called quality of service. Quality of service makes sure that we're using our bandwidth in a way that's going to promote good quality. We talked about two different types of applications and ways that we use quality of service. First, we look at latency sensitive applications. These are the applications that where there is latency, or another word for this might be traffic, it's going to reduce the speed on the network, the quality of the service is going to start degrading. So voice over IP is a great example of this. If there's a lot of things going on in the network, then our voice over IP isn't going to work as effectively, and then I can't count on voice over IP as a good technology. So it's important that I make sure voice over IP always has a certain degree of, say, bandwidth. With latency insensitive applications, we're looking at stuff where the speed, although it still needs to be fast, doesn't matter if there's latency 1 second and no latency the next. When we're transferring or large files, such as through FTP, then we don't need to make sure that we're not modulating between 90 kilobits per second and 90 megabits per second or 1 gigabit per second, as long as the data gets to where it needs to go. I don't need to make sure that it's getting there at the exact time, because, for instance, with voice over IP, if I'm talking, it needs to be able to reach the person sort of the degree that I'm talking. But with FTP, it doesn't really matter if it's getting there in the same instant. We also talked about traffic shaping, which is one of the ways that we use quality of service, and we shape the bandwidth so that it is used in an appropriate way. We talked about 3 different ways of doing this. The first we talked about was based on application. So for instance, I'm going to give a certain degree of bandwidth to one application and a certain to another. Once all the voice over IP bandwidth is used, that's it. Once all the FTP bandwidth is used, I don't have any more. And so I'm only giving, if I have a large bandwidth, let's say this box represents bandwidth, then I'm going to sort of divide this into layers. So FTP gets some, HTTP gets some, voice over IP gets some, etc. We also talked about user specific, which means that instead of dividing things up based on the application, I'm going to divide it up based on the individual. So Maria gets a certain amount, Anthony gets a certain amount, and Amy gets a certain amount. Finally, we looked at priority shaping, which is a really cool term. And what this means is I can give certain priority to certain individuals or groups. So for instance, we use the teachers versus students comparison. Teachers, we want to have a lot more than the students. So students get a very small amount, whereas teachers get a very large amount. Same with on a corporate network, perhaps I want a management or my graphics team to have a lot more than, say, my accounting team or lower management or the secretaries. Finally, we talked about caching engines, and we used the word proxy server. This is going to save us time because whenever I go out to get information from a website, I don't have to go get the information fresh every time. Instead, I'm going to use the proxy server to hold a copy or a cached version of my website, and that way I don't have to go out to the internet every time, and I can reserve that bandwidth for other things I might need to use.
Okay, welcome to Module 11, Lesson 3, Network Documentation. Little bit of a harder on this. It's just a bit esoteric and wishy-washy, although it's obviously important. But just to discuss, what is it? I'm sure you can actually work out what network documentation is. Why do we have it? Importance of it, parts of it, and managing our assets and our network diagrams, RFID, which we'll go into, tracking our IP address utilization, which is quite a handy thing to have actually, information about vendors and contractors and all of our policies and procedures. So the whole principle behind network documentation is professionalism really, and business continuity, and it's an emerging field in the world of IT, non-technical, but looking at audit trails and in the context of documentation really in all of our procedures. So critical role in, especially when there's a problem, because people start scrambling looking for what to do in terms of procedures and policies, who does what, where to find them, how to contact them, and where the technology is and how to fix it. There's a whole bunch of procedures and documents that have to all be easily accessible and come together. And bear in mind that the network could be down, there could be an outage, so if it's contained on a server somewhere, then that might not be ideal if it's only kept on the server anyway. So you can't remember everything, especially if it's a large network, or even worse if it's a small company and somebody leaves the business and you take over from them. If there's no documentation, then it causes a lot of heartache. And if you're the one to have joined, it's pretty difficult because you've got to learn the network from scratch. It's not possible to go and search a network administrators who've quit. Normally they have their phones taken off them, or they're just going on a long vacation, so you aren't going to find them. So it gives network administrators information about the network appearance, logical versus physical, baselines, how it's performing or should perform, to see if there's anything out of the ordinary, where to begin troubleshooting. So the main purpose is to keep the network running smoothly. So we've got that 5 nines, 99.999% uptime, ideally. It's important to maintain the documentation and keep it, well, maintaining means keep it up to date, because out-of-date documentation actually causes more problems than it fixes, because all of a sudden you're looking at the wrong devices or the wrong ports or the wrong IP addresses, and I've been there. So yeah, that's what I've said. Essential parts include network diagrams, asset management, IP address, utilization. You could have more or less depending on your organization and the size of it. You need information about the vendors and contractors, procedures and policies, who should be doing what and when, and also logical and physical. This is a topology diagram of all the hardware and the connections. We haven't named the ports on this particular diagram. It's copyright Scott McDonald. Just to give you an idea, this looks like it was done in Visio, which is a Cisco network creation diagramming tool. There's others out there. It's free to trial, or some are free to use, and it shows you all your different devices. The logical provides the logical view of how the network sees itself, not how we will physically see the network in the server room. Indicates how the traffic flows between devices in the network, so you'll see all of your VLANs, routing, redistribution, all these kind of things, BGP if you have it. Logical network diagrams include domain names, IP addresses, and the task performed by each different device. Logical includes how devices communicate with each other, which direction the traffic flows, and how all the devices work together. The physical network shows the actual physical connection, so you can look at the diagram of a certain router and you can see which ports are on the router, how many, and what it's actually physically connected to. And a lot of companies use the concept of remote hands, so you can use these diagrams to tell the remote hands where to find the device and which cable to plug, unplug, etc. Physical network is the physical layout, and I've mentioned. So here's a typical diagram. Above is the physical topology and below is logical topology. So you might not necessarily see all of the hardware devices. You're going to see things like VLANs, connections going out to ISPs, hot standby routing protocol, all this kind of thing. You won't generally see end devices on the topology diagrams unless it's a very small network, or unless one of the end devices happens to be your network management server or something like that. So your documentation should include notes about asset management, a whole bunch of things: name, model number, manufacturer, data purchase, version of software running, does it need updating, is there problems with that particular release of software update, location, warranty, and who has it, who's responsible for it. If you're sitting under somebody's desk and nobody knows, then it doesn't serve any purpose. So you should keep track of all your assets, and eventually there's normally a disposal procedure as well, where the devices are wiped, fragmented, defragmented, whatever, and whatever type of scrubbing is done on the drives if necessary, so there's no data that's important. Devices are tagged with the barcodes or RFID. Here's an example of one here. These are normally read by a little reader gun like you find in supermarkets. If it's been tagged with a barcode scanner will help retrieve information. The RFID stands for radio frequency ID. The tags normally have electrically stored information, and the readers are used to track devices. This would obviously be on a pretty big network. Network documentation should include your IP address utilization. There's normally 1 or 2 people in charge of allocating addresses or blocks of addresses, because they're aware of which addresses should be where, which subnets, and which addresses are summarized. And this helps with all of our routing updates. I have seen problems in the past, and people should know better, in fact, have manually allocated IP addresses to their devices for whatever reason, and it's caused network instability. So network administrators should keep track of the number of IP addresses that have been allocated to the network, how many have been in use, and it will normally flag up an alert if you're running short. If a subnet grows, the number of IP addresses assigned to it, you're likely to have a problem. Okay, all important to keep the note of the utilization, as I've said, in case we need to run out or buy some more or order them in advance. Should also have information about vendors and contractors. Should include vendor names, their services, the cost, contact information. We normally got a point of contact, and the support hours. Or should have documentation about all of our policies and standards. Well worth looking into project management and also ITIL exams, so change management and managing all your processes and procedures and problems on the network. Provides, for example, the list of people who should be contacted. Certainly when I worked on a pretty large network, there was a number of key people, so you have thousands in the organization, but you would contact 4 or 5 or 6 key people, and they would each have a role of who's going to communicate to who's going to tell the boss, does the press or other customers need to be informed of what's going on. This is to stop confusion and also track back as to who should have been doing what. Policies require compliance and enforce disciplinary actions, or obviously training if a person hasn't been given sufficient training. Normally an acceptable use policy which new people will sign, and everyone has to sign if there's any changes. Standards of acceptable behavior on the network. For example, creating strong passwords is a very good one, and obviously not putting it on a post-it note and sticking it on your monitor. So we've covered network documentation, why, the importance, parts of it, diagrams, asset management, the RFID, monitoring your IP addresses, vendors and contractors, all your internal policies and procedures. Alright, so that's all for now. Thanks for listening. Welcome to Module 11, Lesson 4, Network Troubleshooting Model. You'll actually develop your own model as you get some experience, and obviously depends on your network, whatever your network, or if you're managing just a small part of the network, and if you're managing a certain OSI layer, for example firewalls, or you're a hardware engineer, something like that. So it could vary. This is the generic kind of stuff that CompTIA want you to know and understand and follow. So we'll identify the problem, establish a theory of probable cause. Normally whoever has just made a change or plugged or unplugged something has broken it, in my experience. Test the theory to determine the cause, establish a plan of action, and then implement the solution. It's all common sense stuff really. Verification, documentation. Alright, so we'll normally gather information, duplicate the problem if possible. You'll normally duplicate it if it's some sort of bug and you want to recreate it, so you can send the information to the vendor to release some sort of update. Question users. Users, you've got to be very careful obviously, because they can give you the wrong information, or a lot of users think they know what the solution is, so they'll just give you answers to questions that they think will direct you to what they think the issue is. So you do have to be careful and question more than one user if you can. Identify symptoms, determine if anything has changed. Normally there has been a change, almost always. Not every case, but almost always. Approach multiple problems individually. It's a divide and conquer kind of approach. Okay, question the obvious. It's nearly always something that's pretty obvious. I've seen people waste a lot of time and energy troubleshooting less likely issues when it's almost always the most obvious thing that's wrong. Consider multiple approaches. An example is the top to bottom or bottom to top using the OSI. Is it an application problem and then moving down, or is it a physical problem moving up? And it depends on what the users are telling you and what the symptoms are, obviously. I mentioned divide and conquer. This all depends on your network really, but it could be dividing it into hardware, or all layer 7 issues, or all cabling issues, something like that. It just depends. Or the divide and conquer could be segmenting your network, so looking if a particular VLAN's affected, or all VLANs. Test the theory. Once it's confirmed, determine the next steps to resolve the problem. For example, if it's an email issue, then try sending an email, try it from a different user's device to see if there's more than one person affected. If the theory is not confirmed, you start at the beginning. Plan of action, obviously, if you can fix it there and then, fix it. If it's requiring a network downtime, then you're going to need to schedule an outage if you're working on a production network. Again, generally this sort of issue is decided by the senior IT manager or network manager. Potential effects, what's going to happen? Is it going to make the problem worse? Is it going to fix it? Is it going to cause a different problem somewhere else? When you implement the solution, escalate as necessary. Again, you normally need verification of somebody else, a senior manager, that this is the correct course of action. Verify full system functionality. Speak to the user who actually logged the issue and see if it's resolved for them and whoever else was experiencing it. If applicable, implement preventative measures. Document the outcomes, findings and actions. This is basically useful if somebody else deals with the same problem. I know when I worked at Cisco TAC, you could often put in error messages and similar things, or look at certain model numbers, and you'd often find somebody else that had the same problem, and you could see how they fixed it, or if they'd established that a bug had been found, and then if that bug's been fixed in another iOS. Alright, so pretty common sense stuff hopefully, but we've put it into writing now, so you've got some sort of method to follow. Identify the problem, establish your theory, test it, plan of action, implement the solution, verify, document. You need to write that down a few times so you get the correct order in case it's a drag and drop type question. Alright, so that's the end. Thanks for listening.
Network security. Security fundamentals. In the last lesson, we discussed managing a network and administering a network. Now, this ranged everywhere from troubleshooting to speed optimization. And in this lesson, in the next 4 modules, we're going to discuss security. Now, just like with A+, we talked about networking and security. In Network Plus, we're going to talk about security with the understanding that there is a whole other certification and a whole other lesson that revolves specifically around this concept. So we're just going to sort of brush over the important things that we need to know in a Network Plus or a network administration environment. So to start us off, we're going to talk about the basis of network security and the fundamentals that we're going to discuss in the next 3 modules. So this involves discussing network security and identifying exactly what it is when we talk about the basics. Then we're going to go over some of the things that are fundamental to having a secure network. These include keeping the network up to date, strong passwords, having a secure VPN, virtual private network, administrating user access in a proper way, and making sure to remove any inactive accounts. Now, the reason I focus on these fundamentals are these are the things that we'll see on the Network Plus exam. Now, the word security means the same thing just about anywhere you look. When it comes to homes, it may refer to locks and alarm systems. But when it comes to networks, it refers to a lot of different methods, but the concept is still the same. The point of security, regardless of where it is or what it's protecting, is to keep the threats out and the valuables in. Think of a bank vault. The door to a bank vault is a few feet thick. It's made of very sturdy metal, and this is because the bank needs to keep the money and valuables securely inside, while also keeping the potential threats outside. Now, if someone really wants to break into a bank and steal the money, they're going to be able to. But what we want to do is make it as hard as possible for them to come in and steal the money. Nothing is beyond anyone's purview. It's simply that we want to make it as difficult as possible for these thieves, hackers, or whoever to get in and take it. Now, the same principle applies to network security. On a network, data can sometimes be more valuable than money. In fact, I know a lot of CEOs, CIOs, CFOs out there who would much prefer that you steal some of their money rather than steal their data, especially when it comes to user data or to private or privileged information, because this stuff is literally priceless. This is why it's really important to have a properly secured network and make sure that it stays that way. And these are 2 different things, securing it and then monitoring it to make sure it remains secured. Now, it's very important to make sure that everything on the network is kept up to date. When programs and patches have been used for a long time and they're well known, the attackers who've had an opportunity to find holes with them begin to make use of those holes and hack through them. So the longer something is out there and being used without a new version, the more times attackers have to find exploits within the program or the patch. This is why, as network admins, we need to make sure that all the programs and patches are kept up to date. Programs that get used often should be updated as soon as there is a new version, or as soon as a new version proves to not be buggy. Now, when running a device on Windows, the admin should always check to see if there's anything available in Windows Live Update or Microsoft Update, which we have talked about in A+ quite a bit. Now, usually this can install new drivers and patches that have been updated for performance and security, but other things we need to be aware of are Adobe products, Java, which is integrated into a lot of browsers, and the browsers themselves to make sure that they're all tight and secure. Once again, we don't want to update things immediately because maybe they'll bring down the system. But we need to weigh this against the fact that if a patch goes out there to plug up a security flaw, that as soon as it goes out there, the hackers now know, oh look, there was a security flaw. And now they can begin to make use of that security flaw until you update things. So what we're really looking to do is balance updating immediately versus buggy updates. And this is an important thing to keep in mind. Now, it's very important that we keep another aspect of security in mind when it comes not just to our networks, but to just about anything we're dealing with on devices, and this is our passwords. People tend to think that just because something is password protected, that means it's safe, but this really isn't true. Something that's protected by a password is ultimately safer than something that's not, but a password is nearly useless unless it's a strong one. Think about all the movies in which someone has to figure out someone's password. Looks around the room, sees a picture, types in the name of that person, and bam, they're in. Attackers can use things called keyloggers in order to log what passwords you are entering on your computer and then send that over to the hacker. They can then take the letters, symbols, etc. being used and try to piece together what the password could be. Depending on the attacker, they might be really successful at stealing your password simply by just observing what you type in. This is called shoulder surfing. And it is a big problem when we think about ATMs, people typing at their office, and so on. This is a huge problem in general, but it's really problematic if you use the same password for more than one thing. Think about it. As soon as they get one password, they have access to everything. Especially if they get access to your email, they now have access to your entire life because they can reset everything through your email. So it's really important to keep different passwords for each sort of service that you access. In a general rule, you shouldn't use the same password for more than one thing. This can end up becoming really confusing if you're dealing with a lot of different accounts that require many different passwords. So there are some programs that act as basically password vaults, and they require one master password to access them, and then you have all of your information stored inside of those. But I think some of those just have as many problems as regular passwords. All you need to do is get access to the one program, and suddenly you have access to all of the password programs. So it's important sometimes for you to create a long random password that can contain special characters like slashes, ampersands, etc. And these programs can do that as well, but the problem with that is we're also not going to be able to memorize that. So, and another important aspect of password protection when it comes to strong passwords is to use random letters, symbols, and etc. and long passwords, which are always better than short ones. For instance, using the password 123 is really weak, whereas this one on the right, which I can't even pronounce, is really strong. Now, of course, the problem with this is it's difficult to memorize. And if it's difficult to memorize, you're probably going to have to write it down. If you write it down, that gives someone something to steal. Or you put it in a password vault, or this is maybe made up automatically. But in all these cases, one password can get access to all the passwords. And so it's important, again, we talked in the previous one about we sort of have to decide whether we want to update something immediately or whether we want to update it, after a little bit after it's been tested. The same sort of thing with passwords. We don't want something too weak, but we also don't want something too strong that we can't remember. So the best thing, I think, is to think about, for instance, a code that for yourself. So, for instance, a common one with the term password is to replace the A's with ats and the O's with zeros. If you think about creating your own password, we could do this. For instance, let's say we wanted to turn this secure and organized into a password. Well, I could replace the S with 5s. I could replace the E's with 3s. I could replace the A's with ampersands, and so on and so forth. Even an I, replace that with a exclamation point or the number 1. And voila, I've just created what looks to the plain eye as a pretty complex password that a computer wouldn't be able to necessarily break. But you remember it because you've come up with your own code of how you're going to replace certain symbols and numbers. And it wouldn't hurt to throw in a couple uppercase letters there as well. Now, with virtual private networks, there's a lot that can go wrong security-wise. Because it travels over a public network in order to connect to your local LAN, and the users remotely connect, an attack can happen from literally anywhere. So in order to help stop attacks, the admin needs to require remote users to have multiple points of identification. Remember, in A+, we talked about having multi-authentication. And remember, authentication, we have 3 different things. Something you know, something you have, and something you are. So if we're going to use multiple forms of identification, maybe one thing we want to do is have a standard username and password, and also a PIN or security question they would have to answer. These both fall under something you know. We could also give them a fob key that has a rotating password on it, and this would be something they have. It makes it more difficult if I use multiple forms of this authentication, and that way it's not just things that are written down or known, it's also things that are had, or even better, things that you are. For instance, a retinal scan, fingerprint, voice recognition, etc. The point is, the more of these you have, the easier it is for you to keep your stuff secure. However, it's also more difficult to log in, and it's going to take more time. So again, we're dealing with time and ease versus security. And we have to find the right balance because we don't want people to get so turned off by all the heightened security that then they can't use our product. It also might be necessary to have a firewall between the VPN and the physical network. The firewall acts as a sort of last line of defense, and if somehow an attacker manages to get through the points of identification, the firewall might be able to stop them from connecting to the network based on where they are, the information they're trying to transmit. If they're using an unknown or untrusted IP address, the firewall may be able to stop them before they connect to the local area network. Now, it's often the case that users have to access things that they have no business accessing. For example, someone in the graphic design part of the company has no need to access the accounting records of the company. And sometimes, however, users are given permissions to access data like this simply because it's overlooked by the administrator. So this is a huge security issue and one that's easy to fix and needs to be looked after with care. The admin should only make sure that users are given only access to the data that they need to do their job. This is what we call the principle of least privilege. Now, this change can be made by password protecting, or it can be made using group policy, meaning that we have an accounting group and we have a marketing group. If you're placed into one of those groups, then you're not going to be able to access anything except for what your group has access to. Now, the other thing we want to do is make sure to clean up inactive accounts. When a worker leaves the company, the first thing the admin needs to do is to change the password to the user's account, or what we call deactivate the account. It would be a very bad thing if a former employee were to access the company's files, and who knows what they could do with those, especially if they were fired. So once the password has been changed, there's no way for them to access the account. But it's not necessary for the admin to delete the account right away. If the employee was to come back to the company soon after and needed to access their old files, they could be given a temporary password and then monitored to make sure they could get their old information. However, if an account has been inactive for a while, it should be deleted or discontinued. An idle account is a really dangerous thing to have on your network. If an attacker is about to access this account, they could easily slip past unnoticed on the network. Until something actually happens, we wouldn't really know that there's a problem. So in order to prevent this, we really want to delete accounts as soon as the users do not need them anymore. This is why generally HR and IT talk to one another, so we can make sure once we let a person go or fire someone, their account is turned off almost immediately. All right, so these were some of the fundamentals. We talked about the necessity of network security. Remember, data can sometimes be more important than money, because it's going to cost a lot of money in order to recover and make up for the loss of data. We also identified some of the fundamentals of a secure network. First of all, we talked about keeping things up to date. We talked about keeping up the firmware, drivers, operating systems, patches to software, etc. And we're always dealing with a balancing act here. Are we doing things immediately? Or are we going to wait and possibly be susceptible, but we might have buggy updates? So we sort of want to find a good medium, middle-of-the-road solution there, realizing the longer we wait, the more susceptible we are to attacks. We also want to make sure to have strong passwords. Remember, a strong password generally means It's 15 characters or more. The longer the better. We have numbers, symbols, lowercase letters, uppercase letters, and we want to use them in a varied random combination. We also want to make sure that we're not reusing the same passwords. And don't write them down. That's always a problem. Now, of course, again, we have a balancing act here because the more difficult it is, the more difficult the password, rather, then the more likely someone's going to write it down. And so we need to also make sure that the passwords have a certain degree of ease of use. We also are probably going to want the passwords to expire every once in a while, and so on and so forth. With a VPN, we need to make sure that there are multiple forms of authentication. Remember the three things we have when it comes to authentication: something you have, like a fob, something you know, like a password, and something you are, like a retinal scan or biometrics. Now, when it comes to user access, we want to practice the principle of least privilege, meaning you're only going to be given access to that which you need access to do your job. Accounting does not need access to marketing, and vice versa. Finally, we want to make sure to disable or delete inactive accounts, keeping in mind, of course, that someone who leaves the company might need to come back, and therefore we might want to make it easy for them to have access to their old stuff. Network security, authentication, authorization, and accounting. In the last module, we started off this lesson by discussing the fundamentals of network security. Now, a big portion of network security has to do with AAA, or authentication, authorization, and accounting. The AAA server on a network is probably one of the most important things when it comes to security, and it does quite a bit of work. So in this module, we're going to define and discuss these three A's: authentication, authorization, and accounting in further detail, so we know not just what they are, but how they're implemented in a very general way. Authentication is the first A. It's used to identify the user and make sure that the user is legitimate. Sometimes attackers and bots will try to access a network or secure data by acting like they're a legitimate user. This is where authentication comes into play. Any secure network is going to require something like a username and password to log in, and any data that's really important or secure needs to be protected. Now, there are ways, of course, for these attackers to gather the password and username information, but the smart thing for us to do is to change passwords for all users on a network frequently, probably every 30 to 90 days. Again, we have to balance that with how easy it is for someone to come up with a new password, and if they're going to remember the new password they come up with. We need to make sure that the passwords are documented in some way, although we want to be careful again, because when we write them down and document them, that opens up another way they can be stolen. And we want to make sure that they're all secure. If an attacker has an outdated password, it's going to do them no good. So if we can put this in another way, authentication verifies identity. This is sort of like you have a ID card or driver's license. That provides your identity and authenticates you are who you are. One of the reasons we have pictures on our driver's license or government-issued IDs is so that people can look at it and guarantee we are who we are. This used to be done with signatures. They would look at two signatures, make sure they were identical, and then we could authenticate the person was actually us. Now, we've moved way past this now. We can even use things like fingerprints, which more or less authenticate that we are who we say we are. So here is another form of authentication you may have encountered this one before when you're trying to access things on the internet. This is called, or looks like, a CAPTCHA. and it's used to stop bots from accessing secure data or infiltrating someone's account or making an account when we don't want them to. So the text in the gray box is difficult to read for a bot. It's actually a picture, and it's very difficult for robots to read this and know exactly what to type in. So because of this, the CAPTCHA is usually made for different fonts, distorted text, pictures, etc., and it can be slightly different for a human to read, but not so difficult for them that they can't actually type it in. When you type in the image into here as text, then you can basically ensure that you are who you say you are, that you are a human rather than a bot. Now, authorization is the next security level after authentication. It's the second A. So once a user has been determined authentic, we've authenticated their identity, they're going to be allowed onto the network. But they can't just have free reign and do whatever they want. We want to make sure that they can only access specific things. Remember that concept of least privilege? Well, we want to make sure that the person who's on there is only going to access stuff that they are allowed to access. So you're authorized to access only certain things. Now, there are users such as the admin who can generally access a quite deal more, but we don't want, for instance, the administrator to have access to the partner's private email in a law firm, and we don't want someone who works in accounting to have access to marketing. So authorization basically provides the information on what the person or the ID'd person who has been authenticated is authorized to get access to. Now, authorization procedures can stop users from accessing certain data, services, programs, etc., and can even stop users from accessing certain web pages. For instance, we sometimes have filters that make sure our kids don't access very specific information unless they can type in a password that would authenticate that they're an adult. So here's an example of what a denied web page might look like. As you can see, the user is being told that an error 403 has occurred. In other words, the web page has been forbidden. It requires you to log on, and you have not logged on successfully. So you have not authenticated who you are, and therefore you are not authorized to have access to a specific degree of information. Now, users other than the administrator will most likely not be authorized to run commands in the command prompt, and we've looked at this with A+, running things in an administrator mode. If the user does, they're probably going to receive an error that looks like this. This command prompt has been disabled by your administrator. The administrator can deny every other user on the network the ability to use the command prompt because they could do something that they are not authorized to do. So it's up to the administrator to make sure that only authorized users can access the command prompt or do other things on the computer or on the network. For instance, rebooting computers, accessing servers, and so on. Now, the final A we talked about, authorization and authentication, is accounting. Accounting is not the same as in bookkeeping. It's accounting in the sense that everything a user does while on the network has to be accounted for and carefully watched. This is sometimes also called auditing. Another term that gets back to accounting in a sort of financial sense, but it means something different. The users on a network can often be one of the biggest of our security concerns. Most of the time, someone is going to hack our network from inside rather than outside. And so keeping track of how users spend their time is one of the most important aspects of network security. The accounting function of the AAA servers to do exactly that. It watches all of the users and monitors their activity, as well as all of the resources they're using. These resources could include stuff like bandwidth, CPU usage, and a lot more, not to mention what websites they're accessing and so on. Now, some people say, hey, wait, you're infringing on my right to use the internet. But if you are at your company using your company's internet, then you have signed most likely an agreement saying you're only going to use it for specific purposes. And you've probably also signed an agreement, whether you know it or not, that allows them to monitor you while you're using the internet. So here's a representation of what the accounting function of a AAA server does. It oversees everything the users are doing and keeps track of what the resources are those users are taking up and how they're spending their time. Now, this was a short module, but it discussed the AAA, and these are three really important concepts you need to know and understand for Network Plus. First, we looked at authentication. Authentication makes sure that the identity has been verified. This is just like, in a metaphor, your driver's license, which has a picture ID. Next, we talked about authorization. This is what you are allowed to do. This could be just like you're authorized, if you have your driver's license and you're 21 and up in the United States, to drink. So, authentication is provided by the driver's license. You are who you say you are. And then authorization says whether or not you're allowed to drink or even drive, depending on your age and a variety of other circumstances. Finally, accounting is basically a log of what you do. If you get in trouble with the law, that's put on a record. That way, if you're pulled over by a policeman, let's say for speeding, they can scan your driver's license and see if you have any outstanding warrants or if you've been pulled over in the past. In this way, accounting provides background information on you and can make sure that we know what you're doing on the network, what information you're accessing, and also make sure when you're accessing it, and so on. Let's say that we have someone rob our store at midnight and the store is closed. Well, if your security card was used to get access to the store, then we know that either you robbed the store or someone who stole your security card robbed your store. Network security, system security tools. In the last module, we talked about the AAA, authentication, authorization, and accounting. Now, these three aspects of security are really important to running a safe and secure network, but there are also some security tools and programs that prove really useful when we're trying to put these into action. Most notably, we're going to talk in this module about firewalls and antivirus software. There are a lot of other tools and pieces of software that we can use, and we'll talk about these in a bit. But these two come up quite a bit on the Network Plus exam, especially because they're the two most prevalent that we see in the field, especially from a consumer's point of view. So in this module, we're going to define what a firewall is, and then identify its importance and how it works. We're also going to define antivirus software and identify its importance and how it works. So let's start by talking about a firewall. This is something you've probably heard about, you might even have on your computer or on your home network. A firewall is an essential part of any secure network, especially in today's day and age, and a network would just be at risk almost constantly without it. It's basically a security system that serves as a barrier between the local network and the wide network, or VPN. It analyzes the data packets that are trying to enter the local network and exit the local network, and determines whether it's safe to let them in or out or not. In a more general sense, a firewall is set up between local private network and a public network, like the internet. So internet protection is actually a large part of what the firewall is used for. Now, the reason it's called a firewall is because, if you think about it, the fire is going to burn up all the bad stuff, but not the good stuff, as opposed to a brick wall, which wouldn't let anything in. So the name sort of describes what it does. People often establish firewalls as their main line of defense from internet attacks, and they can be configured to not allow access to certain websites, as well as not allow downloads from certain websites or certain ports to be open. We'll use something called a port scanner to see if there are any open ports on our network that are going to let bad stuff in. And what we can do is actually set the firewall to allow inbound and outbound ports. Now, I know inbound probably makes more sense than outbound, but if you think about it, if somehow I get a virus into my computer and it starts sending information out, I want to make sure to keep that information in so that I don't release any, say, private information about my network. Now, the term firewall, as I was just talking about, comes from the physical firewalls or doors that a lot of buildings contain. These doors are fireproof, and they contain a fire to one area to stop it from spreading elsewhere, which is another way we get that term. They're also meant to block out fires. So this is what a network firewall does, but with threats from outside and inside of the network. So think about a firewall, if we can use a metaphor, as the moat and the stone walls around a castle. Everything within the castle walls is really contained and localized. Outside the walls, however, there's a public domain, the internet. Walls in the moat of the castle are the last line of a large-scale defense before an attack can infiltrate. So this is exactly what a firewall does. It keeps the public network and the private network separate from each other. Now, the castle, much like a firewall, does allow certain things inside. This is like the drawbridge of the castle. So when the walls and the moat keep unwanted things out, but then things are trusted, so they're allowed in through the drawbridge. So firewalls do the same thing with packets of data. They only allow the ones that they trust to enter the network. And we do this, again, by allowing or not allowing certain ports. Now, of course, one of the downsides of a firewall is it can block good stuff. So, for instance, if I have QuickBooks on my computer and it's trying to access its download server to update the program, I could block the inbound port by accident through my firewall, and then it wouldn't be able to get updates. So this is one of the issues. Now, firewalls can be either software or hardware. You probably, without even realizing it, or maybe you do, have a software firewall built into your OS. So if you have Windows 7, Windows 8, Windows Vista, then you actually have a firewall built in. Now, you could also have a hardware firewall, which, if we're talking about your home network, is generally built into your SOHO router. That's right, your SOHO router contains a firewall built in and will allow or not allow certain ports to come in. This offers us two levels of security. One through the hardware, and once it gets through into our network, then we have one on our computer. Now, like we said before, firewalls are mostly used to block attacks from the outside, but it's not the only use. See, there are quite a few, actually. As we already talked about, they keep attacks out by monitoring everything that tries to enter. If something isn't trustworthy, it's not going to let it through. Now, though this might be the most recognized use, there are some other important aspects that we want to talk about. For instance, the firewall acts as a barrier, which not only keeps things out, but it makes sure that important things inside the network don't get out, which in effect keeps the data secure. This is what I was talking about with outbound ports. For example, if secure data is being accessed and taken from someone on the outside, then we can make sure that the data can't get out through our network. It's going to be stopped, just like containing the fire within the building. This is really important to businesses and organizations where data really equals money or more than money. Now, for individuals, it can help secure important information like your social security number, credit card information, etc. These aren't things that you want in the hands of attackers, so a firewall can actually prevent these problems that an attack might cause. Just as a matter of example, I'm here in Windows 7, and let's go ahead and check out the Windows Firewall. Now, I actually have two options here, Windows Firewall with Advanced Security and the plain old Windows Firewall. If we go into plain old Windows Firewall, you can see the firewall is on, and it's working on this network. And if I go over here, I can choose whether or not to turn the firewall off or on. Now, if we go to those advanced settings I referred to earlier, you can see that I have inbound rules and outbound rules. There are inbound rules that allow and disallow certain information. For instance, this rule, which says file and print sharing echo request, allows the connection to be made for ICMP packets, which is basically for ping. Now I can choose to disable a rule or create a new rule. For instance, if I have a specific program or port that I know needs to have access. You remember the ports that we talked about previously, and this is an example of how you would use that. Now, I also have outbound rules. So, for instance, instead of allowing information into the system, I want to talk about information I want to let out. So, for instance, Windows Media Player has a number of rules that are here. Notice that none of them are enabled. So if we were to check this one out, for instance, it says there's an outbound rule to allow the sharing service for Windows Media Player. Now, I could enable this, and that would allow it to occur, but because it is disabled at this moment, it's actually not going to allow any of that information out. So this is how, very quickly, the firewall works on your software, but it would also work the same way if you had a hardware device too. You can also have it monitor what's going on. So, for instance, this is telling me that the inbound connections aren't matching a rule, so that I could go in and check out exactly what that is. And it's also telling me I can see all the active rules and so on that are going on here. Now, here's an example of what a firewall might do. As you can see, it's separating the WAN, which usually would be shown by a cloud, which we could call the internet. And the users on the WAN have to be authenticated and allowed before they go past this firewall. This is useful because an attack could very possibly infiltrate the WAN and try to get access to the local network. But if they're not recognized and not given permission by the firewall, they're not going to be able to enter the LAN. Sometimes what we'll also have is a separate network that they'll be allowed into. That's sort of not between the firewall. In some cases, even if I erase this, we'll actually have two firewalls. One which allows a lot of stuff in and creates sort of a demilitarized zone, which then we can either put a test server on or a test computer. Sometimes we'll call this a honeypot. We'll allow a lot of stuff in through the first firewall, and then when the hackers find stuff, they're going to start attacking this honeypot. Honeypot being sort of like bees going to honey. We can then see what they're looking at, what they're trying to get access to, etc. And this gives us a sense of testing the network security. Then, once they get into the demilitarized zone, they have to pass another set of protocols to get in to our network. And as we mentioned, there might also be firewalls on each one of these computers, if you can pardon my awful drawing. So we're going to have software firewalls just like we have hardware firewalls. In fact, this might be a device, or it could be a server with firewall software built in. Now, antivirus software is everywhere, and there are more companies and softwares that protect against attacks than you can count. Some of the ones you might even know are, for instance, McAfee and Norton, two big ones. There's also AVG, which offers a free one, Trend, and the list goes on and on and on. Now, in general, most of the software is pretty similar, and they all do the same types of things. Some are more expensive than the others. Some are more for enterprises. They have a server set up so you could monitor your entire network without having to go to each individual computer. But in effect, they all do the same thing. So although a firewall is a really good resource against attacks, there's nothing it can do once the attack has already taken place, once the system is already infiltrated. So attacks are not always obvious, and sometimes attacks are so subtle they happen right under our noses. You might not even know you have a virus until it's already done damage. So even though firewall protects the attack, it can't get rid of the malicious things that have gotten through. This is where antivirus comes in. This software has many functions. One of the more important ones is that it offers real-time protection. The software is constantly on the lookout for attacks and malicious things, software that doesn't look right, and firewalls merely block the attacks, whereas antivirus software will go after an attack before it can get through the firewall. Now, this software can also scan for viruses and remove them once they're found. Now, sometimes this can be tricky because just like if I install the antivirus software, after the virus has infected my system, the viruses might not be found by the virus software. It's also going to look at suspicious files and data and place them into what we call the quarantine. The quarantine, just like the name, is a place where we're going to put all those files that might be infected, and that way we can make sure that we can look over them as an administrator, see if they're infected, and either delete them or bring them back into the network. Finally, antivirus software is going to update itself constantly. If you imagine that viruses and hackers are constantly doing their work to keep everything up to date, well, then you probably have an understanding that we need to keep the antivirus software up to date. Just like every year, we have to create new vaccines for the flu and so on, we want to make sure that the antivirus software is kept up to date. This is generally what's referred to as data files or DAT files, and you used to have to download these off the internet and install them. Now, this happens usually automatically, just like Windows Update. But we need to make sure the setting is correct so that it allows itself to be updated automatically. So just to recap, we talked about a firewall. Remember, it works with inbound and outbound ports. It's going to allow some good things in, good things out, but it keeps the bad stuff out and the good stuff in. We're also going to identified its importance, talking about how we can have several hardware and software firewall solutions. And again, we might have to manually edit the inbound and outbound ports to allow, for instance, a software program that uses its own port to get out and get updates. One of that software that might need to go out and get updates would be our antivirus software, which is what we talked about. This is software that does not, it can prevent an attack, but it can sort of take over from where the firewall stops. Whereas a firewall can't stop it once it's already started, an antivirus software program can go a little more in depth. It has to be kept up to date, and it might not necessarily be able to remove the virus, but it will put the virus and the files that it has infected into a quarantine. So that's really what's important about it, and if you've been working on a computer at all in the past 15 or 20 years, you've definitely had to use this. And nowadays, actually, Windows requires that you have a virus scan on, or it will actually bother you in the notification center quite often. So now that we've talked about this, let's end by talking about how we can protect our data in a very raw sense called encryption and cryptography. Network Security, Encryption and Cryptography 101. So to round up our discussion of network security, I want to talk about the way that we secure data at the source. And this gets to basically encoding the data that we send. So even if it's captured or sniffed, we can't allow the hackers to figure out what it is that we were sending in the first place. And so this gets to encryption and cryptography, just like code breaking from World War II or from our military when they would send encrypted messages. And because this is a pretty in-depth topic, we're only going to cover this broadly. So first we're going to define and discuss cryptography, and then we're going to define and discuss encryption, including the difference between plain text and ciphertext, one being the way that text is sent if we don't add any encryption, and the other one if we do add encryption. And then public and private keys, sort of like decoder rings, for how we can read the ciphertext. The public and private part comes about in the way that we have the sender and the receiver decode and encrypt certain messages. Finally, we'll identify examples of both and how they work. Now, this entire subject gets a lot more in depth if you go into Security Plus and the CompTIA Security Plus certification. So here we're just covering this in a sort of very broad sense. There are people whose entire jobs it is to simply deal with this aspect of networking. So in a very general sense, cryptography is the practice of securing information using codes in order to keep adversaries or hackers or outside folks from understanding it. Now, the word adversary generally means an enemy or an opponent. In this case, it just means someone who would want to intercept the information you're sending. It's very likely that this adversary is your enemy, quote unquote, such as a computer hacker. And although cryptography is not only used in computing, in fact, it's been used throughout the world, even in the United States, in military, etc., it's used quite a bit here in networking, and it's used a lot in how we package data into packets. So cryptography simply means writing, speaking, and communicating in code. Now, this practice dates back to the time of Julius Caesar, and quite possibly even earlier than that. Caesar used something that's referred to as the Caesar cipher, which we'll look at in just a second. A cipher is a way to encode and decode data. So Caesar used it to send messages and commands that needed to remain secret. We also used it in the United States during World War II. The Japanese used it. There have been a whole bunch of movies about this. Cryptography and ciphers play a large role in communication, especially when we don't want our enemies to know what we're talking about. This was true all over the world. People began speaking over the radio, writing in codes in order to keep information secure. So a language like the English language might be a form of cryptography to someone who speaks Spanish if they don't understand the language. However, the fact that there is a dictionary out there that translates everything for them means that the code is pretty easy to break. So what we're really talking about, and what the Caesar code did, for instance, is replace every A went down 3 numbers and replace it with a D. So whenever you saw, for instance, the word apple, we would add +3 would be our code. And so if we went down 3, if we wrote this out, from A is BCD, from P is QRS, from L is MNO, and from E is FGH. So if we were to write apple in the Caesar code, this is what it would look like. And that's because if we went back 3 for each of these, we would get the word apple. Now, there was only one code that remained unbreakable in World War II, and it was used by the U.S., so the Japanese could not intercept messages that were being sent. The U.S. actually enlisted the help, this is a really interesting fact, of Navajo Native Americans in order to help them transmit messages, and these Navajo code talkers spoke a language that was so dead and was only spoken by very few people that every U.S. major base had a Navajo code talker with them, and they would translate messages and send them over to each other. It was never cracked by the Japanese. There was even a movie about this. So this is how cryptography worked, right? If we have a language that someone doesn't understand, then that is a form of cryptography if there's no dictionary. In this case of the Caesar code, all right, this is what he did. And if we want to look a little bit closer at how that worked, we can see the Caesar cipher. Basically, every letter, in this case, we're going back 3, was in the original text, and then you would go back, and so A became X, B became Y, and so on. What we did earlier was actually go forward 3. So whatever it was, we could figure out what the code would be simply by minusing or adding 3. So for instance, if we were to write ABC right now in the Caesar code with a -3, it would turn into XYZ. This is a really simple code, which is why it's not used anymore. Now we have much more intense codes that are used. Now, compared to cryptography, encryption is the practice of putting important and confidential information into a code that can't be accessed by unauthorized users. Encryption is basically the use of cryptography, as you can see by the word here. So encryption is usually used for information that we want to keep as a secret, or that someone we want to make sure is not going to get out to other people. Now, a lot of times we're going to use encryption with not just regular data, and we're going to add higher end encryption to stuff like credit card numbers, social security numbers, bank information, etc. So encryption is really just a part of cryptography. Cryptography is broader. Encryption happens with the data that is being sent through a network. So like cryptography, an encrypted message is coded and appears to be complete nonsense to someone who doesn't know what the code is. Now, the data is run through an algorithm in order to place encryption on it. Then, on the other side, the reverse of the algorithm is used to decrypt the data. And an algorithm is a mathematical equation that can be used for several different things. For instance, in the Caesar code, the mathematical equation, if we had X as the plain text and Y as the ciphertext, or the text that had a code added to it, we could say that if we took the code, it would equal y plus 3. So if we had x, y, z, and that was our code, and we added 3 to that, then we would end up with A, B, C. And so that's how that all sort of works. Now, encryption in algorithms are a lot more intense than the one I just sort of laid out, and they're used not only to code data, but also to decrypt it or unencode it in a way that can't be read by our adversaries or people outside of ourselves. So through the encryption process, we come across around 2 different types of text that I just pointed out. First, there's plain text. This is the unencrypted data. At this point, anyone can read what it says because there's no code on it. Then there's ciphertext, which is the encrypted data, the data that can only be decrypted using a special key or using that special algorithm. So in the world of encryption, there are normally 2 different types of keys, or algorithms, in other words, that come into play. First, there are what are called public keys. These are generally used in some cases to encrypt the data. These keys are known by both parties. That's why they're public. They're put out on the web, or they're sent out by email or something, so everyone has it. And these keys are known by both parties so that in a data transfer, they can be used to encrypt the data. Now, in most cases, the end receiving the data receives the public key also. So if I'm sending you an encrypted sort of message, I'm going to send you the public key along with my data. Now, the way that encryption and decryption will work is the same way. These public keys run plain text through the encryption algorithm, and they place coding on it. Now, private keys, on the other hand, are usually only used to decrypt the data. So, I will send you my public key, you will encrypt a message, send it to me, and I can only decrypt that using a private key which only I have. And so this is basically how the whole system works. Now, there are different types of encryption systems, some where both sides have to have public keys, some where we have a private key. Again, I'm not going to get too in-depth with that right now because this really gets into more of security and security plus. But the important thing to realize is that the public key goes to both parties, whereas the private key, which is only used usually to decrypt the data, is only held on to one person. So anyone can encrypt the message, but only someone with the private key is going to be able to decrypt the message. So if we take a look at how this works, Company A needs to send data to Company B, but it's really important information that needs to be secure and encrypted. So Company B sends the public key to Company A. Company B created this public key so that the encryption and decryption would work with each other. Now, Company A uses this key to encrypt the data, then sends it to Company B, and Company B uses the private key that only they have in order to decrypt the data. Now, you can only encrypt, in this case, with the public key, and you need the private key in order to decrypt. That's how this works. But the way that Company A got it is because Company B sent the public key over to them. Alright, so just to recap, we began by defining and discussing cryptography. Cryptography, again, is basically having a code of some sort. We use codes in all sorts of ways. We talked about the Navajo Indians using codes during World War II, and we also talked about the Caesar cipher, which basically just means adding a certain number to a letter. So for instance, if I have +2 as my Caesar cipher, and I want to write the letter A, instead I'm going to write the letter C, because it goes A, B, C, right? There are 2 added. So then if I sent this C to someone, they know, oh, I can subtract 2 from it, and that's my Caesar cipher. Now, we also defined encryption, and encryption is actually the process of doing all this. We have the code, we have the cryptography, and then what we want to do is actually encrypt the data using it. Now, we talked about 2 different things, plain text and ciphertext. Plain text is the data before we apply the code to it. Ciphertext is after we've applied it to it. So, plain text anyone can read, ciphertext only those people with the code breaker can read, or the keys. We also talked about the difference between a public and private key. Public keys are sent to everyone, so everyone has access to them. Private keys are only held by one party. They are private. Now, generally speaking, public keys are used to encrypt, whereas private keys are used to decrypt. So anyone can make a message that is in ciphertext, but only the people with the private keys can actually decipher it. And then we talked about some examples of using this. For instance, not only the Caesar and the Navajo, but we also talked about wanting to use it for social security numbers. Passwords are a big one. And of course, today's market with all the finances going on, bank and credit card information. Network Security, IDS, IPS Implementation. In the previous lesson, we talked about different aspects of network security. Now, because this topic is so encompassing, we're going to continue on with this network security in this lesson, where we're going to focus specifically on two types of security. One is IP security, which we'll talk about in the next module. And in this module, we're going to talk about intrusion detection and prevention systems, otherwise known as IDS and IPS. These are pretty important and come up a bit on the Network Plus exam, which is why I want to commit an entire module to them. So we're going to begin by talking about an IDS, or intrusion detection system. Notice the D there. And we're going to talk about the two different types of IDSs that exist. One is behavior-based, and one is signature-based. We'll discuss what this means in a bit. We're also going to define and discuss IPSs. The difference between an IPS and an IDS is where an IDS is an intrusion detection system, and IPS is an intrusion prevention system. Notice the difference between the D and the P. One simply notifies you, the other will actually prevent. We're then going to discuss the importance of having an IDS IPS, and in some cases we will have devices that do both. And we're then going to discuss very briefly implementation. Now, of course, just like anything, we're going to look at this from a mile-high view. So this isn't the in-depth, detailed version. This is the broad overview. Now, an intrusion detection system is software or network device that's used to detect, again, remember that word D, detect, attacks or intrusions that are made on the network. The attacks that it detects are then reported to either the administrator or to a threat log, sort of like the event viewer. If it logs the information first, it then alerts the administrator so the administrator can look into the issue. Now, while IDSs are up to date and make alerts as soon as an attack occurs, they are still referred to as passive. The reason they are called a passive security system is because they don't do anything to actually prevent the intrusion from stopping. All they do is they passively notice that it's occurring. This is because, again, they merely detect the attack. They don't do anything to prevent or combat it. Now, there are a few different types of intrusion detection systems, but I want to focus specifically on two different types. The first is called a behavior-based system. This makes alerts and reports of attacks based on the behavior that they deem to be suspicious or out of the ordinary. These unusual behaviors can include large amounts of traffic, policies being violated, and even people attempting to access things that they're not supposed to. Now, a signature-based system detects threats by reading their attack signatures. Just like a virus scan program has a signature, remember those data files we talked about, that tells it what to look for in a virus, intrusion or attack systems have a signature and a signature file that they can look at that lines up with the signature of an attack or an intrusion. So, signature-based systems scan the signatures of known attacks, and when it detects one of these signatures attacking its system, it makes an alert to the administrator or reports it to a log. So again, the signature is based on more or less a history, whereas behavior is based on what we see. They're looking at two different types of attacks, and there are the pluses and minuses, of both. But you can see behavior, again, is looking at a more all-encompassing general sort of view, whereas signature-based is looking at previous histories of attacks and aligning the upcoming or current attack with that. So here's how an IDS works. An attacker, shown on the left, sends an attack through the internet in order to access the network, or the local area network. The attacks go through the internet towards the network. Now, in between the internet and the firewall is this IDS. And what it does is it detects the attacks being made and sends an alert to the administrator. Though it doesn't do anything to block the attack, this is okay because the firewall is still set up to handle the attack. So the attacker comes in, isn't able to access the information, but the administrator is still alerted that there is an issue going on, and in case the attacker begins to double their efforts, the administrator can sort of get on it and make sure that nothing is going to get through. Now, similar to the intrusion detection system, an intrusion prevention system also detects attacks that are targeting the network. However, intrusion prevention systems not only detect the attack, they also prevent it from happening and causing more issues on the network. These are considered more reactive or proactive software or hardware, because IPSs do a lot more than IDSs do. They're reactive in the sense that if an attack is attempted, they're going to block it from entering the network. Just like a breaker box is going to sort of kill the circuit by switching the breaker before the electricity can do any damage to the wall, IPSs might even kill the connection out to the internet to stop anything from happening. They're also proactive because certain IPSs are going to seek out attacks and stop them before they even make an attempt on the network. For instance, scanning for ports. In this way, an intrusion prevention system is more expensive than an IDS, but this is because it does a lot more to provide safety for the network. Rather than leaving the job in the hands of an administrator, who perhaps isn't even on site at 3 in the morning, the IPS is going to handle the attack and prevent the attacker from connecting to the network. An IDS only alerts the administrator and does nothing about it. For this reason, IPSs are more expensive. Neither system is exactly cheap, and IPSs can sell for maybe even $50,000, depending on how versatile it is. So here's what an intrusion prevention system looks like. As you can see, it's pretty similar to the IDS, but with one major difference. It's that the intrusion prevention system is actually going to stop the attack from taking place. It still sends an alert out to the administrator so the administrator can take care of this, but it actually stops the attack in its place and makes sure that nothing is going to occur. Whereas the IDS is going to rely mostly on the firewall to add prevention services. Again, this is a lot more expensive, but if my network has a lot of stuff going on in it, I probably want to spend the money in order to provide more security for my network. Now, there are a few reasons why implementing an IDS or IPS is beneficial. First, they're going to help provide additional security to a network. The more security we have, the more, one of the important words we see a lot in computers, the more redundancy we have, the better. Adding layers of security, an IPS and a firewall, for instance, is like wearing multiple layers of clothing in the cold. The more layers, the more protected you are. Now, firewalls and antivirus systems are great, but they are flawed in that they're not able to handle every type of threat. IDSs and IPSs can detect and take care of threats that might not otherwise be found by the firewall or by the virus scan program. So there's really not a single system or program that can protect against all attacks, but the protection features of multiple different types of systems can actually add up to very thick layers of protection for an attack. Finally, the IDS/IPS keeps a record of all the attacks they detect. This comes in handy because it lets the administrator see where on the network they're being targeted most, and then allows the administrator to make changes, add protection to the places that are attacked most often, and most importantly, create new policies that are going to prevent security breaches in the future. Now, while I'm not going to get into the technical aspects of implementing these systems, as I said, I want to talk about what we need to consider while we're considering putting in an IPS or IDS. First, we need to figure out the ideal placement of the IDS/IPS on the network. This means figuring out where the sensors are that are going to provide the most coverage. An IDS/IPS needs to be set up where choke points are available. A choke point is a strategy that involves narrowing down the physical space that an attacker is able to utilize, and the logical space as well. This way, the defense is much easier. So we're really limiting the area of our vulnerability, much like an Achilles heel. Using choke points is actually something that's been in militaries throughout history. Notable is like the Spartan army of 300 men, which it used against the Persians when they were greatly outnumbered. By forcing all of the attackers into a smaller path, so if we had a mountain, right, and we make sure that everyone's coming up through this path, then we can really attack them a lot easier from atop the mountain rather than having them come all around the mountain. Next, the administrator needs to fine-tune the alerts, the IDS and IPS outputs, so that they are more useful. If the alert merely says an attack is taking place, this doesn't give the administrator anything to go off of. The alerts really need to be detailed and tailored to exactly what the administrator needs to know. This is something that has to be set up and tested by the administrator once the alerts have been configured and once attacks start taking place. Next, the monitoring of the alerts needs to be handled. What use are the alerts if no one's seeing them? The administrator can't always be on the network constantly looking out for the alerts they're sent. So it's their job, however, to set up a way for the alerts to be monitored. This might involve hiring an employee to monitor it constantly, something we used to call beeper duty, where someone was always on 24-hour call, or configuring a way for the administrator to get alerts remotely, say a text message. Finally, procedures need to be put in place for what's going to happen in the event of an attack. The question, what's our plan of action, needs to be asked just in case an attack goes on. So we know what is going to, what programs are we going to deploy, what hardware, do we shut off our connection to the network, etc. If an attack happens, it's really up to the administrator to lead the defense and the strategy around that defense. So just to recap, we first talked about an intrusion detection system. And remember that D is really important, which is a passive system because it simply detects an intrusion as it's occurring and notifies an administrator. We also talked about the two different types of IDSs there are, behavior-based and signature-based. Behavior-based looks at behaviors such as high traffic, people accessing things they shouldn't be, or areas being accessed that aren't normally accessed, whereas signature-based looks at historical data in the form of signature files and tries to match these up with known attacks. Of course, if the attack isn't known, then it's not going to be available in the signature, and so this is where a behavior would come in play. We also talked about IPSs, or intrusion prevention systems, which are proactive because they might search for vulnerabilities in the system, such as looking for open ports, and reactive because they actually stop an attack in its tracks, or at least they attempt to. Now, the importance of IDSs and IPSs is added or extra security. Just like, as we mentioned, having multiple layers if you're going out and it's cold outside. It's also important because we want to know how to alter our security policies over time to make them more secure. And when we talked about implementation from a very broad view, some of the things we talked about is placement. We want them, remember, in areas called choke points, meaning we want to limit the amount of areas that our outside network has access to the inside. We also talked about monitoring and how we get notifications, which in some cases needs to be through text messaging or email or anything else. Finally, we needed to talk about what we do, a plan of action, in case we actually have an attack occurring. Network security, IPSEC and IPSEC policies. Having discussed intrusion detection and prevention systems, which are mostly having to do with keeping attacks and malicious software off our network, I want to talk about something called IPSEC, or IP security, which is a sort of group of protocols and policies that are used to keep the data that we have secure on a network. Whenever we talk about security, there's something called CIA, the CIA triad, that we need to keep in mind. C stands for confidentiality, meaning only the people we want to see something actually see it. The I stands for integrity, meaning what we send is what the other party receives. It hasn't been tampered with. And finally, we have to balance all of this against availability. It doesn't matter if something is super secure if no one can access it. So broadening out into this, that's where IPSEC comes into play. So we're going to talk about IPSEC, defining and discussing what it is, and then talk about two protocols that we focus on with IPSEC, AH and ESP. We're also going to discuss three different services that IPSEC uses or serves. One is data verification, protection from data tampering, again getting into that integrity, and private transactions, going along with that confidentiality. All of this supports availability, and the reason we have IPSEC is to make sure that in our security we have available data. Finally, I want to talk about some of the policies, the ways that we use IPSEC. So as I mentioned, a good amount of the security measures that we use on a network are used to prevent attacks and shield the network from viruses and other malicious software. But not all security measures are used for the preventions of this malicious stuff. Some are intended to keep data and communications secure within a network. While preventing attacks is certainly a part of this, there are some security measures that exist to establish secure and safe communication paths between two parties. This is what IP security or IPSEC protocols do. They're used to provide a secure channel of communication between two systems, or more systems. These systems can be within a local network, within a wide area network, perhaps even over a virtual private network. Now, some people might think that data traveling within a local network is secure, but this is only sometimes true. Imagine that someone has hacked into our network and we're sending data across it. Well, now we want to make sure that the data itself is secure. So while the entire network might be protected by firewalls, antivirus, IDS, IPS, there might be nothing protecting the actual connection between the two users. Generally, the data that gets sent across the network is not really heavily protected, or didn't used to be. So people tend to think that just because their network has a shield around it, everything inside it is safe as well. But this isn't the case. It's important to have IPSEC protocols in place to secure the data sent and the connections made over a network, both local and wide area networks. Now, there are two main protocols that are categorized in IPSEC. They are AH, or Authentication Header, and ESP, the Encapsulating Security Payload. Let's talk a little bit more about what these are. As the name states, AH, or Authentication Header, is used to authenticate connections made over a network. It does this by checking the IP address of the users that are trying to communicate and make sure that they're trusted. It also checks the integrity of the data packets that are being sent. In other words, is this the data that we actually intended, and was it received properly? The other one, Encapsulating Security Payload, or ESP, is used for encryption services, which I think we've talked about. It encrypts data that's being sent over a network using AH to authenticate the users. ESP will only give the keys to the users that have been authenticated. So I make sure to authenticate using AH that this is the user I want to give something to, and then the ESP does the encryption for the people who have been authenticated, providing keys only to the people who meet the first condition. Now, if this seems like a broad overview of these two, it is. We're not going to see this a whole lot on the Network Plus exam, maybe one question, But it's not really worth going into depth because that's what Security Plus is going to do. And when you talk about Security Plus, you're really going to talk about these and IP security in more depth then. Now, there are a few benefits and services that IPSEC protocols provide. The first service is data verification. This service ensures that the data that is being sent across the network is coming from a legitimate source or a legitimate place. They make sure that the end users are the intended users, and they keep an eye on packets as they travel across the network. The next service that IPSEC is going to provide is protection from data tampering. Again, that integrity. The service makes sure that while data is in transit, nothing changes. This could mean the data somehow becomes corrupted or that someone literally tampers with it. Again, while IPSEC protocols provide secure communications within the network, they don't actually stop an attacker from entering the network. So while there is a chance of an attacker on the network, they can't tamper with the data as it travels through because IPSEC is going to make sure that doesn't happen. Finally, IPSEC provides private transactions over the network. This means that data is unreadable by everyone except the end users. This is where that authentication comes in and where confidentiality comes into play. For example, if Mike and Steve have to send some private banking information to each other, the service makes sure that Mike and Steve are the only people who can read it. This isn't happening at any level that you can see. It's happening all within the protocols that already exist. When we talked much earlier about IP version 4 versus IP version 6, one of the great benefits of IP version 6 is it has all the IPSEC stuff built in. So all of this is happening automatically within our new version of IP version 6. It's not even something we need to really worry about, just something we need to know is taking place so we can be a little more sure that our data is actually being secured. So here is what IPSEC might look like if they were connecting two LANs to make a WAN. Though the two networks have their own firewalls and protection systems, they still have to connect through a public network, which we know isn't the safest thing. This is especially true when the public network is the internet. Now, using IPSEC, the two LANs are going to create a tunnel of communication through the network, or through the internet. This tunnel is secure and only accessible by people inside their network. This IPSEC tunnel, by the way, is what we're referring to when we talk about VPN or virtual private networks. So when we set up IPSEC, the service doesn't just configure itself necessarily. There are some things that have to be put into place for the services to run properly. These are called policies. And policies is what configures the services that IPSEC provides. They're used to provide different levels of protection, data, and connections based on what is getting passed through them. In other words, just like with passwords, we have the passwords and we know they're built into Windows, but unless we set some sort of policy that tells the users how their passwords have to function, they might not be used very well. Someone might just use the password, which isn't even a safe password. So we have a password policy that ensures that people have a certain length, history, and certain characters included in their passwords. The same thing sort of goes with IPSEC. Now, there are some important elements that we have to address when setting up IPSEC policies. First, we have filters that are put into place. The filters determine which packets should be secure and which can be left alone. Now, every filter addresses a different type of packet, so there's generally a good amount of different types of filters. All of these filters get compiled into a filter list, where the administrator can easily change and reconfigure the filters to address the needs of their network. Now again, the reason we're going to want to have filters is because the more security, just like the more layers you have on if it's cold outside, the more data it takes up and the longer it takes to decode. So the less security we have, the faster the data is going to travel, but the more security, the less easy it is to tamper with. So we need to weigh this. Stuff like browsing on the internet might not be something we need to secure a lot, whereas we probably want to secure, for instance, email a lot more, or even bank social security numbers, etc., etc. Next, policies have to be provided the proper network information. This involves what security methods, connection types, and tunnel settings are being used. The security methods are basically algorithms that are used in encrypting and authenticating the data. Connection types determine whether the policies are going to handle a local area network, a WAN, or a VPN. In other words, IPSEC needs to know what type of connection I have here, so it knows what level of security to put into place. You can imagine that with a wide area network or a VPN, we need more security than with a LAN. Alright, so although this might have been short in duration, we covered a lot of important things. First, we talked about the fact that IPSEC exists. Remember, IPSEC stands for IP security, and it's really not its own protocol. What it is a series or a group of protocols, services, etc. that ensure security over the IP protocol or the Internet Protocol. We also talked about two of the ways we do this. One is the AH protocol and one is the ESP protocol. Remember, AH stands for Authentication Header. As the name implies, it's a header in the IP packet that authenticates to make sure the users who are about to communicate are the ones for whom it's intended and who are sending. ESP, on the other hand, which stands for Encapsulating Security Payload, is literally going to encapsulate the data in an encrypted form. And it'll only release this encrypted information to someone who has been authenticated to receive it. And remember, to do this, we use keys, both public and private. We also discussed the three different IPsec services that are provided, including data verification, which ensures that the data packets being sent are coming from legitimate places. Protection from tampering, which ensures the integrity of our data, that it has not been tampered with, either tampered with from, say, an attacker, or the data might have just become corrupted. Finally, we ensured that we're having private transactions, meaning that the data is confidential between only the people who need to be having it. And lastly, we discussed IPsec policies, some of the things that we need to have when we're creating our policies for IP security. For instance, we need to know the type of network we're on, and also filters, so that the appropriate level of security can be applied to the appropriate type of data.
Welcome to Module 14, Lesson 1, Denial of Service. So we're going to look at what is denial of service. By the way, this is a small subset of what you would get in the CompTIA Security Plus exam and the Network Plus, the CCNA Security exam. There's other vendors do security as well, obviously, like Juniper, but CompTIA is a good foundation, and then in vendor specific, Cisco CCNA Security is excellent. I think you need to do the CCNA first, or at least one of the CCNA exams. The ICND1 would do check. So what is it? Bandwidth attacks, connectivity attacks, common types of denial of service attacks. What is distributed denial of service? Types of those, difference between denial of service and distributed. Reflective, DOS attack, and then types of reflective, unintentional, physical infrastructure attacks, and how to prevent how to identify a denial of service attack. Just bear in mind this is an overview, so you need some fairly specific training on hardening your network and also identifying and troubleshooting and resolving the denial of service attack. So what is it? Basically refers to an attack on a computer network to make its services unavailable to legitimate users. You've heard of it, I'm sure, in the press. Before some big companies have been attacked before. Denial of service basically attacks the network with useless traffic. It's a type of cyber threat. So what do the denial attackers actually put their effort into doing? Preventing legitimate users such as members of the public or employees from accessing network services, emails, websites, online banking, etc. Usually the denial of service attacks occur when the attacker floods a particular network with a huge amount of traffic. So for example, to access a website, we type in the URL, you send a request to the web server. Web server can only process a limited number of requests at a given time. Now there's a whole bunch of things that can go on, for example load balancing and CDN, cloning the website, copies all over the web, but even so there's only a finite amount of resources dedicated to all these solutions, and they can be used up. When the attacker burdens the server with too many requests, the web server is unable to process the legitimate ones. As a result, you can't access it, and that's called a denial of service. Again, you can Google denial of service attacks and look at all the news stories over the past few years. Attacker can send spam email messages to establish a similar attack. Only a limited number of emails are allowed in your corporate accounts usually. Mind you, even large free providers like Gmail have got a limited amount of storage. So as a result, the attacker can stop the users getting legitimate access to their account. In an email bomb, the denial of service attack, the attackers send a load of spam emails and they disable the actual email server rather than just an account on the server. Generally not concerned with stealing information, it's just quite an aggressive way of bringing down a particular service. It could be a person, a business, or an entire company. They can attack and destroy files in an affected computer system or network. In some situations, the denial of service attack actually affects the website accessed by the users. Most denial of service attacks are aimed at the computer's network bandwidth, connectivity, resources also, server resources. Bandwidth attacks harm the computer or network with a huge amount of traffic, huge burst of traffic. Legitimate users can't access network resources. The connectivity attacks harm the computer with a large amount of connection requests. Available operating system resources are quickly consumed and the computer is unable once again to perform legitimate requests. Another common type of denial of service attack is a buffer overflow. All devices, routers, switches have buffers that manage a temporary excess amount of traffic, send and receive buffers, and if these buffers are actually overflowed, then depending on how the devices are configured and what it is, then it's going to cause problems and packet loss. There's SYN attacks, teardrop attack, Smurf attacks, viruses, a whole bunch actually. The buffer overflow is the most used, distributes a huge load to a network, more than the buffer is able to handle. When the attacker has awareness about the weaknesses of the target system or network, that's when you'll get a buffer overflow attack, and they can target certain vendors or certain devices such as Cisco routers or other vendors, firewalls, etc. So when the attacker simply tries to attack not knowing whether it's going to work, so it's quite a brute force attack. Buffer attacks are based on the system or program's buffer characteristics. Another way, distribute emails including 256 character file names, which all take amount of time to process. send huge ICMP packets, send lengthy email messages including a from statement that has more characters than 256, seems to be the limit for emails. Now, this is a SYN and SYNAC, which you should be familiar with from the network of A+ and any other network research you've done. This is what happens before a connection can actually take place if you're using TCP. So with a SYN attack, the attacker sends a TCP connection request faster than the target computer's processing speed. Using client-server technology, it begins to establish a three-way handshake. So you'd have a SYN, SYNAC, SYN, and there should be an acknowledgement happens before the data sent. That doesn't actually happen. So client sends a connection establishment using the SYN synchronized message. A server can then send a SYN synchronization acknowledgement. Client responds with an ACK message, and the connection is then established. If the attacker sends repetitive SYN packets to every port using a fake IP address, the server establishes communications and responds to all requests. And what it also does is it leaves a window open for the actual communication to take place. So for each request, SYN request, for a certain period of time, depending on the traffic, it will reserve resources. It replies to each attempt with a SYNAC packet from every open port. Okay, teardrop attack sends fragmented packets to a target computer. When the computer receives the packets, it's unable to reassemble them because of the following: a bug in the TCP/IP fragment reassembly, overlapping packets, crashing of network devices. Can usually happen on older operating systems. Some of you might not remember these: Windows 3.1, Windows 95, Windows NT, and some versions of Linux. Smurf attacks is where the attacker floods the victim's computer with ping packets. The attacker initiates the attack by sending a ping request and then spoofs the destination address. Ping replies are sent to the victim's computer address. Since the ping request is addressed to the broadcast address, all computers in the network have to respond, and each packet is opened and checked and to see if it's the destination. As a result, the victim can't receive any genuine traffic because it's already flooded with ping packets. A technique of assigning a network packet with a false IP address is called spoofing. Computer viruses. These are distributed and spread throughout the network in a number of ways. The attacker uses and controls the victim's computer to attack somebody else's low and weak network security, and some devices you're waiting to have patches applied to, or they haven't rebooted after downloading some updates or whatever, and this is when they become vulnerable. The attacker floods a target computer with a huge amount of data to a particular site or spam emails using a victim's computer. So the name distributed indicates the attacker uses multiple host computers. This is to throw others off the trail and make it harder to actually identify the attack, because the victims are actual legitimate systems on the hosts. The attacker can increase the effectiveness using client-server technology. In distributed denial of service, master program or software is installed on one computer. Normally they use stolen login credentials. Now, it may not happen immediately, but at some particular time the master program communicates with other agent programs that are installed on computers anywhere on the internet. When the agents receive their command, they start to attack. The master program is able to spread thousands of agent programs within seconds using client-server technology. So some characteristics of distributed denial of service attacks: a botnet, traffic spite, coordinated attack. Not sure if you can see that, but there's an attacker machine at the top there and handlers and compromised systems. Going down to the targeted services or servers on the bottom there. So botnet refers to a group of computers that can cooperate, also known as zombies in this context. The botnet owners are also known as herders. They manage computers in their botnets. Botnets are used to send spam emails or to participate in distributed denial of service attack. So this is why it can be so difficult, because all these legitimate devices at some point in time when there's a trigger, such like a timer, or it's time when everyone's off work, or on a Saturday night on a bank holiday, they'll start their attack. Traffic spy overloads the victim's network or server in order to cripple its services and resources. As a result, the legitimate user will not be able to access the service. They're used when people are coordinated to carry out the attack on a site or sites at the same time. When many people attack the server, the web server slows down or gets overloaded. It's difficult to differentiate such attacks from the normal traffic. When many people do this at a similar time, the web server slows down or gets overloaded. It's difficult to identify this type of attack from normal traffic that can happen, and obviously you do get spikes on networks, and if there's updates been applied to the servers, again it can appear to be slow, legitimately slow. Difference between denial of service and distributed. Using a single internet connection, an attacker can harm a network in a DOS attack. Launching multiple connected devices that are distributed is a distributed denial of service attack. The distributed denial of service also differs in the attacks are performed using botnets, including mobile phones, routers, PCs, etc. Denial of service attacks can harm a single machine, or they can attack an entire network. Moving on to the reflective amplified denial of service. The reflective uses third-party machines to attack a targeted computer. So basically it's one way for the attacker to mask their identity. Reflective denial of service attacks use third-party servers, for example DNS servers, to attack a targeted computer. The attacker sends a request to the reflector server or servers with the IP address of the target, and what it does is overpowers the target using response packets. An example is a DNS response. Type of reflective denial of service attacks: DNS amplification, network time protocol, smurfing. Mentioned DNS amplification. The attacker exploits the DNS server to make change small requests into considerably larger payloads. This can be used to overthrow the victim's servers. Network time. The attacker exploits widely accessible network time servers, destroys the targeted computer with UDP traffic, which is what NTP uses. They're not all intentional, they can be unintentional. This is when a server crashes, for example, can't provide services because of traffic from legitimate users. Again, have a look, there's a whole bunch of quite well reported and embarrassing examples for government and private companies, large companies. So when a popular website hosts a news on a less equipped secondary site, the server on that side won't be able to handle the traffic, especially if there's a big breaking news story going on. A person physically attacks the infrastructure of an organization when it's a physical attack. Example is they snip or destroy a fiber optic cable. Again, I suppose these could be malicious or accidental. I know quite a few cases of work people cutting through cables by accident. If the attacker is able to access the computer system, then they can obtain information on the computers, obviously. There's no set way to rescue computers or a network from these type of attacks. You can put into place certain steps to reduce the likelihood. Install and maintain an antivirus on your end devices. You can also have antivirus on your mobile phones. Firewalls and computers, and configure them to control the incoming and outgoing traffic. Protect emails from spam. There was just the latest hacking on the Democratic National Party, actually, where a guy received a link telling him to reset his password, and that went off to some Russian site allegedly somewhere, who then got into his system and read all of his emails and all the other emails for all the other people on the site. It will manage unwanted traffic and send alerts for spam email messages. You can install a intrusion detection system, an IDS, that will protect systems from the distributed denial of service attacks. The IDS uses connection verification methods. Speak to whatever your network equipment vendor is for more information. You can disable and use networks or segments or devices or ports on switches. Regular system performance. Now you can have legitimate issues that represent denial of service, like a faulty network card, a spanning tree issue, a routing protocol convergence when you've either booted devices or a network has gone down or up. Large file download by a user on the network who doesn't have a limit. A bulk email send for marketing, for example. Unusually slow network. I know some networks I've worked at, for example, a Friday afternoon there was a big backup and the whole network went slow. But if that happened on another time of the week, then it could be a warning sign. Unreachability of a particular website. High numbers of spam messages received on an email account. Denial of service. We've just summarising what we've covered is denial of service, bandwidth attacks, connectivity attacks, common types of denial of service and what is distributed denial of service, types of distributed attacks, the differences between the two, reflective denial of service, types of reflective, unintentional, attacks on our physical infrastructure and then preventing denial of service and identifying one when it happens. So that's all for now. Thanks for watching. Welcome to Module 14, Lesson 1A, Common Networking Attacks. We've heard earlier about a few attacks, but we need to just update the list because of the new stuff in the syllabus. You'll look at social engineering, insider threats, a logic bomb, rogue access point, wireless, evil twin, war driving, I'd love to know who comes up with all of these names, phishing, ransomware, DNS poisoning, ARP poisoning, spoofing, deauthentication, brute force, VLAN hopping, man in the middle, and then some exploits and vulnerabilities. Social engineering. The funny thing about this threat is it isn't electronically detectable, so we don't have a little alarm go off somewhere. It's normally when an attacker convinces an employee to disclose confidential information. So what happens is perhaps they could say they make a phone call and it goes through to your headquarters office, and then they ask to be put through to your office. So what you'll probably see on your phone is the extension 1, 2, 3, 4, as if it's coming from here, so you think it's an internal call, but really it's coming from outside here in the hacker's house, wherever they may be. So it looks like a legitimate call. They pretend to be a senior manager or someone inside the tech support department, and they'll access some information. They'll ask you for passcodes or say there's a problem with your account, and this is a pretty successful way of getting information. The other thing is, or it counts as social engineering, is somebody who walks behind the employee who's already entered the security code for a door, also known as tailgating. Also, another way is leaving the USB ground on the USB on the ground somewhere. This is quite common. Sometimes these USB sticks have actually got a battery in, and it's designed whatever device you plug it into sends an electrical current through it, and it fries your circuit board and fries your hard drive. Or it can actually plant some lines of code. Insider threats, normally an employee or a contractor. They could be under duress, working for a competitor, or a blackmailer looking to get information. Most security focuses on external threats, so it's looking at incoming attacks, malware, trojans, all that kind of stuff. But inside your organization, obviously, you could have people that are posing the threat. So people who work for your organization should know your systems, policies, procedures, and weaknesses, and they should know how to spot somebody who's acting suspiciously or acting for suspicious information. As you've probably seen in the movies, you could have what's known as a sleeper. So we normally associate this with spies, sleeper agents, but a sleeper is somebody who could be waiting to be activated. Obviously, they could easily go undetected, and they could be doing things to your network or passing information for some time. A logic bomb is a type of malware. It does damage after a certain condition is met. So an example is the spyware or the malware, sorry, is on your device, and then when the clock ticks over to the 1st of the 1st, say 2019 or whatever, it then executes the code and then does the damage. It can be left behind after attack, and what it could do is destroy any evidence that it's taken place. So it could destroy whatever files it's actually put on your system, making it harder for you to do a forensic analysis. You may remember the Chernobyl virus. This was an example of a logic bomb. Those wrote to the boot sector of disks, wiped the BIOS on the hard drives, and left the devices unusable. So pretty bad. Rogue access points, so we're talking about the WAPs, wireless access points, major concern especially in large environments. So somebody's brought in a third-party access point by a network user. Often this can happen when somebody's complaining about their signal. So you've got bars on your device. Say you've got 1 or 2 bars, then I've seen instances where people have brought in their own access points, somehow manage to connect to the network, and they get obviously a higher connection or faster connection. So gives network access to anybody in range of the rogue access point. So this is the danger of people who on purpose or just accidentally, they don't know how the technology works. A lot of other devices will be associating with this access point here when it should have actually gone off to the corporate one. You mitigate this with regular site surveys. Basically, you're walking around with your wireless device, checking for legitimate devices. You can force users to authenticate using NATO 2.1x. Also, it can happen if you enable Wi-Fi sharing on your phone. So if you're stuck somewhere, you've got your smartphone, there's a little app in there where you can let other devices, say for example your laptop, if that doesn't have a capability, it can actually piggyback onto your phone with a wireless signal and then connect to the network. So you've got to be careful of that. Wireless evil twins. This is configure an external access point to behave as the trusted access point. It uses the same SSID and security settings. So it'll all look the same, and the user connects. You can see the legitimate one is here, but the signal's pretty weak. The signal here is much stronger, so you'll more likely connect to the rogue access point. This device normally will have quite a strong signal on purpose, so it's chosen over the legitimate one. Again, this can be brought in by network users innocently, or it can be done maliciously. Mitigate with HTTPS or VPN tunnels. War driving is just simply, this happened when wireless first came out and nobody had security, or it was just a very weak security. People drove around trying to find some wireless access somewhere, and if they could see your device and connect to it, even when it wasn't too many years ago, my internet went down, and I could see on my wireless, if you do a wireless search, you'll see a few padlocks, and then it'd have one with a open padlock, and you could connect to that. So you see it less now because most of them are configured quite easily for security. Phishing, email sent which looks legitimate, usually appears to be from an official website, and it asks you to click on the URL, say click here. The sort of things I'll see are, it'll say Amazon or tax message, and even smart people have been caught out. Say for example, if you're like me, maybe every 3 days you've got an Amazon delivery coming, or something from eBay. So if you're busy, you'll see it and think, oh no, I've missed my Amazon delivery, too late. You've clicked on it and the damage has been done. Phishing can be phone-based also. You counter this with email security systems, spam, viruses, phishing, etc. Ransomware's really been in the news lately because even the law enforcement agencies have been caught. It's taken out large areas of the National Health Service in the UK. It limits all of some system access, and it locks your screen, as it does here, until you have paid money to the extorters. Offers threatens to publish your data, and if in the case of I can't remember what, it was some sort of police department anyway, but it accessed all of their systems. Somebody downloaded, or somebody got an email, opened it up, and they downloaded the software, and it spread through all the devices. Often uses cryptocurrencies for payment, so it's hard to trace the money. Often uses Trojans. WannaCry, one of the latest ransomware malware software packages that came out, automatically transferred it, didn't use a Trojan. DNS poisoning, we've already learned about DNS. This is a fake DNS cache entry. It corrupts the data inserted into your system, and the name server returns a false result. So you'll do a DNS lookup, it goes to your DNS server, but for whatever reason this attacker somehow injected this fake entry, and instead of going off to the real server here, it queries the fake one, and it, for all intents and purposes, to you looks like you're actually on the correct site. Obviously then it'll try and get passwords, usernames or credit card information. And again, this false entry here, if you've got a DNS server, it can actually propagate within your, depending on the authority of this server, it'll propagate to other servers. ARP poisoning requires the attacker to have access to the victim's local area network. Again, this could be a contractor or somebody who's managed to get in somehow. It provides a host with the wrong MAC address for hosts, the host IP address. So if we go down to this, host is looking for the, it can't encapsulate the packet, as we already know, until it knows the MAC address. So there's a field here for layer 3, and then but for layer 2, in order to send the packet out, it needs to know the MAC. And if it's got the false entry here from the attacker, then it will send it to the wrong host. It'll send it to here instead of here, or vice versa. You combat this with dynamic ARP inspection, which is, you will enable this on switches, and DHCP snooping. There's a lot of different types of spoofing when it comes to hacking. This is pretending to be someone or something you aren't. One type of spoofing is DHCP spoofing. The idea is the software exhausts the pool of addresses. So you'll have a pool of, say, 10,000 addresses, and it will spoof, keep requesting the addresses until eventually there's 0 left, at which point the DHCP server can't allocate information, and then hosts on your network can't join the network. The MAC impersonates hosts or devices on 2 hosts on 1 switch port. So this is actually poisoning. It looks like the port on the switch here, it should have 1 MAC address per port, but it's got 2 associated with the port, which it can happen if you've got a hub plugged in, but you wouldn't normally have this on your network. With the ARP source, the MAC address is disguised and the ARP cache is poisoned. De-authentication. This is used on Wi-Fi networks. This is more of a pain than anything. It sends a de-authentication frame to the host to end the session. The attacker spoofs the victim's MAC address, which you can obtain by sniffing, wireless sniffing. Now, there's no need for encryption. So even though you've got an encrypted connection, so all your device, all your traffic is encrypted, the de-authentication frame doesn't have to be. So whatever that frame will say, whatever it says in the frame to tell it to terminate the session, that doesn't have to be. So it's a flaw in the technology. Brute force. This is a type of password attack. The other type is a dictionary attack. So what a brute force attack does, it just keeps guessing over and over to try and find the password. Typically the username will have been stolen, and you'll have a hashed version of the password. This is what it's trying to guess. The same hashing algorithm is used. For example, MD5 is used, and it will use this to try and send hash values. You'll combat it using advanced algorithms, so you'd have like millions or billions of combinations, for example RSA or public key encryption. VLAN hopping. Hosts typically require a layer 3 device to reach another VLAN. I don't know if I've got a picture of this actually, but we've seen before, if you've got hosts in this VLAN and they will connect to a switch, and then hosts in this VLAN, so VLAN 10, VLAN 20, and they'll have different IP addresses, but these devices can't connect to one another unless the switch is connected to a layer 3 device. Now this can actually be built into the switch. It could be a multi-layer switch, but it has to have this layer 3 capability. While VLAN hopping, the attacker attempts to bypass the layer 3 device to compromise another device, and you could have all your security or some of your security built into this layer 3 device here. It's done by switch spoofing or double tagging. So switch spoofing, the device impersonates a switch, whatever this rogue device is. It's pretending to be a switch, so probably would need a trunk link here. You combat it by disabling trunking where not required. So say this is your frame here, and you would have your VLAN 10 here and say 20 here. Well, normally when the frame reaches the destination, the VLAN tag is removed because the hosts don't really care that they're in a VLAN. But what they can do with VLAN hopping is they can add an extra one here in order to gain access to a VLAN when this device might be over here on VLAN 20. So that's double tagging. Combat by using a dedicated VLAN for all trunk links. So your trunk link between this switch here, this switch here, this switch here, you've got a special VLAN only used between these trunk links. So say VLAN 101, 102, 103. These numbers aren't used anywhere else on the network. They're just used for the trunk links. This is just a diagram showing you the double tag frame here. So the switch 1 removes the first tag and forwards to switch 2, and this time the tag is still attached to it. Man in the middle attack convinces the sender and receiver that the computer in the middle is the actual host. So this host here thinks it's speaking to the server thinks it's speaking to this host over here. Really it's going between this intermediary device here, which is the attacker. You normally accompany this with DNS or ARP spoofing, so there'd be an ARP cache here and here, and it would say the MAC address for this particular host, but really it's injected a false MAC address here. And the messages are actually sent and received. So there's acknowledgement, it sends, and then this device here will send out an acknowledgement, but really it's going through the middle here. Type of spoofing attack. Vulnerability scanning. This should have appeared in a moment, sorry. It probes the host in order to find an exploitable service or process. So you've got your server here, and obviously there's ports permitted or denied, but it will keep probing until it finally finds one that's open, and then it will try and do some damage. There's a whole bunch of tools. If you do an ethical hacking course, for example, you can download. There's a ton of free tools. The idea is you're trying to learn how to protect your system, but they're obviously available for use by hackers. Now, say there's a particular port open or a service, so like an instant messenger port has been left open. This will then tell the hacker, what type of attack will work best on this particular port. So it may not use that specific port, but it may then be able to target a vulnerability in the application. One of the tools you could use is Nmap. You obviously counteract all of this by doing some penetration testing or paying for it. And here's a result from the Nmap tool here. And then it's giving you your outputs. You'll learn more if you do penetration testing, which isn't really covered in the syllabus. Alright, so we've covered a lot of stuff: social engineering, insider threats, logic bombs, the rogue access point that somebody brings in, evil twin, driving around looking for free wireless, phishing, ransomware, poisoning the DNS entries, the ARP cache, spoofing is pretending to be something or someone you're not, de-authentication, the frame's got, it can be in clear text, brute force attacks, VLAN hopping, man in the middle, and then exploits versus vulnerabilities. That's all for now. Thanks for listening.
Network security, threat mitigation, and user education. We've now talked about a lot of the different types of attacks and security threats that you encounter in today's world when it comes to your network. And we've talked about ways to protect from these threats, from attacks to antivirus software and so on. But let's talk a little further about how we can mitigate these threats. And if that word is new to you, the first thing we're going to talk about is what threat mitigation means. We're then going to identify some of the steps in a good protection strategy. These include developing strong security policies, monitoring the threats on your network, something that we've talked about in the past, a hugely important one, educating users, since almost all the threats we've talked about in some way, shape, or form have to do with what we call social engineering. In other words, getting someone to do what you want them to do. For instance, give them your password. Automating scanning and updates, both from updates of the operating system and from the virus scan program. And patches and updates for our operating systems and our software. So, what is mitigation? One of the only ways that a network can stand a chance against attacks is to do something before the attack is made. Isn't it said that an ounce of prevention is worth a pound of cure? Well, this means more than just having antivirus and firewalls in place. Those things are great, but they can only stop an attack that's already being made. Really, the best way to protect a network is to set up prevention measures before an attack can happen. The idiom of an ounce of prevention is worth a pound of cure means that you save a huge amount of trouble by preventing the trouble from even happening. So one of the best ways to do that is to mitigate the threats that are made on your network. Mitigation is a word that doesn't just apply to networking, but in this case, we're talking about it in the sense of lessening of a chance of an attack. By using mitigation, you're taking measures to reduce the frequency of attacks, the size of those attacks when and if they take place, how severely, most importantly, they're going to impact your network. we need to have a strategy in place in order to mitigate threats and make life on the network easier. So, step 1 of the mitigation strategy needs to be to set up rules and policies within a network. These are set up by the administrator and need to be agreed upon by all the high-up people on the network and all the high-up people in your corporation. They then need to be told to all of the users. These rules should be standard throughout the network with very few exceptions, because these exceptions easily lead to a breach in security. One of the rules that needs to be set up, for instance, is what can users download, such as applications. Can they download stuff like browsers? Well, some of them are trustable, but are we going to trust people on our network to choose the browsers that are actually worth trusting? The administrator needs to be wary of just about any program that a user could download. And as we learned in the last module, viruses can hide within programs. They don't just attack out of nowhere. A user on your network could easily download a virus without even knowing it, and then they end up infecting not just their computer, but the entire network. So a rule needs to be put in place that says whether or not downloading of applications is allowed, and if it is, from what sources. You may even want to limit the fact that people can download by shutting off their user rights to download or to install programs on their network. If they can't install anything, they can't install a virus. Another major rule, and this is really important, is are they allowed to use outside storage devices such as removable hard drives, thumb drives, flash drives, and storage CDs. Any one of these media storage devices can contain malware. One of the classic examples is someone leaves flash drives in the parking lot. When you find the flash drive, what's the first thing you do? Oh, you say it's a brand new flash drive. I'm going to put it in my computer. I want to test it out, see what's on there, see if I can find the owner. Well, the minute they do that, they've just infected your system and your network with a virus. So we need to make sure that even though the person might not be trying or mean to infect the network, they could do it simply because they don't understand the risks that are associated with flash drives and outside storage media. They might also be bringing stuff from their home computer, which very well could have a virus on it. So storage devices could contain malware without the user even knowing it, and this isn't something you want to risk, so a policy is really important. Other things such as this would include stuff like tailgating. When someone logs in, swipes their card to get into a building in the morning, if they open the door for someone else, well, now that person just got in without being audited. They didn't have to swipe their card. So that's a pretty major concern when it comes to security. Another one is something like shoulder surfing or giving out your password. We need to make sure the policies of how passwords are reset, when they're reset, and who you can give them to is fairly important. If I give my password to my wife and suddenly my wife becomes my ex-wife, she could do some major damage to me and to my company by using that password to get access to private information. So step 2 is a mitigation strategy, which is to constantly monitor virus threats. As you might already know, attackers and computer hackers are very well educated when it comes to getting around security systems. This is how they infect networks. And when their attacks are blocked, most of them just update the attack and try a new version. They don't just stop. So this is why the administrator needs to be as on top of the virus versions and attackers and the threats that are out there. It's up to the administrator to make sure that they are up to date and research is being done and they're knowledgeable at the newest attacks that could be coming to their network. Again, it's no one else that's going to get blamed except for the administrator when someone hacks to the network. So not only do we need to monitor our network, we need to monitor the threats that are out there. And this really involves doing research on what the latest and greatest techniques are to hack into a network. Step 3 is user education, which is really, I think, the most important step that we have out there. It's critical to have network users educated in this field so that they know exactly what sort of threats are out there and what safety habits are there as well. There's some safety habits that are obvious, like locking a device and keeping your password secure, but there are other security measures and knowledge that's less obvious but just as important. Network users need to be knowledgeable in how to protect themselves from viruses and how to recognize them so they don't just click on something when it pops up on their browser. First, they personally need to back up their important data because in the event of an attack, perhaps our major system goes down. Alternatively, they need to know that they should be backing up their data to perhaps a central location, or they need to be taught where to back up their data. For instance, to the network share and not to a removable hard drive or not on their desktop. Because if they back it up to their desktop, then what happens when their computer gets broken? Now they've lost all the work they didn't back up automatically to the server. They also need to be diligent about web browsing, what they download, what they click, and so on. If their administrator is going to allow them to download programs, they need to be careful about where they download them from. Again, we always have this interval between responsibility and power. The more powerful you are, the more responsible you have to be. If I can install things on my computer, that also means a hacker could use my information to install something on the computer as well. And finally, if they download a program that seems illegitimate or they think they've been attacked, they need to be able to spot the issue and report it to the administrator before the risky program has a chance to damage. Sometimes they don't want to say anything because they don't want to get in trouble. But if they had said something earlier, we could have prevented more damage. It's really important for them to know when they are being deceived by something and when something is legitimate. So I see this all the time. People send out these emails saying, beware of this. And an easy Google search would show that the thing that they're actually being aware of isn't real. It's something fake. And they've spent time and energy, everyone's time and energy, getting worried about something that actually is not going to affect them. On the other hand, they don't seem to recognize when someone's account has been hacked and is asking for money, when that person would never do that. It's not characteristic. Most of all, they have to check and double check stuff and be willing to ask questions. So here's an example of an extremely common virus that's intended to scam people out of money on the computer that's being infected. The virus takes over your computer and only lets you see this screen or one very similar to it. It claims that the IP address has been used to do very illegal things, and the FBI has seized the computer, and in order to unlock the computer, you have to pay a fine or purchase a code. Now, this virus is extremely intrusive and obviously quite, successfully convincing. Look at all the 7-Eleven, CVS, Rite Aid, all the logos at the bottom, Department of Justice, etc. And the reason they're going to make you pay through MoneyPack, it looks so real, is because that way they know they're getting the money on the other end. So it's important for someone to recognize that this is actually fake. Look on here, it even scares people by saying you have 72 hours to pay the fine or you're going to be arrested. Now, someone might have been doing something like downloading a torrent off the internet, and so they think, oh my god, I'm going to be in trouble, and they don't want to tell you because they think they're going to get in trouble with you as well. We need to make sure that they have a judge-free zone in which they can come tell someone, and that way you could remove the virus and they could go on their way and continue to work. Now, as viruses and malware attacks become more and more advanced, antivirus software improves to combat them. There are thousands of antivirus software, and some are more advanced than you could possibly even imagine. It's not out of the ordinary, however, for antivirus software to have automatic features. So step 4 in the mitigation strategy needs to be to make sure that antivirus systems and software are configured to do things automatically. This means they have to automatically scan the computer, scan the network, and update themselves. We don't want to rely on a human to do this. Very often, when it comes to virus scan, nothing's going to be rolled out automatically that's going to damage our computer. So this stuff needs to happen automatically. When are we going to scan the network? Well, we want it to scan when no one's doing anything. So we want to do it, for instance, at 2 a.m., not at 2 p.m. when people are busy opening things and closing things, and that's when the virus scan program won't be able to get access to 50% of the network, and therefore something could be hiding out. All this eliminates the human element. It allows for more regular and controlled updates in the process, which is important because when we allow humans in, that's when errors occur. Finally, when an update to a program is released, it's generally to address bugs that were found within a previous version. Along with these bugs, there might have been some security weaknesses in the software that need to be addressed. But program updates don't come out very often. In between updates, patches, and so on, there might be a temporary fix that's released or a fix that is manual that have been found. So a patch does exactly what you think it does. It basically covers a hole in the software and temporarily repairs it until an update or a new revision of the software can come out. So as soon as patches or updates are released, the network admin needs to look at them and think about installing them on the network. Now notice that I don't necessarily want you to just install it right away. I want you to test it and think about it, because the patch or update could very well cause another problem on the computer. And one thing we don't want to do is bring down our system because we put in a new update that suddenly stops our printers from working or something. So we need to balance this with the idea that once the patch and the update is released, the hacker now knows that this is something that they can exploit, and so the longer you wait to update it, the longer you're at risk of being exploited. Alright, so we talked about a bunch of things in this module. Some of this is common sense, but these are things that pop up on the Network Plus exam. First, we want to define network mitigation. Mitigation, the word, literally means to lessen. And so what we're doing is we're lessening the threats that can hit us. Some of the steps that we identified in this strategy were first to develop strong policies. For instance, a password policy is important, download policies, internet use policies, and so on and so forth. We also need to monitor threats, not just internal, but we need to research what's going on around the world so we know what the latest things are that are attacking our systems. The most important one, I think, is educating users. Social engineering is how hackers and attackers get around the human element. When there's a human element, there's a flaw. And so we need to educate users so they don't click things that look bad, and they know when to ask questions, since this can help them as well. We also want to automate scanning and updates from virus scan programs and perhaps our firewall. This should all happen automatically, because if we remove the human element, then there's not going to be an issue. We also want scans to happen in the middle of the night when no one else is using it, for instance 2 a.m. or 1 a.m. Make sure that you give enough time for the scanner to actually scan the entire system. Finally, we need patches and updates, and we want to balance the patches and the updates with the patch actually doing harm versus the weakness or exploit that it's correcting. The longer we wait to employ a new patch or update, the longer we're at risk.
Welcome to Module 14, Lesson 2A, Advanced Threat Mitigation. So this is new stuff for the 007 version of the CompTIA exam. Managing your signatures, hardening your devices, in terms of security that is, changing your native VLAN, switch port protection, restricting access with access lists, honeypot and honeynet, penetration testing. So signatures, in terms of signature management, we're talking about IDS and IPS, which we've covered earlier. The signature-based detection examines network traffic for pre-configured and predetermined attacks. So the signature is the thing that is matched against in these devices, the threat signature. These are known as signatures. Attacker convinces the employee to disclose confidential information. If a known signature is identified by the system, an alarm is triggered or the traffic will be blocked. This depends on how you've configured your IDS and IPS. So it will either send an SNMP alert or create some sort of log message or whatever you've designed it to do. The signature codes are updated, or they should be updated regularly for new or false patterns. You really don't want false positives either, because it's just going to mean traffic's blocked when it shouldn't be. There's a website called threatconnect.com. They offer some sort of signature management system for you to look after all your signatures. I only suggest it because I use their graphic and I wanted to credit them for that. But this is what came up when I was researching threat signatures. Device hardening. This is part of your daily, weekly, monthly admin task, especially if you're in charge of security for looking after your network. You'll patch or update software or firmware in your hardware devices. Check for non-compliant passwords. This will obviously be part of your password policy, but I'm sure you've logged into something or had an email updating you saying that your current password isn't strong enough and you need to update it. Removing redundant networks and IP addresses. Strangely enough, I've known equipment found years after people thought it had been decommissioned. It's sitting in an office somewhere, plugged into the network, and nobody knew it was there. And this can be a backdoor for hackers to find and get into your network. Changing security keys. Changing the native VLAN. So the native VLAN is used for any untagged traffic on your network. You'll be familiar with this when you start doing Cisco configuration or any type of Juniper or other network management. Big security vulnerability. Your native VLAN passes important information such as your Cisco Discovery Protocol or the equivalent, which is device information, your operating system that it's running, etc., etc. Dynamic trunking protocol is for trunking. So your native VLAN will normally go across a trunk link, and you've got all of this important information. On the Cisco devices, certainly, and probably a lot of other vendors, the native VLAN is VLAN 1. And if you leave this as the VLAN that the switches can communicate with, you've left a possible security vulnerability, because this traffic is actually untagged. So what you want to do is, on any trunk link, you change it to an unused VLAN. So this is one that isn't being used on, so you've got to VLAN 10, 20, 30 and 40. You would use your an unused VLAN on your trunk links, for example, 222, just something fairly high, and then on another trunk link to another switch, you'd have another VLAN, for example, 223, etc. Here is the output for a Cisco device, and you can see this is trunking, so it's passing multiple VLANs on this link, but the native VLAN is VLAN 1. So I've wiped over it there. The native VLAN is VLAN 1, which you don't want. So what I did, I went to the trunk interface here. I issued the command switchport trunk native VLAN 5. You'll probably use something higher, like I said, like 222, but it's just to illustrate the point. So this traffic that passes over the native VLAN will use VLAN 5. It won't use VLAN 1. And you've got to be careful, because you can't delete VLAN 1. It's there all the time. You just don't have to use it to pass any traffic. And now you can see it's changed from VLAN 1 as a default to VLAN 5. I've already mentioned all this, sorry. So another thing mentioned is BPDU guard. This has arrived in the syllabus. BPDU guard, it's on an interface. The port is error disabled when a BPDU is received. So bridge protocol data unit we talked about earlier. This is used for spanning tree traffic. and it can actually change your layer 2 topologies. For example, let's say this switch is the root. You've got a high powered switch here, and it would normally be a multi-layer switch here, and all of your traffic is pointing to this device. But what will happen is this device will announce a number to say I am the boss, and say for example this is number 99. This is the number that determines the route of all your spanning tree traffic. Well, what happens is if this device connects to the network, say you've found it on a shelf at work, and for some crazy reason all you've done is plug it in, and this has happened, by the way, I've seen it happen. Well, this device could actually be configured with the number 100 in terms of spanning tree, and what could happen is then, or this could be a really low switch that's worth about, say, $100, and it's just got a tiny amount of processing power. All of your spanning tree traffic all of a sudden will be converging onto this tiny little switch. The CPU will go from almost nothing through the roof. It'll probably crash, bringing down your entire local area network, and at that point you'll probably be out of a job, to be honest. So what happens is with BPDU Guard, you configure it on this interface here, for example fast Ethernet 10, and if a BPDU frame is seen coming in onto this particular interface, it will error disable it, and it won't pass traffic until you, the network administrator, shuts it manually, and then manually no shuts the interface, so you have to re-enable it. Root guard. So I mentioned if this is a topology where it's actually, I think from my CCNA book, where I'm telling you on what interfaces, depending on the topology, you would add BPDU guard. Root guard you would add down here on these level of interfaces. So these are your layer 3 switches, and these images here represent layer 2. Root guard is configured per port, so you wouldn't configure it on a device and expect the configuration to be passed out through your network, unlike other configurations. Root ports are the closest to the spanning tree master. These ports are furthest away. If this is the master here in my topology, these are the ports that would normally you would want to be root, and it's basically saying the root equals best paths to take to the master. This is not the best path to take to the master. This would cause you a lot of problems. This is why you would enable root guard on these ports here. So it will monitor for incoming bridge protocol data units, and it prevents the port from becoming a root port. How it does it, you can learn a bit more when you do Cisco, CCNA and CCNP, etc. DHCP snooping. This is the legitimate one here. This is the rogue that somebody's attached it to your network, or they've downloaded some code accidentally onto their device, and it's trying to take over as the DHCP server for this segment of your network, which you don't want to happen. It forces the switch here to examine and filter inappropriate DHCP messages. So if this switch detects it coming on this port, you've configured this port here as untrusted, and you know which ports you trust because you're the network administrator. This port, so it comes in and that is permitted through. Untrusted, it comes in and blocked, and then you would normally get notified as the administrator that hang on, something's not quite right here, with a text, phone call or other type of alert. VLANs, these separate your host into functions. So here you've got the sales team, your accounting team, the IT team, and then your human resources. And what this does, and it depends on the design methodology you're following, by the way, there's a whole bunch of ways to design your network depending on which vendor you're speaking to, but we've separated ours into functions. Now if there's a broadcast, say there's a fault on the network card for this device here, then the broadcast traffic, because each VLAN has its own network address. So say that's in 10.10, 10.20, 10.30 and 10.40. So these are all different subnets, and in order for these to communicate, you'd either have to have a layer 3 module in this switch, or the switch would be connected to a router, as we've spoken about earlier. If there's a broadcast through this faulty network card here, it's basically restricted to all devices on this VLAN. And then what would happen is your phone would go, somebody would call tech support, and it would help you in your troubleshooting, because the broadcast isn't affecting everyone here, but basically you're told that everyone in the sales team is getting a really slow network response. And then this is known as the divide and conquer method of troubleshooting. You know that everyone here is affected, and then so you'd be looking at these ports on the switch. You could use the sniffer, the network sniffer, and you'd probably quite quickly see the IP address .1 is sending out normal amount of traffic, and then it's gone through the roof, whereas all the other devices on this particular segment are sending a normal amount of traffic. Access lists, these can be used to block an entire network or subnet, one particular host or a number of hosts, a particular port number or a protocol. So ICMP or whatever you want. Port numbers could be anything: DHCP, DNS, host.1, and then obviously entire networks. So it's a list of permitted or denied traffic. So if you don't worry about the text here, because you're not expected to know this for the exam, you've created an access list and you've said deny this traffic ICMP and permit IP traffic. And what happens is the access list are always processed top to bottom. I've only got two entries on this, so it'll be pretty quick actually. But as soon as the access list reaches a line, so say it's ICMP traffic, it would reach this particular line, and then it would be a match and it would be denied. The access list wouldn't go all the way to the bottom. If it's not ICMP traffic, it would reach the next item on your list, and the chances are it's going to be some other sort of IP traffic, and it would be permitted. Honeypot, honeynet. Honeypots attract possible attackers into an isolated environment. So this is your attacker and it's a potential victim, and what they don't know, or they should know, is they've actually been fooled into redirecting into this honeynet system. They can't do any harm in this place, and what you can do is, this is a pair of binoculars. I know it's absolutely dreadful, isn't it? This is you as the network administrator watching what they do. You'll obviously be doing it via whatever software. You can see what commands they're executing and trying to inject pieces of code, and this whole environment here is protected, is segmented off from your network, and then that lets you design a series of steps to protect your network. So you're analysing the behaviour and gathering the information. If it's a honey net, it's basically a chain of honey pots. So you've got your honey pot here, but what you've done is you've chained them together for whatever reason. Usually placed in network segments. This will be isolated by your firewall. So they're coming in and they get redirected to your firewall. This is actually your local area network over here. Pen testing. CompTIA have actually got the pen test certification out. I'm looking into adding it now, so keep your eyes open. It scans your network in order to find ports or protocols with flaws. I've talked about this kind of stuff before. Part of your regular security auditing process. So say every Monday you carry out this particular test on your network. It can simulate a type of attack, and it's well recommended that you do this. So we've covered a lot of stuff here. Managing your signatures, device hardening, changing your native VLAN, must do, protecting your ports. We looked at protecting it from the STP packets coming in, the bridge protocol data units, so it doesn't become a root, or and it doesn't change the it doesn't become a root port, and it doesn't become the STP route either. Both very bad things for your network. Access lists, honeypot and honeynet, and then penetration testing. So that's all for now. Thanks for watching. Welcome to Module 14, Lesson 3, Policies and Best Practices. A few things we want to cover here: the Privileged User Agreement, your password policy, on-off boarding, which is when people join your business and leave for whatever reason, your licensing restrictions, international export controls, preventing data loss, and remote access policies. Incident response policies, bring your own device, acceptable use policy, your non-disclosure agreement, system lifecycle, and safety. So your privileged user, the privileged users are people, you could call them super users or administrators, whatever. This agreement should be signed by administrators. So the crux of it is that they should only be using the networking tools for job purposes. I know where I worked at this ISP, we all worked in the admin team. We were doing the network support for large customers, and then obviously there was a whole bunch of teams under us here, like HR, finance, etc. But none of these could get out to social media. So say, for example, Facebook, that was blocked. But the admin team, they could obviously decide what went in and out of the network, so they let themselves get out on Facebook, eBay, whatever they wanted. So we didn't actually have a user agreement there. We just got hired and we started working. But really the point of a user agreement is you're not doing things for the network or giving people access to things that aren't really work related. So access only areas that are under your purview. So as the administrator, you may or may not be able to configure ways of you getting into firewalls and other devices that you might not manage, but the agreement that you've signed should prevent you from doing that. User accounts only changed under company policy and with correct authorization. So this would be something like a friend of yours that's asked to get out on some device, or they're asking if they can access their emails from their home computer. These things that you might be asked to do, but you shouldn't be allowed to do. Your password policy, I've actually seen a few news interviews, especially in the last couple of years, of people giving interviews when they're at work, and you can actually see a post-it note on their monitor saying what their password is. So this is obviously a big no-no. Some of the things that you may be implemented are the no reuse or changing the last character, such as if your password is A, B, C, D, E, F, G, 1, you wouldn't be allowed to change it to all be the same and then 2 on the end, obviously for the work network. No writing on post-it notes. Expiry length, again, this is all a pain because people are going to be forgetting their passwords and login tickets. It just depends how secure your environment is. Upper lowercase is pretty common, plus special characters and numbers. Non-dictionary words, so again you could be just looking at, and people choose things they're going to remember, like I think there's only one L in balloon, but you know what I mean. Balloon, kite, teacup, all these kind of things. Are they allowed to use password management software? I've got password management because I've got maybe 150 different types of software, and service I use. I manage I've got about 14, 15 websites. Some I'm on every day and some I only check in once a year maybe. But just to try to imagine, you can't have the same password for all of these, or you shouldn't, so trying to manage them is a bit too difficult. It's a RoboForm, I think it's called. On-offboarding, so policy for hiring people and then terminating. This should obviously go through the HR team as well, because the chances are if it's a big company you may not know who's come and who's gone, and obviously sometimes people will give notice and they're for privacy or whatever other reasons they're not allowed to work at the company anymore. They're basically in the UK it's called gardening leave. They're told to leave immediately, but they're paid for the rest of their contract. What access and privilege levels they're given, when are they given email access and access to shared directories and files? Are they given best practice training? This is normally in the form of CBT, and then they get a certificate maybe, and then that goes off to the manager for filing, just to prove they've been shown what they should and shouldn't do. Do they get a smartphone, and are they what are they allowed to use this smartphone for? Licensing, use of corporate hardware and software. And I remember when I worked at a large company, I won't say who, they had a few servers that we could use for internal files, but people would download it was cracked software, and it was videos, exams, and a whole bunch of other stuff that technically should have been paid for with hard-earned dollars, but it was all put on there for free. Now, I'm sure the top managers didn't know, but some managers knew what was going on, and this is going to leave your company legally liable. Download and sharing policy, training with a sign-off, which I've already mentioned, could be computer-based training. End of training exam. I had to do all sorts of things, health and safety and harassment, all this kind of stuff when I worked, even when I was a contractor. International export. Certainly in terms of hardware and software, say for example the USA, when they developed the GPS software, it was only allowed, I think, within something like 100 meters accuracy. The software they could drop a bomb within a window of a moving car, but that was not allowed out to the public. And now I think it's in the range of around 10 meters. The other thing is obviously encrypted software is restricted because depending on the level of encryption it's used by for terrorist organizations. So if you buy any software, say for example from Cisco, if it's a high level encryption you'll normally need some sort of license. You can get it from the government, or just do your own research and see how your government deals with it. Satellite technology and images that are protected or sensitive. There could be financial penalties, or you could be criminally liable for what goes on. So just be careful. Data loss could be accidental or malicious. I've even heard instances of I talk about this elsewhere, but the work computer gets decommissioned, sent off for sale in a shop somewhere, and then somebody can see all the data. I've actually on eBay, I bought a Cisco router. I'll do this image here. I bought a Cisco router. I booted it up, and I had a load of IP information, password information, usernames, and this was for a large ISP. An internationally known ISP, so heaven knows who was decommissioning their equipment, but it wasn't being done very professionally. Have a policy for your client devices, your network devices, and any storage devices, and there's normally software that you can wipe off hard drives, or sometimes they have to be destroyed. Identify what's most sensitive, normally addresses, credit card information, emails. Make sure people are trained and review the training. I've talked about remote access equipment. You need to also work out who is allowed remote access. This could be sales if they're on the road. It could be telecommuters, that kind of thing, people who work from home. What VPN software are they allowed to use? Are they allowed through SSH software? Or if they don't have a good internet connection, probably people won't use modems anymore, but disable HTTP access. I've talked about this elsewhere, HTTPS, but when you have a device, a lot of the time you can put an IP address into a browser and manage it. What's your permitted VPN client software? What are they allowed to download, if anything, onto works laptops? Are they allowed the intranet? What can they see on the intranet and where can they access it from? Works email is a big one, especially with the latest presidential campaign. As you know, one of the candidates was accused of downloading sensitive email from the works servers onto their home servers. What happens when there's an incident? There should be a policy, because some places I've worked, people are blaming each other, finger pointing. Nobody knows who's responsible for what. So there should be written procedures and also training, so everybody knows who's responsible and what the procedure is for escalating it, who gets called, who gets paged. Who are the stakeholders? So you know, your chief technology officer, your network manager, security manager, all these kind of people. Who are they involved depending on what the problem is? So identify the procedures, the procedures and the steps that take place. You normally work in some sort of framework like ITIL, IT Infrastructure Library. They have qualifications on them, procedures you should be using. Who declares it's an incident? Within ITIL, you've got different streams. Problem. You've got the problem manager. Normally on any team, that's one person who everyone reports a problem to, instead of basically everyone in the team being told through help desk tickets and then they tell other people. The problem manager will receive all of the reports of the problems and then they will escalate it. When there's a resolution, it will go through the problem manager and they will communicate it through group email, phone calls or whatever. Can the damage be isolated? Can it be who's in charge of actually removing it? Who will they speak to? Can they? Who's got the authority to escalate it to, say, Cisco, TAC, or the AWS senior team if you've got a support contract with Amazon? Then eventually, hopefully, it's recovered, network restored to normal function. There'll be a debrief after. If you go through the ITIL procedures, there's normally a meeting, a resolution, and then something will happen to change the procedures so it doesn't happen again. The training, or there could be some sort of consequence if somebody's made a mistake that they should have known better. BYOD, bring your own device, normally not allowed. In fact, most places really should have the USB ports disabled and decided who can use what where. Per policy per device, so for example, can they bring a WAP in? Probably not. Could they bring a USB device in? Even phones, are they allowed to bring phones in? Could they try and piggyback onto the wireless network? All these kind of things there should be a policy for. And who owns what data? If somebody brings in their device but they're using it for work, you know, who owns the data? This all needs to be clear. What applications can they use? And what can be taken off-site as well? You need to decide what hardware and software can be taken off-site. The acceptable use policy, stop and search. Depends where you are and how secure the site is, but people can search your bag. Speaking of which, I already mentioned the acceptable use policy. There should be a security policy included, how the network should and shouldn't be used, what you're allowed to do. It should be clearly spelled out and signed. Websites you can access. I know when I worked at this particular ISP, at the end of every month, the manager would, per employee, they would have a list of every single website you went to and how many minutes you spent on the website. So if you'd spent 60 minutes on whatever, say eBay, even though we couldn't do it, but say you were found to be on eBay for 60 minutes, then obviously there's going to be a consequence. You'd either be told off, written warning, verbal warning, or you could be sacked. And what you can and can't download, social media, again, this is a killer. You're not really being paid at work to use social media unless it's part of your job, for example, digital marketing. NDA as well, these are huge in the corporate environment. Protects non-public information. So you're learning about customers' names, phone details, who are the key contacts, all of this kind of information. What are the consequences of the breach? This could be criminal, or it could be civil. So you could have to pay financial penalties. And this creates a confidential relationship between the disclosing party and the receiving party, your boss or your company and you, which is fair. The system life cycle, which is asset disposal, something's brought into commission. Oh, sorry, I did this in a weird way. So integrate devices, something is brought into the network and then it would have to go through a chain of events. For example, a router would all have to be cabled up, then it'd be passed on to another team to do username and passwords, for example. Then it might go to the security team for configuration. Then it might go to the backup team to make sure that it could they can download files and configurations and recover it if there's a problem. And procedure to decommission. What happens? Does it go in the bin? Does it go to a shop for sale? And as I've already said, if it's going to go for sale, then all the data needs to be removed. Hard drives, are they going to be scrubbed? Are they going to be physically destroyed in a furnace or some other device? What are the laws for recycling? A lot of countries now are really hot on non-recyclable stuff. So if you can't destroy it, how are you going to render it unusable, or the data on it unusable, certainly? Safety procedures. So who can troubleshoot the equipment? People need to know what their job is. You could ignore that, sorry. Authorised personnel, who can cable stuff? Who's been trained? Who's insured? Monitors as well. Certainly the old cathode ray monitors, there was the back of them and the front. Just massive things. It would take two people to carry them, and they'd have a massive electrical current going in through them as well. Even when unplugged, it still held a massive current and could have shocked somebody or killed them. Who can move what heavy lifting? So I work for, as I said, an ISP, and I work for the network support team. I remotely accessed routers and switches, firewalls, load balancers, and one day one of my bosses asked, you know, you've got racks, these big racks that are full of really heavy equipment, and some of it can take up a half rack, a massive Cisco switch. And he came and asked me if I could remove one of the switches and put a new one in. Now, I wasn't actually there for that. This is down to the hardware team at the time. This stuff weighed something like, say, 150 kilos. And he was asking me to somehow pull it out, put it somewhere, and put the new one in. I wasn't actually trained to install this heavy equipment. I didn't have any safety equipment. I couldn't move it. And maybe he just didn't care, or he was just ignorant, but I had to turn around and say, well, I'm not actually qualified to move this equipment, but I am qualified to support it, but I can only connect to it over the network. He wasn't very happy, but it's better than me breaking my leg or whatever. Is there any safety equipment required? Normally when you're installing heavy stuff, you need a hard hat. So you need your hat, you need your boots. You've got to have read the training manuals. Are you insured? There's a whole bunch of stuff. Yeah, normally it would go in a trolley again. Who can use this trolley? Electrical circuits, certainly in many countries, for example Germany and Australia, you can't even change a plug. You have to be a qualified electrician to access electronic equipment. Alright, so we've covered a lot of stuff: your user agreement, your password policy and the levels of password, leaving the company, so joining, leaving the company, any licensing, export, for example, security images and all this kind of stuff, what's it protected by and what you can export and import, what happens to prevent data loss of remote access, what happens when there's an incident, can you bring your own device? Hopefully not. Signing the acceptable use policy, your non-disclosure, system lifecycle, and then finally keeping safe. That's all for now. Thanks for listening. Welcome to Module 14, Lesson 4, Securing the Wireless Network. A few things we want to cover: syllabus items, WPA, WPA2, TKIP, RC4, CCNP, AES, EAP, lots of abbreviations, geofencing. If you've been using wireless routers for any period of time, you probably heard of WEP, which was the first protocol used to secure your wireless network. It's pretty much better than nothing, I guess, but it was flawed, very easily crackable, and quite quickly after it came out they realised they had to upgrade it and replace it with something better. And it's upgraded, replaced with Wi-Fi protected access, as you can see the title at the top. WEP is Wireless Equivalent Privacy, I think it stands for. From 2003, WPA was available. It uses dynamic key management and it's based on EAP. WPA uses Temporal Key Integrity Protocol, so I'm glad they do abbreviate it. So you've got something like 50 trillion key combinations, which is quite a lot. You can use it with Radius in the enterprise. We've talked about Radius and Radius servers elsewhere in the course. So this basically offloads all of the management and authorization onto another device that's designed for that purpose. It uses an encrypted hash. Each packet has a unique encryption key. WPA2 is based on the 802.11i architecture, if you want to peruse that documentation. It can integrate with 802.1x. They do allude to this, I think, in the syllabus actually, and it's a method of authentication and authorization running on layer 2 networks. It's covered in quite some detail in the Cisco CCNA actually. This allows users and devices to authenticate with EAP, plus it uses TACAX and Radius. So just take a little bit of setting up, but you'll certainly find this in enterprise level networks. The RC4 was replaced by Advanced Encryption Standard, AES. This is 256 bits as a minimum and beyond. TKIP was replaced by Computer Mode with Cipher Block Chaining, CCNP. And I've already mentioned, uses encrypted hash. Each packet has a unique encryption key. Again, I mentioned this earlier. MAC address filtering. I've just found a basic router here, and even this cheap one. It looks like maybe a Linksys one. Looking at the colours, you can use filtering enable. Prevents clients listed from accessing the network if you want to stop certain clients, or you can have a permit only list, whereas you manually decide which packets go and which MAC addresses are allowed. Should be used with other security features in case of MAC spoofing, and it's quite easy, certainly on devices I've managed, to log in and manually change the MAC address of your device. And here's a permit list for just a random device I found. EAP, Extensible Authentication Protocol. It's a framework used in wireless networks. They've got an RFC for it if you have the time to look. 100 plus types available, so I think there only lists 3 or 4 in the syllabus. EAP MD5 uses a series of challenges and responses. TLS, this was designed by Microsoft and uses a certificate system. FAST is designed by Cisco and it uses a TLS tunnel with secure socket layers. And on that note, it also uses shared secret keys. These are unique to each user and they have protected access credentials. TTLS uses a secure TLS tunnel. And then finally, this is also a new one in the syllabus, PEAP. It increases the protection of authentications by creating a protected TLS tunnel. Within the tunnel, an authentication protocol such as MS Chat version 2 can then be used. Geofencing is a feature that is actually built inside software, so you don't actually have it running on its own. It uses GPS or radio to define geographical boundaries, i.e. who's allowed in and out of your network or device. There's triggers defined for devices entering or exiting the network boundaries. Alright, so just we're basically hitting some of the syllabus items, so this is why we went through pretty quick. WPA, TKIP, CCNP, EAP and geofencing. Okay, that's all for now. Thanks for watching.
Network tools, hardware troubleshooting tools. In all the previous lessons, we've talked about a lot of different things. And in the very previous lesson, we talked about network security and how important it is. So in this final lesson, I want to talk briefly about some of the network tools that were going to be useful when we're running a network. Specifically, in this module, about some of the troubleshooting tools. We're going to start off by discussing the general topic of hardware diagnosis and troubleshooting. And then we're going to move on to talk about 4 common tools that are used in troubleshooting software. These are the diagnostic disk, multimeter, cable testers, and a postcard. There are, of course, other tools. However, these are some of the major ones that we want to know specifically for this Network Plus exam. If you recall very early, we talked about some of the cable tools as well, such as toner probes and punch-down tools. And those sort of fall into here, but those are more tools that we use to create cables rather than ones that we're going to do troubleshooting with. So we've briefly discussed hardware in the past, but we need to take a closer look at it for the sake of this module. Hardware is a term that refers to the physical components of a computer system, including hard drives, power supplies, RAM, and other stuff. Hardware, unlike software, it's not a program, and it can't be installed. It can, however, be physically placed or installed or changed in some cases, but this generally requires taking apart the unit and physically installing something new on it. And when we're talking about a computer, I just want to point out that a router, a switch, these are types of computers. A printer, they do have hardware inside of them. So it's important that we realize this term is really all-encompassing. And because hardware is made up of physical components, it generally takes physical tools to troubleshoot them. By saying physical tools, this means tools that physically come into contact with the hardware in order to test it. Now, some of the hardware troubleshooting tools can actually be programs that run on the computer, and one of those I'm going to talk about in this module. So, this non-physical troubleshooting tool is commonly called a diagnostic or diagnosis disk. This is common software that's used to test the system's hardware, or in some cases, the router's hardware and so on. It runs a series of tests on different pieces of the hardware in the system, and if there are issues that need to be fixed, it'll notify you. You might be thinking, if the hardware of the computer is malfunctioning, how can you run a disk? Well, as long as the system's clock circuits, disk drive, and CPU are functioning, a diagnostic disk can be used. So again, it does require the CPU, the disk drive, or the USB contact, whatever it is that is going to contain the disk, or we should say perhaps disk in some cases, and the clock circuits, which are the circuits that allow the CPU to run. Now I just made this C right here because a disk with a K is like a hard disk, like USB drives, flash drives. A disk with a C is optical. Now, in general, these disks aren't going to state what the problem is. They're just going to say that there is something malfunctioning, and then it's your job to actually take that information and relate it into something useful. They usually do this by producing a list of all the different hardware components and basically saying which of them is malfunctioning. The course of action is then up to whomever is going to physically make repairs or test for more. This person is usually the administrator or an IT consultant, or specifically someone who's been sent out by the manufacturer. There are a number of tools that they can use to diagnose once they know what part is malfunctioning. A multimeter is one of the most common tools that we see in the field of electrical work and hardware troubleshooting. It's used to test circuits, outlets, and other electrical components of most devices. Now, there are very different types of multimeters out there, but they all generally test for the same thing. They measure electrical current, resistance, and wattage, or voltage rather. Current is generally going to be measured in watts, resistance in ohms, and voltage in volts. In the case of a hardware troubleshooting, the voltage and resistance functions are actually going to matter the most. And they tell us information about, say, the power supply or the wall socket that's plugging into. Now, the only times that you're really going to see or use multimeter to be helpful for troubleshooting is when we're talking about power supplies and fuses, which are also related. Anything that has to do directly with the electrical. On the OSI model, what we're looking at here is layer 1, the physical layer. Voltage tests are important because they can see if the power supply of a computer or device is actually receiving power. If the multimeter shows there's no voltage, then the power supply is probably malfunctioning. The resistance function is used to test fuses. If the fuse is blown or faulty and needs to be replaced, the multimeter is going to tell us this by the resistance. So this is sort of what a multimeter looks like. This one would be considered analog because you can see right here it has basically it doesn't have a digital output. It's going to measure it with this arm here that will move, and then you can read it based on the numbers that are above. There are as well digital multimeters, but either way, they're all going to have two probes, which are generally black and red. The black probe is usually either for the ground or the negative, and the red, just like on your car, is going to be for positive. The dial in the middle is going to be to test, to determine what you're going to test for. Are you going to test for voltage? Are you going to test for ohms? Are you going to test for wattage, etc., etc.? By the way, the reason it's called a multimeter is because it has a voltmeter in it. It has a ohm meter in it, etc. So we combine all of these into one device, which is called a multimeter. This probably looks familiar if you have already taken the A+ exam. Now, out of all the hardware failures that can happen, the one that's most common and has the biggest effect on the network is cable failure. This type of thing happens all the time, and there are tools that are created to help with this problem. Cable testers are generally handheld devices that are meant to test cable connectivity. They test to make sure that the data is being communicated through these cables properly. And there are a few main types of cable testers. Continuity testers are the least expensive kind, and all they do is test for a broken cable. Basically, they tell you if there is continuity in the line. Data cabling testers are a bit more expensive. They can actually test broken cables, improperly twisted cables, shorted connections, and more. they'll tell you what pins within the cable are faulty. Finally, there are things called time domain reflectors, or TDRs. They're the most expensive out of the three. So as we move, we're going from less to more. They test exactly where a break or issue is in the cable can be found. So they do this by sending basically out a signal, and they wait to see how long that signal, if I have a signal, let's say we make a little cord here, and I have my time domain reflector connected over here, it's going to send a signal out, and it's going to wait and see how long it takes before it's reflected back. Then they convert this time into a distance so they know how far along the cable error was found. This way they can literally tell us where the problem took place and help us fix the problem at its source, as opposed to us having to sort of try to find this blindly. The last thing I want to talk about, and we talked about this in A+ as well, is post cards. POST stands for Power On Self-Test. And you might remember this from the beep that you get at the very beginning when your computer starts up. This card is inserted into a slot of a device, and it can tell us what is not working in the system by giving us generally a sort of code called a post code. Sometimes this is a beep code as well. Generally speaking, you have to relate the code to a manual to figure out what it's telling us. These cards are really beneficial because they allow us to test a non-starting system without having to start from scratch and restore the entire thing. In other words, they can test a system that would otherwise have to be restored to a previous version or which we'd have to rebuild. So the cards run the tests while the system is attempting to start up and gives us this beep code or this error code. Then we can go to the code, look at a list, and determine where the problem is. For instance, perhaps the RAM is bad, or is not seated properly, or perhaps it's not able to find its firmware. So just to recap, we talked about hardware troubleshooting. Again, hardware is the hard stuff, not software. We physically have to deal with it. And some of the common tools we looked at were a diagnostic disk, which generally is just going to tell us which item is malfunctioning. And remember, a diagnostic disk is, in effect, a piece of software. We also looked at a multimeter, which is for electrical things. This is going to test volts, resistance, and current. Volts and resistance are perhaps the most important ones. Resistance for fuses or breakers. Volts for power supplies. We also looked at cable testers. Remember, there are 3 different ones that we looked at. Continuity testers are just going to tell us whether or not the cable works. Cabling testers, otherwise known as data cabling testers, will tell us actually which pins aren't working. And time domain reflectometers, let me write that out. Will tell us where the error is occurring. Finally, we have our post card. Remember, post stands for Power On Self-Test. And this is going to tell us in a non-functioning or non-starting system where the error is. It's very much like a diagnostic disk. However, the diagnostic disk does require that the CPU, clock, and the disk interface is functioning. The post card, it's literally a card we insert, and it'll tell us itself. It does this again by giving us a code that we can then reference on a list.
Welcome to Module 15, Lesson 1A, Physical Testing Tools. Just updated the from the last presentation really. There's a few extra little things slipped into the syllabus which I think is important to cover. The cable crimper, the punch down tool, the wire strippers, OTDR, cable certifier. We may have actually mentioned these in other areas of the presentation, but I just wanted to specifically address each one. Cable crimper, also known as a wire crimper, you'll be familiar with this tool if you've created your own cables. A lot of people do at home just to save money because they're so expensive if you buy them from the electronic shops for some reason. And also if for any reason something goes wrong with the end of one of your cables, you could just snip off the end and just create your own cable. It's fairly easy to do, well, with a little bit of practice, like anything. So you'll need a cable crimper, which you also buy from the electronic shop, used to connect the end of a cable to a connector. It can, depending on which one you buy, it can actually strip the cable. You separate the wires, and then you can insert inside here the connector, the plastic connector, pop the ends of the cable in, which you've also stripped with a stripper, and then clamp it closed, and that clamps down on the wires in the correct order. Different types of cable crimpers for different connectors. The punch down tool, it's known as a crone tool also, used to connect wires into punch down blocks. It strips off the insulation on the wire before inserting it into a punch block. Not something I've used before because I didn't use any of the punch down blocks. I did some cabling but didn't use a punch down. Not something I was interested in. Wire strippers, used to remove electrical insulation from a wire. On this particular figure you can see the different sizes. So you choose the correct size for the cable type, and that strips out the housing of the wire, the plastic covering, and exposes the actual cable itself. Has a center notch. OTDR, this stands for Optical Time Domain Reflectometer. I'm not saying that again. Used to locate faults on networking cable. I mean, there's an argument that if you just think there's a fault in a cable, you just swap it out anyway. It'd be cheaper, but it's a available tool anyway. It sends light into the fibre, and based on the quality of the reflected light, it can determine the following: fault location, length of the cable, loss of signal, if applicable. Cable certifier, it's used to carry out tests. It can test the following: conductors in the Ethernet cable, continuity in the wires, proper pairing of the wires as well. It's quite handy, you just plug it in and it will give you lots of different reading depending on the model you have and how much you've spent. Proper termination of CAT cables. So they're covered in the syllabus, which is why I give them specific slide each instead of just mentioning them in passing as we may have done elsewhere. So the cable crimper, the punch down tool, the wire strippers, OTDR, cable certifier. Alright, so that's all. Thanks for watching. Welcome to Module 15, Lesson 1B, Software Testing Tools. I'm not going to cover stuff that has already been covered unless there's a new point or some other reason for doing it. Packet sniffers, Wi-Fi analyzer, bandwidth speed tester, CLI tools, command line tools, not already covered. Because of the way the syllabus is set out, we have to cover some stuff earlier and later and in the middle because it's relevant to that particular subject, for example security or troubleshooting. I put an image here for Wireshark. Wireshark, I'm going to say a must know. Now you must know sniffing, and Wireshark is just the industry leader. And the good news is it's free to download. You can have a virtual network on my Cisco virtual rack, which is free on howtonetwork.com. It actually, you boot it up, you've got to find your own Cisco image because Cisco don't give them away, but I've bundled Wireshark so you can actually see traffic live passing between your routers and other devices. This is an essential tool and you need to understand it for troubleshooting. So really important. You can see all your protocols and packets and all that kind of stuff. So you'd normally load this software, the Wireshark. It'd be loaded onto your laptop. If you're troubleshooting, you would leave it running. Say for example, you'd leave it running for an hour, and then you could analyze the output and see where a particular problem's happening. Is it happening for the whole hour? Is there some sort of issue, spikes, and then, or does the issue sort of happen over this period of time, that kind of thing? So the traffic is going into your switch from the server, and you will configure the switch over here. You will do a configuration command on the switch to send the traffic out on whichever port you've connected your laptop to. You've just got to be aware of, I'm just telling you this because of the real world, you've got to be aware of CPU, and you've got to make sure that you get permission off whoever the person in charge is. When I've worked on network teams, and I knew the procedures and policies, which we've already talked about, what I can and can't do. But if it could be network affecting, for example the CPU, then you've got to make sure it's done out of hours or you've got permission. So you'll check for traffic patterns, traffic baseline, any irregularities, they will pop up. You'll be mirroring a port. Just be aware that packet sniffers can be used for good and bad, so they can also be used by hackers. So whenever possible, if you're connecting over the network, use a secure shell. This is a Wireshark, and they call it captures as well. It's handy to know the vernaculars. Ethernet 0 looks like the port. This is the dashboard all round here, and in this part here you can actually click on these little arrows and it will expand. So you'll see the layer 1, which probably won't be of interest to you, then layer 2, and then you can click on this and you will see that it's an ARP packet. You will see source, destination, and all this kind of stuff, and then down here is all your 1s and 0s and hex, which you probably generally won't be interested. This looks like it's some sort of pattern over time, and you can see there's a spike here, a smaller one here, and here you can decide exactly what traffic you're monitoring. This is SSH telnet, whatever you wanted to monitor, and then it's in a pie chart here, and obviously a graph form here. Really handy, so you can go to your customer or your boss with all of the facts and say, when this happens, that happens. When this happens, such and such doesn't happen, and you can prove what is or isn't the issue on the network. So please do check out the Wireshark certified network analysis, the network associate, qualifications. Really important. We've got it on how to network.com. I think there's maybe other people offer the course, but most people just seem to just skip by. But this will be a lifesaver if you're looking at being a network engineer. Anyway, Wi-Fi analyzer. This is obviously a graphical output that has been discovered with the piece of software. It reports on your SSID, which you can see here. MAC addresses, channels used, you can see the MAC addresses of devices here, channels used, speed, that kind of thing. It represents the output in the graphical form. As you can see, it tells you the security protocols and, more importantly, lack of. So you could, we talked about rogue access points and bring your own device earlier. You could be doing this in work, or you could be doing it as part of a security survey. And here's another image from the same sort of piece of software. Alright, bandwidth speed tester. I'm sure we've all used these if we've got problems with our speed at home, or even at work maybe. Known as throughput testers. They can be hardware or software based. It's easier for us obviously to use the piece of software which will send a certain amount of packets upstream and give you a report of X megabits per second, and the downstream the same sort of value. So it injects traffic into the network. You could actually use this on your LAN, WAN, or for your home broadband connection. The handy thing is you'll normally get a graph saying you know, how fast or slow it is. Free to download. If you want super duper outputs and charts and that kind of stuff, it'd normally be paid. CLI, this is where the rubber meets the road, and most network engineers kind of worry about using these kind of commands. Like even something simple like ipconfig gives you all of this useful information here that will help you troubleshoot. Now you can use the GUI, but it's just a little bit more clunky. You've got to go through a menu to get to another menu, and then it's only going to show you maybe 50% of what you could actually see if you use the command line. And if you're doing some sort of emergency recovery, you probably only got command line available anyway. Typical exam question: ipconfig will give you the TCP information. On Linux devices, it's ifconfig. Classic exam question, that is. IP information for your local interfaces, including your wireless adapter, any virtual adapters, virtual LAN cards, wireless or Ethernet. You can use switches to drill down, for example, ipconfig /all. There's a whole bunch of switches actually. Most command line tools will let you issue the question mark, and then it will say these are your options. IP tables. This is a Unix command. A lot of people. You'll either use Unix a lot because it's your job, or you've probably never touched it at all. But it configures the kernel firewall. The only reason I mention this command is because it's in the dreaded syllabus. Oops, syllabus. So I think just know this command and what it does. Knowing all this stuff, I've put it here so you can just see some of the options, but I really doubt that you would need to know it. I took this lot here from tutorialspoint.com if you want to look at that URL. Netstat's a handy command, basically short for network statistics, thankfully, so it's easy to work that out. Shows your active connections, tells you the type of services you're running, and you could be in for a surprise if you see things running on your device that you didn't think should be there. There's a few switches: netstat -n, -a, -b. I'm not sure you'll need to know the switches, although I can't guarantee it. Active connections, the applications, the connections without doing a DNS resolution. Here's a netstat from, this is from one of my authors actually, I recognise the name from his device. He's obviously named his device after himself. Netstat -a, and you can see the state of all of these ports. There's an established port here, and you could obviously do a search and find out what this is. He may well be connected to a remote device. He may be chatting on MSN or Facebook Messenger, and you could quite easily find out what all these ports are for. TCP dump, and here's the output here. It's a Unix command. It's a sniffing tool, so what you can do is use it to snoop. If you want to do the snooping, it's the snoop command if you're using Solaris. It's pretty specialised bit of software. I've seen some of the network teams using it, but not many. You can view the packets on the wire. Path ping. Now this is a tracer command actually. It's a TCP/IP tool. It provides information about network latency and sends ICMP echo requests. Nmap, I think I mentioned this before actually. It's used to discover computers and services on a computer network in order to create a map. And you can see there's a whole bunch of services here, and many of them probably look familiar to you. And at the end it says 2 hosts up and how long it took to scan it. Vulnerability scanning tool, just bear that in mind. Again, typical type of question they'll ask you, what's Nmap used for? Or tick the relevant vulnerability scanning tools. Used for auditing by you, or obviously whatever can be used for good can be used for bad, and it can be used by hackers. Dig, and you see the dig command has been used here. Domain information growther. It basically sends off a query to DNS servers. It's the same as the NS lookup tool, but this particular one is used for Linux devices. And you can see it's done a search for example.com, and you can see the name servers here. IP address, DNS servers, cache timers, that kind of thing. That looks like Google actually. If my memory serves, I think they've got 8888 and 8844, but you can check for yourself. Alright, so we looked at some cool stuff, packet sniffer, Wi-Fi analyzer, bandwidth speed tester, and some important command line tools. Remember, we're covering this in other presentations too, so this was just a subset of all the stuff that you need to know. So that's the end of the presentation. Thanks for watching. Welcome to Module 15, Lesson 2, High Availability and Load Balancing. We're just hitting another syllabus topic here. Just a brief overview really. High Availability, VRRP, HSRP, Load Balancing, High Availability. This refers to the ability of a user to access a service. No surprise. High availability is a common networking term. It refers to the continuous availability of a service for a higher period than normal. Now, obviously, we're looking for the 99.999%. In order to get the highest possible availability, we usually need more than one of a thing. For example, some Cisco switches come with 2 power supplies. And even this has been improved upon, so they have not just the fact they've got 2 power supplies, but they're hot swappable. So what that means is you don't need to reboot the switch. You can pull one out, the inactive one, and then slot another one in, and then you've got 2 active power supply units in case one fails. So measured as a percentage of uptime, which is 5 minutes a year. For a network to be highly availability, it should survive any kind of failure. I'm not saying there's such a thing doesn't exist, but even the most robust networks, there was a recent outage due to severe flooding in Australia. I think it was just a few months ago, where it took out Amazon S3 service, which you would think would be one of the most available and secure and robust hosting platforms in the world, but even some of those customers were taken out. So high availability can be achieved by configuring redundant components. So if one part of it fails, the other part takes over. Now, in the context of routing, we've got protocols such as VRRP, Virtual Router Redundancy Protocol, and HSRP, which is Hot Standby Router Protocol. These are what is known as high availability protocols. These enable multiple routers, or layer 3 switches in fact, to act as a virtual router with a virtual IP address. A default gateway is configured with this virtual IP address. So one router will be active, and this handles all the requests to the default gateway, and the other router will be a standby. So the other router actually takes over if the main router goes down. Now this isn't load balancing because you've got one master router and the other one is a slave or backup, depending on the protocol you use. They have different terms. So here's an image of the Cisco hot standby router protocol. At the top, with the red and the blue, you've got a layer 3 switch. There should be another. Oh, there we go. So we'll see. You see the host on the bottom. They both have the same default gateway. The gateway is 10.10.10.1. Now 10.10.10.1 is configured as a virtual IP address on the two layer 3 devices on the top. These two devices are connected and they monitor each other, so if one goes down the other one takes over. You see the priority on the right hand switch is 100, the priority on the left hand switch is 105, so it's got a higher priority. So this one, in the case of HSRP, will be the primary router. All traffic will go via this router until there's an issue with it. If it goes down, then all traffic immediately in a split second swaps to the standby router, which is on the right. They both run a virtual MAC address. We don't need to worry about that because I don't think you'll be asked, but they run a virtual MAC address so that layer 2 connectivity works also. So I think that's all we need to know about this diagram. Load balancing is distribution of work across two or more resources such as servers and networks. If you have a server overloaded with requests, then we can have several servers share the burden of that single server. In fact, even better than that, you can it can work so that the load is balanced automatically, so you don't have to wait till one server to be overloaded. The load is shared over two or more servers. The other thing is, just going back to that last point, the servers are acting as a single server, so devices don't realize that load balancing is taking place. The servers are acting as a group of servers, but the actual hosts that are contacting the services on these servers, for example, surfing a web site, don't realize then load balancing is taking place. So here's an image of load balancing. You've got two load balancers here. So one will be redundant or possibly taking a part of the load from the other one, and then we've got an array of servers providing whichever services they may be, FTP or web services. So load is distributed across the servers. They'll all have the same IP address. If there's a problem with one of the servers, it will be removed from rotation if they're not responding. I presume you'll have some sort of reporting software that will send a message to the administrator saying one of the servers has been taken out of rotation, so that can be looked into. Some of the benefits: optimization of resources. You get faster throughput, obviously requires careful planning for all your bandwidth. Efficiency, high availability, which is the whole point of the presentation. So we've looked at high availability, two types of protocols, VRRP and HSRP, load balancing. Alright, that's all for now. Thanks for watching. Welcome to Module 15, Lesson 3. We're looking at SNMP, syslog and SIEM. These are exam objectives. You could go into each of these subjects in quite a lot of detail actually. There's entire books on SNMP, which we'll only be doing an overview so you're familiar with the terms used. We'll talk about these services, how SNMP works, email and SMS alerting, syslogs and the benefits, and SIEM. SNMP you'll be referring to a fair amount as a network engineer, I guess. Again, it just depends on your network. Some of the larger networks I've worked on, you actually have a team that deals with any SNMP reporting and any configurations, or perhaps as a network engineer you'd have to enable SNMP reporting on a particular device, do some testing to make sure that the receiving station, the network management station, can receive information, which we refer to as traps, from the device, and then you will sign off that device as compatible. So SNMP is an application layer protocol. The idea is it exchanges management data between the devices on the network or from a certain device to the network management station. It's used to monitor and manage devices on the network such as routers, switches, servers, and it even drills down to individual ports. For example, if you have a switch with 24 ports, the SNMP manager, depending on the software you have, some of it's free and some of it's quite expensive, it can drill down and show you a pictorial view of each port on the switch, including the power button, and you can enable or disable and monitor and manage individual ports. So it's very handy and very powerful. SNMP implementation consists of a managed device, the SNMP agent, little piece of software, the SNMP manager, which is normally a PC or server that monitors the network, and reporting is done on there pictorially usually, with a graphical user interface. The managed device on the network, it requires some kind of monitoring, and it would be your servers, switches, routers, firewalls, that kind of thing. An example is a storage array. SNMP agent is a program that runs on the managed device. So these need to be written by whoever the vendor is usually, so it can comply with the RFC. The SNMP collects information from the device and sends it to the SNMP manager. The SNMP manager is typically a computer that has the software running for SNMP, and a lot of the time it's graphical user interface. You'll see different images and diagrams and reporting, pie charts and that kind of thing. This communicates with the SNMP agent. Management information base, we call these MIBs. We don't normally say MIB when we speak to engineers. The MIB is a database maintained by the SNMP agent. It contains information about the managed device, which is shared by both the SNMP agent and the manager. So SNMP is typically enabled when you have a storage system. Again, it depends on your setup. Whenever a specific event occurs in the storage system, the SNMP agent running on it will notify the manager and it sends a message. Now what happens after that depends on how you've configured it. It could trigger a number of events or just be stored. So you can see the I will act now by the SNMP manager. What actually happens? The trap is an event that's reported. The SNMP manager will receive the event and take action. Type of actions could be an email. You can configure it to send an SMS to the network engineer or a number of people. You can even have an automatic phone number dialed or number of numbers dialed, voice messages sent. It just depends on how you configure it and how important this particular message is. Quote from Wikipedia: SNMP agent receives requests on UDP port 161. It can send requests from any available source port to port 161. The agent response is generally sent back to the source port on the manager. The manager receives notifications. These are known as traps and inform requests. There's other types of messages. These are on port 162. So basically UDP ports 161 and 162 is used by SNMP. Moving on to syslog, which has got quite a lot of prominence in the Cisco CCNA exams. It's a protocol for exchanging log messages. So syslog generally sits on a syslog server, although you can configure it a router to be a syslog server. The general rule is leave these devices like a router to do the main job it's designed for, instead of using it to allocate DHCP addresses and record syslog messages, although it can do these and a lot more things. It can be used by devices on the network to move audit logs to a central login server. Again, this is called the syslog server. Why would you do it? It allows the consolidation of audit logs from multiple devices to a single place. Basically, it's to give you usable information and data. You can have different levels of syslog messaging, from urgent messages to just general reporting, and how and what it actually does is down to you to configure depending on your particular needs on the network. Okay, and lastly, SIEM, Security Information and Event Manager. It's a set of software products and services that are used to monitor a network. What it gives you is a real-time output of security alerts generated by network and network hardware. So it's definitely got a security bias. It's a combination of SEM, Security Event Manager, and SIM, Security Information Management. The Security Event Management deals with the real-time monitoring and notification of security events. The SIM deals with the collection of the log files into a central repository. A lot of the time, as with other protocols like this, you would have a graphical analysis giving you some sort of meaningful data that you can interpret. The SIEM solutions are used to log security data and generate reports, a lot of the time for compliance. And security compliance is a whole new and expanding area, a lot of the time for you to comply with national standards and requirements for security. One example is Checkpoint Eventia, which you can Google and look at some more information if you want to do some research. But that's for now. Summary is SNMP, components, managed devices and agents and managers. MIBs we've talked about, how SNMP works, alerting, syslog, and why we use syslog and SIEM. Okay, that's all for now. Thanks for watching. Welcome to Module 16, Lesson 1, Web Services. This would obviously be a massive area. We're just touching on the things that are covered in the syllabus. What are web services? XML, programming languages and web services, components used by web services, how a web service works. I think this has probably been put in as much as you may be asked to do some sort of troubleshooting, not in the respect of web programming, but perhaps access through the network or firewalls or some sort of troubleshooting, so you may need to communicate with the web programmers at some point. What are they? There's a whole bunch of applications that use open standards such as XL, SOAP, WSDL, UDDI. Uses, they're used to exchange data between the web-based applications over an IP network, and this is just a massively expanded area and always has been since HTTP was first used to display web pages. It's been improved upon over and over again to deal with issues, speed, security, usability, mobile devices. It's just never ending. So in a web service, we already know that HTTP is used to transfer machine readable formats such as the following: XML, JSON and JSON. When different software services want to exchange data with each other, a web service allows them to do this over the internet. The software application that requests the data is called a service, and you can tweak these in most of your browsers, such as Google Chrome or Firefox. They normally have ways you can manage extensions or the back end to a greater or lesser extent. Software application that serves the data is called a service provider. And web services are a means of interoperating between different software systems. The software applications are developed using a whole variety of programming languages, and normally you'll have somebody who specialises in one or more, and you can see a few in the fig there. Some have been depreciated, such as Flash, due to security issues. See, software applications want to exchange data. They should be able to communicate with each other. This may possibly be where you become involved as the network engineer. Data exchange shouldn't depend on any particular programming language. So there's a need for a common language that allows different software applications to send and receive data over the web. Most types of software can interpret what's known as XML tags. This stands for Extensible Markup Language, which you can learn if you so choose. It's a standard language for web-based applications to communicate with one another. The exchange of data happens through XML files. XML is a markup language. It defines a set of rules for encoding documents in a format that we can read as humans. Generally, you need to be a programmer to understand what they mean, but it could also be read by the machines. So here's an example of an XML file. You can see it's marked as XML at the top, the version, and then there's various prompts within the greater than and less than markers, and also the actual text in between. Network 100, status pass, subject hardware, mark 100. So you've seen the example, easy to read. Obviously once you've learned what it all means and how it works, but it's also easy for the machine to read also. It allows you to see what's been sent between the web-based applications. Web services. Web applications can send data using the XML format. They can also retrieve data from an XML file. A standard web service uses the following components. SOAP. This stands for Simple Object Access Protocol. This is actually used to transfer the data. UDDI stands for Universal Description, Discovery and Integration. Directory that defines which software system should be contacted for which type of data. WSDL stands for Web Services Description Language, used for describing the services available. How a web service works: it uses XML to tag the data, SOAP to transfer the data, and then WSDL to describe the availability of a service. It's worth writing this out if you haven't already, if you're not making notes, so you understand which part performs which service, because this is the most likely thing you're going to be asked a question about. So we've looked briefly at web services, XML, programming languages and web services, components, how web service works. That's all for now. Thanks for listening. Welcome to Module 16, Lesson 2, Unified Communication. Just call this UC usually to save a lot of breath, as with everything. Different media for same communication we'll look at, and presence. This is a real snapshot of a pretty huge subject area. So, as with a lot of Network Plus stuff, especially the new stuff in the syllabus, you just expect it to have an awareness of it. UC is the integration of a whole bunch of communication methods, including voice, video and data. It all goes into your IP network, which is kind of tied in with the cloud now, and how everything would be. You'd expect everything to be working over IP and over multiple devices, depending on where you are and how you want things to work. The idea is it simplifies real-time communications at an enterprise level, including, it can work, it doesn't have to be enterprise by the way, it can be any small network including homes. making calls, instant messages, having a video or audio conference, sharing your desktop with whoever needs to log in and troubleshoot, presence information. So UC, it's all forms of communications that are exchanged over IP. Integrates real-time communications with non-real-time, such as accessing your voicemail if you're not available, accessing your email, text messages, faxes. I don't even know who uses those now. It allows you to send messages on one medium but receive a response through another. An example is when you send somebody a voicemail, you've probably had this happen before, or you've left a voicemail and it says it will send the user a text or email. You can retrieve, check and retrieve emails and voicemails using any communications at any time. Presence is a component of UC, shows the present status of a user in real time, whether they are available or unavailable, where they are located if you've enabled geo-IP tracking, or geo-tracking, sorry. Allows users to communicate seamlessly even if they're in different locations. You can locate a person by accessing an interactive directory and engage in communications through text, voice or video. So that's a summary of what we've covered. Just wanted to go and show you, just for more context really, Cisco's unified communications. I'm just going to play a video. This video is copyright Cisco Systems, so if you want to learn more, all you do is go to Cisco, or in fact type Cisco Unified Communications. I'll just put a video on now. Welcome to Module 17, Lesson 1, Introduction to Virtualization. This is one of a few new topics that have been added to the syllabus surrounding virtualization and cloud computing. CompTIA offer a cloud certification actually. There's a Cloud Essentials and I think there might be a Cloud Plus. Definitely a Cloud Essentials because we host that course. Alright, module objectives, the definition of virtualization, what is a virtual machine and the software. I'm sure you've heard of it actually. It's the new, or one of the very new and exciting emerging technologies that's made life a lot easier for network engineers, companies from a financial and operations standpoint, and also home users who can do a lot more interesting things on their systems at home. So it refers to the technologies that allow a single physical computer or server, obviously, environment to operate as multiple virtual machines simultaneously, transforms the physical hardware resources into virtual hardware resources. So what you normally have one device running one operating system, you can have, depending on how much hardware you have and how you apportion it, 2 or more virtual machines. A virtual machine is an isolated software replica of the original computer. So for all intents and purposes, it appears as a machine in its own right with all processor instructions and system resources. So you'll often see an image like this where you have a physical computer or server, and inside it will represent a number of virtual machines. Much in the same way as VLANs, they operate in their own right, as if they're an actual machine. Virtual machines are completely separate and independent. By running an operating system in each one, it becomes possible to run several guest operating systems at the same time. So you could have Microsoft, Linux, and other operating systems running on the same physical device, but different virtual devices. A whole bunch of virtualization software around, some free, some you have to pay for, and you get different levels of software up to enterprise and obviously support contracts. The software transforms the hardware of the computer, including the CPU, memory, network adapter, into virtual resources. These are shared amongst virtual machines. It basically provides a layer of abstraction. So for all intents and purposes, there's a divide, a virtual divide between all of these different machines. The layer of abstraction is basically there to hide what's happening underneath, what you can see. As a result, the abstraction provided by the software, the guest operating systems, are not tied to the underlying physical hardware, so this is how we can actually get it all to run. So you have a portability of moving virtual machines from one physical computer to another physical computer if you so wish. Great if you want to do testing, interoperability, stress testing, or just practicing even. If you want to do some install various operating systems onto one device in order to practice for exams or job interviews. So this is just an overview. We've got more to cover in the following presentations. What is virtualization, the virtual machine, the software. That's all for now. Thanks for watching. Welcome to Module 17, Lesson 2, Virtualization Components and Software-Defined Networking, or SDN for short. We're looking at virtual networking, virtual network adapters, virtual switch, virtual router via VRRP, the virtual firewall, and SDN, and why we'd want to use SDN. So a virtual network is a system in which the following is true. You've got two or more virtual machines connected logically to one another. They can each send and receive data as if they were operating as physical devices. I've got an example here, ESXi, which is software available from VMware. I think they do offer some free software. I haven't checked as to which is free for home use or commercial use. And I recommend you check out the VMware certifications on howtonetwork.com. They're very relevant for modern day networking. So they can send and receive data from each other. The virtual network adapter is a software implementation of a physical network adapter, which I'm sure comes as no surprise. So you have a physical adapter, but the virtual one is acting in exactly the same manner. You've got a diagram here of a physical network card, and then you're working as a subset of this is your virtual machine. They're running virtual network cards and virtual machines on top of that. The virtual network card interfaces the virtual machine to the network. They can have one or more virtual NICs, NICs, or VNICs. Each such VNIC has its own MAC address. It needs to follow the same rules as physical networking, so it'll need to have a unique MAC. A virtual network card in a virtual machine, you still have to configure it. All the same rules apply. It's just the fact that it isn't operating physically. So you couldn't go and see it and physically plug and unplug cables. Virtual switch or vSwitch is a software version of a physical switch. It's got network ports similar to the RJ45 connectors you have, 1016 virtual ports. This all depends on your software and hardware platform you're putting it on. There's a limit of 4088 ports on all virtual switches on the VMware ESXi host. Different vendors may well have different capabilities and rules to follow. A virtual switch can send network traffic between virtual machines on the same host, or from virtual machines to an external network that's outside the virtualized hosts. You can go to YouTube and check on videos on how to check a virtual device to a live network. A lot of the time you do it for home use to overcome limitations when you're trying to get different bits of software and hardware to work for certification exams. It's quite common. Virtual switch joins a network with a physical network when it connects to a physical switch using physical network adapters. You can also get virtual routers, a software version of a physical router obviously, performs your layer 3 packet forwarding between your subnets or LANs and VLANs obviously. You need layer 3 capability of some sort. Virtual router via VRRP, which we covered that protocol earlier. A virtual router is implemented when you use VRRP to provide redundancy of the default gateway, so all the hosts still have IP connectivity. It's backed by 2 or more physical routers. Depending on the protocol, you can have 2 or 3. I'm not sure what the limit is actually. Depends on the protocol and it does change. Why use a virtual router? Provides the same routing functionality, but it's virtual, so you've got all the advantages of costs. Virtual firewalls, they're mentioned again in the Cisco syllabus, definitely the CCNA routing briefly, but I would imagine in the CCNA security in a lot more detail. So it's a virtual version of an actual firewall. It's either implemented as a firewall within a virtual machine or as an appliance that provides security to your virtual environment. It does exactly the same job as the hardware firewall. Just moving on to SDN now. It's a big topic and it's been introduced into the new Cisco CCNA exam, and I would imagine it's going to have more and more prominence over the years to come because Cisco have invested heavily in SDN, and there's a lot of some open standards that have had a huge uptake as well. It provides a high level administration capability to network admins. It allows you to manage your entire network through a user interface that abstracts a complexity. So you wouldn't necessarily need to understand all of the underlying commands that have been executed and how it all works just to manage it if you're using SDN. Obviously it helps if you're to be a network engineer that you actually understand what's happening, but now I suppose it's like managing your car. They've got all these different settings on the onboard computers that change your handling and your engine performance and all that kind of thing. You can turn different controls on or off, like traction control, and you don't necessarily need to worry about how it all works. Alright, SDNs are used to control the operation of network devices. Look into more, I think Cisco, I'm not sure which CCNA version, maybe data center that looks into SDN in more details, but there's a whole bunch of controls and formats that have to manage your interface between your network, the user and all of your devices, APIs to name one. So examples of SDNs are Cisco Open Network Environment, Nikira's Network Virtualization Platform. Why bother? It basically makes your life a lot easier as the network administrator. You can interact with your entire network without having to actually connect via telnet or physically connect to your devices, or even understand all of the different commands. Say if you're using Juniper hardware, it's got one type of command line interface for copyright reasons. Your Huawei and Cisco all got different command lines, different commands, all to achieve the same thing. So you don't need to worry about that if you're using SDN. So get rid of the command line. Some of the benefits, again, the graphical user interface provides information about what's going on with your network. It allows you to specify changes, and behind the scenes the actual configurations are done with the interface, one of the APIs between the software and the hardware. Alright, so it's just an overview. We looked at virtual networking, the virtual adapters, virtual switches and routers, VRRP, firewalls and software-defined networking, and why would we be interested in using it. So that's all. Thanks for watching. Welcome to Module 17, Lesson 3, the Storage Area Network. I think CompTIA actually have a qualification, Storage Area Networking Engineer Plus. We actually have such a course on howtonetwork.com. This is just an overview touching on some of the subjects they mention in the exam syllabus. Looking at storage area networks, direct attached storage, network attached storage, SAN v DAS, SAN media, fiber channel, iSCSI SAN, iSCSI architecture, and components of iSCSI, also jumbo frames. SAN, as we already know, stands for Storage Area Network. It's a high-speed network. The idea is it allows transfer between the computer systems and the storage devices. It's optimized for this type of technology, and we'll see this as we go along. Here's an example, which you'll see in a few slides. So why bother at all? Why do we need a storage area network? Again, everything covered really in the Network Plus was created in order to solve some specific or general networking problem. It's the evolution in data storage technology, and we'll look at some legacy ideas in a moment. So unfortunately I put the wrong order here, so the lines are appearing in the wrong order. There's been progress in the data storage technology from DAS to SAN. Direct attached storage is the traditional way, and I'm sure many companies still use it, those who don't use SAN as a solution for storage. So traditional client-server systems, each server having its own storage, and the storage is directly attached to the server internally usually, or it could be external. Such a technology is referred to as direct attached storage, or DAS. So there obviously has to be advantages. It's high speed and it's exclusive access to the storage, so it's not shared. Preferred by small companies, just cheaper to implement, easier to troubleshoot, maintain. Obviously there are disadvantages, which is why it's been superseded by many companies. So what you get is a pocket of isolated storage. It's not efficiently utilized. And this ties into virtualization really, where we've got this whole amount of resources, but we may only be using a certain percentage of it, which is a waste. So for example, when one server has plenty of free storage and the other one has almost run out of space, then we've got a disparity. This is where network attached storage will help. Direct attached storage design doesn't allow the free capacity of the servers to be shared. So when a business deploys more servers in the network, the following occurs. There's an increase in the wastage, increase in the complexity of managing all of these isolated storage, because usually you've got RAID, so you've got to insert and pull out various disks. And network attached storage, another image there, it decouples the storage from the servers. So the servers are still there, but we remove the storage as another feature. Makes the storage a centralized pool of shared devices that can be accessed by all the servers connected to the network. Now, network attached storage is not a network in its own right, but a storage array hooked up to an existing network. Here's an example of a NAS server. That's a Netgear by the looks of it. It can provide centralized shared storage with terabytes of storage. You get NAS servers for home users as well, where everyone can connect to this particular device, and hopefully that device then in turn backs up somewhere over to the cloud or somewhere like that. Disadvantages: doesn't provide the high-speed data protection needed in enterprise environments because it typically sits on an existing shared corporate network. Complete data backup takes a lot of time and obviously takes up a lot of bandwidth. So SAN is a dedicated network that transfers blocks of data at high speed to a storage device. Low latency for the input-output requests to the storage device. What SAN gives you is access to several servers that connect to several storage devices. You can see we've got in this instance, we've got a full mesh connection between the servers, the switches, and the storage array there. Also allows the storage devices to communicate with each other. Limitations, going back to direct access storage. This is the challenge we have with the traditional server attached storage. You can't satisfy the ever increasing demands for storage, and we obviously have more and more complex information, including video and voice. Not scalable due to the restrictions and how many devices you can add physically to servers. SAN is scalable, so you can add a lot of new devices and without having to add new servers. You can aggregate the devices into a central pool that can be accessed by the servers. The server attached storage doesn't provide high availability because if a server goes down, then you lose the data, since the data is tied to the server. SAN obviously overcomes this problem because you remove the storage from the servers. If a server goes down in the topology, then the data is still accessible. So you've removed that as a point of failure. And though the SAN connects a multitude of servers and storage devices, the performance doesn't suffer because the network is characterized by high speed and low latency. You've got the best of two different worlds there. The high speed data transfer, the low latency, can be compared to the high performance of storage directly attached to a server. So your storage area network is a dedicated network. It's scalable and highly available, as we've already said. Primary purpose is providing the high speed and the low latency. SAN media, it's the actual cables and physical wiring. It's associated with a unique protocol and is always managed by that protocol. The protocol is responsible for the format and sequence of data exchange on the storage area network. Now, you're almost always going to have fiber channel because of the speed requirements. Different types of optical electrical transmission media. You can have fiber, you can have copper, but fiber is the preferred connection type. The SANs are typically built using fiber channel. The standards define a high-speed network that transfer dates at around 2 gigs per second. The standards also define the properties of the media and how data is transmitted, which I mentioned earlier. Fiber channel is the de facto standard. The storage area network is built using fiber channel technology. It's called the fiber channel, or FC-SAN. The whole idea is to increase access to all the data, and since organizations have a heterogeneous combination of operating systems, fiber channel was designed to cater for all of these different applications and operating systems. The fiber channels solve the fundamental problem of reliably making terabytes of information available to hundreds of servers, more than likely at the same time as well, so serving multiple requests. While direct attached storage and network attached storage may be appropriate for small networks, the fiber channel SAN is used generally for large storage networks and enterprise networks. The concept of SAN isn't tied to any particular technology or vendor, so it can be used by a multitude. It can also be built using other technologies such as Internet SCSI or iSCSI. iSCSI SAN is a storage area network implemented over an IP, and it uses the iSCSI protocol. It's a mapping of the SCSI protocol over TCP. I'm not sure if there's an RFC for this actually, but you can Google the iSCSI for yourself and see where the proposal started. Carries block level data over the IP network, and block storage can be accessed over the network as if it was directly attached to the server. iSCSI architecture is based on the client-server model of SCSI. In SCSI parlance, it's referred to as the initiator-target model, which you may expect a question on something along those lines for the exam. The iSCSI SAN consists of three components: initiator, the target, and the IP network. The initiator is the system that first initiates a read or write request over the IP network. Example of a device is the server. Target system is the system that responds to the requests. So an example is the storage array. Initiators and targets need the physical iSCSI interface to connect to the IP network. The iSCSI interface is available as a PCI expansion card, or it can actually be built into the motherboard. Again, you need to speak to the vendor and look at your particular specifications and requirements. Jumbo frames you may have heard of before in network parlance. It's an Ethernet frame that's got a payload greater than 1500 bytes, and it can carry a payload of up to 9000 bytes. So, on the contrary, a standard Ethernet frame, can carry a payload of 1500 bytes. The payload, or the size of the largest data that an Ethernet frame can carry, is referred to as the MTU. And if you ever use a packet sniffer, you should see for Ethernet an MTU field, a maximum transmission unit. Since jumbo frames have larger MTUs, they can carry more data. Each transmitted frame in a network requires network hardware and software to process it. So the more frames we have, the more CPU cycles are required to process them. So if we use jumbo frames, it only requires a few. We require less frames because of the bigger MTU size. As a result, we get less CPU utilization, but we get the bonus of increased throughput. We can use jumbo frames when fiber channel frames are to be transmitted over the Ethernet. The size of the fiber channel frames are over 2K, so it becomes necessary for the adapters and switches to support baby jumbo frames in order to prevent the segmentation. I think we covered segmentation earlier. It's when the frame is chopped up into different pieces, numbered, and then transmitted, and each frame has to have an acknowledgement. So you've got a lot of overhead associated. Alright, so we've looked in brief at storage area networks, direct attached storage, NAS, SAN versus DAS, SAN media, fiber channel and iSCSI architecture and SAM, the components of iSCSI, and jumbo frames. Thanks for watching. Welcome to Module 17, Lesson 4, Cloud Concepts. I've mentioned earlier, well worth doing the CompTIA Cloud Essentials exam because cloud computing is just one of the core subjects that you need to understand as a network engineer. There's a few others including routing, virtualization, probably Amazon storage, routing and switching, for example the CCNA, IPv6. So this is just a real brief taster. Looking at cloud computing characteristics, on-demand self-service, broad network access, resource pooling, elasticity, measured service, software as a service, platform as a service, infrastructure as a service, and then private, community and public clouds or hybrid clouds. So best thing is to start with a definition so we can kind of have an agreed kicking off point of what cloud computing actually is. Now cloud computing from the definition is a model for enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources. Examples are networks, servers, storage, application and services that can be rapidly provisioned and released with minimal management effort or service provider interaction. We've all used the cloud already. If you've used any storage, for example Dropbox, box.com I think they're called for storage, any Google services, for example Gmail or Google Documents, things like that. There's many others, are all based on the cloud. So some characteristics that you need to remember these, so make sure you note them down. There's 5 characteristics of cloud computing: on-demand, self-service, broad network access, we'll go into all of these in more detail, resource pooling, rapid elasticity, and measured service. So on-demand basically means the user can provision resources as and when they're needed without getting any human assistance. So if you needed more memory, you wouldn't have to log a ticket and you wouldn't have to have an engineer somewhere turn off the server or whatever the device is, add more physical memory, reboot it and then answer the ticket, as you may well have had to do in the not too distant past. You click a button and more is available. When consumers provision the resources based on their needs, those resources are automatically allocated from a shared pool, and the shared pools provided by the cloud service provider. Broad network access means that when the consumers have provisioned the resources, they can access these from a number of devices: workstations, laptops, tablets, and mobile devices and mobile phones. Resource pooling, the service provider's resources are shared among the consumers on a multi-tenant model, where consumers get a dynamic allocation of resources based upon their needs. So sometimes consumers may need more computer resources and other times they need less, so it has to adapt for this particular requirement. It's resource allocation based upon demand. Rapid elasticity, can't say that word, elasticity. Now a consumer can be allocated more resources if needed. At the same time, if for any reason they need less, because the more you need, the more you pay, obviously. If you need less, then they can be downsized to provide whatever model you need, the resources you need. So it appears to the consumer that there's an actual unlimited amount of resources for them at any given time. The elasticity provides a lot of savings because it's not possible when you have a traditional data center that you've built and you own, you can't grow it and shrink it as and when needed. Obviously it's measured just like a meter, so you're charged based upon your a number of things such as memory you need, storage and bandwidth. So you get what you pay for, which I've already said. It's tracked. Normally you can log in and you can track your use of resources in real time, as well as historical data looking at how much you've used and projected requirements based on previous usage, and you can see how much you're going to have to pay and how much you paid in the past. There's 3 service models you need to be familiar with: software as a service, platform as a service, infrastructure as a service. Service providers provide their services to consumers based on these 3 service models. So SAS, SaaS or SaaS. Consumers can use the service provider's software applications and databases over a network without the need to install any software except for a web browser you need to access. These software applications databases run on the cloud. So imagine you're trying to program some application, for example, or just use a huge amount of resources or develop a program. You can use the provider's resources and scale it as and when needed. It's provided as a shared computing resource to the consumers. It's essentially the aggregation of hardware and software used to support the cloud services. A few examples you can see there are Twitter and Facebook. There's a whole bunch of others you can look into if you wish though. In the SAS model, consumers access the shared applications over a network from various client devices. It doesn't give you the ability to control and manage the underlying cloud infrastructure. So you can't manage the operating system, servers, the network or storage, and you don't want to anyway. You just want to use it as is. Platform as a service, there's an example there, Windows Azure, which you could look into in your own time. In the platform as a service model, consumers have the ability to develop and deploy software applications on the service provider's cloud infrastructure. The service provider typically provides a computing platform comprised of the operating system and the application development environment. This includes programming languages, libraries, tools, databases, and web servers. I recommend you look at the Amazon AWS qualifications for more information on these. In the PaaS model, consumers can develop and deploy software without the need to maintain the operating system. So you can imagine how convenient this is to fire up an instance. For example, if you logged into the Amazon or the Google Cloud and start doing your developing, it's just so easy and quick. Consumers have control over the deployed software application and the configuration settings. It doesn't give you to manage the control and manage the underlying infrastructure. Infrastructure as a service, one example is Amazon EC2 Web Services. Here consumers access a dedicated physical, or in most cases a virtual machine running on the service provider's cloud infrastructure. A lot of people use this for web hosting, especially WordPress. Is quite easy to fire up an instance and get it all working. Virtual machine typically comes with a server operating system. Consumer has complete control over the OS and can control the updates. You have control over the operating system, application, storage. You have limited control over the selected networking components, such as the firewall that's protecting your particular virtual device. Again, you can't control the underlying cloud infrastructure. Probably neither would you want to. Infrastructure as a service, you've got 4 models to choose from for IaaS. You've got the private cloud, the community cloud, public and hybrid. For a private cloud, the cloud infrastructure is provisioned exclusively for a single organization. So you get exclusive use of this. You've probably hired a company to create all of the infrastructure for you, and nobody else can have access to it, and all of your offices and remote offices will have access. Owned, operated and managed by the organization itself, both third party or a combination. Physical location could be within your premises, or it could be located elsewhere on the cloud. Community, it's provisioned for a specific community of consumers from organizations that share common concerns such as security, compliance, jurisdiction and so on. For example, would be law enforcement. In this model, the cloud infrastructure may be owned, operated by one or more organizations, by a third party, or you could have a combination. The physical location may be within your premises, or it could be located elsewhere. In public cloud, it's provisioned for the general public, so it can be used by the general public over a network such as the internet. The cloud infrastructure could be managed by the government, businesses, academia, or a combination. Physical location is within the premise of the service provider. Now, a hybrid is a mixture of any of these. Separate entities but are integrated into the benefits for of the multiple deployed models. Example is when the IT organization uses a public cloud as a temporary solution to meet an excess capacity demand that can't be met by their private setup. So I've looked at quite a few things here. You need to make some notes, obviously, because there's a few things to remember for the exam. Service models, software as a service, platform, infrastructure, private, community and public cloud, and hybrid. Okay, that's all for now. Thanks for watching. Welcome to Module 18, Lesson 1, Physical Security Controls. I'm going to whiz through this pretty quickly because most of it is pretty self-explanatory and common sense really. Physical security, man traps, network closets, video monitoring, door access controls, proximity readers, biometrics, cipher locks and a security guard. So the physical security control is the measures we take from physical threats, basically people trying to get into our data center. I guess RAM raiding might be included, although I've never heard of that. But yeah, physical security. Examples I've already mentioned, the man traps and network closets. They reduce the risk of damage or loss by preventing or slowing down physical attack. I've actually been to a few networks consulting where they don't have any security whatsoever. Everything's shoved in a cupboard, and the entire company website, the financials, the accounting, all stuck on a server, hanging off a cable in a cupboard. And I'm sure you've seen the pictures or may have seen it yourself for real. And it's pretty easy to do. It doesn't have to be expensive. A man trap I've experienced in a internet service provider that used to host some of my equipment. Basically, it's a space, it's a door within a door. So you go through one set of doors, which normally has got some type of security, keypads or whatever, and then you've got a second set of doors you have to go through. If it's a manual man trap, a security guard locks and unlocks each doors in sequence. If it's automatic, the doors are only opened after getting an identification from the person. The one I went to, you had to do a keypad to get through the front door and then actually pick up a phone and speak to the on-call engineer to get through the second door. And it all had to be done by appointment. A network closet is a room where network hardware such as switches and routers are installed. Physical access to the closet is normally restricted by having some sort of security control. Videos normally record who comes in, who goes out, who accesses what and where, and it's recorded for a set period of time. This can be CCTV or video over IP. Door access controls, electronic system. I'm sure you've used these in a lot of different places to get in and out of different rooms and buildings and floors. User granted access door. If the door is open for a predetermined amount of time and the entry is recorded. If the door remains closed when the user is denied access, that attempt is still recorded. If the door is held open for too long, then it should trigger some sort of action or alarm. Proximity reader is basically electronic access where you have some sort of smart card and you swipe your way in and possibly out again as well. You'll normally hold the card on or in the reader. Proximity reader normally bleeps or beeps when it has read your smart card. If it doesn't read it, you may hear a different type of beep, and you may have to go and get your card checked or renewed. When the user is granted access to the door, it will open, otherwise it remains closed. That's pretty obvious, to be honest. Biometrics referred to metrics related to human characteristics, fingerprint, face, iris, retina, and so on and so forth. I'm sure you've seen it if you've watched any of the Mission Impossible movies. Since biometrics are unique to individuals, they're used to verify the identity of an individual before granting access. The biometric locks grant access only if the biometric feature is validated. For example, scanning your fingerprint. Keypad and cipher locks. The cipher lock uses a keypad in place of a keyhole. Used us to provide the correct numerical PIN code by pressing buttons on the keypad. Cipher lock could have 4 or 5 push button combination in order to get in. Cipher code is created at the initial setup, but obviously can be changed, usually changed every week or every month. And the security guard is whoever's been gone on the course, got qualified, and it has become the security person. Deters illegal or inappropriate actions. Alright, so covered some following items, all fairly obvious, I think. Just make a few notes for the exam, and I'll see you on the next presentation. Thanks for watching. Welcome to Module 18, Lesson 2, Basic Forensic Concepts. This is one of the new additions to the Network Plus syllabus, and it's basically because of the increased scope for network engineers and the more formal proceedings we have in respect of computer forensics. So this is quite an emerging field of law and evidence, and obviously we've got forensic investigations going on now in terms of terrorism and other threats and crimes, and we need to be familiar with some of the basics. So what are forensics and computer forensics? The first responder's job, electronic discovery, chain of custody, legal hold, securing the crime scene, high-level view, some steps in basic forensic process including collection, examination, analysis and reporting. So what is forensics, or what are forensics? It's the scientific methods and techniques for collecting, analysing and preserving evidence. That's the definition. Can be used in a court of law, and if anything's going to be used in a court of law, it normally has to follow a certain amount of procedures in order to qualify as evidence, as we'll see. The Computer Forensics US CERT, a government organisation, states the following. Computer forensics is defined as the discipline that combines elements of law and computer science to collect and analyse data from computer systems, networks, wireless comms and storage devices in a way that's admissible as evidence in a court of law. And it all hinges on that last sentence, really. It has to be admissible, and we'll go into the chain of custody in a bit. This, when I worked in the police, it applied to physical evidence, in as much as we had to know who first seized the evidence, who did they hand it to, who examined it after that, and so on. And we have to have this continuity. And it's the same in regards of computer forensics. Computer forensics help organisations deal with security incidents that have an adverse impact on their business. So it could be for internal investigations also. Security incidents are events that violate the security policies of the organisation. So obviously some things may not be a crime, however sharing sensitive information as regards of your company or takeover bids or other information about people that work there can be a breach, even though it isn't officially a crime for whatever reason. Here's a screen grab if you search for computer forensic certifications. the website Tom's IT Pro has listed what for 2017 are the top 5 computer forensic qualifications. The Certified Computer Examiner, NCASE, which is a vendor specific, the other ones are vendor neutral, I think. Certified Forensic Computer Examiner, GCFA and GCFE. Not sure what that stands for. Cybersecurity Forensics. So if you're interested in this particular field, then there's certainly other certifications you can follow. Just do some research and see what the employment prospects are. So examples of security incidents include unauthorized access to data, attacks through malware or denial of service. It's important to understand the technical and legal aspects in order to gather information, because you could be, we'll cover first responder in a bit, but that could be you. You could be contacted by a law enforcement agency, told there's some sort of data or even hardware that's been involved in the commission of a crime, and be asked to take certain steps or be served with a legal notice for criminal or civil court. The risk is, if you don't have these forensic processes, you could lose your evidence, or it could become inadmissible, which can be quite embarrassing because it could mean the case is lost. The security professional needs to know the legal aspects. So US law mandates proper authorization must be acquired before security professionals can monitor and gather information. So it depends what it is. You'll be served some sort of court order or warrant in the form of a paperwork in order to take certain action or preserve a certain amount of evidence or hand it over. Organisations should have a computer forensic competence established as part of its security policy, and you may need to have it in respect of having audits for compliance or certification to work with certain vendors or government departments. So the first responder is a person first to be present on the scene after the occurrence of a security incident, which if you're the duty network engineer, then that could well mean you. You control the damage caused by the incident and ensure none of the evidence is spoiled to the best of your ability. First responder initiates the escalation procedure, so you'd inform the legal authorities, whoever that may be, and internal company management and bosses. E-discovery or electronic discovery refers to a pre-trial procedure where the parties exchange the electronically stored information. This could be emails exchanged between different employees. It could be spreadsheets, video conference calls that have been recorded, anything electronically really that's pertinent to the case. It's different from paper documents because it's not actually tangible, and it could obviously be saved in one place or saved in multiple places over the cloud and have different versions of it. Some examples for electronically stored information are as follows: emails, voicemails, documents, presentations, databases, websites, and it could be for a certain period, like a database, copy of a database from a month ago or a year ago or whatever. It obviously varies. The electronic discovery process, this involves identifying, preserving, collecting, processing, reviewing and producing the document to the opposing counsel. You could actually have to produce it for your own lawyers as well to prove your case. Now the chain of custody is a document. You could have evidence labels if it's a physical hard drive, for example, and this would include the person who seized it, who they handed it to. I'll go into some of the stuff on the next slide. Let's let you know the location of the evidence. So if it's finally handed to a property retention department, like in the police property area, then that would be the last person to have signed for possession. Starts when it was collected, requires who collected it, the date and time, description, where the evidence was stored. It's normally given an exhibit reference as well. Certainly if it's collected by an experienced forensics person, it'll have some reference number on it. how it was initially secured, which software can be used to view it, the transfer history of the evidence, and here's some evidence labels, not necessarily just for computer forensics. But you can see on the left it's received from and by, date, time, the agency, the case number, the badge number, and then on the right the submitting agency again, and chain of custody. So the chain of custody is the transfer history showing the information. Every person, or normally person could be a department, and along with the names and the person signed in. The dates and where the evidence was stored and secured. Now if there's a problem, if person A has signed it, person B has signed it, and then person D signs a label, we've missed out what happened when person C held that evidence. And if the chain of custody is like broken, it means the evidence could be tampered with, and then it'll be down to a court to determine whether or not that evidence is still admissible. In the evidence, I've just said that it may not be admissible, it could be useless in court. Right, there's a document or a process called legal hold used in litigation, but it could also be a preservation order. Basically, it requires an individual or organisation to preserve all information that may be required by an opposing party because of anticipated litigation. Data should be preserved, such as emails, preventing things being deleted because of a certain period of time has transpired or expired, sorry. There's an intervention or hold on the routine destruction until the litigation ends. So, you know, as backups normally get wiped and replaced with fresher backups, then you wouldn't be able to do that. You'd have to keep hold of the evidence. If a crime scene is a physical location, then the area should be first secured. Once the area is secured, it's important to gather as much evidence as possible. Normally this person will be properly trained and qualified, just to go through how the evidence is collected, photographed, preserved, and who it's handed on to and in what manner. And some types of evidence, not that it applies to computers, but say blood on clothing, that has to be dried in a certain way in order for it not to all go stale and lose all the DNA evidence. If the crime is a cybercrime, then the location should be secured to stop the evidence being tampered with. It doesn't mention there, but obviously if there's remote access available to the device, that has to be borne in mind as well, in case somebody can inadvertently log in and wipe the information. A hard drive should be kept in a secure drive. It's probably going to become harder and harder. Now we're using cloud computing. Collect all digital evidence in a manner permissible to the court. That depends on the court, obviously. When crimes are committed, the first responder at the scene controls the damage. This could well be you, as I've said, so down to you to use your technical know-how to preserve data as much as possible. Ensure nobody else tampers with it. Again, you'll be advised by law enforcement as and when they arrive, but down to you to stop people walking all over things or picking them up or moving them, which I've seen happen when I was in the police. During the course of the investigation, the investigators collect as much evidence as possible. The chain of custody is established from the moment of the initial collection until the investigation finally ends. If it has to be transported, the data in some way, it should be done so securely to prevent tampering. Again, this is the chain of custody. When the investigation is finally complete, the forensic report is made available in a format that can be understood by a non-technical person, and normally because it's been presented to the jury if it goes to a jury trial. Okay, we've mentioned the legal hold. Must keep that information until the litigation ends. Just a few steps in the basic forensic process. There should be a process in place according to National Institute of Standards and Technology. The following steps: collection, examination, analysis, and reporting. Collection is the first phase where data is identified, labelled, recorded and gathered. could well be photographed in situ also. Examination is the data is forensically processed using automated or manual methods. Analysis, the results of the examination are analysed to get answers. And then reporting, the results are reported. Details, the actions carried out, the tools and procedure used, who did it and when and why. Okay, so we've covered a lot here, so just to recap, we've looked at forensics and computer forensics, the first responder, electronic discovery in the chain of custody, legal holes, securing the crime scene, the high-level view, steps in basic forensics, collection, examination, analysis and reporting. So that's all for now. Thanks for watching. Welcome to Module 18, Lesson 3, Safety Practices. Another new addition to the topic, and it's something that has been growing over the past few years, and so this has become a recognised area where you go and get qualified in risk assessment or whatever it's called in your respective countries in respect of certainly data centres, the safe storage, manual handling, what to do in the event of an emergency, a fire or other disaster, how to keep the equipment safe and comply with all of the different certifications if you want to be a data center, and keep people safe also. So we'll look at the data center and the need, the environment, heating, ventilation and cooling, HVAC, how HVAC works, typical hot, cold aisle conditions, rack mount servers, rack loading, power distribution and fire risk, the impact of fire, types of suppressant agents you've got available to install, wet pipe, dry pipe and gas, how to lift stuff up without getting injured, anti-static. It's funnily enough anti-static, people laugh about it and don't think about it, but it can actually fry vital components in your devices. Stabilizing your rack, and the material safety data sheet, which is another item added to the syllabus, the MSDS. Alright, I'm sure you've heard of data centers, and if you're very lucky you've actually got to work in one or will be working in one. Great place to work. There's a definition on Wikipedia. It's a facility used to house computer systems and associated components such as telecoms and storage. Generally includes redundant backup power supplies, communications, environmental controls, e.g. air conditioning, fire suppression and various security devices. Why do we bother? It basically helps organisations centralise the entire computing resources into one location where they can have a uniform procedure for installation, upgrades, out of hours, redundancy, a whole bunch of stuff. Reduces the TCO by consolidating all your power and cooling. Otherwise you'd have to have 10, 20, 30, 40 racks spread among different departments or different buildings or different cities, making things pretty difficult to control. Racks and rack-mounted servers are used in data centers at the moment. I'm sure the future will have something completely different. You've got the servers, storage arrays and power distribution units. All the other devices and internal components generate a lot of heat. The heat needs to be removed because it obviously affects the electrical equipment to the point where it reaches a threshold that it can no longer function, and then the device will fail. And you may have had this on your home computer if your CPU fan has stopped working or there's too much dust or dirt inside your equipment, then it starts to lock up and finally fail. I know that's happened to me. Since heat affects reliability, we need to keep it cool. This requires removing the hot air and moving in cold air, just like your PC chassis, but on a much larger scale. Hot air and cold air within the data center shouldn't be mixed, and for this reason you've got the hot aisle and the cold aisle arrangement. This is for your ventilation. If the cold air mixes with the hot air without going through the equipment, then it becomes useless. So HVAC stands for heating, ventilation and cooling, which is an entire set of systems, procedures, best practices and companies that will help you plan and manage and install all of this. It provides the optimum temperature and indoor air quality. So you've obviously got to have an environment that works best for the equipment, but also the engineers can go in and manage and survive in. The HVAC system not only keeps things cool and keeps things humid, obviously not too humid, but there has to be a certain level of humidity in there, removes contaminants from the air also. Cold air is pumped from the HVAC system into the cold aisle as an input for the servers. The servers pull in cold air from the front to cool themselves, and they exhaust hot air, which goes into the hot aisle. Now, my experience when I've gone to data centers is the better ones have got doors to get in and out of the cool aisle. The hot aisle, certainly the ones I've been to, don't have the doors. So you'll be walking through an area that feels quite warm. You'll open the door to go to the front of the servers to connect or do whatever, obviously shutting the door behind you, and it'll be very cool. In fact, you'll probably need to wear a couple of layers of clothing. The AC duct carries the hot air from the hot aisle to the HVAC to cool it again and exhaust it elsewhere. Typical hot-cold aisle conditions. The cold aisle temperatures range from 55 to 78 Fahrenheit. They haven't listed this in Celsius, so I presume this is for the American viewers. The hot aisle temperature goes from 73 to 96 Fahrenheit. The amount of heat carried by the stream of air exiting the heat load should be 15 to 20 degrees Fahrenheit. Rack mount servers. I don't know if you've seen many of these. I've seen a lot over the years. The rack contains the servers. The servers have a different form factor than your normal desktop servers. These obviously need to be compliant to fit into a rack, taking over so many units. U's they call it sometimes, 1, 2 and so on. They need to have the correct eyes, so you can screw in the screws to hold it into place securely front and back, and most of them actually you can pull open so it pulls out from the rest, and you can do various things without having to shut down the server or the cables coming loose. Large rack mount servers and equipment are stored at the bottom, so the heavier stuff at the bottom to ensure the rack doesn't tip over. Rack loading should not exceed the weight rated capacity of the raised floor to ensure that the raised floor doesn't collapse because it's overweighted. Everything has to be documented, planned and measured, so you spread load over inside one rack and among a multitude of racks. So you can have the heavier stuff going at the bottom of 10 different racks, the next heaviest goes on top on 10 different racks, and so on, rather than having one rack with all the heavier stuff, because it could, if it breaches a load, then it's obviously going to break through the floor. The power distribution, your data center is normally connected to multiple power grids, and even after that, you could have the one I used to have my equipment at had massive generators that would take over, and it wasn't one generator. The generator had a backup generator as well. So there's 3 levels of redundancy in case there was a power cut for whatever reason. If you've got 2 grids, if power is lost on one grid, and certainly where I live in Australia, you get power cuts quite regularly, which is a strange phenomenon to experience nowadays. For devices with redundant power supplies, power comes from separate circuits, providing redundancy. So it wouldn't be great redundancy to have your redundant power supply both connected to the same extension lead, because if the extension lead goes down or the power supply providing power to the extension lead, then you lose both your power supplies, redundant and main. As a data center's power requirements are determined by taking into account the power requirements of all the equipment, and you've got to feature future growth. So you can't just plan for what you need now. You need to plan for however many years in the future in the company's business plan. You need to ground all equipment separate to other grounds. Fire, demand for power increases with the amount of equipment. A lot of equipment with increased power consumption are confined to small spaces and susceptible to fire accidents. Again, this is down due to heat. Obviously, fire will be catastrophic. Data centers are fire detection systems that detect the fires. Well, they detect smoke, I think, before the fire. You've got portable fire extinguishers for engineers to use if they somehow set something on fire or see a small fire. Data centers have emergency power off switches, which are big red buttons on the wall that cut off all power. Obviously, if you do that, it's constitutes an emergency because all the servers don't really deal with hard power shutdowns very well. They normally need to be correctly shut down following procedures. Fire suppressant agents put out the fire. You've got to choose the correct one. Obviously, even if you go to a local hardware store and choose a fire extinguisher, there's some for the kitchen, some for papers, some for car fires. There are three types: wet pipe, dry pipe and gas. The wet pipe is basically water that's held within the pipe under pressure, and it breaks a little seal, which you can see in the picture there, the little red seal, and that when that breaks, it lets the water come out. It obviously soaks everything with water, and that's the end of your equipment, and it will bring your data center down. The dry pipe is the same as a wet pipe, but the water is not kept in the pipes. The reason is it accumulates moisture, and if there's a drip, it can damage the equipment, and obviously could cause rust. Since the dry pipe is a water-based system, the disadvantage is the same as the wet pipe. Now you've got gas suppression, which is the norm in your data centers. It basically starves the fire of oxygen, and the fires need oxygen in order to generate the heat. Clean agents such as FM200 remove the heat from the fire. And here's some large industrial scale heat agents. Inert gases such as carbon dioxide deprive the fire of oxygen. You do get immediate recovery of business operations. You've obviously got to vent the area before people are allowed back in, otherwise they'll just pass out. And you've got to have training for the staff. It doesn't actually mention, I didn't put in here, but you obviously need an evacuation plan, so that it's normally a diagram in several key places and signed exits. It's mentioned in the syllabus, but I just thought it was so obvious because we all see them wherever we go. Even coffee shops have got fire exits and fire escape plans. Lifting techniques, well, you can see this guy here is bending his back, not his knees, which isn't a recommended way to do things. Easiest way is to injure ourselves is through improper lifting. Don't really lift the equipment if it weighs more than a quarter of your weight. Lift with your legs with a straight back. Obviously, if you have injuries, especially back injuries, then don't attempt it. And a lot of the time there's lifted equipment there that will hoist stuff for you or hold it in place while you screw things or unscrew them and slot them in. Anti-static, static electricity, as I mentioned at the start, will fry various components, and that's happened to me when I've installed motherboards and other devices. I've just heard a little fizz and something's broken. So use anti-static devices. There's anti-static bags and also wrist straps that you can connect to your wrist and then connect to an earth somewhere that will prevent you causing a spark somewhere. Because as we walk around, we're generating electricity, static electricity. Stabilizing your rack. It's important to have a correctly stabilized rack with the feet, which are all adjustable. Racks are not stable or likely to collapse at any time. You put your large equipment in at the bottom and the lighter at the top there. Moving on to another syllabus item is the MSDS, the Material Safety Data Sheet, which you'll go into. This is a document that contains information about hazardous chemicals used as a primary means to communicate the chemical hazards to staff. I presume you'd go on some sort of training course for this, not just read something on a wall. Preferred by the manufacturer or supplier of the chemical. You have to make the MSDS available in your workplace for each hazardous chemical or a mixture of such hazardous chemicals. It should be readily available to all those who may come into contact with such hazardous chemicals. The Occupational Safety and Health Administration, and I presume these are American, different countries will have different organisations or administrations. They're part of the US Department of Labour, create the Hazard Communication Standard to ensure that all chemicals that are hazardous are evaluated and the information is correctly passed. Should be in English. There should include 12 items mandated, which we'll go through briefly. The name of the chemical, the physical and chemical properties, such as colour and odour, so you can recognise it if it does have a colour. A lot of them have odours added, such as a natural gas has an odour added, certainly did in the UK, so you could smell it if there was a leak. And before that, people didn't know that the house was full of gas and lit a cigarette, and that was the end of them. Physical hazards, such as explosiveness or could it react with something. Health hazards such as corrosive to eyes or skin, you normally have that in a diagram as well. Primary ways it can enter your body such as eyes, breathing. Allowable limits of exposure before you get seriously injured or die. Is it a carcinogen? Precautions before you use it, mask, goggles, special equipment. Do you need any gloves? Protection and engineering controls. First aid, if it all goes wrong, normally has the number of the emergency services, the date when it was prepared, the document, and the last revision. Contact details of the person who's responsible. Alright, we've covered a lot here, and it's all your health and safety stuff, your data center, your HVAC, hot and cold aisles and correct loading of your racks, fire risk, fire suppression and the impact, your type of agents, lifting without injuring yourself or others, your anti-static and rack stabilization, and your MSDS. So that's all. Thanks for watching. Welcome to Module 19, Lesson 1, Common Wireless Issues. We'll look at signal loss, interference, signal to noise, device saturation, bandwidth saturation, untested updates, getting your SSID wrong. I'm sure you can guess how to fix that one. Power levels, open networks, rogue access points, wrong antenna for your device, incompatibilities, wrong encryption, and bounce. Most of these are pretty common sense actually, but I've put these in because it's on the syllabus. And if you've got a home wireless device, or even you've used wireless on your mobile phone, you probably have to troubleshoot most of these issues, but we'll cover them nonetheless just in case. Signal loss, you've got no signal or low signal. There's connectivity. There's no connectivity when there's no signal. There's latency and inconsistent connectivity when the signal strength is low. Move client devices closer to the access point, especially when you're at home actually. If you've got your wireless access point in a different room, and if you've got an older house, certainly in the UK, most of the walls were made of thick concrete, and they built the houses to last. There was no or very few false walls inside houses with just plasterboard or wood. Obviously you can install a booster as well. You can install something in your power unit and it will boost the signal or act as a repeater. Ensure there's minimal obstructions. Metal studs is another one that will reduce your connectivity or signal. Ensure the antennas allow communication as well. Sometimes the antennas come in a box, or they're not attached, or they're just pointed in the wrong direction. Interference, other wireless devices are using the same frequency. You can also have interference from microwave ovens and cordless phones. It tells you this in the documentation, but most people don't read it. When you're installing your wireless router, it'll have pictures of the kind of things that will interfere with your signal. You'll get latency and inconsistent connectivity. Avoid interference, pretty obvious as I said, but you can avoid having your devices near to these things like your ovens or cordless phones. You may be able to change the channel as well if it's got the same channel as your cordless phone uses. Overlapping channels, because other wireless access points are using the same frequency. There's automatic channel selection normally on your devices, but if you have any reasonable amount of ability, you should be able to log in and change your channels. You can correct it by avoiding the manual selection of non-overlapping channels. Signal to noise ratio, it's the ratio of the Wi-Fi signal to the outside interference or noise. Noises, in respect of wireless, have a negative impact on your wireless signal. Other Wi-Fi signals don't count as noise. This again will give you connectivity issues or latency. Signal levels and noise levels can be visualized as heat maps. The ratio of 10 to 15 decibels is considered unreliable. 16 to 24 is weak. Issues can be avoided by increasing your signal strength and decreasing the noise. Told you all this stuff was obvious. Device saturation is when more wireless devices are connected to your network. You'll get a decreased throughput. That's probably your fault for letting your kids have access to phones at home or other wireless devices. Bandwidth saturation is when one or more devices transmit a large quantity of data. I would imagine received also, so if somebody is watching YouTube in another room in the house, then that'll do it. Untested updates. Updates can obviously break things if they haven't been correctly tested, especially with regards firmware. I've even recently installed an SSD drive in my home computer, and while I was just researching it, I found that the latest firmware drive from the manufacturer actually was wiping everyone's data, which is catastrophic for most of us. And the manufacturer was aware, and they said they were releasing an update. But the problem is, if you downloaded the update, it was too late for you. Back up your last working config. Not sure how you do that with your firmware actually, but you can research that yourself. Wrong SSID. All you need to do, because they're case sensitive, you could have the wrong case or just mistype something. A lot of the time when you type these out, you can't actually see the letters you're typing unless there's an option for you to do that. So you could well have typed out the incorrect password, but you can't see it. Avoid having the client device and the access point set to use the same SSID. Power levels. Users will experience a big coverage area or small coverage area because of low power levels on access points. Big coverage areas occur because of high power levels on access points. Avoid it by adjusting the power levels for a good coverage area. Open network is an unsecured wireless network. Used to see a lot of those around, but most people now have become savvy, or the default settings on the home routers have got security chosen automatically. Unauthorized devices may connect to the network if it's insecure, so obviously change the security settings if this is the case. Rogue access points. It's an authorized access point installed on the network. Normally employees, just for a bit of convenience, will go under their desk and plug something in to get wireless access. A malicious attacker can install rogue access points, thus getting them access to the network. Wrong antenna type. Signal coverage depends on your type of antenna. So you could have no signal or poor signal, or a good signal but far away from the access point. Omnidirectional and directional are two main types of antenna. Omnidirectional gives you 360 degree patterns, suitable for inside an office conference area. Directional will give you a signal in a particular direction, so your coverage is limited to that one direction. You got a Yagi parabolic grid patch and panel antennas. The Yagi and parabolic grid are used to connect one building to another. You must have line of sight, so if somebody's got a tree there or something else temporary or permanent, then it's going to cause you issues that you'll have to troubleshoot. If there's incompatibilities, users may not be able to get access to the WAP. The settings may be incompatible. Standard supporting, if you've got a very old wireless card that you've got on your device, a PCI card or USB, it might not be compatible with your other device. So 802.11a is not compatible with 11b and 11g. You've got to look at what is compatible. So B is compatible with G and vice versa. Some are backward compatible, others aren't. Wrong encryption, you may not be get a connection with the wireless access point. The client device and wireless access may have different encryption settings, so you need to check that what's configured on your access point is matching on your wireless card or wireless device, whatever you're using. So do configure it correctly. Examples are WEP, WPA and WPA2. Bounce is when your signal bounces off an obstacle without reaching the destination. You can get weak or no connectivity. You need to remove the obstacle. Obviously sometimes that's easier said than done, so if it's a big thick concrete wall in your house, don't knock it down because your roof will fall down. You need to either get some sort of booster or move where you're connecting from, or just find an alternative connection type, such as connecting through the Ethernet devices that will plug into your power. Alright, so we've covered a lot. Signal loss, interference, signal to noise, saturation, bandwidth saturation, untested updates, wrong SSID and your power, open networks, rogue access points, the wrong antenna type, incompatibilities, wrong encryption and bounce. That's all for now. Thanks for watching. Welcome to Module 19, Lesson 2, Common Copper Cable Issues. That's a mouthful. So some of the common issues you'll experience as a network engineer are shorts, opens, incorrect termination, crosstalk, EMI, distance limitations, attenuation, other cable issues. Shorts is basically short for a short circuit. It allows the current to travel in a path that wasn't intended and the cable wasn't designed for. Copper wires in the cables are insulated so they don't come into contact with each other. If there's some sort of issue, a lot of the time it's because it's frayed. Somebody's bent the cable around a bend or just done something with it, or folded it too many times and unfolded it. Then the cables can touch each other and then you've got a short circuit. Depending on how bad it is, you'll have intermittent connectivity issues. You could use a TDR that will locate the short in the cable. This is one of your troubleshooting tools that you could use. An open refers to an incomplete electrical circuit in which there's no current. If one of the copper wires inside a cable is cut or just broken for some reason, then you've got an open circuit. You would normally then have no connectivity. Again, you can use a TDR that can be used to locate openings in the cable. Incorrect termination generally happens when you've made your own cables, or your cable engineer has done it and just made a mistake or done it too quickly, or just not been watching what they're doing, and it's obviously human error then. Doesn't happen as much in professionally made cables. So you haven't properly terminated as per the standard. You could have got the wires mixed up or not. squash the RJ45 connector onto the wires correctly, and it's a bit of an art to it. So you could have no connection or intermittent connection issues. Straight through cables should be terminated either using T568A or B. Crossover cable has got A on one end and B on the other, so pins 1 goes to 3 and 2 goes to 6 on the other end. Use the cable tester to check if your cable is properly terminated and what type it is. Crosstalk is when the signal from the wire interferes with the signal on another wire. Less of an issue now with modern shielded twisted pair cables. You measure with a cable tester or a TDR again. The issue is avoided if you buy a professional cable, basically, because it will be twisted properly. Two types of crosstalk that you may be asked about in the exam: near end and far end. A near end refers to the crosstalk that occurs at the terminated end of the cable where the crosstalk has been measured. So this is where you're doing the measuring. Occurs near the connectors terminating the cable. Far end is on the far end of the cable from where you're doing the measurement. Occurs near the connectors terminating the far end of the cable. Electromagnetic interference is normally when you've laid the cable yourself and it's gone through or near some device that emits a strong signal, an EMI signal, also called radio frequency interference. Generated by fluorescent lights, electric motors, dynamos, things like that. So it could happen in a workshop, or when you haven't properly housed your cable, or it's not running under the floor and you're running it through the ceiling and it's going through the fluorescent lights. Data transmission in copper cables is obviously disrupted when it's exposed, and it could be intermittent. It could be fine during the day, and then later on in the evening when somebody starts turning the lights on, it could be affected. Avoid if you separate the power source from the cables or by using shielded cabling. You may have to buy a special type of cabling if you're running your cables through devices with a lot of very powerful electrical signals. Obviously there's distance limitations per cable. Lost the signal when it travels over a long distance. You could then have connectivity issues. So if you're running your cable over 120 meters when it's recommended 110, then you may well have issues. Attenuation or dB loss refers to a loss of signal strength. The signal strength is measured in decibels. Users experience degradation in network performance. You can avoid it by using cable runs within the maximum supported distance, using a signal booster. You probably need specialized advice for this, to be honest, if you're installing in a commercial premises. Remove broken or damaged cables. Miscellaneous other problems. Verify the cables are present and plugged in. Yes, I've been asked to troubleshoot devices when somebody hasn't actually put the cable in yet. It hasn't been installed at all, or somebody's removed the cable for some reason because they want to use it somewhere else and not realized that that is connecting to an end user or a server or some other device. Make sure the network adapter is enabled and has valid addressing. Sometimes devices have been up for years and millions of packets have been passed in and out, and it just needs resetting or rebooting, or the address needs refreshing on it. It just happens sometimes every a period of time. Make sure disabled ports are enabled for connectivity. Sometimes ports are disabled for security, and you could plug in a new user into a certain port on a switch, for example, but that port has been disabled. You can have bad cables. Again, sometimes we bend them, or just over time, for whatever reason, the cable goes bad. Misconfigured switch port. It could be the wrong duplex setting or speed setting or something else on there, and it may not work. Misconfigured network card, or a network card that's failing or failed. Software drivers I've mentioned elsewhere, that can cause huge problems, and it's not a problem. You can actually easily see until you start doing a bit more research. Alright, so we've covered shorts, opens, termination, crosstalk, EMI, distance, attenuation, and other problems. That's all for now. Thanks for watching. Welcome to Module 19, Lesson 3, Common Fibre Cable Issues. So we'll look at troubleshooting, supported distances, categories of multi-mode fibre, the bend radius, dirty connectors, I think you can guess what that one's about, attenuation, a wavelength mismatch, fibre type mismatch. So the bottom line with fibre cables is if it's faulty, it can't transport data. It tends to be either a working or not working situation, whereas with copper, you may well have a period of time where the performance just deteriorates when you get in packet loss or intermittent connectivity, and you normally easily troubleshoot that by just swapping the cable out. If it all works, then it points to the fact that the cable was faulty, and they're so cheap you just throw them away. Obviously, fibre cables are not so cheap. First place to look will often be the LED next to the ports where you've plugged the cable in. If it doesn't light up, then you've got a number of possible reasons. The cable's not plugged in properly at both ends. The cable could be broken somewhere. Now here's the troubleshooting flow chart for fibre cable. Well worth maybe just printing the screen and just following it through, plug it into a different port. Does that port light up then? And it shows you it's a problem with the port. Just a few simple troubleshooting steps really. Alright, don't look into the cable when you've got the other end plugged in, because the laser will go directly into your light and it could cause damage. So use, you could actually point it at a white object or a wall or at your hand. But read the documentation that comes with the cable to make sure you're doing the correct thing. There are obviously electronic devices that you can also use. When you can connect two devices such as a server adapter to a switch using a fibre cable, the TX port at one end should always be connected to the RX port at the opposite end. Normally you'll get a housing that both ends of the cable will connect to, and that can only plug in one way to the device. Not always the case, and obviously there's different cable types all over the world, but normally it'll be designed to be idiot proof so we don't cause that issue. If you connect it the other way around, you'll have no connectivity, and then it'll show no connection. Supported distances, multi-mode fibres with 50 microns and 62 microns can support data up to 500 meters and 175 respectively. Again, read the label that comes with your cable in. You may well be lucky enough to have a professional company come in and do your cabling for you, and then again you may have to go and swap some cable out or install a new device without the aid of this company, so you do need to know. Multi-mode fibres are categorized further by optical multi-mode or OM designator. These are labeled from OM1 to OM4. Just check the table, and you've normally got a label on your cable as well to see what you do have, or it's stamped on the side, and just check the specifications and allowances. When you're troubleshooting, check whether the cable supports the speed and distance of the link between the devices. Bend radius, most fibre optic cables are made of glass. A sharp bend at some point, they are pretty flexible, but if you bend it too much it will break the glass. The bend radius refers to the smallest bend a cable can withstand. Again, if you start wrapping this cable round and round a pole in order to take up the slack, then you could break the bend radius, rendering the cable unserviceable. To avoid issues, don't bend them, obviously, or more than you have to. The OTDR can be used to check whether the cable is damaged. Damaged cable obviously needs to be replaced. Hopefully that goes without saying. The broken cable, some people put them in a cable box. If it's broken, make sure you dispose of it in the legal manner. So you can't throw it onto a fire usually. You'd have to have it professionally destroyed or recycled. If you've got dirt, because it uses light on the fiber cables, if you've got dirt on one end, it will cause problems, high loss and reflectance. Clean it using the cleaning methods and supplies provided with the cables. Don't wipe at the end of it on your trousers. Attenuation, signal loss over the fiber optic cable. Following could be the reasons. It could have been overstressed during installation, improper termination, improper splicing if it's been spliced somewhere. Could be broken fiber. Again, you can use the OTDR to locate the fault. Wavelength mismatch. Fiber cable uses wavelengths longer than normal light. It's usually around 850, 1300 or 1550 newton meters. Multimode fiber is designed to operate at 850 to 1300. Single mode at 1310 or 1550. The wavelengths used for transmission are the wavelengths that must be tested for signal losses in the cable plants. When the mismatched fiber cables are coupled, the incompatibility of the core sizes results in signal loss. Now, there's no problem if you're transmitting light from a smaller fiber core to a larger one, but the other way around, you'll have signal loss. The signal loss can be around 20 dB when we couple a multi-mode fiber to a single mode. Again, read the documentation that comes with all your cabling. So we've looked at fiber cable, supported distances and categories, the bend radius, dirt on your connectors, attenuation, and wavelength mismatch and fiber type mismatch. That's all for now. Thanks for watching. Welcome to Module 19, Lesson 4, Common Network Issues. There's actually entire books been written about troubleshooting networks from PCs, switches and routers, and it's something that requires a bit of experience, common sense, and often a plan, and sometimes a bit of good luck as well and guesswork. We're going to look at common things that normally go wrong day to day: incorrect default gateway, broadcast DOMs, duplicate IP address, your duplex and speed mismatches, incorrect VLANs, hardware failures in DHCP, DNS, interface misconfiguration, cable placements, power failures, and then less common MTU black hole, NIC teaming issues. So incorrect default gateway, it depends if there's been a change of default gateway, if the device that is experiencing the problem has had any changes, or somebody's gone in and configured something. So it all depends on the questions you ask, really. But if you've got the incorrect default gateway, then all traffic from your host device is going to the wrong location, and layer 2 devices such as switches also are normally configured with the default gateway. But you should be able to ping from the switch, whatever the VLAN is, to the default gateway when you're installing it, just to check it's working. So the IP address assigned to the default gateway may be correct, and you can check your IP configuration settings on your Windows or Linux device. Obviously, to fix it, put in the correct default gateway and make sure nothing's changed on the default gateway. Broadcast storms, users can experience a degradation in network performance, and it can actually bring down the entire network. So the network is flooded with broadcast traffic. Could be a switching loop, could also be a faulty network card that's just sending a huge amount of traffic out. You could troubleshoot it with Wireshark and other programs, and Cisco provide a whole raft of tools. Obviously, having spanning tree in your switches will help solve the problem. It's normally there. It's normally on there by default. Duplicate IP. Sometimes somebody doesn't release their DHCP address. It's been on there too long or stuck for some reason. Or I've seen people manually configure an IP address on their system for some crazy reason. I don't know why they did it, and it's caused a mismatch. To avoid it, you can change the IP address of both or one of the hosts, normally asking for it to be provided by DHCP, which most devices use. Speed and duplex mismatch you can have on your host or on a switch, in fact on a router as well. You'll have slow or degraded network performance or no connectivity at all. And you could have different port and speed settings. You could have 100 full duplex on one side and 10 meg half duplex on the other side, and you're going to have problems. Normally you'll see issues on the LED of the network card as well, and you could have error messages coming up on your router or switch console and on your PC. So common causes when negotiation is enabled on one side and disabled on the other. It's reliable to manually configure network speed and duplex settings for the server and other critical links. Now, you may use auto negotiation. The networks I've worked at, they generally didn't. They had hard-coded speed and duplex settings for all devices. Incorrect VLAN. If you're on the wrong VLAN, you may have no connectivity or not be able to access the resources that you need because it's in a different VLAN. Configuring devices, it's normally the switch port. The end devices don't have VLAN settings as a general rule. You would configure the switch port to be in the correct VLAN and make sure it's not blocked. That VLAN is unblocked for security reasons on the switch trunk port. Hardware failure, this is a whole raft of things that could go wrong intermittently or just completely break. One of the components of a device may have failed, or an entire device. You identify it with your troubleshooting methodology and you can replace the faulty device or the faulty interface. DHCP, if the server has been incorrectly configured, then you're obviously going to have issues. You could have one person affected or the entire organization. You could exhaust all of the IP addresses on your DHCP pool. It could also indicate that you've got some sort of attack going on, some rogue DHCP server, or the device is causing issues. We've addressed that elsewhere. DNS, obviously, for DNS lookups, you need to have the correct device configured. A host could be configured with the wrong DNS server, either because you've misconfigured the DHCP server or somebody's hard set it. So ensure the host is configured with the correct IP address of the DNS server. On Windows, you could issue ipconfig /all, and it will show you your DHCP server address, your DNS server address, IP address, and a few other settings that you may find interesting. If your interface is incorrectly configured, you'll have no connectivity or intermittent. You could have the source or destination device may have an incorrect IP address or subnet. So if for some reason your router interfaces on either end have been put in different subnets, then you're not going to get connectivity. Check the IP and subnet mask of both source and destination, and check it against your design documents. Cable placement, you could have slow performance, could be close to a source of EMI, which we've already discussed. Power failure, obviously that's going to cause issues either with the device or part of the network or the entire network. Most higher end switches and routers have redundant power supplies so that if the main one goes down, the backup one takes over. MTU backhauls, this is maximum transmission units for your IP packets, and it depends on configurations. It can also happen with routing protocols such as OSPF, which is outside the scope of this course. If the packet's been flagged as do not fragment, then the router is expected to send an ICMP message, destination unreachable, back to the host that sent the packet. If the router drops the packet and doesn't send the ICMP message, then the host then the router is referred to as a black hole router. You can check the interface MTU on your routers when you do the show interface, or you can add some troubleshooting software if you don't already have it. You can use a ping utility, or you can use a trace route. You can send different ping sizes. Certainly on Cisco routers, you can go into a detailed menu of options and send a ping packet of a certain size to see if you're losing packets. NIC teaming, if a user experiences a degradation in network performance, it could be a NIC teaming misconfiguration. This is generally done a lot on servers, and different vendors have different terminology for NIC teaming. So again, check your documentation. Generally, you'll aggregate various network cards into one logical connection. So you could have broadcast storms. There'll be other issues as well with spanning tree and other things. To prevent the NIC team from becoming multiple links, you can use link aggregation control protocol, which is used on routers generally. Alright, so incorrect default gateway, broadcast storms, duplicate IP and speed and duplex. VLAN assignments on your switches, check your documentation for that and your configurations. Should say hardware failure, sorry. Misconfigured DHCP and DNS. Interface misconfiguration issues, cable placements, power failures, empty black holes and NIC teaming. That's all for now. Thanks for watching. Welcome to Module 20, Lesson 1, Change Management Basics. We're going to look at what is a change, what is change management, types of changes and approval processes, what is documentation in respect of change management, what is a maintenance window, what is configuration procedures or what is a rollback, what is a potential impact, what is a notification of change. Now, change management is a new addition to the Network Plus syllabus. It actually dates back to, you can trace change management back to the 1960s, and now it's a recognised qualification and a whole area where you can gain employment as a change manager. So you could Google Change Manager and ITIL, which is the IT Infrastructure Library. But this is bringing IT into alignment with business practices, where we're managing changes, problems. Also, when I worked Yellow Pages in the UK, there was a whole ITIL team looking at change management, problem management. So there's systems and procedures for everything, looking at what we're doing, why we're doing it, who authorises it, if there's a problem, what caused the problem, how do we stop the problem happening again. And it makes the entire business procedure and business run more professionally, and it cuts down a lot of unnecessary procedures, blaming, communications, and debriefing, and makes the organisation work more efficiently. Changes any addition, removal or modification or configuration that could have an effect on the IT service. So this is why we need to have a set of procedures in order to plan for a change, rather than somebody just rebooting one of the main core routers on the network at the busiest time of day. We need to have some sort of procedure. So change management is a set of processes that governs and controls the aspects from start to finish. It reduces the risk, disruption and impact on the business. We can refer to it as CM for short. So CM aims to use the defined standards and methods and procedures across various teams or groups, so we're all basically singing off the same hymn sheet. This is the ITIL, the IT Infrastructure Library, which we actually host some of the one of the qualifications on howtonetwork.com. I highly recommend it because IT people now can't just rely on being technical. They need to have an understanding of how they slot into the business and how the business works, the IT works as part of the overall business. IT breaks into service transition, service design and service operations. And you can see some of the things I mentioned here. You can see change management is highlighted. There's problem management, knowledge management, service testing and validation. And you slot this into your business, how your business works and how it's going to benefit it. So change management includes a risk assessment, reducing change failures, properly implementing any changes, looking at business timelines and service level agreements. It gives you better control, a clear plan for reverting if there's an issue. I've actually seen this when I had my website hosted with a different service provider. Somebody did a change to one of the tables on one of the databases and it caused outages for around 3 days, and I know some people went out of business. It was just an absolute catastrophe, and they didn't I don't think they had a change management procedure in place, otherwise they could have backed out quite quickly. On managing communications, this is important where there's a central person is responsible for communicating what's going to happen, when it's going to happen, and then they communicate just before it happens and then after to say the change has happened and it was a success or failure on what's actually the procedure afterwards for following up. Changes can be performed to adapt or change business needs, hardware, software. It could reactively implement a fix if there's some sort of major issue or bug or attack on the network. Normal changes, for example, a normal configuration or server maintenance, something that was generally expected. Standard changes, pre-approved changes that don't require approvals. These are things that just aren't going to cause a problem. Usually, for example, swapping out a redundant power supply, it's just not going to have any impact, and it's been tested for in the past. Risk associated is low and does not have an adverse effect on the business. Emergency, these are changes that are implemented on an urgent basis to remediate a problem. It's normally network affecting, business affecting, and it has to be done urgently. You need to have approval off the emergency change advisory board, and they'll normally have either a video conference or a quick meeting in order to talk about the impact on the business, because you need to look at the entire structure. Documentation, a change request is documented using applications. There's a variety of applications you can use. The documented change request is called a change record. It could be online or printed. It's used to track the change throughout its life cycle from beginning to end. This is so we've got an audit trail of what happened and who did what and who approved it and etc. The change record contains key details of the change, including detailed technical implementation. The technical parts will probably be read by the IT managers and technical team, but they're there for the record. Key details is who requested it, why did they request it, what's the outcome, what's the point of doing it, is there a business benefit or is it going to prevent something more serious happening, what are the risks involved, what resources, that includes the teams, human resources and physical and software resources. For example, a network card needs replacing or an update required for the software. Who's responsible for building, testing and implementing? What's the relationship between this change and other changes? Is it one of a series? So the effect of one change on another. For example, if you update a VLAN on a certain device, what devices, what physical ports are going to be affected? Is the VLAN going to be propagated on other switches or does it need to be blocked? Maintenance window, I'm sure you've heard of. It's an agreed period of time in which is going to have minimal disruption, normally done on the weekends or out of hours. Just depends on your business procedures. The authorized maintenance window is predetermined and pre-approved to carry out the change. A lot of the time, an alternative server is used or whatever. You could have some sort of load balancer used, and all traffic is just sent through one of the load balancers, so the change could actually be transparent to users. Generally, changes during weekdays are scheduled after business hours. Critical changes Friday nights, and they can run into the weekend, so you can roll back and recover if there's an issue. All changes to service assets and configuration items are recorded in the configuration management system. Server can move from pre-production to production with a formal sign-off before it's accepted into production. Such changes are to be documented for timely support, so everyone needs to know about the fact this new server has been introduced, the configuration settings, and what the possible risks are, and what we do if there is an issue. A rollback is basically going back to how we were before this change happened. Not always possible, obviously, especially if something's completely broken and has to be replaced, and then the replacement, for example, is broken also. Okay, so worst case is a site failover or business continuity plan may be invoked. This is if the entire core system goes down. Is there some sort of backup in place, or what do we do? Looking at the impact, there's a matrix: low impact and low risk, category 4, going all the way to category 1, which is high impact, high risk, and it's a critical category: low, medium, high, and critical. The notification of change is published with the details of the change activity, the window of the change. Obviously, it only goes out to the people that are going to be impacted. Alright, so we've looked at change management, types of changes and approvals, what is documentation, what is a maintenance window, configuration procedures and rollbacks, impact, and the notification of change. That's all for now. Thanks for watching. Welcome to Module 21, Lesson 1, Internet of Things Technologies. This is one of the new subjects that's been added to the latest CompTIA exam. They just expect you to have an overview of what these things do rather than any detail, because there's quite a diverse array of protocols here. Z-Wave, ANT+, Bluetooth, which I'm sure you've heard of, NFC, infrared, RFID. So Internet of Things, it's a network of devices, appliances, vehicles, physical devices, and many of them work with sensors or softwares. So for example, when you're, say, let me go down, there's a car here actually. You'll have sensors on your car. I know I didn't win any awards for drawing. Sensors on your car, brakes, which has been detected by goes into a CPU of some sort. When it detects that the wear's down and say you've got 30% left, then it will communicate to the garage or computer in the garage. That will order whatever part you need from the manufacturer. That will go to the garage, and then you probably, depending on how advanced the car is, have a notification that your tyres are worn, or your garage, next time you take it in for service, will have the part in stock and be able to replace it. So that's just one example of the Internet of Things. There's many others, and it's just a phrase that was coined several years ago. Z-Wave is a wireless communications protocol used mainly for home automation, for example your lighting, your security, your thermostats to set it, and all your favourite settings. Works over a mesh network, so all the devices are interconnected, and is controlled via a keypad, or you could have a key fob of some sort. ANT+, it's a wireless communication protocol again, monitors sensor data. This could be your heart rate, tyre pressure, television, any number of things. And it's created and managed by the ANT Alliance. It's actually a subsidiary of Garmin, who do the satellite technology. Bluetooth Mesh, adopted in 2017. It's many-to-many communications. So the receiver can be a thing, a group of things, or many things. For example, you'd compare that to unicast, multicast, or broadcast. All messages are encrypted and authenticated, so it's pretty secure. Sorry, you can ignore that one. Near-field communications. A set of communication protocols, you're probably using this already. It allows two devices, one's usually a smartphone, to communicate. Now you need to be within 4 centimeters of each other, so you have to be pretty close. Used for contactless payments. I know on my phone I can enable it to act as my card, credit card or debit card, and swipe my phone instead of my card. Quite handy if you've forgotten your wallet somewhere as well and you need to pay for something. Infrared, I'm sure you've heard of that. We used to have, this used to be the competitor to wireless, where companies would add an infrared communication module on top of their building, and as long as they had line of sight they could get high-speed communications with another building within, I can't remember what the range was, but it fell by the wayside really. It's similar to visible light but slightly longer wavelength. For example, your remote control, you click that and per second of holding down the button it sends out 38,000 signals. Used in Internet of Things for medical diagnostics, fire detection, remote gas leak detection. RFID, you probably have seen this if you saw the newest, not the newest Bourne film, with Jeremy, I've forgotten his name now, Jeremy Renner. We had one of these inserted in him, and they tried to, unfortunately, tried to shoot him with a missile, so we had to cut it out. But yeah, it's essential to the operation of the Internet of Things. It allows computers to manage all individual things. This is compared in the picture to a grain of rice, so it's pretty small. Uses EMI fields to identify and track tags attached to objects. The tag can actually contain electronically stored information, so this is what's used to tag pets. For example, when a pet gets lost somewhere, it can be tagged. Also used in tracking vehicles. If you've ever seen a production line, there's tags inserted on the vehicle, and that updates the entire production system as to if it's going too fast, too slow, and when to expect the next vehicle along. Alright, so we've covered, just in brief, the Z-Wave, ANT+, Bluetooth, NFC, IR, RFID. Just you need to be aware of these in case one of the questions pops up in the exam. That's all, thanks for watching.